Welcome to class, our first class together. I'm going to provide some slides to try to describe some of the concepts and tell you a little bit about myself. Thank you. I have a Master's of Science degree in Computer Science from Binghamton University. I graduated in 2001. I also have a Bachelor's degree in Computer Science from SUNY Oswego. I've been a software developer for over 16 years working at various companies. I've been an online instructor for the past 11 years. I've instructed over 20 different classes. And this is everything from object-oriented programming to compiler theory. I've been working with Android and iOS since 2010. I've created many different classes at many different universities, including beginning and advanced Android classes. I've also been using Kotlin for about a year now. Currently, I'm a software developer at Xerox Corporation. I mainly program in C++ and PHP. I also like to concentrate on object-oriented languages and mobile programming. It's a ton of fun and I love Android. Lastly, I focus on writing high-quality code. I think a lot of students kind of lack this focus, and so I'm going to try to emphasize writing high-quality code in this class. Some of the topics that we're going to cover in this class, we're going to start off with an overview of Kotlin. We'll talk about the goals of Kotlin, mainly that it's concise, expressive, null-safe, and works with Java. It's interoperability. We'll then move on to language features, talking about static typing, compile time checking of types. Kotlin also supports object-oriented languages as well as functional. And then some of the really big concepts, lambdas, we'll talk about that and how you can pass around blocks of code. Follow that up with identifying the advantages of using Kotlin, mainly that it's efficient, reliable, and easy to learn. It's important to understand the language, its advantages, and the language's features before you can really start using the language. We'll follow that up with talking about static typing and type inference in detail. We'll move on to immutable and immutable variables. This is really creating variables with the val and var keywords. We'll then talk about strings and string templates. String templates is a really nice feature where you can place $ symbols inside strings and those variables will automatically be interpolated. We'll talk about the any and any types. Any is similar to the java.lang object. It's the top level object in Kotlin. Unit and nothing types. Unit is similar to a void. Nothing is when you return nothing from a function. This may seem kind of odd, but everything in Kotlin is a type, and all types get returned somehow. Smart cast. Smart cast is a great feature that will do automatic casting for you. The compiler will automatically know the last time you used the is operator and cast it to whatever you did it on. Is similar to the instance of operator. Basic operators. We'll talk about logical and arithmetic operators, pretty much the same that are in Java, plus, minus. The big difference is they have matching functions, so you can easily override them. We'll talk about nullable types, which is you use the question mark before variables. I mentioned that Android is a null-safe language, so you got to be able to identify when things cannot be null. Safe call and else operators, these help support null safety. Safe cast operator, similar to this as well, when you want to cast something and first make sure it's not null. If statements and while loops. These are typical construct of a language, and we'll talk about how these can also be expressions. The when construct, similar to the switch statement in Java, but much more powerful. A really good addition. We'll talk about functions, how to declare and use them. Functions are a big part of the language. You can create member functions, but you can also create top-level functions, functions that have nothing to do with any enclosing class. As I mentioned, we'll talk about top-level functions, not part of any class, member and local functions. Default name parameters, a nice technique that will make code more readable, and default parameters can also reduce overloading. Infix calls, variable number of arguments, similar to the Java, but uses a keyword. Extension functions, a great feature of the Kotlin Programming Language where you can add new functionality to existing classes that you don't even have the source code for. The Kotlin Standard Library, some core functionality that's provided for you mainly through the use of extension functions that make it easier to communicate with the Java APIs and also provide many nice features to make things easier. Operator overloading. There's no operator overloading in Java, but there is in Kotlin. Lambda Expressions, an awesome thing where you can pass around blocks of code. It is in Java 8, but Android includes Java 6, so you can't do it in Android apps. Higher order functions. This is where you can pass lambdas to functions as a parameter and where functions can return functions. Object-oriented concepts. We'll do a review of that, or if you're new, we'll cover it in detail. Classes and constructors. We'll talk about primary and secondary constructors in Kotlin. Properties, which are similar to member variables, but they have the accessors automatically generated for you. Inner and nested classes. Inheritance and interfaces, using the open keyword. Interfaces can also have default implementations like Java 8, and interfaces can have attributes. Singletons and companion objects. There's a nice keyword in Kotlin named object that will create a single instance. Makes singletons very easy to create. Exceptions. We'll follow that up with generics, the ability to have this, the same behavior for different types. Collections. There are a ton of information on collections where you can communicate with the Java collection classes easier in Kotlin. A lot of new features. Reflection and annotations. Concurrency. And then we'll dive into Android practices for Kotlin, some tips, also some ways to use Kotlin on Android specifically. And then lastly, we'll have many code alongs for Android projects written in Kotlin. This will help you become familiar with writing Kotlin for Android apps. By the end of this course, you're going to be able to write advanced Kotlin programs. We're not just covering the basics of Kotlin, we're covering all the details of Kotlin, all the program language features. You'll be able to write intermediate Android apps. We're not covering the Android APIs in detail via the lecture. We're going through code alongs that will help you become familiar with Android, the Android platform. You'll be able to write efficient, high-quality Kotlin code. We'll have cohesive classes, low coupling. It will also be very expressive. You'll be able to find and fix your errors. You'll have good debugging skills. And you'll understand all the aspects of the Kotlin programming language, from beginner to advanced. But lastly, you're going to have fun. I like to have fun in my classes, and if this is not enjoyable, I really don't want you to stay in the class, because you're paying good money for this. You want to have fun in the class. So that's really the most important thing. Thank you for listening. Hello and welcome back. In this lecture, I wanted to talk a little bit about how the class is organized. The reason I wanted to provide this quick, short lecture is so that it can help you better decide on whether or not you want to sign up for the class, purchase the class. So this class is a little different than many of the classes on Udemy in that it's not just a how-to. This class is organized around explaining all the concepts of a programming language. It's really focused on the why. In addition to providing the how, I'm going to provide many how-tos on how to write certain programs and demonstrate different concepts. But again, it's a little unique in that it's just not a how-to. You're going to understand concepts. You're going to understand why you're doing the things you're doing when you're writing your code. So it's a complete learning experience. At the end of this class, you're going to fully understand the programming language. Specifically, you're going to understand how the programming language works and all the concepts associated with that language. And again, as I mentioned earlier, I find this is lacking in many of the Udemy courses. Many of the Udemy courses are nothing more than demonstrations of projects, of certain how-tos on how to create a particular coding project without fully understanding what you're doing or why you're doing it. I also want to describe how I'm going to present this information and how you're going to learn it. First and foremost, we're going to have all video lectures. You know that the policy in Udemy is mainly that. The way they're going to provide a lot of some of the material is I'm going to provide it through PowerPoint slides. And some people are negative on PowerPoint slides. They don't really like to learn from PowerPoint slides. They're just real not keen on it. The reason I provide PowerPoint slides is because I have to provide these concepts and definitions, often is the case, and they're very abstract. And I can't just go into an IDE and demonstrate the code. I have to provide the concept in some kind of text. Now, I could provide that in Notepad, WordPad, any other editor. I choose PowerPoint because it has a nice visual representation, and it's very useful in that manner. I'm not going to just be reading from the slides. So I will hear some complaints often in other classes where, hey, you're using PowerPoint slides and you're just going to read from them. Well, no, I'm not just going to read from them. I'm going to provide insight via my experience. So the PowerPoint slides, again, they're designed to provide for you the understanding of the material. I'm not sure any other way I can do that without providing at least some PowerPoint slides, especially concerning abstract concepts and definitions. I just don't know no other way to do it. You have to listen and you have to try to understand from it. Now, that doesn't mean we're not going to provide other concepts of learning, but there are going to be PowerPoint slides. So understand that coming into class, and these are going to contain thorough explanations via my experience. It's a way for you to understand the concepts in the class. It's not the only thing that I'm going to provide, but you are going to see PowerPoint slides. So don't just necessarily get negative on the entire class because there are PowerPoint slides. It's one technique in helping you learn, and I think a technique that is needed in the class. In addition to the PowerPoint slides, I'm going to do tons of practical hands-on demonstrations of code. So I'm going to bring up the IDE. I'm going to bring up an editor. I'm going to show you how to write the code in an editor. I'm going to provide code examples. I'm going to type in the code. These are going to be concrete. They're going to be real world. So this type of learning will be more practical and it will be more hands-on learning. And I know many students like this, and it's needed. I love it because it's more practical and you can see how I'm writing code. Again, though, if I'm trying to present information or concepts such as polymorphism, I also want to provide a lecture or a PowerPoint slide associated with that to give you a formal definition. So that we don't just dive into the code and then you have to kind of scratch your head and say, what exactly is he doing in the code? So PowerPoint slides, in addition to demonstrations, are going to be provided in this class. This will help supplement your learning of the language itself. In addition, you need a way to assess how well you're doing in the class and what you're learning and if you're learning. So we're going to provide challenges. Challenges are essentially coding assignments. They're additional projects. How it will work is I'll provide you with this assignment. I'll tell you the requirements, explain, maybe give you some tips on how to complete the challenge, and then you'll go off and do it on your own. And then I'll provide another video which will be a solution to that lecture so you can see whether or not you did it correctly. The solution will be a complete walkthrough or what is called a code along of the solution. I'll go line by line explaining every line of the solution in an integrated development environment, in an environment where you write your code. I'll run it, I'll demonstrate how it works, everything. And then in addition to going through this video walkthrough, I'll also provide all the source code to you so that you can download it and you can compare the source code to your source code in text. But again, I wanted to just provide this quick lecture so that you know how the class is organized in terms of how you're going to learn and what you're paying for. And if you see a lot of PowerPoint slides, try to give you an idea of why I provide them and why I think they're useful. Again, I want to provide a complete learning environment. And I don't think I can do that by just doing a how-to of walking through projects. So I hope you appreciate this lecture, and I hope you understand where I'm coming from and how you're going to learn in this class. Thank you. Another lecture. I'd like to give you an overview of Kotlin. It's nice to understand some of the basics, maybe give you a little information about some of the goals of Kotlin, and try to have you understand why you want to use Kotlin. So traditionally, Java was the language that you used to create Android applications. It's been like this since Android's been around 2008, 2009. You can also use C++ to create Android applications, but those are the native libraries. Java is a hybrid language that is both compiled and interpreted. When you write your Java source code files, they're in .java files, and you use the javac command to compile the source code. And what happens is new files are created called .class files. This is the compilation part of Java. A compiler will check the Java language for syntax errors, and if there's any errors, it will display them. Otherwise, it will generate these class files. This is referred to as bytecode. Once you have the bytecode, you then run an interpreter, which is the Java virtual machine. The Java virtual machine interprets the class files. And this is what allows Java to be portable across many platforms. One of the big advantages of Java when it first came out back in the early 90s is that you could write it once and you could run it on Unix, you could run it on Linux, you could run it on Windows. It didn't matter the platform, you only had to write it once. And with other languages, this isn't the case. If you write C code, you have to write it on Unix with a particular compiler, and then if you write it on Windows, you may have to change things so that it can run on a Windows operating system. So Java has this hybrid approach that is both compiled and interpreted. It's an extremely popular language. It's used for everything. I'm sure you have heard of it. It's used on web page development, embedded systems, standalone apps, to mobile apps. And that's what we're going to concentrate in this class. We're going to concentrate on mobile application development. However, the Android platform mainly supports features from Java 6. Currently, the current version of Java out is Java 8. Java 6 is a bit old. It's 2 versions below. And as a result, it doesn't have a lot of modern language features. It doesn't have this concept of lambdas, which we're going to talk about a lot. It doesn't have many other things as well. It's more of an older language, and it's very tedious to write some Java code. There's a lot of wasteful code. When you write an Android app, you end up writing a lot of code over and over and over again because you're required to do it, and it's just not fun to write Java code in an Android app. So, since Java uses JVM, the Java Virtual Machine, this allows developers to create Android applications with any language that generates bytecode. And some other languages out there that generate bytecode are Groovy, Scalar, and Clojure. The big one that we're going to obviously study in this class is Kotlin. Kotlin, it will run on the JVM, so that means we can use it to write our Android applications. It's a JVM-based language developed by JetBrains. JetBrains is the company behind the IntelliJ IDE. It was developed in about 2011. It's been around for a while, but just recently Android is recognizing Kotlin as a first-class language. It's supporting the language fully, and that's one of the reasons I created the class, because it's going to become a major component of Android. So you want to learn it as quick as you can. It was created with Java developers in mind, and with IntelliJ as its main development environment. So the source code is normally stored in files with the extension .kt. So like Java files have .java, Kotlin files have .kt. And because it was created with IntelliJ as the main development environment, we get all the great benefits of this great IDE, just like Android Studio. The most common areas to use Kotlin are server-side code, which we're not going to concentrate in this class, backends of web applications, the server-side applications you could write in PHP or Python. You could also write the applications in Kotlin. They're also going to be used a lot now on Android devices and Android mobile applications. Again, because now it's a first-class language and it's a lot of fun to use and it's very, very efficient. It's very intuitive and easy to learn. The learning curve is very low. It's an expressive, concise, extensible, safe, pragmatic, and focused on interoperability with Java code. And we're going to talk more about that in the coming slides. But these are really the goals of Kotlin. The designers kept in mind all the issues that they had with Java and designed it to be expressive, concise, extendable, and so forth. So Kotlin can do everything Java can do with less code and fewer annoyances along the way. And at the end of this lecture, I'm going to give you an example of that less code, mainly with the data classes. Very, very minimal amount of code compared to Java. It's also super fun to read and write Kotlin code. Now that you don't have to do all these tedious things in Java with Android development, it's more enjoyable to write the code in Kotlin. It's just more fun. You don't have this wasteful activities where you're just copying and pasting boilerplate code. The goals of Kotlin we just mentioned, and what these goals mean are, Kotlin has a goal of being pragmatic. And what that means is the language is practical and designed to solve real-world problems. Its design is based on many years of industry experience. Its features are chosen to address common issues and complaints encountered by many software developers. So focus on features and solutions that have already appeared in other programming languages and have proven to be successful. It greatly reduces the complexity of the language and makes it easier to learn by letting you rely on familiar concepts. So the pragmatic part of Kotlin is very, very important. Another aspect of Kotlin's pragmatism is its focus on the IDE and why IntelliJ was chosen. The tools will automatically detect common code problems, patterns that can be replaced by more concise constructs, and offers to fix the code for you. So with the IntelliSense that's built into IntelliJ and all of the common errors, it does a lot for you. Just like when you use Android Studio and you have a red circle around an error, you can right-click on it and it will say, import this package, fix this problem, create it will create an anonymous inner class, for example, for Java. For Kotlin, it will do the same things. And this is very, very important. It's practical. Common problems should not take a long time to fix. You should be able to easily select something in the IDE to have automatically be fixed for you. It increases your efficiency, reduces the time to write the code. So it's very practical in terms of the chosen IDE. It's concise. Very often developers spend more time reading existing code than writing the new code. And this is just a fact, especially when it's not your code. If you have to write additional code, you have to study it and you have to understand what it is. And if the language is harder to follow or it's just very verbose, you're going to, again, it's about efficiency. You're not going to be able to write as much code. So you have to read a lot of code to find out what you have to do. The simpler and more concise the code is, the faster you're going to understand it, and the easier it is to be able to add additional code or fix bugs. So concise code takes less time to write and, more importantly, less time to read. Kotlin's excellent design and expressive names increase the ability to understand the code. So this is the concept of meaningful names. It looks very English-like when you read it, and even non-programmers can follow it somewhat because of the descriptive names. The syntax clearly expresses the intent of the code you read and doesn't obscure it with boilerplate required to specify how the intent is accomplished. It's very, very intuitive. So a lot of the standard Java boilerplates, such as getters and setters, and the logic for assigning constructor parameters to fields is implicit in Kotlin. Kotlin has a standard library that lets you replace these long, repetitive sections of code with library method calls. And that's very, very apparent when you do a find view by ID in Android. You don't have to do that. It's just much smaller. And you have to typically do that on every onCreate call in Android. You have to get all your resources and you have to do multiple find view by IDs. With Kotlin, a lot of that goes away. And again, I'll give you an example of this at the end of the lecture when we use a data class. The getters and the setters can automatically be generated by Kotlin. You don't have to provide all that boilerplate code. It's safe. And what safe means is its design prevents certain kinds of errors in a program. Now, we know that you're going to have bugs in your program. No language or compiler can prevent all possible errors, especially logic errors. But Kotlin does a much better job than Java. There is a trade-off between the level of safety you get and the loss of productivity required to put in more detailed annotations. So what happens when you try to make a language more safe is you tend to add more things that the runtime system can know about, the JVM can know about. So you have to provide more information to the JVM. And when you do that, you may lose out on performance, because if you have to have more data, more runtime information, it can decrease the performance. And if you decrease performance, then that's not a good thing. So you have to have a trade-off here. You want to be more productive, but you also don't want to decrease performance. You can increase the productivity by having this safe operations. But Kotlin does a great job of managing this trade-off. There's a high level of safety in Java and a small overall cost. So although that Kotlin has these concepts of nullability and things like that, it doesn't cost the performance. It doesn't impact performance much. So Kotlin ensures the type safety of your applications. We're going to talk about static typing and compiler checks, but Kotlin will infer types automatically. In Java, you have to declare data types that are associated with variables, int, float, double. In Kotlin, you don't always have to do this. Depending on the data that you assign to the variable, the compiler will automatically understand the data type. So this type inference is a big deal, and you're going to notice that when we start writing some code. And also, type safety is automatically checked by the compiler because of the statically typed language. It also, and this is a big, big deal, it handles nullability much better than Java. A big problem with Java is that you have null pointer exceptions and you have to check for them. Well, Kotlin strives to remove that problem from your program. It has a type system that tracks the values that can and can't be null and forbids operations that can lead to a null pointer exception at runtime. And I'm going to show you how to do this in examples, but this is a huge deal. You don't have to worry about your program crashing at runtime because something's null, an object is null. Most of the things that are built into Kotlin will do this checking automatically for you. There's operators that you can use that can do this for you, but mainly the type system just doesn't allow you to have null pointers. It will give you compiler errors. Interoperability, another big, huge deal. that Kotlin provides. It's very easy to get started using Kotlin because of its interoperability with Java on Android. Now, if the Android or whoever designed Kotlin, IntelliJ engineers, if they decided, hey, we're going to write our own language, it's not going to work with Java, it wouldn't be used as widely. Everybody would have to ditch Java immediately for Android apps and go straight to Kotlin and learn it. Well, the designers are pretty smart because they made Kotlin available with Java interchangeably. You can keep your existing code, continue to use the various Android libraries, and incrementally add Kotlin code to your project. Over time, you can learn Kotlin. If you're not a Kotlin expert, you can start writing a little Kotlin code here and there with your Java code in an Android app. And then over time, you can add more and more and more as you realize how great the language is and how less tedious it is than Java, you can adapt it fully. But Java and Kotlin can coexist. They can mix their source files. It doesn't matter about the dependencies. It doesn't matter about anything. You can write Java code and Kotlin code in an Android app and it will compile and run. It's a drop-in replacement. You can call into the Java language from Kotlin and you can call into Kotlin from the Java language. So vice versa. Mixing the code. Very, very beneficial, and again, allows you to learn the language at a slower pace, as well as maybe you like Java in certain instances better. You use Java sometimes, use Kotlin the other times. Maybe you don't like some features of Kotlin that you don't want to use as much. You don't have to. You can use the Java language as well. So Kotlin classes and methods can be called exactly like regular Java classes and methods. You don't have to learn new things here. It gives you the ultimate flexibility in mixing Java and Kotlin code anywhere in your Android project. You can also extend Java libraries. This is the concept of extensions, and this is huge. This allows you, Java libraries and the Java APIs, you can never extend them, right? You would just use them. Kotlin doesn't have, so an example would be Kotlin doesn't have its own collections library. Collections are a framework in the Java API that allow you to store data. Using generics, you can store any type of data, linked lists, array lists, maps and sets, and you can reuse this functionality from the API. Well, if you want to add new functionality to those classes, you can do that in Kotlin by extending the collections API. So it's a really, really nice feature that you can use in Kotlin. It makes things much more convenient. These are the goals of Kotlin. At this point, I want to just show you an example of how Kotlin is so expressive, and also how you can write a lot less code with Kotlin versus Java. So I don't have, we haven't learned about the IntelliJ IDE, so I'm just bringing up Notepad++ here and showing you an example of some Java code. This may look familiar, it may not. Don't worry about it. But here's a Java class called artist. A class is defining an object, and we'll get to all that stuff. We have some member variables here, long ID, string name, so forth, and then we have get and set methods. Get and set methods are traditional, something that you traditionally include in class to provide for encapsulation. And we have all these get and set methods. You'll see that there's quite a bit of code here, get sets, and then you also have a toString method and so forth. About 47 lines of code. You can do this exact same thing in Kotlin in roughly 5 lines of code. So with Kotlin, all you have to do is create a data class. Here's a data class called artist. It has 4 member variables just like the other class in the previous example, right? We just had 4 member variables, and that's all it has. So this can show you the simplicity of Kotlin and all the boilerplate code that you do not have to write. Kotlin knows how to auto-generate all the get and setters that you would have to add manually in Java. It's also will automatically inherit some of the methods that are based off the base class of object. In Kotlin, it's not an object class, but it's an ini class. But you can automatically get the equals hash code methods in the toString method for free. You noticed earlier in this example you had a toString method. You don't even have to put that implicitly inside the class for Kotlin. You automatically get it. So again, this isn't going to necessarily make sense, but it should illustrate to you that, wow, there's a lot less code with Kotlin and you can do a lot more. The language does a lot more for you. You don't have to tediously add all this boilerplate close. So as we go through the course, we're going to provide a lot of examples of Kotlin's goals, and everything we discussed here, it will become a lot more clear. But hopefully this was a good introduction of just what Kotlin is, what its goals are, We'll talk about some of the advantages of Kotlin and some of the other language features of Kotlin in other lectures. Thank you. Hello, welcome back. Another lecture and some more important information. I want to tell you all the important features of the Kotlin programming language. This will help you understand why Kotlin is so awesome and why I recommend it. Static typing. Before we talk about static typing, I just want to give you a little overview of what a data type is. We're going to have a detailed lecture on data types and variables, but in order to understand static typing, you have to understand what data types are. And so a data type is just associating a variable with a type of data. So some examples of data types would be things like strings, ints, floats, numbers versus text. And in languages, you either have to identify the data, the type of the data, or you don't have to identify the type of the data. And that's referred to as strong or weak typing. Strong or weak typing is not concerned with static typing. Static typing is a little bit different, but I wanted to give you that overview. It's just data that's associated with variables, the type of the data, numbers versus text. So there are many interesting features in Kotlin that are shared with Java or that do not exist in Java. I'm going to try to identify those differences, the similarities, and as well as the similarities, and identify some of these great features that Kotlin has that Java doesn't. Kotlin and Java both are statically typed, but there is an advantage with Kotlin because we have this thing called type inference, which I'll talk about in a second. But a statically typed language has nothing to do with strong or weak types. All it has to do is when is the data checked? Is it checked at runtime or is it checked at compile time? With a statically typed language, the variables, the data that they have, are always checked at compile time. The JVM does support both dynamically and statically typed languages. Some of the dynamically typed languages are Groovy and JRuby. But Kotlin is a statically typed language. It checks its data at compile time. The advantages of checking your data at compile time, performance is better. When you have runtime, when you do runtime calculations in any language, it's going to hit the performance a bit. If you have dynamic lookups, polymorphism, it's always going to hit performance. If you don't have to look up the types of the data at runtime, performance is going to be increased. You don't have to figure out this extra thing. The JVM has enough to worry about. They don't have to worry about dynamically looking up data types. Programs are also a lot more reliable because there are fewer crashes at runtime. Instead of runtime finding the error, the compiler finds the error. And so if you find the error earlier, the program is less likely to crash. What happens with dynamically typed languages are that since the compiler is not checking the type of that data, you may assign number data to a string data. And at runtime, the JVM doesn't know how to handle that, so it just crashes. So compile time checking is a big deal. Code is also easier to maintain because you can identify the types better. When you look at the code and you're identifying, now this has to do more with strongly versus weakly typed languages, but if you look at the code and you see data types that are associated with variables, it's easier to follow the code. Dynamic typed languages tend to be more loosely typed versus static typing that are more strong typed, but that's not the case. They're two unrelated concepts. Also, the big feature of Kotlin in relation to static typing is this concept of type inference. Like I mentioned, in Java, with static typing, you identify the type of the data when you declare it. You say int x, float y, and so forth. It's tedious. You have to identify the data. In Kotlin, you don't always have to do this. The compiler will figure it out for you. If you're assigning a string or text data to a variable that doesn't have a type, the compiler will say, "Oh, you must be assigning a string, so I'm going to make that type of string." It automatically does this calculation for you. So types can be determined from the context. That's type inference, and it's supported by Kotlin. And it's cool. It's really cool because you don't have to specify data types all the time. It can increase productivity. Kotlin also supports the object-oriented programming paradigm, and the functional paradigm. So this is pretty cool because you can do functional concepts along with object-oriented concepts. We'll have lectures that define these methodologies in detail. But Kotlin is both an object-oriented language and a functional language. It's designed around objects. It supports concepts such as inheritance, polymorphism, and generics. Again, those terms might be completely clueless to you, but we're going to explain them. You just need to know that you can program in different methodologies in Kotlin. You're not restricted to just objects or functions. It's not a purely functional language, but it supports many concepts of functional programming. Functional program has things like Lambda Expressions, first-class functions, immutability, this concept of no side effects. So you don't have to necessarily declare anonymous interclasses every time you need to implement an event handler like you do in Java, especially with Android apps. For those of you that created Android apps, we all know these anonymous interclasses for event handlers. You don't have to do that in Kotlin because it's functional. You can pass blocks of code that represent functions. And so it reduces the amount of anonymous interclasses that you need. And functional programming also has a lot of other benefits. You don't have to use functional or object-oriented. You can do one or the other. You can mix them. It's a really good feature of Kotlin. Another big language feature is this concept of lambdas, which I just briefly mentioned. They're also referred to as higher-order functions. Lambdas lets you pass around blocks of code, providing a concise syntax for creating immutable objects. So as I mentioned earlier, Android only supports Java 6. I think with the latest Android O, it's starting to support some Java 8 features. Java 8 has lambdas in them, but Android apps don't support lambdas. So with Kotlin, you can pass around code as blocks into functions. It's a really neat concept, and it has a lot of advantages. Referred to as an anonymous function, that's what a lambda is. It can replace anonymous classes. It's only used once. It's often passed as an argument to a function. We're going to go through lambdas in great detail. You can utilize lambdas in the following situations. If you need a function to return another function, if you have a large number of very similar functions, all of which will be used for the same purpose, you can pass in a block of code. When you're generating an arbitrary number of functions based on input from the user, from a configuration file, database, or similar source, you can use a lambda and just pass that around. Again, very, very useful. Another great feature of Kotlin is this concept of null safety. We briefly talked about this in a previous lecture. But before we talk about this, we know interoperability is a big deal. That's a big language feature where you can continue to use most libraries and code written in Java. You can mix projects with Java and Kotlin code. They can coexist. There's also null safety. When you write Java code, you often have to write defensive code. This is where you have to check whether an object is null before using it. You have runtime exceptions with null pointers. It's a real pain in the butt. With Kotlin, you don't have to worry about this. You can use save call operators and many other ways to prevent null pointer exceptions. Kotlin only allows null pointer exceptions if you have an explicit call to cause a null pointer exception. You throw it with the throw keyword in Java, or if external Java code has caused it. So Kotlin is a null safety language. Less crashes. We also have this idea of extension functions and operator overloading. Extension functions, you can extend any class with new features even if you do not have access to the source code. So the Java APIs, you can extend the collection classes. You can add any new functions to any class. There's an any type in Kotlin that's supported that's similar to the Java object. It's the superclass of all types. And you can extend any class in Kotlin. So it's a better substitute than adding the usual utility classes. In the past, in Java, you would have to add a utility class if you wanted to add new features to API classes. You don't need to do that in Kotlin. We also have operator overloading in Kotlin. This is where you can redefine behavior for operators. Operators are things like arithmetic operators or logical operators, plus equals or equals equals or and. You can override all these operators to have your own behavior. So the overload operators are treated as polymorphic functions, different behavior with the same type. And as a result, they have different behaviors depending on the types of its arguments. So nice feature that Java does not have, operator overloading. And as I mentioned, Kotlin does the extension functions quite a bit with the Java collections package. Generics. Java has generics. Kotlin does too. This is kind of the opposite of polymorphism. Generics enable types, classes, interfaces to be parameters when defining classes, interface, and methods. So you have this concept of type parameters. They provide a way for you to reuse the same code with different inputs. The inputs to the type parameters are types. Typically when you pass information to a method, you pass data. You don't pass types. Generics allow you to pass in types. based on the types, you have the same behavior. You can greatly reduce your code by using generics. Like I mentioned, it's the opposite of polymorphism. Polymorphism is this concept of you have the same type of data, but you have different behavior. With generics, you have different types, but you have the same behavior. It's similar to C++ templates, if you've ever used those. There's also many other features in the language that we don't have time to discuss in a single lecture, but we'll talk throughout the class. Things like properties, similar to member variables, but more advantageous. Reflection. Reflection is an advanced concept. We'll briefly talk about it. It's a way to do compile time stuff and not have to compile things and so forth. Smart casts, this idea of the compiler automatically inferring data type conversions. Companion objects, range expressions. We're going to talk all about this, but a lot of nice features in Kotlin. Data classes, another nice feature. These simplify classes. I showed you that example in our previous lecture where you could have a data class. You don't have to add getters and setters, and you automatically have methods equals hash code copy and toString. In Java, you would automatically have to override these methods in your class. So data classes can clarify the intention of the model and what should go in it, separating pure data from the business logic. And I showed you an example of this previously. Comparison to Java. Some Java features that Kotlin lacks. Java has checked exceptions. Kotlin does not. Exceptions are a concept where if you have a runtime error in your code, as opposed to the program crashing, you can gracefully exit by handling that exception. Checked exceptions are compile time checks that Kotlin does not have. Java also has primitive data types like ints and floats. They're not objects, and as a result, you have to convert them to objects when you pass them to methods using the autobox classes in Java, integers and strings. Integers and floats, I should say. Static members. There's no concept of a static member in Kotlin. Static members are class data, global data shared amongst all classes. Non-private fields. Java has public fields. You can share the data publicly outside of the client. The client can automatically access it. You can't do this in Kotlin. Public data can cause problems with encapsulation. There's also wildcard types in Java that does not exist in Kotlin. Mainly has to do with generics. Kotlin features that are not in Java. We mentioned the Lambda expressions, passing blocks of code to functions, inline functions, extension functions, the ability to extend existing classes without the source code, null safety, reducing null pointer exceptions, smart casts, the compiler automatically infers type conversions, string templates. String templates are a nice concept where you don't have to do concatenation as much with string templates. You can have concatenation automatically handled for you with triple quotes and things like that. Properties, singletons. Singletons are creating a single instance of a class. Very nicely done in Kotlin. Operator overloading. Companion objects, data classes, coroutines. All these things we're going to talk about. There's a lot of features that improve upon Java that are included in Kotlin that Java lacks. Mainly because Android is still stuck on Java 6 and Java 8 doesn't have some of these nice things. So we're going to talk about all these awesome features. You're going to recognize how great Kotlin is, how it makes your life much easier, and you're going to love Kotlin. So thanks. Hello and welcome. Let's talk about object-oriented programming. This is a necessary topic to discuss because Kotlin is based off of Java, and Java is object-oriented, and Kotlin has objects. So, object-oriented programming is a methodology based upon objects. Objects have data and methods. It allows for software modularity and software reuse. There are a ton of advantages of using an object-oriented programming language. We're going to talk about them and also some of its properties. Objects, which are usually instances of classes, two terms we haven't discussed but will become clear. Those are used to interact with one when designing a program. You interact with these different objects. Features of object-oriented languages. The program is organized around this concept of an object, and all the data is grouped into classes of that object. It focuses on data with methods to operate upon an object's data. Objects communicate by passing data to different methods. Interaction between objects is through functions, methods. Typically, an object-oriented methodology uses the term method to refer to the behavior. You don't use the term functions. But Java sort of started this convention. C++ uses member functions. It's really just a personal preference. But if I use the term function when I'm talking about Kotlin or whatever, an object-oriented language, it's the same as a method. Reusability of design through creation of new classes by adding features to existing classes. So it's very easy to add new features when you have this concept of an object. You can just add new behavior using methods, or even easier, you can subclass using inheritance. Examples of object-oriented languages include C++, Java, Smalltalk, C#, and many, many more. PHP has objects. Object-oriented design and programming is really the way to go nowadays. Structural language or something like C or something organized around functions that uses a lot of global data is just more problematic. It's harder to maintain. So any modern programming language usually nowadays contains objects. Kotlin is no different. It's going to have objects, a lot of advantages. Some terminology. We have to understand what an object is if we're going to understand object-oriented programming. Objects really can be thought of as a noun, a person, place, or a thing. Right now, wherever you're sitting, look around. Look around in the room. What do you see? Typically, you'll see an object. So I'm sitting here at my desk. My desk is an object. A table could be an example of an object. A TV, a car, a microwave. Really, anything that's a noun could be an object. And that's how you represent your program. You represent as a collection of objects, things that you can act on. Each object has a state and behavior, right? So, for example, if you had an object that was a dog, dogs have state. They have a name, a color, a breed, a hunger. They have characteristics. Characteristics, same as state. They also have behavior. They do things. Behavior things like for a dog would be barking, fetching, wagging its tail. There are so many examples. Bicycles have state, properties, current gear, current pedal cadence, current speed, and they also have behavior. Changing gear, changing pedal cadence, applying brakes. Cars can be thought of as an object. They have characteristics, make and model, color. They have behavior, accelerating, decelerating, changing the engine, changing a tire. That's all behavior. So we can think of objects as real-world entities that you can perform operations on by calling methods, essentially, and that all have characteristics and characteristics as attributes, member variables. It's a really neat concept, but it's really relatable and practical as well. Methods operate on an object's internal state and serve as the primary mechanisms for object-to-object communication. That's how you communicate, by calling other objects methods or passing objects to other methods with the uses a relationship. Classes, another big term. Classes is the blueprint for an object. It's where the definition of the object resides. So in the real world, you'll often find many individual objects of the same kind. So if you have an object like a car, there are thousands of cars. Right? All cars have the same make and model. They have the same characteristics. They share the same characteristics. They're built from the same set of blueprints, which is a class definition. And therefore, they have the same components. In Kotlin or in Java, you would create a class called car. You would define the characteristics in that class. You would define the behavior in that class. The characteristics are represented as member variables. The behavior is represented as methods. All instances of that class have the same member variables in the same behavior, same methods. So they share this. But they have different values for that data. So I may have my dog. My dog has the same characteristics of all dogs, but it's a different color. It's a different breed. But it shares all the same behaviors. All dogs can bark. They all can run and so forth. So member variables have specific values based on the instance. The instance is the actual object. So you create individual objects from the class definition. You define your class. In Java, you can create an object by using the new keyword. And we'll talk about how you can create objects in Kotlin. An instance of an object is the object that was created from the class. Again, thousands of instances. A class is just the blueprint. It defines all the attributes. Inheritance, this is a concept associated with object-oriented technology. Some objects share commonality, same characteristics or behavior. For example, cars, motorcycles, trucks, and boats all share the characteristics of a vehicle. They all have a speed, they all have a color, make, model, type of engine. They share some of the same attributes. They also have some of the same behavior, right? They all can maybe accelerate, decelerate, they all can change their engine, they all can change, I was going to say tire, but that's not true. They can change other common behavior characteristics. Now, although they have a lot of common characteristics, they may also have unique characteristics that make them different. So in an example, trucks have four-wheel drive, or they have a cab, right? Cars don't have that. Boats don't have that. Motorcycles don't have that. Cars have four doors and different behavior concerning driving. Motorcycle doesn't have four doors. Boats operate on water and have an anchor, right? These are unique characteristics, unique behavior. So object-oriented programming allows classes to inherit these commonly used state and behavior from other classes. So everything that's common you can automatically get through inheritance, this concept of inheritance. What this means is you have this base class, this superclass. Remember, a class defines an object. So you have this class that defines all these characteristics that are shared, all the behavior that's shared, it's defined in a class. That's called the superclass. So for example, a superclass of a car, motorcycle, truck, and boat would be the vehicle class. That would be the base class, the superclass that defines all the commonality. You then would have something called a subclass, child class, derived class, whatever term you want to use. And the subclasses would be the things that identify the uniqueness. That would include the car, the truck, the boat. You could even go further from that and have even more subclasses, because we know all cars have some differences, right? Some cars have different behavior. You may have maybe you would have a car like an SUV versus a different type of car, a mid-sized car, something like that. Trucks could also have more specific behavior. So again, the concept here is you have this hierarchy, this tree, with at the very top of the hierarchy, everything is common. As you move down each level, you get more and more unique. And the big advantage of inheritance is this concept of software reuse. You don't have duplication. All the commonality can be in one class at the top, and all the other classes still get that commonality, but you don't have to define those characteristics or methods inside the subclasses. So this is a common characteristic of object-oriented technology, inheritance. And luckily, Kotlin supports inheritance. So we'll provide detailed examples on inheritance in Kotlin, but you need to understand the concept. High-level concept, very, very advantageous for software reuse, avoiding duplication, this concept of a superclass and a subclass. Interfaces. Interfaces are objects. We mentioned already, objects need to communicate with one another via their methods. And typically the way they do that is they have public methods. They expose their methods via an application programming interface. And that's referred to as an interface. So a more real-world example would be the buttons on the front of your television set. Those are an interface between you and the electrical wiring on the other side of the plastic casing. Right? So you can press the power button. When you press the power button, the TV goes off. But you have no idea what's going on after you press the power button. The internals do something. The only thing that is exposed is that power button. So an interface is what you're exposing. The interface would include the power button. When you hit the power button, the behavior would do something. That's the high-level description of an interface. Now, an interface in object-oriented technology is a group of related methods with empty bodies. It's an abstract class. It doesn't have any attributes, properties. It's just a class that defines methods. And a class with no properties and method definitions. Classes that implement an interface must implement all the methods defined in the interface. So what an interface really is, it's a contract. It's saying that if you implement my interface, you have to implement these methods. And so what happens in interfaces, the interfaces are what the client sees. Anybody that wants to reuse a class, you can see what that class does by an interface. So a lot of the Java API, a lot of the Java packages that come with the language define interfaces that you can access. And then the abstraction is hidden behind the interface in implemented classes, concrete classes. So interfaces, we'll talk more about this, but I wanted to describe the term to you just so you know what it is. It's in a way to provide abstraction. It's a contract between a client, anybody that implements that interface. It doesn't have any properties, just methods, just behavior. Other terminology closely associated with object-oriented design: polymorphism. This is we talked about generics a little. Generics are where you have different types with the same behavior. Polymorphism is a runtime thing. It's not a compile time thing. So when you run your program based on the type of the object, it will run certain behavior. So you have different behavior based on type. And we'll provide examples of this, but it's a really neat concept. You're required to have overriding. When you have polymorphism, you're required to implement inheritance. But another advantage of polymorphism, just like inheritance, is you can reduce duplicate code. And you can pass around reference objects, and then at runtime, the language will decide where to go, the JVM. A package is a namespace that organizes a set of related classes and interfaces. It groups a number of classes or interfaces. You should be, if you're not, Java has a number of packages that you can access as part of the language. They have a package for networking, so there's a bunch of networking classes. They have a package for writing to the console, so there's a bunch of those. There's writing to files, so there's a file package. Groups functionality together, way to group all of your objects and classes. Encapsulation: this is a mechanism that allows each object to have its own data and methods. What you'll usually do in object-oriented technology is you'll have private data members with getters and setters, get and set methods. This is what that data class I showed you in Kotlin is all about. It's having these get and set methods so that you hide data. It's information hiding. It allows data to not be corrupted or accessed globally. So it's important. You don't want to have global data because it's harder to maintain your code. If you have data that can be modified anywhere, and this is what we talked about when we talked about functional aspect of languages, the less data changes, the better. If it changes and then it also changes all over the place, it's going to be really hard to find where it changed, where the bug is. So encapsulation can reduce maintenance. Overloading: this is where methods have the same name but a different number of parameters or type of parameters. Multiple methods that take different types. We'll provide examples of this as well as we go through the class. Overriding: this is an inheritance concept. It's required for polymorphism. It's when you have a method in the subclass that's already defined in the parent class, the base class, the superclass. So we talked about inheritance where we have commonality in a superclass. Well, you're going to have that same functionality in your subclasses, but sometimes you want to change it. So subclass is not just for uniqueness, it's also for overriding any commonality that you want to change. And you can utilize this polymorphically. Advantages of object-oriented technology: objects provide modularity, and for some reason I typed that twice. Should do a better job of my checking here. Anyways, objects provide modularity. Modularity is this concept of breaking down your code into modules, and an object is a module. At a more granular level, an object or a module could be a method. But when you break things down into smaller chunks, it's easier to maintain. It's an advantage. So encapsulation and objects are made independently from other objects. They're not dependent on other objects. And as a result, an object can easily be passed around inside the system. And you don't have to worry about bad things happening with data changes if you have good encapsulation. So modularity is always an advantage of a language. Information hiding: by interacting with only the object's method, the details of the internal implementation remain hidden from the client's abstraction. You can do abstraction through these interfaces. Big advantage. You hide complexity. If I want to use a Java package, I don't have to know how that's implemented. I don't have to understand how networking is working in Java in order to utilize a networking class. Software reuse, a big deal. If you can reuse software, it's more efficient, right? It's quicker to write code if you can reuse code. So you can reuse objects in a program with object-oriented design by just including that object. The Java API is an example of reuse, software reuse. All the packages associated with the collections framework, everything. That's all part of the API. Inheritance and interfaces also allow for software reuse because you're putting commonality in the base classes. With interfaces, you can pass around an interface object a reference object, and you don't have to have multiple objects that take different types of parameters. You can just have it take an interface. So maintenance is easier. It's much easier to maintain your code. It's easier to add new features when you have objects that have encapsulation. It's much easier to fix issues because you can just replace an object. In inheritance, you can just add a subclass. So you want to add a new feature in an object-oriented system, add a new subclass. You want to fix an issue, it's going to be easier to find because classes are encapsulated. So object-oriented programming is the way to go. In this class, we're going to use object-oriented programming along with functional programming because they both have good advantages. And we'll dive into much more detail on how to create classes and how to utilize objects in code. Thank you. Hello everyone, welcome. Since Kotlin supports functional programming, we have to talk about functional programming. So functional programming, it's a programming paradigm, it's a methodology, it's how you approach the writing of your code, how it's organized. In functional programming, you create the software by writing functions. Everything is essentially a function. And as a result of writing functions, you avoid shared state, shared global variables. You don't have problems with sharing the data all over the place. You use immutable data. Mutable data we'll talk about, but it's data that doesn't change. And as a result, you have no side effects. And we'll give examples of side effects, but side effects can cause things to change. Your program is changing state. Functional is declarative rather than imperative. There are mainly three types of programming languages. You have your imperative languages that are structural in nature. You have statements. They consist of statements, logic. Statements are run sequentially. Examples of imperative languages are things like Java, C++. It includes object-oriented languages. You have declarative languages, which is what a functional language is. Declarative language is this concept of the application state flows through pure functions. You don't share a lot of data. You don't have immutable data. Really what you're doing is you're describing the what. And then the third type of programming language is a logic type language. Examples of this would be like Prolog or Lisp. Used for artificial intelligence, you have predicates, you ask questions, you get answers, you have rules. A little different. But each one has its own characteristics. And if you look at each one, they seem really, really different. But they aren't necessarily. I mean, they still accomplish the same goals. Most of you have probably programmed in imperative programming or have not programmed at all. Imperative is probably the most intuitive just because you're used to it. But functional languages and this declarative concept, very easy to understand once you get started. So you don't share application state, usually shared and co-loaded with methods and objects, with imperative languages and object-oriented programming. Declarative program logic is expressed without explicitly describing the flow control. You just say what to do. This is what I'm going to do. I'm going to call a function. Function's going to get this data. It's going to do this. You don't have a lot of control flow. It relies more on expressions and statements. Expressions are things like calling a function, passing data to it. An expression would be adding two numbers. A statement is more of like a declaration, an assignment, a condition, things like that, where you have more logic. Functional programming uses lots of generics and reusable code. Generics are this concept of taking any types and having the same behavior. And functional programming, because you're calling functions and you can pass in blocks of code, lambdas, you can reuse the code a ton. You don't have to define a ton of functions for all sorts of different configurations. You can use lambdas. Some examples of functional languages include Lisp, Scheme, Haskell, and ML. I actually learned Haskell and ML when I was in college. It was a big difference when I first learned it. It was a little tough to follow, but it has a lot of advantages. Some terminology, if you want to understand functional programming, you have to understand some of the terms that go along with it. Pure functions, you're going to hear this a lot in functional programming. Pure functions are you work with functions as pieces of behavior, as values. Right? So functions have values, they take values and so forth. You can store functions in variables. A function is a value, right? So it's kind of a different thing. Usually you call a function, you invoke it, but if you can pass around functions as input to other functions, it's pretty cool. You can do a lot. So you can store functions in variables because they're just values. You can pass them as parameters, or you can return them from other functions. Pure functions, if you're given the same input, you're always going to have the same output. You're not going to have any side effects. Side effects will have global impact. And so functions are always going to return the same data. You can expect the same outcome. Pure functions. Functional composition or function composition. This is the process of combining two or more functions in order to produce a new function or perform some computation. Not much to say about that. It just means that you're utilizing two functions to produce a new function. Shared state, any variable, object, or memory space that exists in a shared scope or as the property of an object being passed between scopes. This is a concept of shared state, and you don't want to share state in a purely functional programming language. Shared state and this concept of kind of global data can be very problematic. Functional programmings do not share state. They rely on immutable data structures that do not change, and pure calculations to derive new data from existing data. Immutability and side effects. Immutability is exactly what it implies. It's an object that can't be modified after it's created. A mutable object is an object that can be modified after it's created. Functional programming in Kotlin do not allow objects to be modified if you're using them in functions. The state cannot change after the creation of the object. Immutability is a central concept of functional programming because without it, the data flow in your program is changing. And if it's changing, you're not going to get the same results in a function. You're not going to have pure functions. Side effects. This is again avoided in functional programming, just like sharing state data. Any application state change that is observable outside the called function other than its return value. So anything that changes outside of the function. Examples of side effects are modifying any external variable or object property, a global variable. So if your function takes data, you modify that data inside the function, and it affects data outside the function, that's a side effect. And that's what global data does. You're going to affect things outside of the function. Logging to the console, that's also an example of a side effect. Writing to the screen, writing to a file, it's outside of the function. It's doing something externally. Triggering any external process is a side effect. Advantages of functional programming. Why do we use functional programming? Why should you utilize it in Kotlin? The code tends to be more concise. It's more predictable. It's easier to test than imperative or object-oriented code. When you have control flow and data is changing and you're using global data, anything can happen. It's harder to isolate bugs. It's just functional programming is much more concise. With testing, the testing is a lot easier because you don't have all this coupling and all this dependencies. So if you have a function that's isolated, it's much easier to test. And for you test geeks out there, you should know this. If you've ever tested with legacy code, old code that's tightly coupled, it's really, really hard to test because you end up testing 10 other functions. With pure functions and no side effects and no shared state, the functions are easily tested because they're essentially isolated. You don't have to isolate the code or create new functions or new files for the functions. Very, very easy unit testing. Another advantage is it gives the programmer the ability to provide abstraction better. Abstraction is an important concept. Abstraction is the idea of reducing complexity or at least not showing the complexity to a client, somebody using a class or an object. If you can provide better abstraction, hide implementation details, this lets you avoid duplication in your code. It's just much less complex. So you extract the common part of the logic into a function and pass the differing parts as parameters. This is how you can provide abstraction. The parameters act as Lambda expressions. So you have blocks of code, lambdas, you pass them into a function, things that are different as the parameters. And this allows for abstraction. The function itself doesn't have to know about those different parts, right? It can just operate on it. So you can extract anything that's different inside of a function and just pass them in as lambdas. Immutability allows for safe multi-threading. We're not going to talk about a lot of multi-threading concepts, but multi-threading can be very problematic. Multi-threading is the concept of having multiple execution points in a program. So as opposed to a single execution point, multiple code could be accessing data at the same time. And this can cause race conditions where one component of code could change something and the other component might not get that change, or it's a whole nother concept. But really, to take away from this is immutability allows for less multi-threading problems. Kotlin support for functional program. How does Kotlin support these concepts? One is they have functional types. They allow functions to receive other functions as parameters or return other functions. They have Lambda expressions. Lambdas are just blocks of code that you can pass around. This reduces boilerplate. And so Lambda expressions are functional. Data classes, providing concise syntax for creating immutable value objects. Right? They have getters and setters. They just have data. The data doesn't change inside the class. So the data classes are concise, and you don't have changing data, state data for objects. A rich set of APIs in the standard library for working with objects and collections in the functional approach. So we can use functional programming in Kotlin through the standard library to work with objects. We'll see that as we go through the class. Kotlin supports functional program, but you're not required to use it, right? You can just go the object-oriented route if you're more comfortable with that. I would recommend at least try functional program because of the advantages we just mentioned here, but only use it when you need it. So you can work with mutable data and write functions that have side effects without jumping through any extra hoops. You don't have to have this functional approach where functions don't change and so forth and always return the same value, no dynamic in it. But there are advantages to the functional programming. So at least give it a shot. Start using the lambdas, start using functional types, start using data classes. It's a good programming practice. You can combine both the object-oriented and functional approaches and use the tools that are most appropriate for the problem you're solving. And this is really the best approach. Don't just get focused on, I'm only going to use objects, I'm only going to use a functional style. Use both, depending on the problem. You always have to do that. As a programmer, as a problem solver, you do what you need to do based on the problem. You solve the problem. As long as you solve the problem in an efficient and a good programming practice manner, you're good to go. And usually that involves both approaches, both the object-oriented and functional approach. So as we go through the class, this will become clear because we'll use lambdas. I'll show you how to use them. You'll see how state data doesn't change. You'll see this immutable data for objects and so forth. This is just to get you an introduction to what functional programming is. Thank you. Hello and welcome. In this lecture, I would like to talk about the advantages of Kotlin. Some of this we've discussed in previous lectures, but I wanted to be explicit. I really wanted to show you the benefits of Kotlin in detail. So, compatibility, big advantage. This is this idea of interoperability, right? So we're fully compatible with JDK 6. This ensures that Kotlin applications can run on older devices with no issues. So when you write an Android app, you want it to be able to run on as many devices as possible. Typically, you'll support Android API level 15. Those are older devices. You don't have to worry with Kotlin because Kotlin runs on JDK 6, and so it's going to run on all the older devices that use JDK 6. So this is a big deal. If you had a language that didn't support older devices, it wouldn't be very good to use. So you can benefit from all these cool new language features of Kotlin, and your users will still be able to run your application on their devices, even if they don't run the latest version of Android. We like this. It's fully supported in Android Studio and compatible with the Android build system. Again, we're going to write Android apps. Better work in Android Studio and better support a lot of devices. This compatibility thing is a big deal, and if Kotlin didn't support this stuff, we wouldn't be using it. Performance. Kotlin runs as fast as an equivalent Java application, mainly because the bytecode is very, very similar. We know the bytecode gets interpreted by the JVM. So it really, as far as the JVM, it doesn't know that it was written in Java or that it was written in Kotlin. It just interprets it and runs the application. Now, because the footprint, the size of the application and all the data going to the JVM is roughly the same, there's no performance differences between Java and Kotlin. Some people may argue that Kotlin runs a little slower, but with Android apps, it's not a factor. Also, Kotlin supports inline functions. The code uses Lambda, and these often increase performance. So there's also things that make up for some of the inadequacies of Kotlin in terms of extra information. Some of the compile time checks that Kotlin does gets offset by the use of lambdas and inline functions. Interoperability, similar to compatibility, except it has to do with the languages, right? So Kotlin's 100% interoperable with Java. We talked about this quite a bit, so I'm not going to cover it in detail, but you can write Kotlin applications intermixed with Java, vice versa, whatever you want to do. It's a really, really nice feature. You can call new existing libraries in a Kotlin application, in Android libraries. There's specific Kotlin packages that provide wrappers and so forth. Footprint. The footprint of a Kotlin application is very small. It's roughly the same size as a Java class, Java bytecode. So it's a very compact runtime library. The runtime adds only a few hundred methods and less than 100K to the size of the APK file. It's pretty nice. Compilation time. How long does it take to compile your code? This is usually not a big deal at all. If you have a really, really big project with hundreds of thousands of lines of code, this would be more important. But a lot of the apps that most people write, you have 5-10 screens, not too much there. But the compilation time is good. So Kotlin supports an efficient incremental compilation, so there's no additional overhead for clean builds. Incremental builds are usually as fast or faster than Java. Nice. Easy to learn. We talked about the learning curve for Kotlin. Very, very easy, especially if you're a Java developer. If you're a Java developer, you can pretty much understand the Kotlin language at a high level in a few hours. To become an expert at Kotlin may take you a little longer, but not that long. It's rather small. It's not as big as Java with all the APIs. So the syntax is lean and intuitive. We talked about how the language is very concise and how it's very very descriptive. So you're using descriptive names and you're easily be able to understand what a program is doing in Kotlin. It's very expressive. That's the term I was looking for. It's also very, very reliable. We talked about null types. This is a big deal, right? You have less crashes, less null exceptions. So because of the type system and this tracking null values, problems with null pointer exceptions go away, reliability increases. Most of the code that would lead to null pointer exceptions in Java fails to compile in Kotlin. So, big deal, more reliable. Better efficiency as a program, and this is a big advantage, and this is one of the reasons you're going to want to use Kotlin. You're going to have more fun writing Kotlin. You're not going to have to write all this boilerplate code in Java. I like the Java language, it's great, but it is tedious, and you do have to write a lot of code. So, and it is less efficient. So if you write Kotlin and you have all these nice data classes that do things for you, you have these nice APIs that can get rid of anonymous classes, all these nice things, it's much more fun to write the code. So common development tasks such as adding listeners to controls or binding layout elements to fields can be accomplished with much less code, or sometimes with no code at all. The compiler generates a lot of code for you. We saw that data class in an earlier lecture where a Java data class with getters and setters had like 15 lines of code. The same exact class in Kotlin had like 5 lines of code. So you're going to be more efficient when you write code in Kotlin than you are in Java, especially because of the removal of all the boilerplate code. There's also friendly adapters around. For many of the standard Android APIs, adapters are essentially wrapper classes. They are created so that Kotlin can better effectively communicate with Java packages. Now, we know that Kotlin can automatically call in the Java packages, but if you add these adapters, it makes it even easier with less code. One of these adapters is the Anko library, which provides a lot of this functionality. We'll talk more about the Anko library later. It's free and open source. Wow, this is a big deal. No one wants to spend money when they do their development. So the language, including the compiler libraries and all the related tooling, is entirely open source and free to use for any purpose. It's not like iOS, right, or Macs, where you have to buy a ton of hardware and you have to buy, well, I guess that's a little different because you still need hardware for Kotlin, but you don't have to pay for the language. You don't have to buy a developer license. You don't have to spend all this money to start writing code. It also has terrific support and great tools. We know we're using the IntelliJ IDE. You know Android Studio is based off the IntelliJ IDE. If you've ever used it, super intuitive, super useful. Ton of great features. right? It has IntelliSense. It completes code for you. It also finds and fixes errors for you before you compile. It has an awesome debugger. It has awesome monitoring tools. You can easily interact with the Android file system using DDMS. I mean, there's all nice stuff about the IDE. A bunch of nice templates. You can create simple classes by using the templates. It will generate layout files for you, all sorts of nice things. There's also an awesome Java converter tool that we're going to talk about when we talk about tools, but you can write Java code and it will automatically be converted to Kotlin by the click of a button. And in that way, you can compare and contrast, and you can learn Kotlin a lot quicker by doing this. So there's a Java converter that's nice to use. Kotlin comes from industry, not academia, so it solves practical problems for working programmers. If it comes from academia, you have research, and research tends to not solve practical problems. They just do research and theoretical things. The fact that it's so practical is it's not solving problems that people don't care about. It's solving problems that programmers encounter. That's the end of our first section, our introduction to Kotlin. And hopefully everybody's still awake, because this was a lot of talking, a lot of lecture material. As we move forward in the class, we're going to do a lot more practical stuff. We're going to do hands-on things. We're going to write code, we're going to see examples, and we're going to be learning by doing. So hopefully everybody didn't fall asleep during the introduction section, and they'll stick with me through some of the nice hands-on training when we go and we actually write some code. We're going to start getting into more exciting stuff, so stay with me. Thank you. Hello and welcome. We're at the point in the class where in order to do anything productive, we have to install some software. There are two requirements to get your Kotlin code running. Installing the Java Development Kit, which is the Java Programming Language, JDK. We know that Kotlin is based off of Java, and we need that JVM, the Java Virtual Machine, so we have to install the JDK. We're also going to install IntelliJ. IntelliJ will be the integrated development environment that allows us to create and edit our Kotlin programs. But let's first start with Java. Very easy to install Java. To install the JDK, you can go to one of the two following links. Either one will take you directly. You just have to paste this into your browser, and once you're done installing, then you have to make sure that your Java path environment variable is set up. So I'm going to bring up my browser and go to one of these sites, and we'll proceed from there. Okay, so I have Chrome up. I'm going to go ahead and paste in the website, oracle.com, Tech Network Java, Java SE, which is a standard edition, downloads, index.html. When I go to this website, you're going to see Java Standard Edition downloads for the JDK and also NetBeans IDE. You don't need that. You can just select Download Java JDK. This is going to take you to another page where you can select the version that you want to download. We want to download Java 8. Even though we're only using a lot of the features in Java 6, because that's all that Android supports, we still download Java 8. You have to select the correct platform for Java that you're running, that your computer is running. So if you're running Linux, you have to select Linux. If you're running Windows, you have to select Windows. I'm doing my development on Windows, so I'm going to select Windows x64 here at the bottom. Before you can download anything, you have to accept the license agreement. So don't forget to select the radio button for the accept license agreement. Select the link. Once you select the link, it will start your download. You can put your download wherever you want on the system. Usually the best spot for it, well, actually for downloading the link, the executable, you can put it anywhere. When you install it, you want to probably put it in program files. So I'm going to go ahead and start the download. The download, it's about 200 megabytes. Depending on your network, it may take a couple minutes to download, maybe faster, maybe longer. Mine's going to take about 3 minutes. Okay, once it's done downloading, you'll want to execute the exe if it's Windows. If it's Linux, it may be a tar file and you have to extract it. But you need to go and execute that, double click on it for the exe in Windows. Make sure you say yes if you have any firewall things you need to run. But once you start installing, it's going to be pretty straightforward. It's just going to run a wizard to install the Java. So you're going to see a screen like this where it has some information. You can basically just keep hitting the next button. So if you hit next, it's going to ask you what to install. It's going to install it in Program Files Java. You can go ahead and click next. It will start doing some things. It's a rather fast installation. But again, pretty straightforward. You shouldn't have any issues. You may see this folder where if you want to change it or install it to a different file, you can select the change. I'm going to just keep it in the default folder, which is C Program Files Java. The last screen you'll see is this successfully installed screen. You can hit close and you've successfully installed Java. The only other issue is that although you've successfully installed Java, your system might not be able to see it. So you have to make sure that your path environment variable is set up correctly. The way that you can verify whether or not your system can see it is you can go to the Start menu and you can go to the DOS prompt. If you go to search, you can just type in command. I've been having problems with my search, so if command doesn't work, you can type in CMD. And once you type in CMD, you should see a little black box and you can run your DOS command prompt. This is just the prompt that allows you to enter in commands, so forth. What we want to test here is whether or not our path variable is set up for Java. So if we type in Java C, which is the Java compiler command, and we type enter, if it says Java C is not recognized as an internal or external command, that means that your path environment variable was not set up correctly. If you see a list of options, that means it is set up correctly. So if it's not set up correctly, what you'll have to do is you'll have to go to the Start menu, and you can go to search and type in environment variables, and you should get to the same spot. Or you can go to the settings option, and once you're in settings, you can type in environment variables, and you can say edit the system environment variables, and you'll see this little screen come up. Inside here, you have to select environment variables under the advanced tab, and under the system variables, you want to select path, and you want to say edit. And when you say edit, you want to add the path of where Java is installed. So you can bring up Windows Explorer to find the path of where Java is installed. You may have selected a different path, but if you selected the default path, just in the previous installation step, which is C, Program Files, Java, you'll see here that I have many Java versions installed. You want to make sure you select the JDK version, not the JRE. The JRE is the runtime environment. You want to select the development kit. So here for JDK, I'm going to select that, and I want to select the bin folder because this is where all the executables are located. Once you select that, you can go up to the address bar here, and you can either click it and say copy, or you can say copy address. Once you've added or copied it, you can then go back to the environment variables and add it. So inside here, I can select my path variable as a system variable. I can hit edit, and then I can say new, and I can just copy and paste in the JDK path. Do a Control V or right click and say copy. Make sure it's JDK and then bin. Once you say OK, you can start clicking OK, and then you can go back to the DOS prompt and test to see whether or not your system can see the Java executable. So right at the DOS prompt, you can just type in Java C, hit return, and if you see something like this, which is information that you can pass to the command, that means you're all set and everything's good to go. So a pretty smooth installation of Java. The next step will be to install IntelliJ IDE so we can start writing our Kotlin programs. Thank you. Hello and welcome. In this lecture, we're going to install the IntelliJ IDE, a pretty straightforward process. Again, we need to install this in order to write Kotlin programs. We've installed Java. We now need to install our integrated development environment so that we can compile, run, debug Kotlin programs. The link that you need to put in your browser to download is just the JetBrains link. It's pretty straightforward. HTTPS www.jetbrains.com/IDEA/download. HTTPS www.jetbrains.com/IDEA/download. So I'm going to paste this link into my browser, and you may or may not go to a platform page. I've been here before, so it took me straight to a Windows page. If you've never been to this site, you're going to see a page that says, where do you want to install? Windows, Mac OS, or Linux. This automatically selected Windows for me because I'm on Windows. So all you need to do, depending on your operating system, select that. You can either select the Ultimate or the Community. The Ultimate just has a free trial, so I would select the Community. You can just select Download from Community Open Source. And this will bring up a window where you want to download it. I'm just going to download it in my Downloads directory. And this is about 340 megabytes. May take you a few minutes, but it will start downloading. While it's downloading, you can go ahead and take a look at some of the features of the IDE. I'm going to talk about these, and I'll be using a lot of these as we go through, but If you're bored, go ahead. Once the download is finished, you can just double click the executable. It will be similar if you're on a Mac. If you're on Linux, you may have to extract a tar and run a shell script. But once you execute the executable or click the executable, the process is pretty straightforward. Again, if you see any firewall things, make sure you bypass the firewall. First screen you'll see is this nice wizard screen. Welcome to IntelliJ. You can select Next. You can keep it the destination folder by default, which is in your program files, somewhere under JetBrains. And you can also create desktop shortcuts, 64-bit launcher versus any associations. You can say, if we're doing Kotlin, you can say .kt or even .java so that those files will automatically open up in this IDE. And you can also, I'm going to select 64-bit launcher. I'm going to hit Next. I'm going to hit Install with the defaults, and then the installation process will start and it will create the shortcut. This may take a few minutes. Once the installation is finished, you'll see this screen, which is the complete screen. You can run IntelliJ if you select the box, or you can double click on the icon from the desktop. I'm going to go ahead and run it and just hit Finish just to make sure that my installation was successful. You can import settings from other IntelliJ IDs, so I have Android up so I could import it. I'm just not going to import any settings. And then it will come up with a policy agreement. You can say Accept. You can read through it if you like. You can also customize your IntelliJ IDE if you want to have a different theme. I'm just going to go ahead and just skip all and say Set the Defaults. And that will start up IntelliJ, and it has this nice splash screen for you. And for those of you familiar with Android, this looks very, very similar. We're going to go and go through on how to create a project. But at this point, you should have IntelliJ already up and running, and you should be able to start and write Kotlin projects. Thank you. Hello and welcome. Before we create our first Kotlin project in IntelliJ, I wanted to give you a little overview of some of the tools that are available for Kotlin. So there's a Java to Kotlin converter. This is very, very useful. It converts existing Java code to Kotlin. There's a menu option inside the IDE. This will speed up your learning and adoption by relying on your existing knowledge of Java. I talked about this before, but this is a super useful tool because if you're really good at Java, you can write code in Java and then see what it looks like in Kotlin. And it's a great way to learn Kotlin as well. Also, if you're unsure of your Kotlin code, you could write it in Java and then see how you write it in Kotlin. So it can help you express something when you don't remember the exact syntax. So you can write the corresponding snippet in Java and then paste it into a Kotlin file. And the converter will automatically offer to translate the code into Kotlin. Using the converter is very easy. You can use it in the IDE, IntelliJ, or online. You can copy a Java code fragment and paste it into a Kotlin file. That's one way to convert it. Or you can go to the menu option and invoke a convert Java to Kotlin file action if you need to convert the entire file. So let's try and do this. I'm going to go ahead and bring up my IntelliJ IDE by double-clicking it on the desktop, the icon. When this comes up, if you haven't created a project before, you're going to see this Welcome to IntelliJ screen. You're going to see this with options to create a new project, import the project, open, and check out version control. I'm going to show you in details how to create a new project, but in order to show you the converter, I have to have a project up. So I'm just going to create a simple project really quickly. We'll go over this in more detail. You want to make sure you have your project SDK version set if you have problems doing this. This should be pointing to your Java path that you just installed. But I'm just going to keep everything default and create a sample project. And once we have that up, you'll see the show tips on startup. Again, we'll cover this later. You'll see that there's a project here and there's no source file. So I'm going to go ahead and just create a Java source file, new Java class, and I'm just going to name it test. And I'm going to write some Java code. So I'm just going to write a public static void main method. This is just standard Java code. And I'm going to just print out something to the screen. and add a semicolon. My semicolon key is broken, so got to get that fixed. Anyways, so this is a simple Java program. Again, you don't need to understand the details of this. It's just a Java program. I want to show you how to use the tool to convert to Kotlin. So first, if we want to build this, we can just build it to make sure there's no compilation errors. But it's very, very easy to convert to Kotlin. You can go to the code menu up here, and you can go down, you say convert Java file to Kotlin file. Once you do that, it's going to start converting it. It will tell you, give you a little warning saying some code in the rest of your project may require corrections. Do you want to find such code and correct it too? And just say OK. And then once you do that, it converted it to Kotlin. You see it's not Java anymore. It has a fun keyword. There's no more there's an object for class, and there's a println as opposed to a system.out. You can also convert your code if you were to bring up a Kotlin file. It may do it for you implicitly. You can also use the online converter. So if you bring up a browser and you go to the Kotlin site, which is right here. If you go to the kotlin.org, try.kotlinlang.org, and you select that, this will bring up an editor where you can write Kotlin code and run it. But you can also convert from Java. So if you convert from Java, if you hit this button right here, this menu option, you can start writing Java code, and you can see how it's converted to Kotlin. So if you say public class JSON, and then you just want to convert it, you can scroll down here and say convert to Kotlin. Hit the button, and it will say class JSON. So two very useful tools, converting your Java code to Kotlin, either online or in the IDE. Another useful tool is the online playground, which I just went to. That's where the converter was shown. But if you go to kotlinlang.org, you can write, compile, and run your Kotlin programs. This also includes code samples demonstrating the features of Kotlin, as well as a series of exercises for learning Kotlin interactively. So that was this website, right, where it had our editor, and it also has basic syntax walkthrough, deconstructing declarations, Kotlin cones, which are exercises that help you learn the language better. All sorts of nice resources here, but the big resource being the editor and the convert from Java button. Well, it's a nice little online tool you have if you didn't use the IDE, IntelliJ IDE, but you can't write big programs here. You only write small ones. Another tool is the interactive shell. If you want to quickly try out small fragments of Kotlin code, you can do that using the interactive shell. This is called the REPL. You can type Kotlin code line by line and immediately see the results of its execution. To start the REPL, you can either run the Kotlin C command with no arguments or use the corresponding menu item in the IntelliJ IDE plugin. So let's bring up IntelliJ IDE and I'll show you that. So once you're inside here, you can go to the Tools option and you can go to Kotlin and you can go to the Kotlin right there at the bottom. Once you select that, you can start typing in commands. So what you could do is you could just type in simple things like you could do 2 + 2, and you have to hit the play button to run it, and that will say 4. You can say print welcome. You don't need that semicolon at the end. Again, hit the play button, and when you hit the play button, it will print welcome. So you can run snippets of Kotlin code in this interactive shell. Pretty useful. Other nice tools are the Kotlin Android extensions and the ANCO. The extensions allow developers to perform basic Android functions using libraries without having to add any extra code or shipping any additional runtime. You can use these libraries. So it allows you, these extension libraries allow you to get rid of some find view by ID calls in your code as an example. We'll go through this in class, but it's a nice tool to have these Android extension libraries that provide these wrappers to make your life easier, especially with the find view by ID. Not built into the language, but wrappers for basic Android functions. ANCO is also a library that you can access. This provides a set of Kotlin-friendly wrappers around the Android APIs. So similar to the extensions, except the extensions don't require you to do anything. There's also for ANCO the domain-specific languages. This lets you replace your layout files. So in Android you have your resource files that define your user interface. You can replace those with Kotlin code using a domain-specific language in this ANCO library. We'll talk a little bit about ANCO in later lectures. It can be useful for certain things, but both the extensions in ANCO are nice tools to utilize. Thank you. Hello. In this lecture, I want to show you how you can create a new Kotlin project in IntelliJ. So we first got to start by bringing up the IntelliJ IDE. You can double-click the icon if you have a desktop shortcut, or go through the Start menu and select it. Once you double-click the icon, the first thing you're going to see is the splash screen, followed by the Create Project screen. This is what you're going to see. Welcome to IntelliJ IDE. There are a number of options here when selecting what to do. If you already created a project in the past, you're going to see projects on the left-hand side. If you left a project open in a previous session of the IntelliJ IDE, it's going to load that project and you won't see the welcome screen. But if it's the first time you've ever used IntelliJ, the first thing you'll see is this welcome screen. You have four options here. You can create a new project, which is if you're new to IntelliJ, that's the first thing you're going to do. If you have an older project, you can import a project. Importing a project has a simple dialog that comes up where you can select the project that you want to import. Importing usually means that you had a project in a different IDE, like an Eclipse project, a Maven project, or a Gradle project. It will import it into the IDE and convert it. You can open an existing project by selecting Open. You just have to specify the path. Most of the projects by default are going to be installed in the users directory under C. Usually it's C users, the login name on Windows, followed by the name of the IntelliJ, which is Idea Projects, and then under there you'll see different projects listed, and you can select them there. You can also check out a project from version control. Here you'd have to provide the actual server of the version control, the GitHub, what client you're using, GitHub, CVS, Git, Mercurial, Subversion. Version control just allows you to get something from a server. So we're going to go ahead and there's also configure options where you can configure settings and plugins and all sorts of other things, or get help. We're going to go ahead and create a new project. This is the first screen you're going to see. We're going to be writing Kotlin programs, so we're going to want to check the checkbox for Kotlin. Also at the top where it says Project SDK, you want to make sure this points to your Java installation, wherever you install Java. If you select new, you can specify that path. Mine was in C program files Java. We added that for our when we had to add our path variable, environment variable. You also see on the left there's different types of project. If you select different things, you'll see different wizards. You can select Android, see the Android wizard here. We're just going to, for the first part of the class, we're going to write Kotlin projects that aren't part of Android applications, so we're just going to select Java. It's Java FX for graphical user interfaces and so forth. So make sure you have Kotlin selected. You can use the library, just the Kotlin runtime that's installed, and you can hit the Next button. On this screen, this is the new project screen. You have to identify the name of your project. I'm just going to say test. When you say test, you'll see it's appended to the project location, which again for me is my users directory, Idea Projects. There's some more settings here where you can specify the module name. Module name is just the application name, and root directories and so forth. I usually just leave this as default. Hit the Finish button. And this will create a project for you. This left project screen doesn't always show up. It may be closed. You may see something like this. If you see something like this, you can select Test, and you can just say, or the name of your project, you can say Source. And then from Source, this is your project that's empty. So this is how you can create a simple project. This is just a real quick demonstration of this. We're going to talk about how you can add new source files and also explore the different menu options in this ID in the next lecture. Thank you. Hello and welcome. In this lecture, I just want to give you a little bit overview of the IntelliJ IDE, some of the features, some of the menu options. I want to show you how you can navigate through the different things. It doesn't have a ton of different ways to navigate, but I want to just describe the IDE and the structure. So let's bring up the IntelliJ IDE, and I created a project beforehand, so it's going to bring up the previous project that was loaded. And the first thing you'll see is you'll usually see a tip of the day. You can uncheck this box if you don't want to see tips, which I usually don't, so I say close. And then what you'll see here is you'll see some menus and some toolbars and some editors. So at the very top, you'll see the menu bars. This is your main area of navigation, or to select different options. File, from the file you can create new projects if you're already inside here. You can do some of the things you can do on the welcome screen previously. You can create new modules. Modules are just executables. New files, a lot of different things. You can play around with this. Mostly you won't be using any new FXM files, HTML files. So you can create new files this way. If you select the source file and you say file, you can see new, and you can see other options such as a Java class or a Kotlin file class. And if you select one of these will bring up wizards and will automatically create class files for you if you put in the name. And so depending on what you select here on the left-hand side, it may change some of the options in the menu. Other important options in the file menu are settings for the project. If you select the settings for the project, you can change the appearance of how IntelliJ looks. And you can also modify the menus and toolbars that are showing different colors. For the editor, you can do things with coding style, which is important. If you want to indent or change the style, it will automatically do that for you. There's options for version control if you're using Git. Build, execution, and deployment. Other options, if you have dependencies, you can have libraries and all sorts of things. Languages and frameworks and tools. The main thing, usually there's options in here for automatic imports if you have Java selected. So if you select editor and go under general, you can say auto import. It will automatically import all of your classes for you. You don't have to manually do that. So I usually have these checked. And also I don't even say ask, I just say all. Automatically import. So you want to play around with this, you can hit apply. The auto import feature is usually one that I like. Code completion, whether or not IntelliSense is working, all sorts of different things you can mess around with. My main focus is usually the auto import. I don't really change the appearance too much. The other thing that I like is the code and style for the automatic formatting. So when I have Java files, I'll set up my tabs and indents, my spaces, my wrapping braces. You can do the same thing for Kotlin. Set up your tabs. This will auto format your code. So as you're writing the code, it will automatically be formatted. Very, very useful. I'll set those up for settings, but that's about it. Not too much here. Other options in the file that you might care about. The project structure is sometimes important because this will give you information about your module, your app. So you can select the app and you can check the dependencies. You can modify your project name. It will tell you where the Java version of the SDK is located, what version it is, where all the compiler output is going to. For specific modules, you can manage your dependencies. So if you're including additional libraries or jar files or other things, you can set dependencies here. Or if you create a Kotlin library, you can include that. You can set up your sources and paths. Again, libraries options, platform settings for the SDK. So I'll look at the project structure and I'll look at the project settings. And then I also might use export options to create a zip file if I want to export a project. In the edit option, this is basic edit commands, copying, pasting, all those things, not too much. View, you can manage your windows. So you can say tool windows, you can select other tools if you want to access things. The terminal, the event log. Also you have disabling of different navigation bars. Navigate has options for jumping around in the navigation bar. This is the navigation bar right here with the folder. The menu's at the top, navigation. The toolbar here is to the right. This has shortcuts, which we'll talk about in a second. Code. Code has that nice option for converting Java files to Kotlin files. That's important. You can also automatically move some of your code around, reformat your code, optimize the imports, which I showed you before. There's usually nice options in here. Generating delegate methods. You can generate some code. Analyzer. This will use some static analyzing tools to analyze your code. Things like lint tell you things that are wrong with your code. Clean up some code automatically for you. Analyze your dependencies. Refactor is a nice menu option. If you want to change the name of a file, you want to use the refactor tool so that it changes all the dependencies. So rename, move copy, those are all important things you want to do. You don't want to just rename a file, you want to rename it. Build menu option, this is how you compile. You can say build project and it will compile everything. You can also say rebuild in here. And usually there's a clean too once it's built. I've never built this project, so there's not a clean. But if I had source files in here, this is an empty project. I don't have any source files, but if I would have built it, you can also clean. Clean means it removes all the executables and rebuilds them from scratch. The run option is how you run your Kotlin program. You just say run. You can also run it in debug and bring up the debugger. The debugger is an important tool that helps you find and fix your errors. You can set breakpoints. You can step through your code at runtime and stop it to look at the value of variables, analyze your code. It also has the call stack where you can analyze if your program crashes, you know exactly where it crashed. The debugger is a useful tool. Hopefully maybe we'll have a lecture on how to use the debugger. Tools. There's specific tools for Kotlin in here that you can utilize. Configuring Kotlin in a project, plug in updates. You can check your updates. That's how you can get to the Kotlin console to execute snippets of code. VCS is your source repository. So if you have some files that are under source control, you can access them. You can set up the settings here. You can check things out. Window, you can access the different windows. Help, you can check for updates is the main thing I do in help to get new versions of Kotlin API or new versions of the IDE. As I mentioned, the thing below that is the source project folder tree. And then the right-hand side is the toolbar, which has shortcuts to building and compiling. The first one is build. These are shortcuts for the debugger. Also running. You can run your application just from the toolbar as opposed to going to the menu option. Here's a debug option. Run with coverage. That will do like some test coverage to see how much code is under test. And it's nice because each one gets highlighted. Stop will stop the program. Project structure will access the project structure just like we did from the file menu. And then you can also search. Below this is you have your project. You can have different views. You can have a project view, which displays a tree-like structure of how the source code is located on the disk. So this is exactly how the files are on disk. You can change that view to use a package view, look at your Java packages, project files, a different view. I usually use the project view, but you can play around with that. There's other options for scrolling, collapsing all, accessing different settings to flatten packages and so forth. This little arrow button will synchronize the source file, or no, this will actually hide it. So it will hide things. Whenever you see that arrow anywhere, it will hide things. And then you get back to it by selecting the source. And so this is the left-hand side is really the project tree. This right-hand side is your editor. So whenever you create source files, this is where your editor is going to be created. So if we create a new source file, like a new Kotlin file class, we just say test. Now we have our editor and we have tabs for each file. So we can easily navigate between different tabs and have multiple editors open. At the bottom, when you compile things, you'll see the consoles come up and everything. So if I just create I want to wait to do that for Hello World, but if I were to create a simple program and you build it, compiling, you'll see options down here for building and status. This is called the status window. See, it says compilation completed and so forth. So this is the IDE. You'll become really familiar with this because you're going to be using it a lot. It's pretty intuitive, very easy to navigate, a ton of nice features. We'll talk about those features again as we go. Thank you. Hello and welcome. In this lecture, we're going to finally create our first Kotlin application. So very exciting. First thing we need to do, we're going to bring up IntelliJ. We've gone through the process of creating a new project, so we're going to go through that really quick. We just hit create new project. We got to select Kotlin, Java, select next, and I'm going to call this Hello World. And just so you know, all the projects and all the assignments or all the example code that we run or create is going to be attached in the class as a resource. We're creating a new project here called Hello World, and we're going to say finish, and this is going to create an empty project for us. If we want to write an application, the first thing we need to do is create a Kotlin source file. All the source files in Kotlin end with .kt. You can create a Kotlin source file very easily by going to your source folder right-clicking and saying New Kotlin File Class. When you select that, it's going to bring up a little dialog where you provide a name. For our name, we're just going to name this Hello World. Hello World is a typical application you write when you learn a new language. All the application does is print something to the screen. So we're going to create a new Hello World. We're going to keep the kind file the same. You see there's other options here if you wanted to create a separate class, an interface, enum class object. We're just going to create a whole file. Once we do that, you'll see that under the source file, there's a helloworld.kt file that was created. It's empty. It doesn't contain any source code, but it does create a file. Once we create the file, we have to actually add some Kotlin source code. We haven't talked a lot about Kotlin source code yet, so the source code that I write here, I'll explain, but it will become much more clear when we start talking about those concepts. All I want this application to do is the basics. I want it to print out some text to the screen. So what I'm going to do here is I'm going to edit the file manually, and I'm going to just type in some source code. I'm going to type in fun main, and this is Kotlin code, args : array, left bracket or angle bracket, string, another bracket, an ending parentheses, a bracket, and then that's it. So it should look somewhat familiar to you if you're familiar with Java. It looks like a main method, right? Main entry point. Then I'm going to say print ln, and I'm going to put some string in a hello in quotes, hello world. And I'm not going to put a semicolon. I'm going to leave it like that. So again, there's Kotlin source code here, but you don't need to understand it right now. What I'm doing is I'm going to print something out to the screen. Once I'm finished editing my source code, I can run this in a number of ways. I can right-click and say Run, which will automatically build for me, or I can just go to Build and say Build Project. When I build a project, if I don't have any errors, you see that it just says Compilation Successful in the status screen. Now, if I had an error, let's get rid of one of these and save it. You can save files using Control-S. When you have an error, usually you see a highlighted red, and you also see the light bulb, which will help you fix the error. But I just want to show you the build window. So when I say Build Project, if I had an error, you'd see the messages window in the build window, and it would show you those errors. And then you also have options for refreshing, closing the window. You can, if you're looking at the call stack, you can select the arrows. There's other things nice here. But it says there's an error, and it says that I'm expecting a quotation mark. When you have compiler errors, you usually want to solve the first error, because the other errors may be a result of the first one, especially if you're missing brackets. This is telling me there's an error on line 6, column 27. And I'm just missing the quote, so I'm just going to re-add it. But I wanted to show you that build window if compilation doesn't succeed. Now that my compilation succeeded, I want to run the application. In order to run the application, you just hit the Run menu button and you say Run. If you wanted to debug this and bring up the debugger, you could hit Debug. So I'm just going to say Run, and I'm going to say Hello World KT. You can edit configurations, change things. I'm going to say Run, and now it's going to bring up the console, and it's going to say Hello World. So you see that this program ran with text to the screen, Hello World. And so this is your first Kotlin program. Pretty simple, not real complicated, but you did output some text to the screen. So congratulations, you wrote your first Kotlin program. Now to analyze some of this code, at the very top you'll see there's some comments. They look just like Java comments, multi-line comments from lines 1 through 3. The next thing you're going to see is the fun keyword. That's on line 4. The fun keyword is used to declare a function. And again, we'll go over this in much more detail when we talk about these concepts, but I want to give you a brief description. The main is the name of the method, name of the function. Next thing you see is the args. Args is the parameter. The colon after it is the type, which we're not used to, right? In Java, we always define types of parameters before the name of the parameter. But in Kotlin, you define the name, and then the colon identifies that there's a type. It's an array of type string. So the parameter type is written after the parameter name. This applies to variable declarations as well. The function can be defined at the top. You'll notice this is not inside of a class. So the functions can be declared at the top level of a file. You don't have to put them in a class. Arrays are also classes. There's no special syntax for declaring array types like there is in Java. You have to use the brackets. It's another thing you could have noticed. You noticed here we're using a generic, so we're applying a string as our type. And then we're ending the parentheses. Inside the body of the function, you'll see it also has brackets to start and end the block of code on line 5 and 7. And then we see this print line. This is the function we invoke to output data to the screen. It's different from system.out.println. It's a lot shorter for one. So the Kotlin standard library provides these wrappers around the standard library Java functions, like the system.out.println. It's more concise syntax, and this is using that Kotlin standard library so that we don't have to use system.out.println. We talked about the Kotlin library, Kotlin extensions. This is what that's using. You also notice there's no semicolon to end the statement. You don't have to end statements in Kotlin with a semicolon. And then you have the string inside double quotes, and that's what's output to the screen. So those are some of the syntax differences to Java, the fun keyword and so forth. But pat yourself on the back. We've completed our first program of many more. This is just an initial description of how you can run a simple program in Kotlin. Thank you. Hello everyone. I wanted to provide a code along to show you some variations of Hello World. We did a very simple version of Hello World. I'd like to show you how you can read command line arguments of a Hello World program and also show you how you can use a for loop. These are concepts that we'll discuss in greater detail in later lectures, but it's just to give you an introduction, get you somewhat familiar with a main function, a main routine inside Kotlin, and just to get you a little head start. Let's create a new project and let's name this one Hello World. Variations Hello World, since it's a little different from a basic Hello World. Hello World is often used as the name of a first program they write in a new language. So you'll see Hello World programs in PHP and C++, whatever language you're learning. So let's create a new file here, new Kotlin file. We're going to name this main. We're going to have the kind be file. We even haven't even discussed how you can get classes and objects and interfaces. This is going to be our main routine. We know how to create a main routine now, so it's just fun main. It's going to take a named parameter args, and we're going to have it be of a type array, which is a string, array of strings. So we say array and then string. And so what's happening here in these parameters right here, you can pass arguments to a function. You can pass data to your program when you run it. And so we can read this parameter. So what we want to do is we want to check if the size of that is 0, if they passed parameters or not, command line arguments. And if it is, then we don't want to do anything. Otherwise, we're just going to print out the command line argument. So we're going to use an if statement here, conditional expression. Again, a concept you may not fully understand, but that's quite okay for now. What this is doing is it's mixing in Java code. We're calling a method on the array type, which is actually this is not a method. This is a member data, a member type, member variable, args.size. Checking if it's 0. That's saying the size of the array is 0. And that would mean that the user did not pass any data into this program. And if they didn't pass any data, we'll just print out a message saying, please provide a name as a command line argument. Something simple. Otherwise, if they did print something out, or they did enter a command line argument, we'll also want to return from the function, jump out of there. If they didn't, we're gonna print out the argument. So we'll just say hello, $, arg sub 0, an exclamation point inside of string. So we're doing a lot of different concepts here that may not be familiar with. Again, do not worry about it. It's just a simple demonstration. We're using string templates here. We're using an if statement. You see the return keyword. All of this stuff is new. We haven't talked about arrays. Do not worry about that for now. Let's go ahead and build this and run it and pass an argument and then not pass an argument in. So we're going to run this first with no arguments to the program. So we're going to see this line printed out first, 4. So when we run this, it's going to say, please provide a name as a command line argument. Right, and that's exactly what we see. To pass data into a program, you have to go to run, and what you'll have to do is say edit configurations and go down. If you don't see any Kotlin there, you'll have to go down to defaults, select Kotlin. And then here we can pass in an argument. I'm going to pass in an argument, JSON. So now I'm going to put apply. I'm going to say OK. And now when I run it, I say run main KT. And you're going to see hello JSON. So it read in the command line argument. And I also have a parameter or an extra bracket there. And so that's just a simple hello world where you can read in arguments. We could write a more complicated hello world where we could read in many arguments. We could do that using a for loop. We can use the enhanced for in Kotlin, which is really just Java code. This is Java code that's enhanced for loop. You can specify the variable that's going to be created, and then we can use the in operator. That's Kotlin. We're mixing Java and Kotlin. Args is there. We're going through, and if there's many different parameters, we're going to read in each one. So let's build this, and then I'll show you how you can add more parameters. You can just say run, edit configurations, and then add a space and say Tom, Joe, John. We're actually adding four command line arguments here. We'll say apply, OK, run it, and here we're going to see 4 pieces of data printed out. Again, just a little demonstration of how you can pass in command line arguments to a program. We talked about a lot of things here. We're going to cover these in detail. Thank you. Hello and welcome. In this lecture, I'd like to talk about packages. For those of you that are familiar with Java, this is a familiar concept. A package is a way of organizing many different classes together. Usually what you'll do in Java is you'll use the package keyword at the top of the file, and the package will represent the directory that all of the classes are located in. And if you want to use any of those classes that are in the same package, you can just start using them. If you have classes that are in a different package, you have to import them with the import statement. And so Java has many classes that come along with its API that you can utilize. There are packages in Java like the network package that has network functionality, or the I/O package, which is input-output for files and streams and all sorts of things. Other examples would be a graphical user interface package, java.swing or java.fx. So it's a way of organizing your code and organizing your classes and then including them, importing them in your program. And so Kotlin has the same concept. You can organize your classes into packages using the package keyword. All source files in Kotlin can have a package statement at the beginning, just like Java, and all the declarations, classes, functions, and properties defined in that file will be placed in that package. So remember, Kotlin can have many different classes in the same file. You can have many different public classes. In Java, you can only have one public class per file. And you can also have top-level functions in Kotlin. And so everything, all declarations are inside the same package. Declarations defined in other files can be used directly if they're in the same package. You don't have to import them. You can just start using those class names. Again, usually in the same directory as well. They need to be imported if they're in a different package. Import statements are placed at the beginning of the file and use the import keyword. That's how you can tell your program or that particular class that you want to use some functionality or some software, some other classes that are outside of this directory. Just like in Java, if you want to import functionality for networking, you import the networking package. If you want to import graphical UI elements, you import the graphical UI package. Same thing with Kotlin. Kotlin doesn't make a distinction between importing classes and methods. So you can import the top-level functions by name. So there's no difference between importing a class or a method in Kotlin. And that's because in Kotlin, remember, you can have methods, functions that are outside of a class. And so you have to be able to import them if you want to reuse them. Another example here is importing geometry.shapes.createRandomRectangle. So you define the package using the package keyword. You're saying that all the classes in geometry.example directory are part of this package. And then if you want to use them, you use the import keyword. And if you want to import a method, you just say the name of the method. And that's what this is doing here. Geometry.shapes.createRandomRectangle. Create random rectangle is a method, or a top-level function would be the correct term for Kotlin. So here you would then also be able to use it very easily. Just call it by name, like you call any other method. You don't have to use the absolute class name. You can import all declarations defined in a particular package by putting the star after a dot, after the package name. So this star import will make visible not only classes defined in the package, but also the top-level functions. Just like in Java, if you want to import all the packages in java.lang, you say import java.lang.star. In Kotlin, the only difference is any functions that are in their package will also be imported, and you'll be able to use them. File names. In Kotlin, you can put multiple classes in the same file and choose any name for that file. This is also a difference from Java. In Java, any public class in a file, you have to have the same name of that file. In Kotlin, the file names don't mean anything. You can have different file names for different classes, and you can have multiple public classes. Kotlin also doesn't impose any restrictions on the layout of source files on disk. You can use any directory structure to organize your files. Again, usually packages have a directory structure, and the package name is that directory structure. In Kotlin, you don't have to do that. You can have different package names and have different directory structures. So packages on a whole are very, very similar to Java. The only real difference here is multiple classes in a single file can be part of a package. And also, because you have functions that aren't part of classes, those functions are also part of a package, and you can import them as well. So you use the package keyword to define the package, use the import statement to import a package. Thank you. Hello and welcome. Let's talk about comments. Comments are placed in your source file to describe the source code. Comments are not looked at by the compiler. The compiler will ignore the comments. So the only purpose of comments in source code, again, is for other people that review your code. They'll describe the code. Sometimes you'll provide comments at the top of the file for the author of the code, the purpose of the code, things like that. So comments and how you provide them in Kotlin are very similar to how you provide them in Java. So they're essentially the same in Java, JavaScript, C, any other languages you used. Kotlin has the same concept for comments. You have block comments and line comments. And what this means is you can have a single line that contains a comment, and you use specific syntax telling the compiler to ignore that line. It's not source code. It's a comment. And then you also have block comments. Block comments are multi-line comments. They span multiple lines and you just want to use specific syntax. So here would be a single line comment. You just do /, 2 forward slashes. This will tell the compiler that, hey, this is not source code, ignore it. And you usually put this above a line of code. Sometimes you'll see it on the right of a line of code. I particularly like it above it. It's easier to read than something to the next of it. Comments are tricky because you have to have a good balance of enough comments and not too many comments. And nowadays with comments, a lot of people advocate for self-documenting code. And what that really means is you'd hardly have any comments at all. The comments are minimal. And what you do instead of providing comments is you provide good, meaningful names. Variables have names, meaningful names. Your logic has meaningful names. And so what that means is there's no need for comments because you can tell what the code is doing by just looking at the code and the meaningful names. Now, there's arguments either way. People agree with that, people don't agree with it. I would say that you have to find the middle ground. You have to have enough comments along with good, meaningful names that represent the code and somebody can look at it and fully understand it. And you don't want to have comments for every single line of code because then it just makes the code look cluttered. It's harder to follow. It kind of defeats the purpose of the comments. So you have to kind of understand when and how to provide comments. And like I said, I'll usually provide comments at the top of the file for author, purpose, and so forth, kind of describing some of the classes. I'll provide comments for any logic that's somewhat confusing. I don't provide comments for just variable declarations or simple logic. So single line comments have the 2 forward slashes, and then multi-block comments can start with the /* and end on another line with the */. And then anything in between those blocks is ignored by the compiler and represented as a comment. And the other thing with Kotlin, unlike Java, is the comments can be nested. So inside those block comments, you can have another / asterisk and another asterisk / to end it. Nested comments. In Java, you won't be able to do that because it doesn't know when it starts and ends. And so let's just bring up IntelliJ real quick. So if I want to provide comments in a single line comment, I can just do it for 2 /. And in IntelliJ, it's nice because it will grade out and you know exactly what the comments are. And like I said before, I do like to provide comments at the top, and I'll do something like author, and then, put my name, maybe purpose of the file. This class adds 2 numbers or something like that. And then I usually put the date for when it was created. Again, it's up to you what you want to provide. I usually do this at a minimum, and then I'll provide single line comments here and there. The nice thing with Kotlin is you can have nested comments. So inside here, you would be able to have another comment. I don't know why you necessarily do that, but you could do that if you wanted to. And then end it as well. And then anything in between. So comments, pretty simple things. You want to have a good middle ground on when you provide them, when you don't. You can also have some comments automatically generated for you. If you go to the File menu option and you go to Settings, you can go to the Editor, and you can go to File and Code Templates, and there's different tabs here. For includes, you can add comments right at the top for the file header, and this will automatically be added every time you create a new file. So here I have just created by, and it will put the user that's currently logged in, and then the date. And then I could add to this, and I could say, I could put my author comments as well if I wanted to, and instead of doing that, something like that. And if I hit apply, anytime I create a new file in Kotlin, or in the IDE I should say, if I go to source and I say new file, and just name it test, and I'll put the extension KT, and when I do that, it will add test.kt and it will say the new file comments. That's how you can automatically generate them. Just a nice little feature. Thank you. Hello and welcome. In this lecture, I want to talk about variables and data types. This is a very basic lecture. This is if you have no programming experience at all, we have to understand what a variable is, and we have to understand what a data type is. So variables are the names you give to computer memory locations which are used to store values in a computer program. So computer programs need to store data. They need to store data in order to perform operations and perform functionality. And the data that's stored at runtime is stored in memory. Things that are stored in memory are things like variables. Sometimes you'll store data from a program on the disk, on the hard drive. Sometimes you'll store data in files, or you'll store data in a database. But when you run a program and it's running fast or it's running slow, it's usually because data is in memory. And so that data in memory is performing calculations on the CPU and everything else. When you store data in memory, you want to give the data that's stored there a name, a symbol. Right? If you had to access address, so memory on hardware is just addresses, hexadecimal addresses. And if you wanted to access those addresses, you'd have to memorize the address locations, hexadecimal numbers. Obviously, that'd be really, really hard to maintain. It'd be really hard to remember memory addresses. So you can create variables in your programs, which are symbols, usually meaningful names, that map to locations in memory. And so when you want to use that data, you access the variable name, and you can perform calculations using the variable. You can change the data, all sorts of things. But variables are stored in memory. They're simple symbols that represent data in memory. So for example, assume you want to store 2 values, 10 and 20, in your program, and at a later stage you want to use these 2 values. The steps that you need to do in order to store these values are the first thing is you have to create variables. And you have to give those variables names, often referred to as an identifier. Because you'll need to access that data in your program, and so you want to give it a name so you know what that data represents. You then store your values in those 2 variables. So the first thing, creating the variables with the appropriate names, is referred to as declaring. You're declaring variables. You're really just saying in your program, here's some data that I want to store, and here's the name of the symbol. After you've identified or declared the data you want to store, you then have to actually store the data. Storing the data is just assigning the values to the variable, usually with an assignment operator like an equals. Once you store the values in the two variables, then you can retrieve and use those stored values from the variables just using the meaningful name. So if you want to add those two variables together, you can do that. You can perform operations on those variables. And we'll provide some examples on how you can declare variables using var and val in Kotlin. Data types also are closely related to variables. A data type represents a type of the data which you can process using your program. So in the introduction section, we were talking all about static typing, referred types, and all this. And you're probably like, what the heck is he talking about? It has to do with data types. When you have data that's stored in memory, you have to identify the type of that data if you're a statically typed language. Or a strongly typed language, I should say. Not all static typed languages are strongly typed. And so the data type identifies the type of the data. Right? So you can store numbers in memory, you can store text in memory, which are often referred to as strings. All these different types of data have data types associated with them. So some examples of data types are things like ints, which store whole numbers. Floats store usually decimal numbers, and so do doubles. There's other examples like bytes. You can also store booleans, which are true or false values. We'll talk about the specific data types in Kotlin in another lecture. But each data type is going to correspond to a byte size for that platform. And it really determines how much data can be stored there. So an integer may only store 8 bytes. So the size of the integer cannot be that big. It can be a million or it can be whatever. Floats and doubles will store larger sizes, so that means you can store more data, higher numbers. There's also this concept of primitive data types. These primitive data types are usually not objects, and they store all sorts of data. So in Java, you have roughly 8 primitive data types: int boolean, char, float, double. I'm probably missing some. I think I said byte, but there's roughly 8 different primitive data types. Primitive data types are not objects. So we talked about object-oriented programming. There's objects. Everything in Java is an object except these 8 primitive data types. With Kotlin doesn't have any primitive data types like Java. So there's no int, floats, or booleans as a primitive data type, meaning it's not an object. Kotlin does have data types for int, floats, but they're all objects. The advantage of this, not having them be primitive data types, is you don't have to do auto boxing and things like that in Java. So in Java, whenever you want to use primitive data types and you want to pass them to methods, you have to use a wrapper class in Java, like an integer or a float class, and convert it to an object. In Kotlin, you don't have to do that. So it's another nice feature of Kotlin where they don't have these primitive data types. We're going to talk about the basic data types in Kotlin in another lecture, and I'll specify what data types Kotlin supports. But this was just to get you identified with the terms and the concepts of variables and the data types associated with variables. Thank you. Hello and welcome. In this lecture, I'd like to talk about static typing and type inference. We previously touched on the concept of static typing in older lectures, mainly when we talked about the advantages of Kotlin. In this lecture, I want to contrast it with dynamic typing and also show you how Kotlin supports type inference. So static type programming languages are those in which variables need not be defined before they're used. So static typing has to do with the explicit declaration or an initialization of variables before they are used. Java is an example of a statically typed language, as are C and C++. We see some terms here that might not be very clear. Declaration and initialization. Declaration is when you define a variable and maybe define its type, depending on the language features. Declaration is just saying, here's my variable, here's my type of data with it, but I don't assign any data to it. Initialization is when you assign data to a variable. You initialize it with some default value. So static typing, you have to explicitly declare your variable before you can use it. You don't always have to initialize it, but initializing is important. You usually want to set your data to some default value because it can cause problems in your program if you do not do this. We also know that Kotlin is a statically typed language. We talked about some of the advantage with that related to compile time checks. And we'll touch on that in a second as well. So static typing does not imply that you have to declare all the variables first before you use them. It means that the variables can be initialized anywhere, but developers have to do so before they use the variables anywhere. So initialization is not required, but declaration is. If you want to use a variable in a statically typed language, first off you have to declare it. You can't just start using it. So for example, here's an example that creates some variables called num and sum. They're static variables, they're class variables, looks like Java syntax. They're of data type int. In the first declaration, in the first line here, we're declaring the variables. We're saying, this is what the variables are, here they exist, here are their names. But we haven't actually used them, we haven't assigned any data to them. In the next line, we say num equals 5. This is where we're initializing the variable. We're also using it. Sum equals 10, same thing. And then in our third line, we're saying sum equals sum plus num. That's where we're using it. In Java and in Kotlin, because they're statically typed, you cannot just start using a variable, you have to declare it. Declaring it means in Kotlin using one of the two keywords of val or var, which we'll talk about in detail in another lecture, and also optionally specifying a data type. Dynamic typing are languages in which the variables do not need to be defined before they're used. You can just start using them. So they don't require any declaration of the variable. Python and PHP are example languages that include dynamic typing. Here's an example of Python code where we just start using our variable num. We haven't even declared it. We're just using it immediately. You also notice that there's no data type associated with that. And that has to, data types and associating data types with variables has to do with whether or not the language supports strong typing or weak typing. Languages that support strong typing, it means that you have to specify the data type with the variable. Weak typing means you don't have to specify the data type. And typically, it's not required, but typically statically typed languages are strongly typed and dynamically typed languages are weakly typed. But that's not a steadfast rule. Java is strong typing with static typing as well. So Python, PHP, you can just start using variables. Statically typed languages also are those languages with type checking is done at compile time. We touched on this when we talked about the advantages of Kotlin. Statically typed languages will make sure before it gets compiled that you're assigning the right data to that data type. So if you declare a data or variable with an int and you try to assign it a string, the compiler is going to complain. It's going to give you an error. You can't do it. And all statically typed languages will do this. They'll check the data at compile time. With a dynamically typed language, the checking is not done until runtime. Because of this, it's much more prone to errors. If at runtime you try to assign data to a variable and the data is not correct, you try to assign a float to a string, the program could crash. So, there are advantages and disadvantages to both, which we'll talk about in a second. But I also want to emphasize again that static versus dynamic typing is not the same as strong or weak typing. Strong typing, data types associated with variables. Weak typing, no data types associated with variables. They're two totally different concepts. Static or dynamically typed language can be either strongly or weakly typed. Either one. Strongly typed, here's an example. Variables have specific data types when defined. So here it looks like something like Java code. You would say int x equals 5. X has type int. In a language that's weakly typed, the variables are not specific data type. You just say x equals 5. You don't provide a data type. The advantages or disadvantages of each approach. Dynamic typing is simpler, saves time for the program. You have to type less. But again, because the compiler is not checking, programs can crash more. If the programmer assigns the wrong data to a variable, you're screwed. Compile time checking is important. It may add some performance issues depending on what you pass to the compiler, but it's something that's necessary and it's useful. I mean, there are arguments for dynamic checking, and that's why languages include them. But if you want to be a careful programmer, compile time checks are very helpful. So static typing is checked by the compiler and finds the errors before you can actually run your program. So you have no risk of the program crashing because data types are not assigned correctly. In Java, you have to start a variable declaration with a type. It's required. So Java is a strongly typed language. You have to put data types. In Kotlin, you can omit the types from many variable declarations. So you can start with a keyword, or you don't have to. It's up to you. If you start with a keyword and you put the data type after the variable name, then that's fine. Either way of doing it is fine. When we talked about the Hello World application, you should have noticed that the parameter name into the main function was defined before the data type. And that's different syntax than Java. So in these three examples, the first example, val question equals the ultimate question of life, the universe, and everything, is enclosed inside quotes, which means it's assigning a string to val question. The val keyword is a way that you can create a variable in Kotlin. There's two ways you can create a variable in Kotlin. Val is one of them. We're going to talk about how you can create variables in Kotlin in much more detail in another lecture. Val answer equals 42. You're assigning an int to answer. You're not specifying the data type. You didn't specify the data type in the first example. In the third example here, val answer colon int equals 42. You're specifying the data type. You're specifying the answer is of type int. And so Kotlin supports either way, either specifying the data type or not specifying the data type. Type inference, this is, so in Kotlin you can either specify the data type or you cannot specify a data type. If you don't specify the data type of a variable, the Kotlin compiler can automatically determine from the context what the data type is. So it allows you to omit the type declaration. If you say val x equals 1, you're declaring a variable, and because it's initialized with an integer value, Kotlin will automatically determine that it's of type int. It's smart. It knows based on the context. It sees that 1 is not enclosed in quotes, and it knows that it's an integer. It also can infer from Boolean types and other things. So it's a smart compiler. It will identify the type of the data based on the context. And this concept is referred to as type inference, when the compiler is smart enough to determine the types from the context. If we said val x equals some string inside double quotes, it would know that x is a string because of the context. So this is nice. This is nice. We have the best of both worlds here. We have a statically typed language where we have our data types checked at compile time, which avoids errors at runtime crashing. But we also have some ability to do some weak typing where we don't have to specify data types and the compiler won't complain. Because of type inference, it will automatically determine the type of the data, which will allow us to be more efficient when we write our code. We can write less code. We don't have to identify data types. A very nice feature. So thanks to Kotlin support for type inference, most of the extra verbosity associated with static typing disappears because you don't have to declare types explicitly. Thank you. Hello, class. Let's talk about creating variables. Mutable and immutable variables. So in Kotlin, there's two ways you can create variables. Declare variables. You can use the keywords val or var. The var is a mutable variable. So mutable means you can change it. Immutable means you're not able to change it. So with var, you can change the variable to another value by reassigning it, which you can do in most languages, unless it's a constant. So unlike Java, you can assign any data to any variable if it's not declared as final, a constant. So it's the same as declaring a variable in Java. Val name equals Kotlin. This slide should say var, it says val. We'll talk about val in a second. I tell you, I got to proofread these slides better. Using var, it can be initialized later. We talked about this already when we talked about when we talked about type inference. But you can declare the variable in one line, and then with var, you can initialize it later. So you can say var name string. And you see this syntax here. We're identifying the data type, var name colon string. And then we're saying name is equal to Kotlin. We're declaring the string on one line. We're initializing it or assigning it on another line. Variables defined with var can be reassigned since they are immutable. So var name equals Kotlin, name equals more Kotlin. So mutable variable means they can change, right? and var is a variable that can be changed. So if we were to take this example and try to put it into IntelliJ, we wouldn't get any compile errors. And we'll do this at the end of the lecture. The keyword val is used to declare a read-only variable, a final constant variable in Java. The same thing. Can't change the data. A val must be initialized when it's created, since it cannot be changed later. So you don't have the option of declaring the variable on one line and then defining it on another, or assigning it on another. You have to do it all in one line. So you'd say val name equals Kotlin, all in a single line. You should only be initialized once, or you can initialize it with different values depending on some condition. So although it has to be on one line, you can still initialize it inside of an if statement. So you could do something like this, because you're still only initializing it once. Now, it's on separate lines in this case, but it's inside a conditional. And so when the program runs, it only initializes message once, depending on whether or not the if condition evaluated true or false. So don't get confused when it says you can only initialize it once. If you see it multiple times in a program, as long as it's an if statement, that's okay. If it's not, the compiler will complain and you'll get an error. For member variables that use the val keyword, read only, they can still be changed via functions or properties, but the variable itself cannot change its value or be reassigned to another value. So keep that in mind. Member variables are variables that are part of a class. And when val is used as a member variable, it can still change if it's inside of a function or it's a property. And when we talk about functions or properties, you'll know more about this, but it's local, so it doesn't matter if it changes, and as long as the member variable itself isn't changing the value. By default, you should strive to declare all your variables as val, as read-only. Using immutable references that do not change, immutable objects, and functions without side effects. Side effects, remember, affect the outside world. They affect things outside of the function. It makes your code closer to the functional style. And we know that advantages of functional style are that it's more concise, it's easier to maintain because you're not changing this data all the time. So we want to try to make our variables immutable. They can't change. We can do that using the val keyword. So let's just try bringing up Android Studio and putting some of these examples inside the code to see if the compiler gives us errors. So I'm going to bring up IntelliJ. It's going to bring up my old project from Hello World. And I'm just going to try to declare a couple of variables with the val or the var keywords. And when I declare the var keyword, I should have no problem trying to reassign the data. But when I use the val keyword, I should get an error. So let's just try creating a val, or I'm sorry, first a var keyword, which is mutable. And you'll notice when we create the var keyword, we can create the declaration on one line, line 7, and then we can assign it on line 8. And if we build and compile this, we don't get any errors. There's no problems with that. We get a warning saying the variable name is assigned, but we never use it. So that's not a good thing. We should be using name somewhere, but printing it out or something. We can get rid of that error if we say print line name. Now when we compile, the error would go away. Or the warning, I should say, would go away. So nice. We can also change name. After we've assigned it to Kotlin, we can change it to Jason. And then again, if we build it and we run it, we wouldn't have any issues. It just so happens that now the first name is never used. The value Kotlin assigned to var name is defined but never used. It's kind of a pointless thing, so it's just warning you. If we run that, we'll see that println prints hello world and it prints Jason. Now if we try to use the val keyword, it's going to be read only and we have to assign it on the same line that we created. So we'd have to do something like this. I should probably create a bigger font. Let me try doing that real quick. To change the font, I should be able to go to Project Settings, go to my editor, and select Colors and Fonts, and I should be able to make my font larger, just so you guys can see it. Okay, let's make it 26. Apply that, hit OK. So it's a little bigger. I want to make sure you guys can read it. So now I create a val name. Val is a readable only variable. I can print it out. Print line prints a new line. say name. I build that. It's going to build successfully, and when I run it, it will print out hello world in Kotlin. Now, if I try to change name to be equal to something else, the compiler will give me an error because val is a read-only variable. So there's an error here. Val cannot be reassigned. So this is how you can use val versus var. Again, val are read-only variables, similar to final constants in Java. In var are a mutable variable. You can change it. Declare it on one line, initialize it somewhere else, use it somewhere else. Thank you. Hello and welcome. Welcome to another exciting lecture. This lecture we're going to talk about some of the basic data types in Kotlin. These are some of the ones that don't have any tricks to them. They're just similar to primitive data types in Java, but they're actual objects. So one of the big changes in Kotlin from Java is that in Kotlin everything is an object. So Java, you kind of think everything is an object, but technically not everything in Java is an object. Specifically, the primitive data types in Java, they're not objects. So Java does not have, it's not truly object-oriented because it's primitive data types. So Kotlin doesn't differentiate between these primitive data types and these wrapper objects. So Java introduced these wrapper objects. If you're familiar with Java, the wrapper objects are classes like integer, double. You'll typically use these classes when you have to convert primitive data types to an actual object. So these wrapper objects provided a workaround in which primitive data types were wrapped in objects. So for example, java.lang.boolean wraps a Boolean primitive data type. And the reason they wrap these data types is because a lot of the other classes in Java, the Java APIs, didn't support primitive data types. They'd only take objects. So in Java, you were constantly converting primitive data types to objects so that you could use them. For example, like the collection classes. The collection classes are data structures. They store data, and if you wanted to store, they didn't store primitive data types. So if you wanted to store data in a collection and they happen to be ints, you had to convert the ints to integers. And the integer is the wrapper class in the Java API. So it was kind of cumbersome in Java having to convert all these primitive data types to objects. So with Kotlin, they removed all of this. You no longer have to do this conversion. They automatically promote the primitives to full objects. So there's no int, float, or double primitive data types in Kotlin. You may see the term primitive used in Kotlin, but it's really referring to the basic data types. So you always use the same type regardless if you're passing a parameter to a method that takes an object. Val I, right? Remember from our last lecture, val and var are how you create variables. Right? Val is immutable. You can't change it. And we want to try to strive to use val. So here we're saying val I colon. After the colon, it means we're specifying the data type of the variable. Here we're assigning to an int named I, which is only readable, the value of 1. We're then saying val list colon, and we're having a list. So remember, the collection classes in Java had to take objects. In this case, this list is taking an int, which means it's an object. So pretty nice. We don't have to take that int variable in I. We don't have to actually autobox it or promote it or convert it to an object. So val list colon list int. We're specifying list is a data type of list int. And then we could say list of 1, 2, 3. So at runtime, the number types are represented in the most efficient way possible. We're going to talk about number types. In most cases, for variables, properties, parameters, and return types, Kotlin's int type is compiled to the Java primitive type int. So what will happen under the hood? Because the JVM supports Java, it expects primitive data types. Under the hood, some of these objects that are represented as primitive data types in Java will be converted by Kotlin's runtime system to the actual primitive data type. But it doesn't matter as far as you're concerned. As long as the language, Kotlin language, doesn't make you use these wrapper objects, that's all you care about. It's more efficient to not use it as far as you can write code quicker. So number types, the first one we want to talk about, we just touched on. The built-in number types are as follows. There's a long, and I mentioned earlier that data types specify size as well. A long represents 64 bytes, so this is really the largest number that you can store, the biggest number, the longest number, whatever you want to call it. It's many, 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 many digits. An int is 32 bytes. It's a bit smaller. A short is 16 bytes, even a smaller number. A byte is only 8 bytes, which makes sense, or 8 bits is really a byte, so 8 bytes is a little different. Double is 64 bytes. It's big, just like the long. You can use either a double or a long. Float is 32 bytes, bigger. It's the same size as an int, but it represents a rational number, not a whole number, so like a decimal number. Some examples of numbers. If you want to create a number literal, you have to use one of the following forms. Val int equals 1, 2, 3. Val long equals 1, 2, 3, 4, 5, 6, L. You notice the L at the end of long. Double is a rational number, so that's the difference between a double and a long. They're the same size, but a long is a whole number, specified with the L suffix. A double has a decimal, and a double is bigger than a float. A float's smaller, and to identify a float, you can use the F as a suffix. Distinguish that from a double. Hexadecimal. A hexadecimal number will start with the 0x prefix. Binary has zeros and ones, starts with the 0b prefix. So, just to reiterate, a long value requires the suffix L, and to float, the suffix F. You also saw the 0x for hexadecimal numbers that prefixed, and 0b that prefixed a binary number. That's how you would use number literals in Kotlin. Conversion methods, you often need to convert data types, right? You can do casting, which we'll talk about in another lecture, which technically doesn't really convert. It just allows your program to be referred to as a different data type. But conversion methods, there's a full set of functions for conversion methods between types. They're just two methods. 2 byte, 2 short, 2 int, 2 long, 2 float, 2 double, 2 char. And they do exactly what they imply. Converting to a byte, converting to a short. So here if we create a val, a read-only variable, float, and we say 12.34f, and remember through type inference we don't actually have to specify the colon followed by float. The compiler will be smart enough, it will see the 12.34f and it will say, hey, this is a float, I'm going to make the val float a float. We can then say val double, and we can say float.toDouble. So this kind of looks like Java in a way, because Java has those wrapper classes where you can say parse int, parse double, which parses doubles and converts them to objects. You have the toDouble, which converts a float to a double, and you can then assign it to a double. And this is okay to assign, remember, because the assignment, even though it's a read-only variable, is happening in the same line as the declaration. There's also bitwise operators that are supported by Kotlin. This is Kotlin. But they are not built-in operators. They're named functions. So here are some examples. Left shift, you can do, they're unary operators, unary functions. So some of them are unary. Some of them look like they're binary here because they're in between. So left shift, you can say 1 SHL, 2, that will do a bitwise operator. Bitwise operations you can use for comparisons, all sorts of things. If you want to store data, you can store them in bitwise operators. I don't use them too much, but sometimes you need to. Sometimes they're very useful. So you can shift bits left and right using these nice method names with the numbers on the left or right hand side. You can do the same thing with hexadecimal numbers using, so here you have some shifting left and right. And I think this other one's an unsigned shift right. And then you can do and, ors, and XORs. And you can also say .inv, which calls a method name and is not an operator. Booleans evaluate to true or false, 0 or 1. They're rather standard. They support usual negation, conjunction, and disjunction operations. They also use short circuit evaluation. So short circuit evaluation is when you have a condition, you use a Boolean in a condition, and you have multiple conditions, like if this is true or that is true. Now, in an OR condition, if you say the first condition evaluates to true, there's no need to evaluate the second condition, right? If true or true, no need to do it. If the first one is true, it should just go and execute the if block. This is referred to as short circuit evaluation. You only evaluate the first parameter of a condition, and if that evaluates as true, you're good to go. So this is short-circuit Boolean OR evaluations. It's more efficient. It's supported in Kotlin. So val x equals 1, val y equals 2, val z equals 2. 1 and 2s are representing numbers here. And then you can create a Boolean saying val is true. Is true is going to be set to equal true or false based on this comparison. If x is less than y and x is less than z. So what the actual output here would be if 1 is less than 2, which is true, and 1 is less than true. So the value of is true is going to be true. This is not an example of a short circuit evaluation because in an and, all the parameters have to be true in order to be true. If that was an or, after the x is less than y was evaluated, it wouldn't even look at the other comparison because it would already return true. And that is short circuit evaluation. So here's an example of short circuit evaluation. Also true if x is equal to y or y is equal to z. Well, x is equal to y. Actually, this is not doing a short circuit because the first condition is false. If x is equal to y, it's not 1 is equal to 2, so it has to evaluate the second one. Y is equal to z is true, so either one's true makes also true. Chars are another data type that supported a basic data type in Kotlin. They represent a single character. Character literals use single quotes, such as A inside a single quote or Z inside a single quote. Not double quotes. Double quotes represent strings. Chars also support escaping for the following sequence of characters. So backslash T, this is a tab. Backslash B, backslash N is a line feed. Backslash R is a carriage return. Backslash is delimiting a backslash. Backslash $sign. So you can escape the following sequences by providing a backslash, just like in Java. The char type is not treated as a number as used in Java. So in Java, technically, the char primitive data type, you can treat it as a number and it represents an ASCII value. It doesn't work that way in Kotlin. Strings and arrays are also basic types. We're going to talk about those in another lecture because they're a little more, need to be discussed in a little bit more detail. We'll talk about strings and string formatting, and we'll also talk about arrays. Arrays are actual classes, class types. So these are the basic data types in Kotlin that we will use. We'll talk about objects, which are data types as well. But this will get you started on how you can create variables with specific data types that represent numbers, chars, booleans, and bitwise operators. Thank you. Hello and welcome. I'd like to provide some Kotlin code-alongs. A code-along is the concept of walking through the code to demonstrate some of the concepts that I've talked about. So I provided a lot of lecture material on the concepts. Now I want to show you how it works in code with some more examples and some more demonstrations. This will help learn the concepts a bit more in a practical sense. So let's go ahead and create a new project in IntelliJ. We can go to Create New Project. And we can select Kotlin here on the left-hand side, and we want to say Kotlin JVM. Kotlin JVM is for the Java virtual machine. We want to hit the Next button. We want to give our project name a title. I'm just going to say basic data types. These will be some simple programs that utilize some of the basic data types. I'm going to put it in my normal project location. The project SDK is going to be Java version 1.8, and I'm going to use the Kotlin Java runtime. This is going to create 2 files. I'll also post the zip files for this code as a resource so you can download it and play around with it. I'm going to go ahead and hit finish. This is going to create my project. I have a basic data types folder over here under project, and I'll see inside source I don't have any files yet. It doesn't create any mains yet. So the first thing I'm going to do is create a main. So I'm going to right click on source. I'm going to say new, and I'm going to say Kotlin file class. From here, I'm just going to give it a name for one of my files. And the name I want to get it should be something descriptive relative to what you're doing. I'm going to print the area of a rectangle. So I'm just going to say print the area of rectangle. Not a great name considering this, but this isn't a class. And so I'm just going to describe the file on what it's doing concerning behavior. So I'm going to say print the area of a rectangle, okay. Creating a new KT file, print the area of a rectangle. It created the file with the comments. I'm going to delete those. And I'm going to start creating my program in Kotlin. We know from the Hello World application that there's an entry point into the program, which is the main function. Just like Java with the main method inside of a class, Kotlin has a main function. The function can be inside of a class, or it can be standalone top-level function, which is what I'm going to do. So I'm going to create a function just by fun. We'll talk about functions more later. Fun main. This will know that it's a special function. It gets called when the program gets invoked. And the main function takes strings colon arg. Strings, remember, is the type, or I'm sorry, the name. String is the name, and the name followed by the type, and this is going to be an array. This is standard stuff for Kotlin. We need to have the type be a string, and you'll see this a lot. I described this in the Hello World application, but this is the main entry point to the program. It's of the parameter passed in here is named strings. It's of type array. It represents the command line arguments. And you can actually pass things to the program, strings or data of the program, and you could read them in here. Right now we're not doing that. I'm going to go ahead and create 3 variables. They're all going to be of type val because they're going to be read-only. I don't need to change them. 2 of the variables I'm going to just keep as doubles, and 1 is going to be inferred by the equals. So I'm going to create a variable called width. It's going to be read-only. I'm just going to name it width, and I'm going to assign it to type double. We know how to assign types to variables. We just do the colon after the identifier. And I'm going to initialize this to 5.6. We don't need the semicolon in Kotlin, so that's all I need to do. I'm going to create another read-only variable called height, and this is also going to be a double, and I'm going to initialize this to 8.5. Some arbitrary numbers. The third variable I want to create is the perimeter. This will be as well read-only, but this time I'm not going to provide a data type. I'm just going to assign it some data, which is 2.0. And this is referred to as type inference. The JVM will or the Kotlin compiler will automatically know that this is of type double and assign the double. I didn't have to explicitly assign a data type here. So it's pretty nice. While I'm at it, I'm going to make sure this is spelled correctly. So perimeter. And I also want to do 2.0 and then have the height plus the width, which is how you can calculate the perimeter of a rectangle. So I want to initialize that to that. I also want to create a variable called area, but this is going to be a var because it's going to be able to be modified. It's a mutable variable. I'm going to say area, and I'm going to just initialize that to 0.0. Again, I'm not going to provide a data type for that because it's going to be inferred as a double. And now I'm going to print out, I'm going to calculate the area. So I'm just going to say area equals width times height. And we're using a multiplication operator there, just like we did with the height plus width, which is a plus operator. But again, I don't have to provide semicolons, which is nice. And now I'm going to print out the data. I want to print out the data in a certain format, so I'm going to actually use Java code for this. Remember, we can mix Java with Kotlin code. And so I'm going to use the printf method in Java to print out some data. So I'm just going to say system.out printf. Perimeter is 2 times, and then I'm going to format some of the stuff. %.1f. This is Java stuff for formatting the decimal points for the floats and doubles. Use F for doubles and floats. And then I'm going to print out height, width, and perimeter. I also want to print out the area. I'm going to format that as well. So I'm going to go ahead and print that out. Areas, and then it's going to get interpolated by what we pass in. This is standard Java stuff. But what we're doing is we're printing out the values of the variables. And what you should be doing as you're writing this code is you should constantly test it and work in small steps to make sure you don't have any errors. This can limit your bugs. Now this is the program. Again, it's just a program that calculates the area of a rectangle. So let's go ahead and build this and try running it and see what it prints out. You should print out both the perimeter and the area. Right here it's saying double cannot be invoked as a function. So we have to make sure that we have a multiplication here. So I just want to have 2.0 times. And it says the variable area initialized is redundant. It's okay. I just wanted to demonstrate using a mutable variable. That's why I initialized it. Let's run this program by going up to the run and just saying print the area of a rectangle, selecting that one. And now you'll see the output. Let me see if I can make this bigger. Here we go. So what we're doing is we're printing out the perimeter and the area of a rectangle with width and height of 5.6 and 8.5. And we're using double data type. Remember, double allows us to have floating point numbers. And so the perimeter is 2 times 8.5 times plus 5.6, which is 28.20. The area is 8.5 times 5.6, which is equal to 47.60. So a quick program, a code along, that helps you understand some of the data types and also type inference. You notice with perimeter and area, we didn't have to specify types. But when you do specify types, use the colon. And then we just use Java code in lines 11 and 12 to format some print data, the height, width, perimeter, and also, again, the area on the bottom line. We'll provide some more code alongs on different data types and other concepts. Thank you. Hello and welcome, everyone, again. I'd like to provide another code along, another simple program that demonstrates the use of data types, some arithmetic. We haven't talked about specific operators yet, but this will get you a head start on that, and how you can use Java intermixed with Kotlin. This program is going to convert the number of minutes to years or days. So let's bring up IntelliJ, and I'm going to create a new project again. Pretty basic stuff here. We can just go to New Project and use the wizard. So create new project. This one I'm going to also use Kotlin, JVM. We're doing a lot of this. And here I'm going to name it convert days to, or is it minutes to years and days. So minutes to years, days. Again, not great naming convention, but okay for now. Let's hit finish. This again, we'll create a new project, no files. So I need to create a new source file, right click, say new. I'm going to say Kotlin file class. And I'm just going to call this one main because it's really just a main. In here, it's going to be empty. Should have noticed also that when I created this, I created a file, just main.kt. There's other options to create Kotlin classes and enums and things like that, but for now we're just creating files. So we're going to do some of the most standard stuff we've done in other programs. We're just going to create our main. So fun main, and we're going to give it the standard. It takes strings as the name, and and we're going to add a colon, and it's going to be of type array. And this is the standard main routine that you can read data from the command line. So string, array, and it's going to be of type string. All right, let's create some more variables. We can create val or var variables in Kotlin. Val is read-only, var is mutable. We're going to create a minutes in year, and we're going to make that a type of double, using double a lot. And here we're just going to do some arithmetic. We're going to say standard 60, which is how many minutes in an hour, times 24, which is the number of hours, times 365 days, and that will give you the number of minutes in a year. We have to convert that to a double though, so we're going to call the toDouble function. We're also going to create an input. We're going to read information from the user here. So we're going to use the Java scanner class, which allows us to read data from the keyboard. So here I'm going to say, and I'm going to make this a var, and I'm going to say scanner system.in, and you put this inside parentheses in Kotlin. And we'll have to make sure we import the scanner class so we can resolve a lot of errors by clicking the light bulb when something is red. So we can say import, and we can just say java util.scanner. So you see doing that a lot. When you see things in red, go to the light bulb and it will suggest an error. You can also turn on automatic imports in your project settings. If you go to File, Settings, and you go to the editor, go to General, say Auto Import, make sure everything is checked. Also optimize imports on the fly, all of this. And then hit Apply and hit OK. That will resolve a lot of your imports for you. But this input is where we're going to store the scanner object so we can call a function on it to read in from the command line. The next thing we want to do is we want to print something out to the user so they know what to enter. So we're going to use the print function. That's how you can print stuff to the screen in Kotlin. You just say print, input the number of minutes. And next, we're going to create another variable called min. And this time I'm going to use type inference. Whatever the user enters, they got to enter a double. So I'm going to use my variable on line 6, which is my scanner object. I can call a method on that in Java saying next double. That will read a double from the keyboard. I'm going to store it in the variable called min on line 10. I'm going to then do some calculations. I'm going to create a couple more variables, years and days, which will just do some arithmetic. So val years on line 12 is just going to be min divided by minutes in year dot toLong and dot toInt. So you see a lot of these two methods which do conversions. And then I'm going to print out all the data using println that I'm interested in. So here I'm going to say println min.toInt, minutes is approximately, and so forth. And what this program again is going to do is it's going to take input from the user and convert the minutes to the number of years and days. So again, let's run this. Let's first build it. So there are a couple things that I need to do to fix this. In has the wrong quotation, single quotes. So I want to fix that. And let's build this. We're going to have some more errors. We have some problems with operator overloading. So we can't use println with the plus because println doesn't work that way, right? That's how Java works. So what we need to do is we need to use string templates, which we haven't talked about, but I'm just going to do this just to quickly compile, just to demonstrate the program. So what we want to convert this double to an int first. And then what we want to do is print out the variables in a Kotlin style, which is using print templates with the $signs. So we can just add $sign symbols here and have it be a complete string, something like that. This will be explained later, but we're using a string template here. So now this should compile, and we'll be able to convert our input, whatever we enter, the number of minutes, to years and days. So compile, let's run this. First thing that's going to happen is it's going to ask me to enter some information because it's reading from the keyboard. So I should put a high number in minutes in here if I want to convert it to years. So I'm just going to do like 88,000. I'm going to hit return, and then this is going to perform the calculations. So it's going to start reading and putting some data in variables and then printing out the data. So I'm going to hit return, and it's still kind of a small number. So it says 0 years and 61 days. Let's try to see if we can get the years up. Let's run this again. This time I'll enter 880,000. This time I have 1 year and 252 days for 888,888 minutes. So we demonstrated again some basic data types, conversions using some Java code with next double. Showed you how you can use the scanner class to input data from the keyboard, store that in a variable. We used all vals, read-only variables for here, which we should try to do as much as possible. And then we use a string template, which we'll explain in a more thorough example. Thank you. Hello and welcome. I'd like to continue our discussion on data types and talk about strings and string templates. A string represents text. We talked about numbers before, and we talked about chars. Chars are single characters. Numbers are numbers. Many different data types represent numbers, from floats to ints to doubles. Strings are data that represent a word, a text, more than one character. They're represented by the type string. Here's an example of creating a val, a read-only variable, val message, and then identifying the variable as type string. After the colon, you see the data type string. And so that's how you declare a read-only variable as type string. Remember, we try to create all of our variables read-only so that we don't have state changes as much. Strings are immutable. Immutable means that they cannot change. This is similar to Java. Java strings are immutable. When you write new data to strings, you create new references. Elements of a string are characters that can be accessed by the indexing operation. So this is kind of similar to C. If you're out there, you can access the individual characters of a string by just using the array kind of quote brackets, the left and right brackets, and then have an index inside there. A string can also be iterated over with a for loop. So you can see something like this, for C in string. We haven't talked about the in operator, but the in is specifying you're in some data type. C is representing a character. So for C in string, you print this out, you'll see all the characters in a string. String literals. String literals can be created using double quotes or triple quotes. String literals are when you create a string inside these double or triple quotes and directly assign them to a data without creating a reference in memory. Kotlin has two types of string literals. Double quotes, it creates an escaped string. Special characters such as the new line must be escaped. We talked about this when we talked about characters. If you want to have things like a new line or a tab, you have to do a \n. So an example here, we're creating a string, val string. This is doing type inference. We're not actually specifying the data type for the string here. We're just assigning it some text inside double quotes. And this is how you can create a string literal. You'll notice in there's a \n. The \n is escaping a character, and it's saying this has special meaning to the compiler. \n is a new line. So you'll see string with followed by new line. Raw strings that can contain new lines and arbitrary text. So double quotes around a string literal and also raw strings. A raw string is delimited by a triple quote, contains no escaping, and can contain new lines and any other characters. So a raw string is super useful for strings that span many lines. So you start the string with 3 quotes, you end the string with 3 quotes. The nice thing about this is, again, you can have multiple lines. So here's an example of val text equal to, and you have the 3 quotes, you have a new line, you don't have any escape sequences, and then you have for C in foo print C. So what this would actually print out, and I'm going to demo some of these, what this will print out is for C in foo print C. It's not going to do a print. It's not going to consider foo inside double quotes. It's going to print that out as a literal. Trim margin. You can remove leading white space with trim margin, the trim margin function. So here's an example. You again have another triple quoted string, so you can span it multiple lines. In here we're saying multiple lines and we're saying trim margin. By default, trim margin will take the parallel bar as the prefix. But you can choose any character you want if you pass it into the parameters trim margin. So here we say val text and we have a triple quoted string, and then we say trim margin, which removes all of the white space, the leading white space. So let's try some of these examples out of creating strings and using the triple quotes versus the double quotes. So here we have our hello world application. We have our one function, our main function. It's a function because it has fun. We've seen this before with the args and the array. Let's try creating some strings and just seeing how we can create strings and print them out in Kotlin. So in order to create a string, we can just create a, say, val message colon string. We're not using it anywhere here, but we can say val message colon string. After the colon is identifying the data type, val is identifying that the variable is read-only. We can then just assign something to message using a string literal like JSON. And then we can print something out using println JSON. And if we save and we try to build that, or I'm sorry, message. Message is the variable. Save that out, build it, and run it, you'll see displayed to the screen the message, which is JSON. So it's very simple to create basic strings. That's a string literal inside the double quotes, assigning to message on line 8. You can also see the characters in a string by using the for loop. So if I don't want to print out the entire string with println, I can put it inside of a for loop, like for c in string. But we got to make sure we use the right variable. And then we're going to print out the characters. So let's see what this prints out. What we'll want to do though is we're using println, so it should print out a line after every character. So let's build this and run it. And we'll see JASON printed out on separate lines. And that's what we see down here. I wonder if I can create bigger output here so you can, bigger font I should say. Well, hopefully you can see the output here, but you can get each character out of a string by C in message. And then to create triple quoted strings, you can see how triple quoted strings ignore new lines. And so again, if we create another string here and it's inside triple quoted strings, what we're going to see printed out here, and we don't want to actually print this out in a for loop, we just want to print it out. We'll see that everything there's no delimiters, there's no escape sequences. So we're going to see actual for C and foo print C displayed. And that's what we see. And we actually see new lines printed out because it takes the new lines as literals. So it's pretty nice, that triple quoted string. Let's also take a look at this trim margin function to see what this does. So from the slides, the example, we have val text, read-only variable, triple quoted string, and we're using a parallel bar and then saying trim margin. Let's see what the output of this is. We didn't actually print it out, so let's make sure we print it out. Do a println, print line, text. And you'll see you can just run. You don't have to build it every time. So now we see tell me and I forgot, tell me and I remember, and it removed all the leading white space. Everything was printed on a new line, but it removed all leading white space. So trim margin is a useful function to remove white space. And you can pass in a parameter trim margin if you don't want to use that parallel bar to identify what to trim. Now let's take a look at string templates. So string templates. Java developers are familiar with the usage of string concatenation to mix expressions with string literals. So here's an example. Val name equals Sam. Val concat equals hello plus name. We use the plus operator in Java to concatenate two strings. If we were to print that out, what we would see, print out concat, what we would see is hello space Sam. We're familiar with that use case. String templates are a simple and effective way of embedding values, variables, or even expressions inside a string without the need for pattern replacement or string concatenation. So we'll give an example of that in a second. String templates improve on the Java experience when using multiple variables in a string literal, as it keeps the string short and more readable. And so here's an example. As opposed to doing the $, and this looks something like PHP. If you're familiar with PHP, you can have a value or variable can be embedded simply by prefixing with $. The compiler will know that that $, represents a variable. It will interpolate that variable and print out the value of it. So if we say val name equals Sam, val string equals hello $name, it's going to print out hello Sam. So just like PHP. Arbitrary expressions can be embedded by prefixing with $, and wrapping it in braces. So you can also wrap things in braces if you want to call methods and things like that. So here we have val name equals Sam, val string equals hello $name. It's going to hello Sam. Your name has whatever name.length is. It's going to interpolate that by calling the method on the variable name, print out the value of it, characters. So very useful. It's a lot easier to write. You don't have to do pluses. You don't have to make strings so long. You can also use string templates in multi-line strings. Multi-line strings do not support escape sequences, so you can't do a \n or a \t. You have to use an embedded expression if you need to use a literal $, in the context of your string. So here, what we're seeing is val price equals, and we have double-quoted string, but it doesn't know that that's a double-quoted string. So you need to use the literal $, in the contents of your string. So here we want to print out a $. We don't want the $, to be interpreted as a variable inside the quotes. so we can put the $sign inside these brackets. And so let's go through these examples in IntelliJ. So let's try to use string templates here. Just going to take the example. We're going to say val name equals Sam, val string equals hello $name, and then we're going to print out string. And again, what you'll see is hello Sam printed out. And you see that down here. So it's pretty cool. You can see hello $name automatically gets interpolated. And then we can use the brackets if we want to interpolate in braces as well. So here we have Sam, hello $name. Your name has $name length characters. So here we see hello Sam. And we want to make sure we have actual double quotes. When I copied that in, it didn't post a double quote. And now we have hello Sam, your name has 3 characters. So pretty cool. Then the last example was this price where we wanted to actually print out a $sign, but we weren't able to add an escape sequence. And then we also want to make sure that this is copied and pasted incorrectly. So now when we run this, you'll see it says 99.9. So instead of taking the $sign and thinking that's a variable, it will escape it and actually print it out because it's in a single quote inside the brackets. So you can use the brackets as well to embed expressions. So we'll use string templates and strings a lot in some of our projects and so forth, but hopefully this gives you an idea in how it is quicker than Java and you don't have to use concatenation as much. Just like PHP, really. Thank you. Hello everyone. I'd like to do a little code along that helps you understand the concept of a string data type. This will be just a simple program that converts strings to starts with. So we're going to mix some Java code in here that uses the starts with method. We're going to check to see if a string starts with a particular prefix. Let's create a new project, Kotlin. We'll just call this project name string starts with. And keep everything else as default and create a new source file. Right click, say new. And we want to say Kotlin file class. I was mentioning before under the kind, you can select different options if you're selecting classes for objects, but we haven't gotten there yet. So we're just going to say file. We're going to keep it named as main. And we're going to create our normal function, our main function. Takes a string and some arguments. You can copy or provide the named parameter, whatever you want, but right here it's just args. We're going to have our ending bracket. We're going to create a couple read-only strings. So we'll just say val string1, where it's going to be of type string. So we need to say after the colon string, and we're just going to put something in double quotes. Red is my favorite color. Something very basic. Create another string called string2, and this is also going to be of type string, obviously, and this is going to be orange is also my favorite. So we want to see what these start with, so let's create another string that just says start string. We could use type inference here because the types would be inferred, and usually that is what you want to do. By default, don't provide the type. If the compiler complains, then you provide the type. Here we're just going to say red. And now we're going to create a couple variables that we want to display to the user. And we're going to use Java code, the Java string methods. So here we want to just say starts1 or start s1 equals stir.1, and we can call, because this is of type string, we can call methods in the java.lang.string class. So we want to call the starts with method, and we want to pass it in the start string. Something like that. We're checking if our string starts with red. Create another one called start s2, and this will see if string 2 starts with our start string. And you'll see this nice IntelliSense Right? This code completion is very nice in IntelliJ, where you can helps you write code a lot quicker. We say starts with, and we pass in start string again. Now we want to output some data to the user that's useful, so we're going to use our print method. And we're going to use a string template. String templates are this awesome concept of allowing your variables to be right inside the double quotes, prefixing them with the $sign, and Kotlin will know enough to understand that's a variable and give you the value of that variable. So you don't have to use the plus concatenation operator anymore if you're familiar with Java. So here we can just actually say $sign, and we want to print out string 1, and then starts with, everything's in double quotes, we don't have to use plus anymore, and we want to print out the start string, start str, we know it's a variable because of the $sign, and we're going to put in question mark, and then the $sign for starts S1. Something like that. We also want to check for, and we want to make sure we have an extra line after we print that out, so we're going to print ln, and then do it again. This time we're going to print out string 2, so again we use the $sign, str2, starts with, $sign, start, stir, question mark, space, this time $sign starts, start S2. So these string templates are very handy. So we're demonstrating a couple things here, how we can create string data types, assign those string literals inside the double quotes, using the starts with method of the java.lang string class, and then on line 10 and 11 using string templates to display variable data of the strings. Let's go ahead and build this and see what the output is. We'll run it. And what you'll see here is red is my favorite color, starts with red. So the red is my favorite color is the string, and it starts with red. And then we're printing out a Boolean, which is true. So the other thing I didn't get to mention is on line 7 and 8, the starts with method returns a Boolean, which is true or false. We know Boolean is a basic data type. So what we could do here, instead of using type inference, it would be clear to the user if we were to use a Boolean type. So here we could just say Boolean, because that is what is returning. You're not required to do that because of type inference, but let's do that because we're trying to learn about data types. So now after the question mark, it's going to be true or false. And this would still build, and it would still run with the same output. It's just printing out the Boolean. So red is my favorite color, starts with red, equals true. Orange is also my favorite color, starts with red, is false. Question mark after that. So a pretty nifty program where we can define strings inside double quotes, use string methods from Java, intermixing the Java code with the Kotlin, and using string templates, and also declaring Booleans, true or false values. Thank you. Hello and welcome. Let's talk about the any and any question mark types. So the any type is a supertype of all non-nullable types in Kotlin. When you see any, it just means it's the top level object. So this also includes basic types such as int. Remember we talked about ints, doubles, and how they're not actually primitive data types. They still refer to them in Kotlin as primitive data types, but they're actual objects. You don't have to do a lot of the auto boxing or wrap integers and stuff in those primitive data types in Kotlin. So for the basic data types, same thing, and that's why any is the superclass of those primitive data types, because those primitive data types are objects. You cannot hold the null value in an any type. It's very, very similar to java.lang.object. So if you're familiar with Java, Java's very base class, the class that's highest in the hierarchy, the very top of the hierarchy, is the java.lang.object. Every other object in Java is derived from that. And it's the same thing in Kotlin, except instead of java.lang.object, it's the any type. The any type is the supertype of all non-nullable types. So the toString method, the equals method, and the hashcode methods, those are all going to be inherited from the any type. So in Java, you have this concept of the object, which is the top level object. Inside there, you have a toString method, which gives a string representation of an object. you have the equals method, and you have the hash code. And what you typically do in your own class, because it's a subtype of an object, you override these methods. You override the toString, you override the equals, and you override the hash code. You provide your own implementation. For toString, you usually print out member variables. For the equals, you'll usually implement the comparator interface and check whether or not member variables are equal. Returning values 0, greater than 1, greater than 0, less than 0 for equal, not equal, and less than not equal, and so forth. So the same happens for these any type. You have the toString, equals, and hash code inside that base class. Wait and notify are also methods that are available in java.lang.object, but they're not available in the any type, but you can call them if you manually cast the value to a java.lang.object. So Kotlin doesn't support those methods. The reason this is important is because you can use the any type a lot, just like you do in Java, where you can say if a method is returning something and you want to pass an object around, you can use any. And we'll have some use cases of using this type, but it is important. So just as in Java, assigning a value of a primitive type to a variable type any performs automatic boxing. It's transparent to you. I know I said before that any is an automatic object, so really automatic boxing doesn't even happen in Kotlin. So in this example, val answer : any. Any is just like saying object equals 42. And because any, 42 I should say, is a primitive type, it's still an object and it converts it to an object. Doesn't really need to convert it. If you need a variable that can hold any possible value in Kotlin, including null, you just use the any question mark. So just like we've had this constant theme with nullables, we will in this class, where when you have a nullable, you're using a question mark. So we have other operators that we're going to talk about to check for null. And to check for null, you're gonna see this question mark. So you're gonna see it a lot. So it'll become pretty familiar with. So any question mark just means the object can be null. Remember, Kotlin is a null-safe language, so there's a lot of things in the language where you can check for null or return null. So when you see any or any question mark, you'll be familiar with what that means. I just wanted to have a quick lecture to describe it and why it's important. Thank you. Hello and welcome. In this lecture, I'd like to talk about the unit type, which is also the void type. We know that everything in Kotlin is an object, not like Java, where Java has primitive data types. Everything in Kotlin is an object. So there's also this type called unit. The unit type in Kotlin fulfills the same function as void in Java. The void is not a type in Java. The void is more of a modifier that tells you whether or not a method is returning any data. When a method doesn't return any data in Java, it defines the method as being void, but it really doesn't return anything. With the unit type in Kotlin, you're actually returning something. You're just telling the system that you're returning nothing. So it's a type. So it can be used as a return type of a function that has nothing interesting to return. You do not have to explicitly declare it. Kotlin's automatically going to return this type if your function returns nothing. So you would declare it like you would create any function. So in most cases, you're not even going to notice the difference between the void and the unit. The issue is here, you need to understand what's going on behind the scenes with Kotlin, because if you didn't understand this, you wouldn't know how generics work, and you wouldn't know how certain methods that are required to return a value aren't having errors in the compiler because they're not returning anything. In essence, under the hood, they are returning something. And so to get many of the features of Kotlin to work, you have to have this type, this unit type. Again, it's just telling Kotlin that you're returning nothing, and you really will never even notice it. But it's how things work in Kotlin. It's how many things work. So unlike Java, unit is a full-fledged type. And unlike void, it can be used as a type argument. So you can pass it in. So for you C programmers out there, you might notice this because you could have a void parameter. But in C, it's more of just an indicator to say that this function doesn't take any parameters. In Java, it's an indication that you are passing a type. Or I'm sorry, Kotlin. So unit is useful when you override a function that returns a generic parameter and makes it return a value of the unit type. Right? So if you override a function and it has a generic, and we haven't talked about generics, but generics are a type. The generic is saying it returns something. If you were to try to override this function and you didn't return anything, it wouldn't work because you're required to return something as an overridden method. So as long as unit type exists, you are actually returning something. So here's an example. You have an interface processor and you have a method function inside that interface called process that's returning a T. That's how you see the :T. It's returning a type, a generic type. You have class noResultProcessor that's going to implement this interface processor. Since noResultProcessor is implementing an interface, it has to have a method called process that returns a T, returns a generic. Now, inside this funProcess method, you don't have to explicitly return anything. If you don't actually return anything, the system, Kotlin, is still going to return a unit type. And this is what allows you to override a method that is returning a generic. It makes generics run more smoothly. So just to reiterate this, the signature of the interface requires the process function to return a value, right? You've seen that. Interface, funProcess T. Process method, process function has to return a T, which is a generic. The unit type does not have a value, so it's no problem to return it from the method. You can return a unit type. You don't need to write an explicit return statement in the process method of the class that's implementing the interface because the compiler will automatically return unit. So Kotlin unit means only one instance. You also use this in a singleton. And that is exactly what distinguishes unit from Java's void. Java does sort of have this concept of a unit type because if you look at the Java APIs, there's a class called java.lang.void. And void is an actual object in Java. So it's similar to that, but traditionally when you think of Java and you think of the void, you just think a method that returns no data and really returns nothing, doesn't return a type. In Kotlin, you're actually returning a type. So the advantage of having this unit type is it can make generic code work more smoothly. It allows the any type to be supported. If you didn't return a type and you're returning void nothing, you'd have problems because you wouldn't be able to use any because any, remember, is that top level object. You'd have problems with any if you didn't have the unit type. If you pass unit for a generic parameter T, the code written for any T will expect an object. You have to have an object, and there must be an object. And in cases where a method doesn't return anything, unit is returned, and that is an object, so you adhere to the requirement of returning an object for a generic. So this is why there's a unit type in Kotlin. Most likely, you're not even going to know it exists. You probably won't even use it. You can implicitly or you can explicitly add it to a parameter, to a method, but you probably won't do that. But again, if you want to fully understand Kotlin, you need to understand these types of concepts. Thank you. Hello, class. Let's talk about the nothing type. You thought the unit type was kind of strange. Now the nothing type comes into play. And it's a little different from the unit type. We talked about the unit type. The unit type will return void. It represents void in Kotlin. It's necessary because everything is a type in Kotlin. Everything is an object, and you utilize that when you want to work with generics. So now we have the nothing type. And so again, I want to remind everyone, everything in Kotlin has a type. It's important. So this type, the nothing type, has no values. It's used to mark code locations that can never be reached. So the concept of a return value doesn't make sense because they can never complete successfully. If you have a function like a forever loop, or you have a function that throws an exception, and it always throws that exception or has a loop, it's never going to return data. And so there's no reason to have that function identified as returning something. Even the unit type, it doesn't make sense. Right? So you can use nothing to mark a function that never returns. It only makes sense to do this if you have a function return type or as a type argument. Right? Because everything else it wouldn't make sense. Everything else is going to return something. So functions return values. If a function never returns a value, use this nothing to basically let Kotlin know that this is never returning. You can also use it as a type argument. There are no instances of the nothing type. It's defined as a type, but it can never be instantiated. You can't create an instance of nothing. It's, again, just used for return types and functions and arguments. Some examples. Many testing libraries have a function called fail that fails the current test by throwing an exception with a specified message. So fail will jump out of a method. And so that method is not going to return anything because it jumped out of it. Just like maybe a goto, if you had a goto method in an older programming language. So any kind of method that throws an exception is going to jump out of the method and not return anything. And that's when you use a nothing type. A function that has an infinite loop also is never going to complete successfully. So if you're writing some kind of monitor where you're waiting for something and you're constantly just listening or monitoring something and you never return, again, this is when you'd use the nothing type. So here's an example. You have this function called fail. It takes a parameter named message of type string and it returns nothing. And the reason it returns nothing is because inside this method, you're throwing an exception. So you never return any data from that method. You're not even going to return the unit type in this case. So this is how you can tell the Kotlin compiler here that generates the bytecode that this method is not going to return anything. So when you call this function, the compiler will know that the execution doesn't continue beyond the call. It helps optimize the compiler too, because anything after the throw the compiler is not going to care about. So it can be more efficient. So here's an example. This is an example. We're creating a read-only variable called s. We know that because it's type val. Well, not type val, but it's declared with a val keyword. And then we're saying person. Person is an object. It has a property called name. We know that because it's using the dot operator. The question mark colon we haven't seen yet, but this is referred to as the Elvis operator. This is asking if person.name is equal to null. It's a null check. And so what it's saying is if person.name is equal to null, then call this fail method. Fail method is going to print something out name required or return some data name required. But what this is saying is this is no code after this is going to be executed if person.name is equal to null. And so if we have another statement after here, println s, if we ever get to this line, we know that s is going to be initialized. Because the only way s would not be initialized is if person.name was null. Right? So implicitly here, we're using a nothing type to say fail name required. So again, this is a function that returns nothing, can be used on the right side of an Elvis operator to perform precondition checking. You don't have to check for null. If we didn't use this Elvis operator, we'd have to have an if statement. We'd have to say if person.name equals null, call the fail method, which would return nothing. Right? Because fail is not going to return anything. Else, println s. But again, we're using nothing here on the right-hand side of the Elvis operator. And we'll talk about the Elvis operator in a lot more detail. Don't worry about that. So the compiler can infer that the type of s is not null because the branch handling the case when it's null always throws an exception. So remember that Kotlin is a null-safe language. The way that it can tell things are not null and not complaining the compiler is by having this nothing type. If this nothing type wasn't there, it wouldn't be able to, it would give you an error and say println s may be null. So it's a way for optimize the compiler with this nothing type. The compiler can use the nothing type to know when things are not null. It can know when methods aren't going to return any data, and it can make sure other things are correct. So in this case, it knows that s is not null. So again, it's a different concept, but hopefully it's not too confusing. It's just for whenever a method doesn't return anything, different from the unit type. Thank you. Hello and welcome. In this lecture, I'd like to talk about casting, more specifically smart cast and explicit casts. So casting is a concept where you take an object of one particular type and you turn it into another object type. Casting does not mean that you're converting a type. What it really means is you're just telling the compiler, I want to use this type as this type. It's a common concept in object-oriented programming. You'll usually cast types. If you have a base class, an inheritance, or a subclass, you'll cast them. And it's not actual conversion, but it's telling the compiler, I'm going to use it like this. So Kotlin has this concept of casting as well. There are cast operators in Kotlin, which will be discussed when we talk about operators. Specifically, we'll talk about the safe operators and the as question mark operators and so forth. In Kotlin, you can check whether a variable of a certain type is something by using an is check. So this is similar to the instance of operator in Java. If you wanted to check what type of an object something is, in Java you would say if this is an instance of this, then do something. And what the instance of operator did was it would check whether a variable is of a certain type. Kotlin doesn't have an instance of. It has an is. So whenever you see the keyword is, you're doing an instance of. You're checking whether or not this variable is of a certain type. So here's an example. Again, in Java, you check that a variable is a certain type if you needed to access member variables of that type. And what you would do is you would have object B, which would be a base class. And you would say if A is an instance of B, it would turn true. And then you would cast it into object B. And in casting Java, all you did was you put the name of the object inside parentheses next to the object that you wanted to cast, that you wanted to change. You don't need to do this in Kotlin because the compiler will automatically do it for you. Now, in this example, if A is an instance of B, in object-oriented design, you really should never ask what type an object is. It's kind of something what you call a design flaw. But anyways, Java does it a lot. There's not a lot of high cost with it. And so there's a lot of these dynamic casting going on. If you were to program in C++, dynamic casting is much more expensive, and you want to do something like this. But I don't want to go off too much on a tangent. But one of the things I see when I see this instance of in Java, I just kind of think, this is kind of a strange thing. You really shouldn't be doing this. But anyways, they do it a lot, and I think they do it a lot because, again, it doesn't cost much. But for Kotlin, you don't have to actually do this to cast something, but you can still use the is check to check whether or not a variable has a certain type. So there's this thing as smart casts. In Kotlin, if you check the variable for a certain type, you don't need to cast it afterwards, which is really nice, right? Because then you don't have to do all these is checks. So you can use it as having the type you checked for previously, right? So you can still have the is check, but you never have to explicitly cast it. So it's going to save you time, right? So the Kotlin compiler is more intelligent, and it will remember the type check for us, implicitly casting reference to the more specific type. So this is pretty cool. It's, again, another feature that gets rid of boilerplate code, right? In Java, you would do a lot of this instance of, and then you cast. Well, now you don't have to do instance of and cast in Kotlin. You just do is. You do the type check, is, and then you don't have to do the casting. So it saves you time. Again, it's getting rid of these nuances. Kotlin is getting rid of these boilerplate stuff that you always have to do. That's just annoying and doesn't make programming fun. So Kotlin makes programming fun by getting rid of these things. So smart cast is when the compiler performs the cast for you. It's kind of similar if you think of this type inference. The type inference is you don't have to specifically specify a data type for a variable. It looks at the context, and whatever the context is, the compiler will know it. Same thing here. The compiler is going to know what you want to cast to because you just did an is. So it reduces a lot of duplicate code. Here's an example where you have a function called printString length, and it takes an any name as a parameter that's of type any, and it says if any is a string, don't have to do any casting after that. It just prints out any.length because it remembers that if any, it will cast any to a string implicitly. So you can access the methods of the string class, you're good to go. You're reducing duplicate code. Pretty nice feature. Some restrictions on SmartCast. You can only use SmartCast on objects or variables that the compiler can guarantee has not changed between the time when the variable is checked and the time when it's used. So if you do an is check and then you do like 30 lines of code and then you try to use it, it might not work because something may have changed. So you want to make sure that when you do the is check, you use it right after. And you also want to make sure that any variable fields and local vars. So var, remember, is variables that can change. They're mutable data. So when you declare member variables using var or any local vars that you have inside of a method, if they have been closed over and mutated, they cannot be used in SmartCast. Right, so if they change, var fields might have changed. It might be a different type of an object now. And so then you go and you try to implicitly cast, and it won't do that for you. So it's not going to cast these var fields because they can change. So when a variable changes after the is check, or if a property of a class has a custom accessor is a get, and is a var, then you need to use an explicit cast. Another reason why you want to use val for creating variables, because you don't have to do these explicit casting. Any member fields that are var or custom accessors, you have to use an explicit cast. So explicit casting. The way you can do an explicit cast in Kotlin, you don't put the type of the object inside parentheses like Java. What you'll do is you'll use an operator. The operator that you're going to use is called as, the as keyword. So if you say as, you're doing an explicit cast. It's the same as doing the parentheses in Java. This operation will throw a class cast exception if the cast cannot be performed legally. So if you're trying to cast to something that's incorrect, just like in Java, you're going to have a runtime exception. So you better be making sure when you do these static casting that you know what you're typing to. If you don't, you're going to have throw an exception, the program's going to crash. So don't cast to data types that are not compatible. So here's an example. You have a length function, takes any type. You have a val string, and this is a local variable, any as string. And what you're doing here is you're saying val string equals any, and then you're casting any to a string by using that as keyword. All right, we didn't do an is check here. So if we did an is check, we would need to do this. In this case, we're explicitly casting, and then we're accessing the length method of the string object so that we can return it. Also, you cannot use the null value to cast that a type that is not defined as nullable. We haven't talked about nullable, but nullable uses the question mark. If you wanted to use null in this example, you would have to say string question mark, and that would say it can be null. There's also another operator that you can use if you want to check for null. It's the as question mark. We'll talk about that in more detail when we talk about checking for null with the as question mark. So to cast to a value that can't be null, we simply declare the required type as nullable using this question mark, val string that says it's nullable, and then we could do the as keyword. So we'll discuss as briefly when we talk about the as question mark, which is checking for null as well. There's two ways you can do it. You can do this val string question mark, or you can do val string, and then you can do any and then as question mark string. But we'll get to that more. So again, just some more information on some different keywords, different operators in Kotlin. And this was explicit casting and SmartCast. Thank you. Hello class and welcome. I'd like to provide a quick code along on how we can use the SmartCast with the is operator to show you how you can check your data type before you do something important. Let's create a new project called SmartCast example. Create a new file under source, Kotlin file class, and we'll just call this main. Very familiar with this concept so far. We also are familiar with our top level function called main, which you can have, name it whatever you want, strings, whatever the case may be. Let's create a couple of variables. Read only. This one we'll just make it a string. And this other one we're going to make it an integer. So we'll just, using type inference here, one val string, one val int. So what we can do is we can use this nice is operator to check whether or not our type is of a particular instance. The same exact thing as using the instance of operator in Java. So here we can say string 1, actually it might even be better to let's demonstrate this using the any type. So we haven't talked about functions yet, but let's create one then we can actually use the any type, which is another good demonstration. So we're going to say just get the string length, and this is going to take a named parameter object of type any. Remember, we know what any is, right? Any is that top level object. It's the equivalent of java.lang object. Every object in Kotlin inherits from any. So here we're going to return an int. So we just want to say, and it might be null. So we're just going to put that question mark there. What we're going to do here is where, in this function is where we want to use to see if an instance is of a particular type. So we can say if the object is a string, then we can call a method on that string. And what we'll want to do here is we'll want to return the length. So we'll just say object.length. Otherwise, we're just going to return null. So again, what we're doing here in our function is it can take any type of object, an integer or a string, because we have the any as the parameter. We're then checking if that object that was passed into the getStringLength function is of type string. If it is, we're going to call a function on it called length. It's going to return the length, an int. So what we can do to invoke this is we can just call print line, and we can say getStringLength and pass in string 1, and it should return the length. And if we pass in the integer, it should return null, because that's what we're returning if we don't pass in of type int. So let's see this work. Let's compile it and run it. So what you're seeing here is first it returns 5 because JSON has 5 characters. Then it returns null because we're trying to pass in an integer. We can't call the length method on an int. We can only call it on a string. So we use the is keyword followed by if the object passed in is of type string, we get the length. Otherwise, we return null. So we return null when we called the getStringLength function on line 7. So we can use the is instance with the object.length to check. Right? And what is this object.length doing? It's doing a smart cast. Because remember, object is of type any. You can't call the length method on type any. That would have to be a string. So what's happening implicitly in line 13 is it's automatically casting object to a string. That's a smart cast. In Java, you would normally have to do something like this. You'd have to say instance of, right? And then what we would have to do is we'd have to say, if it's an instance of a string, then we want to return, what we want to do is we want to cast something into a string, the object, and then we want to call the length on it. We would do something like this in Java, right? We would have to cast the object to a string, then call the length method on it. With the smart cast, we don't have to do that. Much easier, much quicker to write. Very nice feature. So a quick demonstration of a smart cast and also using that is keyword and also the any type. Thank you. Hello and welcome. Let's talk about operators. Operators are functions that use a symbolic name. In Kotlin, there are many built-in operators which are actual function calls. In operators, there's all different types of operators. We have comparison operators, arithmetic operators, logical operators. Operators are just a symbol in Java. In Kotlin, they're both a symbol and a function call. You can use operators to compare data, compare numbers. You can use operators to assign data, the equals operator. You can use operators in conditional checking, where you can do ampersand, ampersand for ands. Operators used almost in all languages, in some way. So there's no different. Kotlin, you can have operators. You just also usually have a corresponding function call as well. Many operators are predefined in Kotlin, just like they are in most other languages, and most operators tend to be combined with the infix style. Infix style means that the operator is a binary operator. Infix means that there's an operand on the left side and an operand on the right side. So it's kind of like if you had a variable called x and you had a variable called y, x would be on the left side, that's an operand, plus would be the operator, y would be the operand on the right side, and that's referred to as infix style. If you had prefix style, the operator would be a unary operator, or actually it doesn't have to be a unary operator. Binary, unary operator, ternary operators, that just means how many arguments they have, how many operands they have. A plus operator has 2 arguments, right? Because you have to add 2 things. Well, actually that depends too, but anyways, there's different types of operators, different styles of operators. Infix notation is what you're traditionally used to in most languages, but there's also prefix and postfix notation. Infix notation means, again, that the operator is in the middle. Prefix notation means that the operator is at the beginning, and then the operands are after. Postfix notation is where the operator is at the end and the arguments are before it, or the operands are before it. Often operators are preferred over real names if the operators are already familiar to the users. And operators look just like mathematical operators. Plus, divide, multiply. So use what you're familiar with. Don't use the method just because you're in Kotlin, right? Use the original operators with the symbols, with the symbolic name. A logical operator, sometimes called a Boolean operator, is an operator that returns a Boolean result. Booleans are true-false values. Remember this from our data types discussion. It returns a Boolean result that's based on the Boolean result of one or two other expressions. So examples of logical operators would be like or, and, not. They're not performing the arithmetic. Arithmetic operators are a mathematical function that takes two operands and performs a calculation on them. And then again, we also have comparison operators and unary operators which do single operations. So here are some unary operators. Unary operator means it only takes one operand, one argument. And in this case, in these examples, we have prefix notation here, plus a. The operator is before the operand. So what this is saying is a plus a, and then minus a, and then a question mark a. And so you can also call functions in Kotlin a.unary plus, a.unary minus, a.not. Other unary operators, here you have the postfix notation, a++. This is the same as saying a equals a plus 1. You're incrementing, so the corresponding function for a++ is a.inc. And then the same goes for a minus minus. It's equal to a equals a minus 1, or a.dec. Right? So with the unary operators with the plus a, you're just converting a negative to a positive with a plus a. You're converting a plus to a negative with a minus a. And then not a is saying if it was true, now it's not false. Arithmetic operators, these are the ones you're probably familiar with just from math. A plus b, a minus b, a star b is a multiply. A divided b is the /. A percent b is modulus. Modulus is when you say 5 divided by 2, what's the remainder of that? The remainder is 1. So 5 module 2 would be 1. And then a.b is a range. And this may be a little different. They don't have this in Java. And then you see all the corresponding methods in Kotlin. Very intuitive. Plus is a plus b, a.minus b, a.times b. The way that you can invoke a function in Kotlin is you use the dot operator, just like in Java. A.div b. A.rem is a.reminder b. There used to be a.mod b in Kotlin, but that's deprecated. You should use a.rem b. And then to check a range, a.range2b. Here's some more arithmetic operators. A plus equals b. This is where you're using the assignment operator in addition to I shouldn't say use the word addition. In also using an addition or a subtraction or a times. So a plus equal b is the same as saying a equals a plus b. A minus equals b is the same as saying a equals a minus b. A star equals b is the same as saying a equals a times b. You're doing the assignment and the arithmetic in one single operation. And then you have divide and modulus. And again, you see the same corresponding Kotlin methods, plus assign, minus assign, times assign, div assign, mod assign. Whatever you're comfortable doing, you can use either one. Equality and inequality operators. These are important. A equals b, a not equals b. Remember the exclamation point is not. This is translated to a question mark. A question mark is checking for null. A question mark dot equals b. And then we're using the Elvis operator here, question mark colon, which is saying if it's equal to null, then b is equal to null. And then you also see the triple equals. So this needs some explaining. Referential and equality. There's two types of equality in Kotlin. Referential equality and structural equality. Referential equality is when you're comparing references. A reference is a memory location. So a reference has an address. So if two separate references point to the exact same instance in memory, that's how things are equal. So to test whether two references point to the same instance, we use the equals 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 operator, the triple equals, or the not equals equals for negation. That's referential integrity, or referential equality. Two separate references point to the same instance in memory. Structural equality is when two objects are separate instances in memory but have the same value. So to get back to the referential equality, it's a little different in Java, right? When you do the dot equals or you do the equals equals, those are the two differences. Those are the ways that you can check for equality in Java. Dot equals will compare contents, values. That's the structural equality. Equals equals will compare references. That's the referential equality. But when you compare references in Java, you're checking if the same instance is there. So you can think of referential equality as using the equals equals in Java. You can think of structural equality as using the dot equals in Java. Referential equality is you're seeing if two references are pointing to the same object. Structural equality, you're seeing if two objects have the same values, same instances in memory. So to test whether two objects have the same value, use the equals equals or the not equals for negation. So again, just kind of think of Java with the dot equals and the equals equals. This comes into play when you're either comparing values or comparing objects. The equals equals operation is special. It's translated into a complex expression in Kotlin that screens for nulls. Again, Kotlin is type safety. So null equals equals null is always true, and x equals equals null for non-null x is always false, which makes sense. And it will not invoke the x dot equals. Comparison operators, you may want to compare data using less than, greater than, less than, greater than equal, less than equal. You can call the compare to method a.compare to b. This should be somewhat intuitive, except when you're comparing objects. If you're comparing objects, you have to override the equals method. In Kotlin, you can use the compare to have the compare to is going to use an overridden method in Kotlin, which is the compares method, or the equals method. The equals method. So it's going to implement the comparable interface. You're going to override the equals method, and you're going to determine how two objects are equal, less than, or greater than, right? Because how else would you compare two objects? You don't know if an object is less than or greater than one because who knows what the behavior is. Usually what you do is you compare two member variables, and if this member variable is greater than the other one, then you say the object is greater than the other object. So anyways, if you want to use the compare to method on objects or the a is greater than b on objects, not values, not variables, then you have to override the equals method and implement the comparable interface and also the compare to method. So to indicate a is less than b, you must return a negative integer. When b is greater than a, you must return a positive integer, and for equality, you return 0. And this is a Java thing. Implementing the comparable interface, overriding the compare to, and also then calling dot equals on it. So I said overriding the equals method. You don't actually override the equals method. You call the equals method. You override the compare method. So these are all the operators, the basic operators, I should say, in Kotlin. These should look very familiar, and then their corresponding methods. There really is not a lot different here than most languages. The only thing you have to kind of remember is the null safe and other things related to the referential equality versus the value equality. We're going to talk about other operators that have to do with null safety, but for now this should get you started on doing some mathematical arithmetic operations as well as some comparison operations or any logical comparisons, logical operators. Thank you. Hello and welcome. In this lecture, I want to talk about some of the other operators that we haven't discussed yet. We've talked about comparison operators, arithmetic operators, logical operators. There are a lot of operators we talked about. We've also going to talk about null operators. But there are a couple more that have to do with collections that I want to just give you a heads up on. We'll talk about some of these in more detail when we talk about collections. So we have the in operator. The in operator has the keyword in. It's a binary operator. You have left and right hand side assignments. It also has a function. We know the operators can get mapped to functions. So b dot contains a, not b dot contains a. The in operator can be used to check whether an element is in a collection or a range, and also to iterate over a collection. Collection classes are data structures that hold data. So if we want to find out if something is inside of a collection, an element, we can use this operator, or we can call the function. It's very useful. You'll use it a lot when you want to look for data in a collection. An example here would be we're creating some variables here, some read-only variables. We can use them on all the collection classes. So val ints equals array of 1, 2, 3, 4. We're creating an array, 4 elements named ints. We're creating a val a, and we're saying is 3 inside of ints. Does the ints array contain the value 3? And then we can also say ints.contains 3. We can use the not to say 5 is not in ints, and ints.contains 5. So it's going to return a Boolean value, true or false, based on whether or not that element is in that collection or not in that collection. The index operator. The index operator looks like you're accessing elements in an array. What you're really doing is you're calling get or setter methods on a class, a collection class usually too. So here are some of the examples of the expression and how they're translated. So reading an element uses the index operator is translated to a call of the get operator method. So instead of having to call get inside to access a member variable in your class, you can just put a bracket around it. If you want to write an element, that just becomes a call to set. The invoke operator, this is an expression where it has parentheses, and it also is translated to invoke function. Parentheses can also be used as operators by naming your function invoke. So if you have a class and you have a function called invoke, you can also access that function by using a parenthesis. So in this case, we just invoke the function directly on the instance. This makes a class itself look like a function, right? Because look how you're invoking it. You're saying a and then parentheses I. That looks like you're calling a function. But what you're really doing, if that's a class, you're saying a invoke, call a function on that class called invoke, and you're passing it I. So pretty neat. It's just really kind of turning a class into a function. We now have the range and the is operators. We talked about is previously, but first let's talk about range. When you see a dot dot, that's a concise way to call the range2 function. We're going to use ranges when we talk about loops, but range is exactly what it says. It's a number that starts at some point and ends at another point. So you can say 1 dot dot 10. That's going to enumerate all the numbers from 1 to 10. And then you have the is operator, which in Kotlin is the same as instance of in Java. You're checking whether a type is or a variable is part of a type. And so you can do the is check, and then you don't have to do a cast. We talked about the is check when we talked about casting. A smart cast is a concept where as long as you do the is, you don't have to do the casting in a subsequent call, as long as it doesn't change. So the is check, same as instance of, it checks whether a value has a specified type. And then you can also say not is with the exclamation point, and that will denote the negation of the check. Make sure that a specific variable or an object is not of a different type. And so the real benefit of all these operators and why we use them, it makes your code easier to read. It's a lot easier to read and a lot quicker to read when you're using these operators. So these are 4 operators. Some you'll use in collection classes, others you'll use for what I mentioned. We'll talk some more about these operators in specific use cases in collection classes and so forth when we talk about collections, as well as some example assignments that we go through. Thank you. Hello class and welcome. In this demonstration, I'd just like to show you quickly how you can use the in operator in a loop. I provided some examples previously, but I wanted to actually go through a code along real quickly. So this should look familiar. We have our main function. Remember, this is the entry point into the program. The main takes arguments. It's a name parameter with args, followed by the colon, and then we have the type. And that's an array of strings. This is the program arguments to the program itself, command line arguments. So what I'd like to do is I can use the for keyword, and from the for keyword I can iterate through what is in the array of args. I can do that by just specifying a identifier, a variable that represents an element in the array. So I could just name this something like args, and then I can use the in keyword, and then I have to specify the actual name of the array. So what I'd want to do here is probably say arg and then say args. And this will, for each iteration inside the loop, it will assign the variable arg the element inside the args array. So if I use the brackets, and I can just print out the actual argument by doing something like that. It's very simple, and what we can do is we can pass some arguments to the program to demonstrate how this works. So when we say run, we can say edit configurations, and we can add a couple arguments separated by spaces. Let's just say Jason Fedden is your teacher. That would be a total of 1, 2, 3, 4, 5 arguments. So now if we apply this and we try to run it, what we'll see is the actual each argument being printed out for each iteration. So let's go ahead and run it. And the output will show you each element inside the array, which is Jason Fedden is your teacher. So in is just a special operator that is used in for loops quite a bit. We could also do something like this if we didn't want to just specify the keyword in args. We could actually look at the indices. Another way of doing this is maybe creating for arg in, and we could say args.indices. Indices is part of the array itself, and if we say that, then when we print out something, we would have to print out args sub arg. And probably what we'd want to do is name this something more useful, like I for an index. And so here we're iterating through, we're going through the args.indices. Indices is a special property of an array, and then we have to index the array. So this looks more like Java type syntax. So if we run this again, we'll see the same output doing the same type of thing, just using the in operator a bit differently. So in is often used in collections when you want to iterate over collections, and also in the array. A quick example of how you can utilize this operator. Thank you. Hello and welcome. In this section I want to talk about nullability. We know that Kotlin has a super big advantage over Java in that it's a null safe language as much as it can be. And so we don't have to worry about null pointer exceptions. We don't have to worry about our programs crashing all the time because of this. In order to understand how this works in Kotlin, we have to understand things like nullable types and also how to check for null. So we're going to start it off by talking about nullable types. So one of the most common problems in many programming languages, including Java, is that of accessing a member of a null reference, resulting in a null pointer exception. They're a real big pain in the butt. So Kotlin, one of its goals was to get rid of this pain. It's very tedious. You have to check for null all over the place, and it's boilerplate code, and it makes coding not as fun. So Kotlin tried to tackle this problem, and the way that they solved it is they started adding stuff at compile time. So Kotlin's type system is aimed at eliminating the danger of null references from code. Your program is going to crash less in Kotlin because of this null safe language. So what Kotlin does is it converts these nullability problems from runtime errors into compile time errors. So the compiler can now detect many possible errors during compilation and reduce the possibility of having exceptions thrown at runtime. A big deal. And really, really cool if you think about it. You no longer have to sit there and worry, is my program going to crash because it's running and there might be null data. No, if you have null data and you're doing something wrong, the compiler is going to tell you before you can even run your program. So another reason why everyone loves Kotlin, because of this null safe language. The only possible cases of null in Kotlin is if you explicitly call null pointer exception, you throw it, you cause an exception, which makes sense. If you cause a null pointer, there's going to be a null pointer. If you use the not operator, and when we talk about using that, it will be more clear. But if you use that, you can cause a null pointer. And then any external Java code, right? Any Java code that you're using in your program, obviously that's still can have null pointer exceptions. So if you don't worry about these three issues in your program, you don't use the not operator, you don't throw an exception, then really all you have to worry about is the Java code. If you don't include any Java code, everything's written in Kotlin, your program's almost guaranteed not to crash because of a null pointer exception. So nullable. If a variable can be null, calling a method on it isn't safe because it can cause a null pointer exception. So Kotlin does not allow these calls. And by not allowing these calls, it prevents possible exceptions at runtime. So what I'm describing now is how Kotlin implements the null. There are certain things you have to do in the language, and certain things in the language that Kotlin will not allow, the compiler will not allow, because it's possible that null pointers could happen. And one of them being, you can't call a method on something that could be null. So if you don't expect a call to have a null variable, you declare the function in Kotlin as follows. Fun string length, we know it's a function because of the fun keyword. And then inside parentheses, we have the parameters. We remember that the types of the parameters are after the names, a little different. So the name of the parameter is s, colon is saying the type is string, and then we're saying equal to s.length. So we're declaring a function and the body is s.length. And when we declare the string s, we're saying that string cannot be null. So it's perfectly valid to say s.length. Because s, if it is null, it's not going to call s.length. You don't expect it to have a null value. So calling string length with an argument that may be null isn't allowed and will be flagged. The way that you know string length is called with an argument that may be null is because it will have a question mark, and we'll get to that in the next slide. But you may be asking yourself at this point, well, what do you mean may not be null? Well, Kotlin will specifically know at compile time whether things could be null by syntax, by a question mark. So if you say string length of null, you're going to get an error. Null cannot be a value on a null type string. So you can't call things that could be null, you can't call methods on them. You can't call that string length function with something that's null. And again, you'll know it's null because of how it's declared. The parameter is declared as type string, and in Kotlin this means it must always contain a string instance. And the compiler enforces that. So you can't pass an argument containing null to this function. You'll have a compiler error. And again, you're going to know if it's null by the syntax. So it guarantees that the string length function will never throw a null pointer exception, because the function is defined as not allowing any nulls. You can't have a null. And so you're going to know if you're trying to call that function with null because you're going to be passing in something that has a question mark with it, null. And that's where we get to this. So nullable types, how do you know what a nullable type is in Kotlin? Things that may be null. You know that because there's a type called nullable. Things that may be null are called a nullable type, and they're defined with the question mark. So if you want to allow the use of this function with all arguments, not just things that are not null, but also things that may be null, then you mark it explicitly by putting a question mark after the type name. So if we want to say that string length safe could be called with values that might be null, we say s:\string question mark. So now, if we pass that null, what we'll really have to do is we'll have to check for null before we call that. And there's operators in Kotlin that will check for null. But this function now can take things that may be null. They're still not going to take things that are null because you have to check for null, but they may be null. So it can take everything. If you don't have the question mark there, you're saying that this will never accept anything that can even have a chance of being null. So the question mark, when you see this operator, this question mark, it refers to as a nullable type, but a question mark is also going to be used for checking nulls. So you can put a question mark after any type to indicate that the values of this type can store null references. They can be a null type. To reiterate, a type without a question mark denotes that the variables of this type cannot store null references, and that was in this previous example, right? We had fun string length, s:\string, no question mark. That means you cannot pass it. Anything null will not be accepted or may be null. When you have the question mark, that means that it could be null. It means all regular types are non-null by default unless explicitly marked as nullable with a question mark. So once you have a value of a nullable type with a question mark, the set of operations you can perform on it is restricted. You can't call any methods on it. You can't assign it to a variable of a non-null type, and you can't pass it as a parameter to a function expecting a non-null argument. So at this point you might be saying, well, why would I ever mark something as nullable, as a nullable type? I can't do anything with it. Well, what you do is you check before you do it. So what can you do? The most important thing you want to do in order to be able to call these methods, in order to be able to assign a variable to a non-null type, is you compare it with null first. And when you compare it with null first, the compiler will remember that you did the comparison, and so it will automatically treat it as not being null, and it will allow you to do what you need to do. It will allow you to call methods on it. It will allow you to assign it to a variable of a non-null type. right? So you can define something as a nullable type by using the question mark, and then you can check it to make sure it's not null, so the compiler remembers that check, and then it allows you to do calling methods, so then it becomes useful. So the key here is, if you identify something as being null, make sure you check it. And so in order to check for null types in Kotlin, we're going to get to this in subsequent lectures because there's specific operators for this. But you can check for null in a number of ways. You can do safe checks with the safe call operator. This is a question dot. You can do an Elvis operator, which is the question colon. And the reason they call this the Elvis operator, just so you know, is because if you look at that sideways, it looks like Elvis's haircut, I guess. The not operator, you can use this also to check for null, and then safe cast as question mark. We talked about the as explicit cast. There's also an as question mark, which will cast something if it's making sure it's not null. So these are all null checks that you can perform. We're going to talk about these operators in detail: safe call operator, Elvis operator, the not null operator, and the safe cast operator. So let's just go through a couple examples in IntelliJ to show you how this null stuff works. So here I have my very popular main method, main function I should say. I keep saying method. Let's try to check some things for null. So if we put in the following code, we're just creating a function, string length safe, s colon string question mark. Oh, we see the question mark. So that function is saying, I will accept null types. But then inside the function, we're saying s.length. Are we allowed to call methods on things that may be null without checking them? No, we are not. So the compiler is not going to allow this. It's going to complain. So we're not going to be able to build this. We're going to try to build, and then the compiler is going to say, only safe or non-null assertion calls are allowed on this receiver type. You can't call a method on something that may be null. You have to check that before you call the method. That's one rule. So again, just to emphasize here, if we create another variable, val_x means it's not readable. We have the colon, so we know that whatever's after the colon, we're identifying the type. Here we're saying the type may be null, so we have the question mark. Now if we create another variable called y with a string type, but not a string that accepts nulls, just val y colon string, we can't assign that to x because x is of type string may be null. Y is of type string. So again, if we were trying to build this, we'd have a problem, type mismatch. And so what would happen in Java if you did this? There's no way to identify null, so you would have a runtime exception. It'd be perfectly valid at compile time to say y equals x, even though x may be null. In Kotlin, you cannot do this. Right? So if we create a function, we just have to check for null. This is what we want to follow. So here, I'm going to create a function called string safe. I know it's a function that can take a null value because I have the question mark in the parameter. It's going to return an int, and the function definition is if s is not equal to null, then you call the method, else 0. So this is perfectly fine. Now we can call a method on this that may be null. So we could even say create a variable called x that may be null, and then try to call that method, and we'll be able to do it. It will just return a different value. So we can say val_x string that may be null is equal to null. Perfectly fine to call stringless safe because it accepts a null. We know that from the question mark. And then if we say println string length safe, call it with null, it's going to go in and say s is equal to null, so it's going to return 0. So if I build this and run it, it's going to return 0 because we declared x as being null. Now if we change this, passed in a string literal ABC, it's going to return the length of the string, 3. And I did increase the font here. I'm not sure why it's smaller. But this is what you want to do. This is the mechanism you want to follow. If you have parameters that can take null, a null type, then you check for null. Otherwise, remember the other rules. Thank you. Hello and welcome. In the previous lecture, we talked about nullability. We talked about this great feature of the Kotlin language where at compile time, it will check for null, and so you won't have runtime exceptions. It's a big advantage. But there are restrictions, right? You have to, if you have something that may be null, you define it with a question mark. But if it's maybe null, you can't call methods, you can't do all sorts of things. So to enable to make something that may be null useful, you have to check for null. And it would really stink if you had to go in your Kotlin program all over the place and have all these if statements. Right? So there are some nice operators that allow you to check for null without having if statements. First one we're going to talk about is the save call operator. The save call operator is a question mark dot. It allows you to combine a null check and a method call into a single operation. So one of the things you can do if you have something that may be null on a type is you can't call a method unless you check for null. Well, wouldn't it be nice if there was a handy operator that automatically checked for null and all we had to do was type in 2 characters? Well, that's what this is. That's what the save call operator is. If you want to call something on a variable or an object that may be null, all you have to do is use the question dot on that method and then the method name. So s question mark dot to uppercase, it's calling a method on a variable that may be null because s was defined as a question mark. And normally you wouldn't be able to do that if you didn't have that question mark dot. Question mark dot to uppercase, it's the same thing as saying if s is not equal to null, call the method, else null. Again, Kotlin's about reducing duplication, reducing all boilerplate code. Stuff that you automatically have to do that you don't even think about. You have to do it because the language says so. How nice is this to just be able to say s question mark dot to uppercase? Pretty cool. If the value on which you're trying to call the method isn't null, the method call is executed normally. If it's null, the call is skipped and null is used as the value instead. Right? So it is equivalent to this if statement. It just does all of this if statement in one question mark dot. But if it is null, it will return null. It won't call the method. The save call operator calls methods only on non-null values. So it doesn't call s to uppercase. If s was null, it returns null. Again, just reiterating this point. Save calls can be used for accessing properties as well, not just for method calls. So if you have a class employee and your class employee has a val name string, has some member variables. So here we're defining class. We haven't talked about classes, but again, follow me here. We have a class employee and we have 2 member variables. We have a name and a manager as a member variable. Properties is what they call them in Kotlin. We're defining each property as a read-only value variable because we have val, and we're identifying name can be a string, manager can be an employee, but the employee can be null. Right? So in this case, if we just had this class definition, we wouldn't be able to call employee, or we wouldn't be able to say manager dot method name because we can't call a method on something that may be null. So if we say function manager name, it takes an employee may be null, and then we say string, it's going to return a string, maybe a null string. Then inside the body of the method, you say employee.manager, and you want to call a method on that property. You can do it if you use the save call operator, :dot. If you didn't have that, question mark dot. If you didn't have that question mark dot, you wouldn't be able to say employee.manager.name. Okay, so you can use the save call operator on properties as well as on normal variables that want to call something in they're a nullable type. So again, just to reiterate what this code is doing, because it may not be familiar with you, you're creating a class called employee. It has 2 properties. It has a name property and a manager property. Name is of type string, manager is of type employee, but employee may be null. You then have a method function called manager name that takes an employee, and remember, employee may be null. So you say the body of the method, the function returns a string that may be null. That's what the : string question mark is after the parameters to the function. We haven't talked about functions yet, but this is what the function is doing. A manager name function, a parameter of employee type, and it's returning a string that may be null. The function body is trying to access a method, employee, which is the parameter, dot manager. Manager is a member or a property of employee. And then it's saying dot name. It wouldn't be able to do that if it didn't have the question mark dot. So if we run this and we say val CEO, we create a new employee object and we pass in the boss and null. So employee would be null as a member variable, manager would be null. And then we say val developer equals employee Bob Smith CEO. So we created 2 variables here that are pointing to an object. And if we say println manager name on developer, or it's going to print the boss. If we say println manager name CEO, it's going to print out null. Because remember, it won't call employee.manager.name. Right? So CEO has an employee of the boss, and its manager is null. So it's checking if the employee manager is null, and if it is, it's not going to call the name method, the name property. It's not going to access the name property. It's going to return null, and that's what it does, returns null. So let's try some examples in IntelliJ. So we're here, we have our important function called main. We're going to create another function and then try to invoke the function. So print all caps. We have a function named print all caps. It takes a name parameter called s. It's of type string that may be null. And then we have a variable inside there, a local one called all caps that takes a string that may be null. That's equal to s question mark dot to uppercase. So it's going to call the to uppercase method on the variable passed in if it's not null. If it's null, it's going to return null, and all caps would be equal to null. So println all caps, if you pass in something that's null, it will return null, otherwise it will do it to uppercase. So if we try calling this method with something valid, like a string, something like that, and we run it, it's going to just uppercase A, B, and C. Right? And that's what we see. A, B, C. If we call this method with a null value, it's going to print out null, because it's doing that safe check. So the safe check operator is pretty good. It does a lot for you. So here it returns null. And so we can get into more examples. We saw that employee example of how it does a null check on a property. So we know how that works. We know we can use it for checking properties of a class, or we can check it on functions of parameters that want to call methods. When we talk about classes, we'll provide more examples. But since we haven't talked about classes yet, I don't want to throw you a big example with, a whole big class and an object. But this should give you a good idea of how you can use this safe operator. You don't have to do the manual if this is null, do this, else null. Very simple. Reduces a lot of code. Thank you. Hello and welcome. Let's talk about the Elvis operator. This is the question mark colon. Again, this is something we can use for checking for nulls. The Elvis operator, question colon, is an infix operator that provides default values instead of null. So an infix operator means that it has a left operand and a right operand. Infix means it's in the middle. And also the Elvis operator, the reason it's called this is because if you look at the question mark colon sideways, it kind of looks like Elvis Hair's haircut. But there are other names for this as well. It can also be, I think it's called the null coalescing operator, something like that. But whatever, name doesn't really matter. So here's what we would need to do in Java if we didn't have this Elvis operator in Kotlin. We'd have to have this string postcard equals null, if address equals null, postcard equals no postcard, else if address.get postcard equals null, postcard equals no postcard. Else postcard equals address.get postcard. See a lot of if statements here. If, else. These are conditional statements. This is where you're evaluating if something is true. If it is, you execute the body of the code. And here postcard is equal to null, and then we're saying address is equal to null. So let's just keep this in mind. We're doing all these checks. So the operator can be placed in between a nullable expression and an expression to use if the nullable expression is indeed null. So it's like saying, if this is equal to null, then do this. It's very similar to the ternary if statement in Java. In Java, in many languages, you have a condition, and then you use the question mark, and then if that's true, the thing to the right of the question mark will be executed, and then you have a colon, and if it's not true, the thing to the right of the colon will be executed. Anyways, it does look like that syntax. What you're doing again with the Elvis operator is you're saying, if this is null, do this. And so here's an example. We have a val, a read-only variable called nullable name. It's of type string, which can be null. It's a nullable type. And then we have val name, which is a string type, and the string is going to be equal to nullable name if nullable name is null, it's going to be equal to default name. So again, what this is doing, the question mark colon, the Elvis operator, it's saying if this is equal to null, then do this. So if nullable name is equal to null, then return default underscore name in quotes, a string. So it's a nice way to evaluate something if it's equal to null to do something. So the operator takes two values and its result is the first value if it isn't null, or the second value if the first one is null. Right, so there's two things here. Its result is the first value if it isn't null, which is nullable name, and if it's the second value if it is null. So what this is saying is, again, if nullable name is null, return default name. If it's not null, return nullable name. So that's why it kind of refers to, it looks like the ternary statement. So the right-hand side is an expression, so anything can be placed there that evaluates the value, such as when an expression or a function call. As a when expression, we haven't talked about whens. The Elvis operator is often used together with the save call operator to substitute a value other than null when the object on which the method called is null. So here is an example. We have val nullable address is of type address, which could be null, and then we're signing it to null. So it is actually equal to null. We have a type called address, which can be null, and it's set to null. We then have a postcard, which is a string, and it's going to be equal to nullable address dot postcard if nullable address is not null. It's only going to call that method if nullable address is not null. So we're using the save call operator, question mark dot here. And then after that, we're using the Elvis operator, the question mark colon. So if nullable address dot postcard is null, it's going to return a default postcard. If nullable address is not null, that means we can call access the property postcard and we'll return that. So we're doing two null checks here. First, we're checking if nullable address is null, and if it's not null, we'll access postcard. We're then saying if nullable address dot postcard is not null or is null, we return default postcard. See that? So we're using it in combination with a save call operator to both check whether two things are null. It's a good example of how this Elvis operator is used with a save call operator. So it's doing exactly the description here. It's the Elvis operator substituting a value other than null. We don't want the postcard to just be equal to null. So it's going to be equal to default postcard. And that happens when the object on which the method is called is null. So the object on which the method is called is null. Nullable address dot postcard. Because we're already doing the save call operator. So it's nullable address dot postcard. It can also be used with operations such as return and throw on the operator's right side, expression side. So if the value on the left side is null, the function will immediately return a value or throw an exception. This is helpful for checking preconditions in a function. So again, if we go back to our if statement here on our first page that's written in Java, postcard equals the null, we can essentially reduce this to 2 lines of code. In that late example here, we can do multiple checks. So we would, in string postcard is equal to null, and then if address is equal to null, this is where we would use our save call operator. Else, if it's not equal to null, we would get the postcard, right? And then we use the postcard to say if it is equal to null, this is where we use our Elvis operator, and we return no postcard. If it's not equal to null, it's going to get the postcard. So all of these lines of code, which is what, 1, 2, 3, 4, 5, 6, 7 lines of code, can be converted to these 2 lines of code. We're setting nullable address to null, and then we're saying if this nullable address is null, then we can't call postcard, and if that's null, we return default postcard. So hopefully that's clear there. Again, we're doing all of this in that one check. Address equals the null is the save call operator. Address dot postcard equals null is the Elvis operator. And then if that's not equal to null, it actually returns the postcard. So pretty cool. Again, very, very efficient. A lot less code there. Another example of Kotlin's strategy of being more concise and more efficient with less code. All right, let's bring up a nice example here in IntelliJ. Here we have a function called string_length_safe that takes a named parameter named s of type string that may be null, and it returns an int. The body of the method is saying if s is not equal to null, it's using the safe operator, dot, we're going to access the member variable of length. If it is null, we're going to use the else operator to return 0. So if we call this with null and build it, it'll return 0. And this is the most basic example of using the else operator in conjunction with the safe operator. Return 0. Now if you were to call this with some value, you would see the value is the length is returned. Right? So you can use the else operator with the safe operator in conjunction. This is how it is often used. You can also use it as properties in a class, which I showed you earlier. So again, a nice tool to have that minimizes your code in Kotlin to check for null. Thank you. Hello and welcome. In this lecture, I want to talk about safe casting. We talked about casting in previous lectures. In order to understand what a safe cast is, using this as ? Operator, you have to remember what casting is. So I just wanted to quickly refresh in your memory about casting. Casting is taking an object from one particular type and turning it into another object type. In Java, you can cast by using the parentheses and just specifying the class name for the object that you want to convert. Okay, under the hood, we're not really doing a conversion. We're just telling the compiler that we're going to use the object this way. But you can do this in Kotlin by using the as operator. So if you want to cast something of a reference to explicitly cast it, forcing the compiler to do it, you use the as operator. Just as in Java, this operation will throw a class cast exception if the cast cannot be performed legally. So if you do something incorrectly, you try to change the type to something that it can't be. So if you're using inheritance or something and you do a subclass that can't go to a parent class or whatever the case may be, you're trying to cast something that's invalid. What will happen at runtime is an exception will get thrown. We know that when you throw exceptions at runtime, it's a bad thing because your program crashes. And so you have to be careful when you're casting, especially when you do an explicit cast in Kotlin, because you still have a danger of a class cast exception happening when you use just the as operator. So for example, if you have a function called length and it has a named parameter called any that takes type any, returns an int, and you declare a read-only variable called string, and you say this string is going to be equal to any as string, you're casting the any parameter to a string using the as operator. And then you can call a method on that object, string.length. This is an explicit cast. You're specifically telling the compiler that you want to cast this data. Now, we learned earlier that when you do a cast normally, you do an instance of in Java. A traditional use case for doing a casting is you check the type. If it's an instance of the certain type, you cast it. We know there's a shortcut in Kotlin. You can use the is operator to check for the type, and then you don't have to do any kind of casting. Right? That's called a smart cast. So we're familiar with smart casting. We're also now familiar with explicit casting, which we talked about when we talked about smart casting, but now it's even more in your guys' brains. So an explicit cast can still be dangerous because of the class cast exception. In this case, the null value cannot be cast to a type that is not defined as nullable. Remember these nullable types? These types that were defined with a question mark? In this function called length, any is of type any. But there's no question mark there, so it's not a nullable type. So what that means is you can't cast it to a type that is not defined as nullable. So the above example is going to throw an exception if the value is null. If this function took a nullable type and then we tried to cast it, we wouldn't be able to cast it if it wasn't defined as nullable, if string wasn't defined as nullable. So to get around this, you would have to say val string question mark of type string nullable. You'd have to make string a nullable type, and then you could do the cast. Right, so you have to be careful here. If you have functions that take nullable types, and when you go to cast them, you have to make sure that you're casting to a nullable type as well. The safe operator This is as question mark, and again we see this question mark, so we know it has to be related to nullability. Here's an example of using as that would throw an exception because any is not a file. Right, so here we have an example. We have a variable called any. It's pointing to a string. That's the type of any, right? We know this because it's inferred. The type inference will, even though we didn't specify that any is of type string, it's going to be a type string because we have a little string here in quotes. We have a variable named string that's of type nullable string, and we're trying to cast it to a string, right? So that's okay, right? Because any is of type string, and we're casting string to something that may be null. But any is not may be null, so that's okay to do. So in the previous example, we had string, or we had any that may be null, and we were trying to cast that to something that's not null. In this case, we have something that may be null, and we're just trying to cast it to string, which isn't null, which is perfectly valid. So hopefully you see the difference here in the previous example. Casting something that may be null to you can't cast something that may be null to something that's not null. But you can cast something that may be null to something that's not null. Hopefully that made sense. So anyways, that second statement is perfectly valid. The third statement, where you're creating a variable called file of type file that may be null, and then you're casting any as a file, that's going to fail because any is not a file. Any is a string, right? And so you're doing something that's going to throw a class cast exception. And this is what I was talking about where you have those runtime exceptions. You're trying to cast something that you can't cast. A string is not a file, so you can't cast that to a string. And so in this case, you throw a class cast exception. It's very dangerous. To avoid this class cast exception and instead have a null value if the cast fails, you need to use the safe cast operator. This is the use case for as question mark. This operator tries to cast a value to the specified type and returns null if the value doesn't have the proper type. So file would just be a null type here. And that's why it's a good thing file has the question mark so we can assign it null. But what would happen here is if you said any as question mark file would be null because any is of type string. So let's look at another example. Here we have 3 variable declarations. We're creating a location variable. It's of type any and it's equal to a string, London. Perfectly fine because any is the top level object. We then have a safe string. It's of type string, which is nullable, and we cast location using a safe operator as question mark to a string. Perfectly fine because location is a string. Now we have a safe int, and int could be nullable, and we have location. We're trying to cast it to an int. Normally, if you didn't use the as question mark, this would throw a class cast exception because you cannot cast a string to an int, right? Because location is a string. So if you just had location as int, you would have a class cast exception thrown at runtime. By using the as question mark, it's not going to throw that class cast exception. It's just going to return null. So this is a use case. This is a scenario where you would want to use the safe operator as question mark to avoid the class cast exception getting thrown when you're trying to cast to something that is not okay to cast to. So let's try this example in IntelliJ. So here's IntelliJ. Here we have our example inside of our main. We don't need our string length safe. And we have 3 variables, and we're just going to use the as. We're not going to use the safe cast operator. We're just going to use the as. If we try to run this, we're going to get a class cast exception because we cannot cast we cannot cast a string to an int. And that's what we get. Class cast exception, Java lang string cannot be cast to an integer. If we add the question mark here just to the int, we'll be okay because now it's just going to return null. London is null. That's what it returns. So this is a way, again, an example of how you can see that it actually works. Another common pattern of using the safe cast is combining it with the Elvis operator. So it comes in handy when you have to implement the equals method. This example might not make complete sense because we haven't talked about classes yet, but I wanted to show it to you anyway, and you can review it later when you know what classes are. So here we're going to have a class And we're going to, I'll try to explain some of this code, but I just want to make sure the indentation is correct. Okay, so here we have a class called person. This is an object. We have a person that takes two variables, a first name and a last name. They're both of type string. We're overriding a function called equals. It's named O, and it's of type any that may be null. It returns a Boolean. The body of the method is creating a variable called other person. It's going to be equal to O as question mark person, and then we're using the Elvis operator here, right? So here is where we're using the safe cast with the Elvis operator. We're going to cast the parameter O in the equals method to a person as long as we're able to do that. We don't want to throw a class cast exception. If we do have a class cast exception, instead of returning null, we're going to return false. Right? So this line is key here. We're using the safe cast in conjunction with the Elvis operator so that we don't just return null, we return something valid. And here we're returning false. We're not able to cast whatever was passed into the equals method to a person. If we were able to cast successfully, then we just do our comparison. Pretty nice. And so this is how you can use the safe cast in combination with the Elvis operator for the overriding the equals method. And you'll see this quite a bit. So thanks for listening. This is the safe cast operator. Show you how you can use it as question mark so class cast exceptions are not thrown. Hello and welcome. Let's talk about another operator that's used for null safety. This is the not null assertion, the double exclamation point. The not null assertion is the simplest way for dealing with the value of a nullable type. It's represented by a double exclamation mark. It will convert any value to a non-null type. So remember, how do we create a value or variable to be nullable, to be a nullable type? We do the question mark. So we know all variables that can allow nulls because they have the question mark when they're declared. If we know that it's null type, we can now use this operator, the double exclamation point, to force the compiler to treat it as non-nullable. For null values, an exception will be thrown. So you really only want to do this if you know that the value is not null. So this is going to be used in situations when we want to dispense with the compiler's null checks and we want to force a nullable type into a non-nullable type. Right? So we have to be sure that this type that we're forcing into a non-nullable type is not null in the given situation. So there are some situations where this is useful. When you're dealing with Java code and you know the Java code is never going to be null, you need to use a variable with a function, right? So we can't call functions on variables that are not nullable types. We know that. And if we want to call a function on Java code that we know is never null, then we would want to use this operator. We want to force it to be not null. Now, if it is null in a case, it's going to throw an exception. So you have to be prepared to accept that. So you can also check for null in one function and use the value in another function. The compiler can't recognize that the value is safe, and you would force it in this way too. So in this situation, it's kind of like you're double checking for null. And you don't need to do that double check. You've already checked for null in one function, and you're passing that value to another function. You're going to have to check it again. The compiler doesn't know that it's safe, so you're going to end up checking again. So what you end up doing is you know it's not null, so you just pass it in as a non-nullable type. So the simplest way to use this operator is here we're creating a variable, a read-only variable called nullable name of type string that could be nullable. It's equal to George. We're going to assign that to a string that's never null because we don't have the question mark in the declaration. And the way that we do that is we just say nullable name, exclamation point, exclamation point. So when you see the exclamation point, you immediately know that you're converting this nullable type to a non-nullable type. A more useful example is when you want to call a method on something that you know is not null. So here, this method, this function takes a nullable type, and you want to call the length method on the string, but you can't because it could be null. So you either have to do a check for null using a safe operator, or you can do this. You can do a not null assertion on it. You can say, assign it to another string, make sure it's not null, and then call the method function on it. So again, what happens if s is null in this function? We already said that it's going to throw an exception at runtime, a special kind of null pointer exception. The exception is thrown in the assertion itself, not on the subsequent line where you're trying to use the value. So right when you try to assign that nullable type to be not nullable, that's where the exception will be thrown. So it's not when you try to use it. What you're really telling the compiler, this is what you're saying. I know the value isn't null, and I'm ready for an exception if it turns out I'm wrong. You're taking a risk, but you're really betting on that it's not null, so you don't have to do this other checking. You want to call a function, whatever it is. You may need to use this in some situations, specifically the ones I mentioned, but it is there. I wanted to make sure that if you saw the double exclamation point, you knew what it was. Thank you. Hello class, welcome to another exciting lecture. In this demonstration, I'd like to provide a code along that shows you some of the features of the null safety in the Kotlin language, a very important concept, right? This is all about the language not having null pointer exceptions in runtime, which is a very, very common error in a program like Java, program language like Java, where you have null pointer exceptions all the time. We can use this nullability types in these null operators to make sure we don't have these exceptions. So I want to create a little program here that's going to take some program arguments, integers, and it's going to take those. When you pass in program arguments to a program in Kotlin, they're strings. But if the string is inside quotes, is an integer, we can parse it and then do something with it. But I want to demonstrate nullability when I'm doing this. So we have our function main here, and the parameters for main take program arguments. They are an array of type strings. So we're going to first make sure that we have program arguments. So we're going to do a little validation. We're going to check the size of the array. Args is a string array. We're going to say args.size has to be greater than 2, otherwise we have an error. So if it's less than 2, we're going to print out an error saying that no numbers were supplied. Again, the whole purpose of this program is to just parse some integers that are inside strings. So no numbers are supplied. If they do provide some arguments, we're going to create a couple local variables and call a helper function. So here we're going to say else read-only variable x is equal to a helper function called parseInt, which is very similar to the integer.parseInt in Java. But this is going to be our own function. And we're going to pass in our strings that are our command line arguments. So arg sub 0, and then we'll say val y equals parseInt arg sub 1. And at this point, we're going to create our helper function. So let's add a top level function. And this will be called parseInt. And this is going to take one string. We'll have a named parameter here. It's going to be of type string. And it's going to return an integer. So we say return, right? So this should, for functions, we have the fun keyword, we have the name of the function, and then we're using named parameters where we have a string, colon, and then followed by the type. We can return data from a function using a colon and then an int. And we're going to talk about functions in a lot more detail. That's how you can create a function. We're also going to use a try catch here, which you don't need to worry about now, but this will make sure that the code doesn't crash at runtime if it's some kind of problem. And what we're going to do is we're going to convert that string to an int. So we can use a string function to do that. We're going to return it from the function. We're just going to say return stir, which is the parameter passed in, and say toInt. This is a conversion function that converts a string to an int. If we're unable to convert that string for some reason, we're going to catch an exception, which is just going to be a number format exception. Again, this may not make complete sense, but it's a way to just write complete code with try catch. And if we do have an exception, all we're going to do is print out an error. Say print line, one of the arguments cannot be converted to an int. Something like that. Otherwise, we're going to return null. If we return null from a function, that means our return type has to be able to be null. So we forgot something when we said we were going to return an int. We have to put the question mark, because the question mark says that that type can be a null. And in the case where we have an error, we are going to return a null. Okay, so remember that question mark specifies a variable may be null. Now if we go back to our main function, after we've created x and y, and we call the function, remember x and y can be null. All right, because parse int may return null. So what that means is we can't just start using null. All right, we want to be able to start multiplying ints. We want to be able to do something like this. If we try to do this, the compiler is going to complain because x and y may be null. And it gives us some operator errors, but it's really complaining because x and y may be null. And the language doesn't allow for nulls. So we have to check to make sure these aren't null if we're going to use them. The easiest way to check is to just use an if statement and saying if x is not equal to null and y is not equal to null. Then we can actually try to perform an operation on it. And if they are equal to null, we'll just do something else. We'll print out one of the arguments is null, something like that. And so now if we build this, we should be good to go because we checked for null. And so when we get to either line 26 or when we try to use x and y in line 26, there's no way that x or y could be null at this point. So there's no possibility for a null pointer exception. So now when we build this, we are able to build it. It's fine. We want to make sure we pass arguments to this code. So we can pass arguments to the code by going to run, edit configurations, and passing 2 arguments in the program arguments. We'll pass in 7 space 9. That's 2 arguments. Say apply, say OK, and let's run this. When we run this, you'll see that we were able to multiply 9 times 7. So that's nice. Now we can also use the Elvis operator to make sure that we aren't null and that we can perform an operation on the integers. Remember, the Elvis operator gets executed if something is null. So instead of using the if statement, we could do something like x and then use the Elvis operator, which is question mark colon. And we could say if x is null, then just return from the function, return from the main method. And then we'd also have to check y. And we could say y colon return. And then we could print on this line because, again, we're guaranteed to never get to line 28 with those being null because we use the Elvis operator. So we could run this and we could do it this way as well. The problem with this way, there's no else statement, but we were able to run. There's no else statement, so you can't tell the user that it was null. So the other way might have been nicer, but this is the Elvis operator. The other thing I want to show you is without using strings, but we can also use the safe call operator, not null assertions as well. So if we didn't have integers here, and instead, let's just create a string. We can create a string called JSON, and we can give it type. We'll give it a type of, it could be a null string. So if we say something like val JSON and say string with the question mark, we're saying this string may be null. But we'll initialize it with JSON. Now, if we were to try to call a method on this string, something like println JSON.to uppercase, we tried to compile this, this is not going to compile. This is going to say we either have to use the safe call operator or we have to use a not null assertion, which we can do because, again, on line 23, we're not guaranteed that JSON may be null because we have this here, even though we initialized JSON. So we could do a colon dot, and now we could run it, and this would print out to uppercase. The colon dot, the question mark doc, sorry, this is saying that this is only going to call to uppercase if JSON is not null. We could also use a not null assertion here if we wanted. Something like that. And that's also saying that JSON cannot be null. And so here if we run it, we'll get the same output. except it's expressing we forgot the dot. And now we run it, and we see the same thing. So this null safety in Kotlin is pretty cool because you're never going to have null pointer exceptions. The compiler is going to check it at compile time and tell you if it's a possibility to be null, and it won't let you compile. So you can use these not null assertions. You can use these safe call operators. You can use the Elvis operator, or you can just check for null explicitly by looking for null. But Kotlin's going to protect against all these null pointers. Thank you. Hello class, welcome to another lecture. In this lecture we want to talk about control flow. This is a common concept in programming. Two essential things that you're going to need to understand are repeating code and asking questions in code, conditional statements. So the statements inside your source files are generally executed from the top to the bottom in the order that they appear. Right? If you see source code, it's sequential. First statement is executed, the next statement, and so on. This is a structured programming. Control flow statements, however, break up the flow of execution by employing decision making, which is if statements, looping, repeating code, for loops and while loops, and branching. Branching is like continue and break statements inside of a loop. They enable your program to conditionally execute particular blocks of code. So it kind of takes away from this structured approach where you have sequential. Everything is sequential. You're not necessarily sequential when you're doing decision-making statements or looping statements with branching statements. So decision-making statements, those are if statements. You ask a question. If the answer is true, you do something. If it's not true, you do something else. Also, there's switch statements in part of that as well. But the switch statement isn't supported in Kotlin. Instead of the switch statement, we have a when statement in Kotlin, which we'll talk about. Looping statements repeat code. Kotlin has the for, while, and do while. Branching statements break and continue in most languages. Return. In Kotlin, there's just return and jump with labels that also have break and continue. So to understand decision making, which is conditional statements, structures require that the programmer specify one or more conditions to be evaluated or tested by the program. You constantly have to do certain logic based on maybe if the user entered some certain data, you may want to do something. And if they didn't enter the data, you want to do something else. Part of programming is doing this conditional logic. So if a condition is true, then a statement or statements are executed. This is the body of the if statement. If a condition is false, then the other statements are executed. This would be like an else statement. So here's just a little data flow diagram. It kind of tries to describe this to you in a visual manner. Your program is this little black dot starts. There's a condition, which usually is represented by an if statement. If that condition is true, you execute some code. If the condition is false, you don't execute the code in the true block. You execute other code, or you just move on, depending if you have an else or not. And this is a basic structure of programming, these conditional statements. And we're going to describe how you can implement this in another lecture when we talk about if statements. Here's a nice table that kind of describes the different types of conditional statements you can have. I mentioned you have an if statement. If is very intuitive. You're saying if something is true, do something. You can have the if statement by itself. And if the statement it's a Boolean expression is something that evaluates the true or false. If that statement in the Boolean expression is true, then you execute some statements. A more complex if statement would be if then else. An if then else statement does something if something is true, but also if it's not true, it does something. Now you may ask yourself, well, why not just have an if statement and then have the other one execute? That's not the same, right? In an if statement, if it's true, it executes that, and then if you have something immediately after that, it still executes that regardless. There are times when you only want to execute something if a statement is false. And that's what the if-else statement does. And again, we'll provide examples of this when we get to concrete Kotlin code. Nested if statements is another type of conditional statement, except you have an if inside of an if. So you may say, if the sky is blue, and if the temperature is 85, and if it's sunny, then it's a great day. Nested if statements ask multiple questions. So you can use if or else if statements inside another for nested if statements. So it can get more complex, but overall this concept is not too difficult to follow. And it's standard as part of every programming language. Repeating code. There may be a situation when you need to execute a block of code several number of times, many times over and over. You would not want to just duplicate the same line of code over and over and over. That would be really bad. So you can do something called a loop. The statements are executed sequentially. The first statement in a function is executed first, followed by the second, and so on and so on and so on. So what this is describing is the body of the loop. You have a loop that goes for some time, for a condition. Inside the body of the loop, you execute the first statement, then the second one, then the third one. And then when you go back up at the top of the loop, you do it all over again. A loop statement allows us to execute a statement or a group of statements multiple times. Repeating code. Loop control statements change execution from its normal sequence. So this is another part of a loop where normally a loop you're going to execute 10 times, 20 times, or depending on some condition. There's different types of loops. There's enumeration controlled loops and there's counter controlled loops. Counter controlled loops are loops that run a specified amount of time, 10 times. An enumeration controlled loop is a loop that runs on a condition. So maybe you have a loop that says, I'm going to get input from the user. I'm going to keep reading stuff from the user until they enter the exit. So it could be 5 times it runs, it could be 100 times. You don't know. So in any kind of loop, when you have enumeration controlled or counter controlled, you never jump out of that for an unknown reason. So when execution leaves a scope, all the objects that are created in that scope are destroyed. This is referred to as like a break and a continue. It's when you're jumping out of a loop when it's not expected, based on another condition outside of the loop. So inside the body of the loop, maybe you said jump out if the answer is yes, something. We'll provide examples of this as well. There's also the concept of an infinite loop. This is a loop where you never exit. The condition inside the loop or at the top of the loop never is false, so you never exit, and typically you'll implement this using a for loop. You really should not have an infinite loop in your program unless you're monitoring or listening to another process or another application. If you have a for loop, an infinite loop, your program will never respond to anything else, so it could hang. Here's a data flow diagram of a loop. Again, you just have this condition and it executes over and over and over. If the condition is true, the block of the code executes. If it's false, it jumps out of the loop. You no longer execute that repeated code. Some of the loops that are in Kotlin, in most programming languages, you have a while loop. So this is the while keyword. And luckily, the loops and the if conditions in Kotlin aren't really changed much from Java. They're pretty much the same. The only one different is the for loop. There's really not a for loop in Kotlin. The for loop really just uses the in operator and also can use ranges. But anyways, back to loops. Loops, you have the while loop. This repeats a statement or a group of statements while a given condition is true. It tests a condition before executing the loop body. With the while, the for, and the do while, they can all accomplish the same things. You just may use them in different situations. But you could substitute a for with a while and vice versa. The for loop, it executes a sequence of statements multiple times and abbreviates the code that manages the loop variable. Typically, a for loop will have 3 control variables inside the for loop at the top. It will initialize the loop control variable. It will check a condition to jump out of the loop, and then it will increment the loop control variable or change the loop control variable for an exit condition. The do while loop is referred to as a post-test loop. It's always guaranteed to execute at least one time because the condition that gets checked to exit the loop is at the bottom of the loop. So you'll use the do while if you want to execute at least one time. And Kotlin supports this loop. And then with all these concepts of loops, you can also have nested loops. And this again is just like a nested if statement. You have a loop inside of a loop. So if you want to iterate through a data set and then inside that data set you want to search or you want to go through another data set, you have nested loops. And so nested loops complicate the matter, but again, they're pretty intuitive. You're just repeating more code. You just may be repeating multiple sets of code, multiple data structures. Kotlin control flow. Kotlin is a little different than most languages. Kotlin has expressions. And so an expression is a statement that evaluates to a value. That's what an expression is. So in this example, there's an example here that says hello dot starts with H. That evaluates to true. So that's an expression. A statement, on the other hand, has no resulting value returned. So an assignment operator or an assignment statement would be an example of that, saying val a equals 1. That's a statement, right? You're just assigning a value to a variable, but nothing gets evaluated, nothing returns. So that's the difference between an expression and a statement. It's important in understanding these concepts when you're talking about control flow in Kotlin, because in Java, the control flow blocks, the if statements, those are statements, and that's why they call them if statements. They don't evaluate to a value. In Kotlin, this is different. In Kotlin, the if and else flow control blocks are expressions. They can return values. So what this means is the result can be directly assigned to a value, returned from a function, or passed in as an argument to another function. And mainly because we have lambdas. We can take small segments of code and pass those blocks of code to functions and so forth. So they have to return data. And so this is a big deal in Kotlin. It's a big difference, I should say, as well. And the reason they do this in Kotlin is because it can reduce boilerplate code. And that's one of the big things that Kotlin is trying to go after. Java, you end up doing a lot of repetition, a lot of nuanced code that you just have to write just for the sake of the language. And it gets boring. Kotlin wants to avoid that. So by returning expression, having the if blocks return as expressions, you can reduce this boilerplate code. It also makes it a lot more readable, and the use of mutable variables is avoided. And remember, we don't want to use mutable variables. We want to try to use immutable variables as much as possible because of the advantages with functional languages. Less state changes, less side effects, easier to maintain. So the typical use case of declaring a variable outside of an if statement and then initializing it inside of it can be completely avoided. And you can avoid that because you're returning expressions. Just wanted to provide a quick overview of these common control flow concepts in all programming languages. We're going to dive into the exact syntax and provide demonstrations of what Kotlin provides. Mainly the if-else statements. There's a when construct as well that's similar that we're going to talk about for control flow, which is really the switch statement. And then we also have our looping, which are do whiles and are whiles, and then not really a for loop, but there is some for syntax. So stay tuned, and this will become even more clear. Thank you. Hello and welcome. Let's talk about Kotlin if statements. We know that if statements are a conditional control flow type deal in programming. You're asking a question, and if the answer is true, you do something. If the answer is false, you do something else if you have an else statement. So the traditional if statement, if it is an expression, returns a value. So, okay, this is what we talked about earlier. It's not a statement, it's an expression. Expressions return values. So an if statement really isn't an if statement, it's an if expression. It should be called an if expression. So the traditional usage of an if statement would be something like this. You would have a variable. In this case, we're creating a variable that can be mutable. It can change. That's why it's defined as var. We say var max equals a. Then we have our if statement. You'll notice the syntax looks pretty much the same as Java. You have the if keyword, you have a left parentheses, and then you have a condition in between the left and right parentheses. The right parentheses ends the condition. Anything in between those parentheses has to evaluate to true or false, a Boolean expression. So if a is less than b, that's true, then you execute the next line. Now here is an if statement that does optional brackets. So the curly brackets are optional if there's only one expression in an if branch. So if you have, and it's really the branch, or it's called the body of the if statement, if you have multiple statements inside the body of an if, you use the left bracket and the right bracket to end the block, just like you do a function, just like you do a loop, everything. So if a is less than b, the condition inside the parentheses, we only have one expression here, max equals b, so we don't have to have the brackets. So what this will do is it will assign max the value of b if a is less than b is greater than a. Another example here is an if statement with an else statement. So in the previous example, you just had if this is true, do this. You didn't have any case if it was false. So that's what an else is. An else will say if something is true, do this, else do something else. And this example here is using the brackets. Even though we only have one statement inside the body, we're using the brackets. The brackeners are optional with one statement. They're required with many expressions or statements inside the body. So here we're saying again, if keyword, a is greater than b, inside parentheses the condition, bracket starts the body, max equals a, ending bracket ends that if statement. Then you can have an optional else, use the else keyword, left bracket, max equals b, and then the right bracket ends the else statement. So this is the concept of an if-else. If something is true, do something. If something is false, do something else. You should notice that the code is not sequential. You're not executing all that code. In some cases, you're executing the max equals A. In other cases, you're executing the max equals B. If as an expression, so in those previous examples, we just showed you how you did some code if it was true or false, but we didn't return a value from the if statement. To return a value from the if statement, you would have a block. So if branches can be blocks and the last expression is the value of a block, then the last expression is returned as a result. So you can return data from an if statement if you have a branch, a block in a branch. So as an expression, you could do something like this. Val max equals if A is greater than B, you're going to return A, else you're going to return B. Here is your returning data from an if statement, and that's what makes if an expression and not a statement. I'm sorry if I keep using the word if statement. I'm just a bad habit. It's really if expression. Here's another example of returning something, and this probably looks a little different if you're familiar with Java. You have val max equals if A is greater than B, print A, and then return A. If otherwise, print B and return B. So you see how this makes it an expression, and in Java you wouldn't be able to do this because Java is a statement. Right? You should also notice that you're assigning something from an if statement to a value. You can do that because it's an expression, because the if statement is returning a value. So it's pretty nifty. You can do all, and it's quicker. It's more efficient. You can write more code quickly. So if you're using if as an expression rather than a statement, for example, returning its value or assigning it to a variable, the expression is required to have an else branch. Right? You have to have an else branch if you're returning something from an if statement. In the previous example, even though if is an expression, you weren't returning anything. You were just printing something or assigning something. In this case, you're returning something, and when you return something, you have to have an else branch. So otherwise, the compiler will not know what to do if the if did not evaluate to true. So if you didn't have the else branch, the compiler will display a compile time error. So you have to have the else branch when you're returning something from an if statement. No ternary statement in Kotlin. Ternary statement in Java is a one-line if-else statement. Usually you'll use something like you'll have the if condition without the if keyword, and then you'll have a question mark. If it's true, anything after the question mark will be if it's true, and then a colon, anything after the colon will be false. It's a way to write a quick if statement in Java in one line. It's not necessary in Kotlin. So unlike Java, there's no ternary statement because the if already returns a value with an expression. So in Java, you might have something like A is greater than B, question mark A, colon B. And what this is saying is if A is greater than B, return A, otherwise return B. In Kotlin, you don't need that. You would just say if A is greater than B, A else B. So no ternary statement required in Kotlin. Nested if-else statements, this is where you have an if statement inside of an if statement. It means that you can have one if or else if statement inside another if or else statement. You could also just have a nested if statement, one if inside of another if. It doesn't have to be nested if else. And again, if you just have an if statement, it's just if this is true, do that. Nothing for false. So you could have nested if else statements. You could have nested if statements. Here's an example of the semantics here, the syntax. If Boolean expression 1, something that evaluates true or false, a bracket, and then an if inside of another if. So this is an example of a nested if. An else, nested else, would just say if, else, if, and then an if statement and else statement, both of it. It's just missing the else. It's the same concept, same idea. Let's bring up IntelliJ and go through some examples. So first, let's just try a traditional if statement and print out the result. So in our main function here, our entry point to the program, if we say A is less than B, max equals B. Well, we didn't create any values, so let's just create some values. We'll say val A equals 5, val B equals 6, and then we'll just say val max equals 0 as an initializer. And so we say if A is less than B, max equals B. Well, let's print out max. And so what this is going to print out, you can probably guess, this is pretty basic. It's going to print out if A is less than B, and remember we can't use vals, we have to have var for our max, so that's a good catch by the compiler. I got into a habit there. Remember, vals are read-only variables. Var you can modify, and max is being modified after it's initialized to 0. It's being modified to b in some cases. So now if we run this, if a is less than b, and a is 5, and it is less than 6, then max is going to be 6. And that's what you see printed out right here, 6. So that's the basics of a very simple if statement. Let's try another one with an else statement. And remember, we could also declare these variables with types. What was happening here is type inference was going on, and because it was a 5, it automatically had the type of a as an int. So we could do, if we want to declare a variable as an int, we can just do a colon after it, right? So we could say a colon int, and that will create 5 as an int. But let's get back to our else statement. And the else is pretty basic. It just executes if something's false. Here we're going to say if a is greater than b, max equals a, else max equals b. Let's change our variables here a little. Let's change a to be 8. And now max should be 8. So when we run this, we didn't print anything out, so let's make sure we print out our result. And when we run this, it says 8, right? Because a is greater than b, so max equals a. Now if a is less than b, we would print out 6. The else gets executed when that condition right here is false. So now it's 6. So that's an example of a simple else statement. We can also do it as an expression, multiple ways. Let's try doing something similar that we did in the slides. So here we're saying value max is equal to a constant. Val max equals, if a is greater than b, it's going to be equal to a else b. And we're going to print out len max. We'll do another example after. And so let's run this. And we see that it's equal to 6. Now if we do another example, again, we're using an expression, so it's returning data. Val max is going to be equal to a. If a is greater than b, it's also going to print out choose a. So we can actually just see what prints out, and we'll know what part of the block was executed, the if or the else. So here it says choose b, and then it prints out 6 because I have this down here, which I forgot to get rid of. So again, if we change this and a was greater than b, it would say choose a. So I think you're getting the hang of this. It's pretty straightforward. I can get more complicated with nested ifs, but it's pretty there. You can also have an example with an else if, which I can show you. Here's an example of a nested else if. We have val string equals hello, and if the string.length is equal to 0, we print out the string is empty. Else, if the string.length is greater than 5, we print out the string is short. Else, if the string length is neither 0 nor greater than 5, we print out the string is long. So you see, this is not an expression because it's not returning anything, but let's run this. And what we see here is the string is short. So it ended up getting the else if. So if it's greater, let's make it 3. Let's make string length equal to something like 3. So let's change it to that. And then we'll see the else block get executed. So we see the string is long, the else block gets executed. So again, pretty basic stuff, but if you're new to programming, maybe a little more complex. But this demonstrates the if statement, the conditional statement, asking questions, and also demonstrates how you can return values from an if statement. Thank you. Hello and welcome. Let's talk about the when construct. As we mentioned previously, the when construct is similar to the switch statement in Java. The switch statement in Java is sort of like a comparison. It uses a switch keyword, and you evaluate some kind of variable or some constant, and if that variable or constant satisfies some case statement, you execute the code inside the case statement. The when construct does something similar to that, except you don't use case statements, you don't use select as the keywords. You use the when keyword, and you use branches. So the when construct can be thought of as a replacement for the switch statement in switch construct in Java. except it's much more powerful and you use it a lot more than you would use a switch statement in Java. The switch statement in Java actually isn't used a lot because you can use the if statements. There's no real reason to use it other than efficiency. It sometimes is more efficient and it's a little bit cleaner. But you don't need to use it. In the when construct, you prefer to use it, and you would need to use it in a lot of cases because the if can't handle things. So it's very powerful. It's used a lot more often in Kotlin than any switch statement in Java or any other language. There are two forms of the when construct. One of the forms is when accepts an argument. One of them is when it doesn't accept an argument. I'm first going to tell you about all the details when it doesn't accept an argument. And also, let's remember this concept of expressions versus statements. An expression returns a value. A statement doesn't return anything. You can use a when construct as a statement or as an expression. And when you use it as a statement, it doesn't return anything. When you use it as an expression, it does. So for the when that accepts an argument, what it does is it matches its argument and gets all the branches. And remember, the branches are the same as the case statements in other languages. It's what's evaluated. It's kind of like the conditions. So when the argument matches the branches, it will go through each branch sequentially until a branch is matched. And this is where you're looking at it similar to a traditional switch statement. The value of the satisfied branch becomes the value of the overall expression if you're returning it. And you're using when as an expression. So remember, you can have blocks of code return data in Kotlin, referred to as lambdas. So the when used an expression, can return data, and that can be a block of code. When could be a block of code. So when can have blocks as branches, just like the if statement. The last expression in the block is the result, and that is what is returned when is used as an expression. You have to remember those two rules. You may have multiple expressions inside the block of a branch, and the last block is the one that's returned. You can also write a function with an expression body returning the when expression directly. So you could have a function and all it contains is a when, and you can return that when. You can only do that because when is an expression in that case. When returns a value. So it makes the when a lot more useful because it can be used as an expression. You can return data. And because now you have lambdas, you can just return when blocks that equal some data. So when you pass when with an argument, the else, the same as default in Java switch branch, is evaluated and none of the other branch conditions are satisfied. So the else is not required. The else is only required if you're using when as an expression. And again, remember, when can be used as a statement or an expression. If it's used as an expression, it's returning data. It's most likely inside of a block and used as a lambda. Now, when you use it as an expression, the else block is required. You have to, because it's returning data, and if none of the branch conditions are evaluated, you're not going to return anything, and the compiler doesn't know what to return. Right? So you can have an else clause, which is just like the default. It's a catch-all. If none of the branches match, it will match the else. And so this is how you can use it in an expression, because the else is always going to be caught. So again, if when is used as an expression, the else branch is mandatory, because you have to return something. Otherwise, the compiler doesn't know what to return, because it doesn't know if all cases are covered. It's common to remove the else when you're using a seal class or an enum when you're not using it as an expression. If you're using it as an expression, you have to return something. And remember that else is access default in a regular switch. The when expression isn't restricted to checking values for equality. So if you're thinking of a switch statement where you just evaluate equality, the when does more than that. The when can use a different form of a branch, allowing you to check the type of the when argument value, SmartCast. So what this means is you can use the is operator as a branch. We'll give an example of this using the is, but it's nice to be able to check types as just checking for equality. Now, when you use the when construct with no argument, remember this is the second form, you can use it with an argument or no argument. It can be used as a replacement for a series of if-else conditions. So the use case to use this with no argument is if you have a lot of if-else. It's much easier to use the when. So if no argument is supplied for the when expression, the branch condition is any Boolean expression. What this means is the branch condition, again the case, has to be true or false. That's the only thing you can evaluate, a Boolean expression. And when that is either true or false, you execute some code. Well, when it's true, you execute the code. When it's false, it goes on to the next branch. You're not required to have the else with no argument if you're not using it as an expression. It's optional. But again, if you're using an expression, it's returning data, you have to have the else. The else has to do with expressions. With statements, it's optional. You do not need to write break statements in each branch. So again, another common characteristic of most languages that use a switch, which is similar to the when, is for each condition, each case statement, you need a break in order to jump out of the case. And that will ensure that no other case statements get executed. So you could have 5 case statements, and if you didn't do a break, all 5 branches, case statements would be executed, all the code inside there. And this often caused a bug in code because you meant to put a break in there, but you forgot. So now you have 2 matching things. Well, in Kotlin, you don't have to have a break statement because you only have one match and only one match. So if the match is successful, no other branches are executed. So this is helpful. So unlike the switch in Java, which requires you to use constants, again, another big advantage of the when, you can use objects, any objects. So in Java, you can only use constants, enum, strings, or number literals inside the when argument. Well, you don't have to worry about that for Kotlin. You can use any object. Again, all these examples are demonstrating why you use when a lot in Kotlin, because it can do so much. It's there for a reason. The switch statement tends to be in other languages, and you don't even use it. But not in Kotlin. You'll use it, all these big advantages, passing arguments, not passing arguments, returning, when it's used as an expression, returning data, so you can use it as a block of code like a Lambda. Super awesome. And you also don't need to put in break statements. All these things should be very clear that this is a pretty cool thing to use. So when you use it just as a constant value, which is one of the most often cases of using it, it looks something like this. You have here in this example, we have a variable named greeting, which is read-only. And then we using it as an expression, when, because we have the equals. So it means wins has to return something. When we have when, we use the when keyword, and then inside the parentheses, that's what we're evaluating. Whether it be a variable, an object, whatever it is. We have the left bracket to start the when construct, and the right bracket at the end ends it. Each of the things on the left-hand side of the dash greater than symbol are the branches. The things on the right-hand side is the code that gets executed for a branch, and that can be a block of code. The last block is what you would return in a when. So in this example, you have branches for English and German, and you have a branch for else. Else is the catch-all, similar to the default. So if x is equal to English, it's going to return how are you string. If x is equal to German, it's going to return a German string. And then the catch-all else, anything else, it's going to say I don't know the language yet. And the else is required because we're using the when as an expression here. We're returning something and assigning it to a variable. And then we would print out the greeting, and it would display whatever x is equal to, English, German, or I don't know the language yet. Note that, again, when must be exhaustive when you're using it as an expression. The compiler is going to enforce that the final branch is an else. You can also add commas. So when your branch code is duplicate or is doing the same thing as other branches, don't have that duplication. Use commas. So constants can be combined together if the branch code is the same. You just use a comma. So very simple. Here's a function called is0 or 1. It takes x as a parameter that's of type int, and it returns a Boolean. It's returning a when expression, so we have to have the else. We're evaluating x, but we have a comma in one of our branches. We have 0, 1, because either one of those is going to return true. So if x is equal to 0, 1, it will return true, this function. If it's equal to anything else, it will return false. Pretty nifty. You can use arbitrary expressions inside the when construct, not just constants as your branch condition. So here's an example where we have an expression, parse int s, and what that will do is it will utilize x and call the parse int. So we'll say x.parseInt s, and if that's able to happen, if it evaluates to true, it will return print s encodes x. And so in this case, we don't actually need the else because we're not using when as an expression. It's just a statement. But we include it anyways because it's usually good practice in case one of the branches doesn't meet the criteria, you have something that does happen. But you see the most important thing here is the parseInt method function. We're calling x.parseInt there. So anything on the branch uses x, the argument passed in. You also tend to use the in operator quite a bit when you use the when construct. Remember, the in operator is used when you want to find something in a collection or a data set. You can easily use the in operator. You'll use the in operator a lot with a for loop as well. So you can check for a value belonging in or not in a range or a collection. We haven't talked about ranges, but ranges are represented by the dot dot notation. You can look at something in a range or collection. So here's an example. We're evaluating x, so we're using when, passing in an argument. It's a statement though because we're not assigning it to anything and not using it as a block. So we don't need that else clause, but again, it's good practice to have it. We're saying if x is in, you see this in keyword. In is just saying, does it contain? Is it inside that? And then 1.10 is a range. So that first branch is saying, if x is in 1 to 10, print out x is in the range. So if x was assigned to 5, the value 5, before we called the when, it would print out is x is in the range. Our next branch is in valid numbers. It's looking at a variable called valid numbers. So valid numbers would be equal to something. If in was inside there, it would print x as valid. And then we're also saying not in 10 to 20, using a not in operator with a range. So if x is 5, it's not in 10 to 20, it would print x as outside the range. And if none of those branches get evaluated, it's going to go to the else, and it's going to print none of the above. You can use when with a smart cast. If you remember from previous lectures, a smart cast is used with the is operator. The is operator is the same thing as an instance of in Java. It checks whether or not a type is part of, or what a variable or an object is of a particular type. Often you use it when you want to cast. Now with a smart cast, you don't have to explicitly do a cast. It will automatically cast it for you just depending on what your last is was. So you can also use this in a when. You can do something like this. You can have a function, starts with foo, takes a parameter any of type any, and returns a boolean. And we're using when as an expression here, so we have to have the else. When takes a variable named any, the parameter that's passed in. And what this is saying is if any is of type string, we know that because one of the branches says is string. If any is a string, then call the starts with foo on it. And if it starts with foo, it will return true or false. Otherwise, it returns false. So if we called this function and we passed in foo fighters, it would say foo fighters is a string. It would cast any to a string because it does a smart cast. And then it would call starts with on any. And foo fighters does start with foo, so it would return true. If we call this function starts with foo and passed in JSON, it would return false. Because it wouldn't be able to, it would be able to cast string, but it doesn't start with foo, so it would go to else. So these are all the use cases for when you pass an argument to a when construct. Let's talk about when you don't pass an argument to a when construct, which can be used as an expression or a statement. So you can sometimes, when you pass it without argument, it can sometimes result in clearer code, especially if many of the conditions are simple comparisons. And this is when you'd want to use it. If you're using a lot of if statements, a lot of multiple else if branches inside your if statement, you want to use the when without an argument. So an example of this is you have your when, there's no argument there. You just have the left bracket. And when you have a when construct without an argument, that means that the branches have to evaluate to true or false. You can't do equals. So here it's saying stir.length equals 0. If that's equal to 0, evaluates to true, then it will print out the string is empty. If stir.length is greater than 5, it's going to print out the string is short. Else, it's going to print out the string is long. And else would not be required there because we're not using it as an expression, but again, it's good practice. So here is how you can evaluate your branches with true or falses using it as opposed to if-else statements. So if you were to use the same code, write it in an if-else chain, look how much more code that is. If, else, else. It's very cumbersome. It's a lot more typing. And what is Kotlin all about? It's about making things more fun. It's about making things more efficient. So you don't have to do all this boilerplate, write all this necessary code just to meet the requirements of the language. You should see the advantage here. Very nice to use if you don't want to pass an argument. Let's take a look at some of these examples inside IntelliJ. So in this first example, we have a variable called x, which is read-only. It's called yes, signed yes. We have our win. We're passing an argument called x. We're using win as a statement here. We're not returning anything or assigning it anything or returning from a function. And what we're saying here is if our branch condition is English and a branch condition is German, if x is equal to English, it's going to print out how are you. Otherwise, it's going to print out a German string. Otherwise, it's going to print out I don't know the language yet. Now, the else is not required here because we're not returning anything. But let's run this. And what you'll see here is it's going to print out else. I don't know the language yet. Now, if we passed in English, it's going to print out how are you. If we pass in German, it's going to print out something in German. Unfortunately, I can't read German, but I'm guessing that says how are you. And we already showed the else clause. Now, we could remove the else here, and the compiler is not going to complain because this is a statement. It's not returning anything. So it just prints out German still. Actually, let's make this correct. And when this happens, nothing will get printed out. Now, if we made this an expression where we said val y equals win, and then we tried to print out y, you're going to get a compiler error because it doesn't have all the matches there. And this is not okay to do. So here it says win expression must be exhaustive, add necessary else branch. So we would be required to add the else here, do something like that. And then we will be able to compile and we'll be able to run it and we would see matches displayed. Here's another example of using the in clause. Here we have names, which is a list of, that's just a data structure, it's a collection. And then we have to create a variable named x. And we could say x is going to be equal to John. And so x is going to be in names and it's going to print in, I know that name. And it doesn't know how to, it said type inference failed, the value of the parameter t should be mentioned. So this is a collection, so we have to make sure that we identify the type here. So let's make sure this is a string and build it. The real problem here is you can't do a range and a number that's a string. So now we run this, you'll say, I know that name. Right? If we had something else where it wasn't in that range and it is a string, it will print out x.length, which is 5. Right? So we can see that we used in to check a collection. If Jason is in this list, prints out I know that name. If it's a string, we're using the is operator here and we're using a smart cast. We're just printing out the length. So these are some examples of how you can use the when construct. It's very useful. We'll have more examples of this when we do some exercises. Thank you. Hello and welcome. I'd like to provide a little code along of the when construct. Remember, the when can return an expression, return a value, and it also can take an argument and not take an argument. So I just kind of wanted to run through some of these different scenarios. The first thing I want to do is I have my main routine, my main entry point of the code. I want to write a little helper function that demonstrates the when. So I'm going to create a top level function and I'm going to just call it cases. And it's going to take a single parameter, an object, which can be of type any. Remember, the any object is the top level object. It's equivalent to the object class in Java. Every type in Kotlin is a subclass of any. So we can just say any, and this is also not going to return anything, so we could either put inside here the unit type, or we could just leave it blank. All I want to do here is have this function be able to use the when construct to check different cases. So this is going to use the when keyword, and that's how we can use the when expression or when statement, and we're going to pass an argument to this. Remember, for when, you can either have an argument or not have an argument. And we're going to include this with the bracket, so it's going to be a block. And we're going to have our cases. And remember, you can put in your cases many different things. We're going to start off and say if it's equal to 1, we're going to just print out something, a message, 1. Remember, the when construct is very similar to the select statement in other languages, select case. But you can evaluate many different things. It's much more powerful. We're going to also check if the object passed in was equal to hello. If it is, we're just going to print out greeting. We'll also check a type check. Remember, you can use the is operator as well to check the type of an operator. We're going to say if it's a long, we're going to print out long. All right, so we have many different cases here. We're also going to say if it's not a string, using the is check, we're going to print out not a string. And then lastly, when we have the when construct that takes an argument, we're required to have the else keyword. It's similar to the default case. Anything else, we're just going to print out unknown. So now let's try to use this helper method by calling it and passing in different parameters, different objects. Let's pass in hello. And when construct is executed by calling this helper function, it should match the hello argument there, and it should print out greeting. So let's go ahead and run that. And we'll see to print it out greeting. So that's good. Let's add another case. And this one will pass in the value 1 so that it will match the first argument. So now we should see two things that are displayed as output, greeting and 1, which we do. So it's matching. We can also call it with, how about a long? And the way we can actually specify a long in Kotlin is 0L. This time it will check the type and it should print out long for that third call of that function. And it does, it prints out long. Let's also try to call an arbitrary object such as a new class. And just for demonstration purposes, I have to create this. So let's say, just create a simple object here, an empty class. And inside the case, I can then pass in an instance of it, something like this. And in this case, it's passing in an object called my class. It shouldn't match anything. Well, it should be not a string, so it will print out not a string. So now we run this. We see not a string because my class is not an instance of a string. Now let's try to pass in a string to get to that else cause, but no string that recognizes, something like hello. And when we run this, we'll see that unknown was called, so it matched the else statement. So again, you can see how the when construct works with an argument. It'll print out any of the matches that it encounters. Now remember, you can also put in the comments multiple matches if you wanted. We could have hello match also hello. And for both of those, we would print out greeting. So now if we were to run it, we wouldn't see the exception or the unknown being displayed. What we would see is greeting displayed as the last because it matched either hello or hello. So the comma is enough way to match multiple things. That's the main use case for when. Now, as I mentioned, you can also have when take no argument, and in that case, it can evaluate a parameter and do something on it. You could also have return an expression. When can return a statement, so you could assign it to a variable. But mainly, the most common use case is passing in something and then evaluating it, and it's very useful for efficiency with similar to a select case statement. Thank you. Hello and welcome. Let's talk about the while and do while loops. These are constructs used in Kotlin to repeat code, avoid duplication. So out of all the features of the Kotlin language, the iteration concept is probably the most similar to Java. In fact, the while loop is identical to the one in Java. So this lecture is not going to be too long. Kotlin also supports the do-while loops. The do-while loop is same as the while, except it's the post-test loop. So the do-while loop is always guaranteed to execute at least once. Syntax for both loops is identical to Java. I'm still going to describe it because there are some of you out there that don't know Java. So the while statement looks like this. You have a while keyword, and then inside the parentheses you have the condition. It has to evaluate to true or false. So it's an expression that evaluates to true or false. You have the left bracket to start the body of the loop, right bracket to end the body of the loop. Inside the body, you can have any number of statements or expressions. And those statements and expressions will be executed sequentially. The do while loop is similar, except that the condition that evaluates to true or false is at the bottom. And this is why you're guaranteed to always execute the body of the do while loop at least once, because you never check until you get to the bottom. But again, notice in this example, you have the do keyword, the left bracket, no condition after the do, a bunch of statements or expressions inside the body. You end the body with the right bracket, and then right next to the right bracket, you have the while keyword, followed by a condition inside parentheses. Some examples here. In the while loop, the body is executed while the condition is true. Right? The condition has to evaluate to true. For the do while loop, the body is executed for the first time unconditionally, a post-test loop. You're guaranteed to execute once. And so after the initial execution, where you execute one time, if that condition is false, you don't execute again. You don't go back up. The body is only executed while the condition is true. So here's an example where we're decrementing a variable. We have the while keyword. X is going to be equal to some value. If x is equal to 50, this loop is going to iterate 50 times. Right? Do you see that? Because in the body of the loop, you're doing an x minus minus. You want to modify, if you're doing, I mentioned this before, but there's two types of loop. Counter control loop, which is going to execute a specified number of times. And then you have an enumeration control loop, which the loop will run either 5 times, 10 times, 100 times. This example is a counter control loop. If x is equal to 55, it's going to run 55 times every single time. There's no variation in this loop. It depends what x is equal to, but it's still going to run a counter number of times. And so when you use counter control loops, you want to make sure that you modify the loop control variable, the counter, inside the body. Otherwise, you're going to have a problem where the while loop never exits, and that's referred to as a forever loop, even though you're using while. So make sure you modify the loop control variable somewhere inside the body of the while loop. And this is exactly what this example is doing, x minus minus. Do while is always going to execute once. In this example, we're creating a variable, a read-only variable called y. It's going to be equal to a function call retrieve data. And if y, it's going to execute the do while loop and call retrieve data every single time while y is not equal to a null. So y is still visible in that while keyword. Right? So even though we declared y inside the body, you can still view it in the while condition. You should notice that. Take note of that. But again, another simple example, and it really doesn't change from most do whiles or while loops in other languages. You have conditions evaluate to true, body gets executed, and then you go back up, keep looping until you modify that loop control variable. But a nice way to avoid duplication, you don't want to repeat code. You use loops for repeatable code. Thank you. Hello and welcome. Before we talk about for loops, I wanted to talk about ranges because ranges are often used in a for loop in Kotlin. And even in Kotlin, for loops that really don't exist. They do. You use the for keyword, but they're not like traditional for loops. And we'll talk about that when we talk about for loops. But let's first talk about ranges. A range is essentially an interval between two values, usually numbers, a start and an end. So it's the same type of definition for a range in the real world. You can write it using the dot operator. It's just a beginning, starting, and an end. So here's an example. Creating a variable 1 to 10, we're going to assign it 1 dot dot 10. It's a range. 1 to 10 is equal to 1 dot dot 10. If you can iterate over all the values in a range, the range is called a progression. So you'll see this term progression. It just means you went through all the values in a range. Right? And when we assign that variable 1 to 10 a range, it's not all the numbers in the range, right? Because you can't assign multiple numbers to a variable. It's just you can then use that 1 to 10 as a block, like in a lambda. So you could pass 1 to 10 into a function or something, and then it would be used as a range. It's returning a range. Ranges and progressions allow Kotlin to use a uniform syntax and a set of abstractions in for loops, and also work with the in and not in operators that check whether a value belongs to a range. So the traditional use case when you'll utilize it is in for loops and where you're using in and not in operators. And we'll provide some examples of that. But you can use it to check whether a value belongs to a range for the in and not in. You also want to note that ranges in Kotlin are closed or inclusive. What that means is the second value is always also part of the range. So in that example, 1 to 10, 10 is part of the range. Right? It's inclusive. If it was exclusive, 10 would not be part of it, only 9 would. So when you say 1 dot dot 10, you're actually going all the way to 10. 10 is part of it. You use the in operator to check whether a value is in a range, or its opposite, not in, to check if a value isn't in a range. All right, so we talked about the in operator. The in operator can be used to see if data is inside of a data structure, often with the collection classes. The most basic thing you can do with the integer ranges is loop over all the values. We'll get to more examples of this when we talk about the for loop, but just to show you, you would use it like this in an if statement. And what this is doing is it is not looping, but it's saying if I is in 1 to 10. So it's returning a true or false. If statements have to return a true or false. So the condition is I in 1 to 10. And it's saying it's looping all over the values because it's actually the in operator is checking whether I is in there. The 1 to 10 is all those values. So this would be the equivalent of 1 is less than or equal to I, and I is less than or equal to 10. Right? Right. So if I is 5, this statement's going to be true. I is greater than 1. Or 1 is less than I. And this is in this example, you would just print ln I. And so what would be output from this is the value of I. So this is not going to print out 1 to 10. It's just going to print out once. Again, the I in 1 to 10 evaluates true or false. It's not a loop. Here's another example of where you'd use it in a loop, except you're using it incorrectly. Here you're saying for I in 4 to 1, print I. It's not going to print anything because you can't start from 4 and go to 1 in a range. You'd have to use a certain step inside of a loop. So it prints nothing because if I is even 3, it's not going to print anything because you can't go backwards. This won't actually give you a compile error. It will just say I is never used, but you don't want to go from 4 to 1 when using ranges. You can't. The only way you could go reverse is if you use something in a for loop, which we'll talk about. Ranges aren't restricted to numbers either. Any class that supports comparing instances by implementing the java.lang.comparable interface can use ranges. So you don't have to just go numbers. So you could do something like print line Kotlin in Java to Scala ... We know it's a range because of the ... And what this will do is it's just going to alphabetize. So Kotlin is in Java to Scala. If you did Java to, Bob, that would not print out anything. So that would print out false, actually, is what it would print out, because that evaluates true or false. So that would print out true in this case. Utility functions. So you can use certain functions in a range, such as the down to function. It allows you to iterate over numbers in reverse order. And here's some examples of some for loops. You could say for I in 4 down to 1 and print I. That would print 4, 3, 2, 1. So we're starting to talk about the for loop. We'll get you familiarized with it. And one of the reasons I want to talk about range is because it's used a lot in the for loop. And this would be an example. Ignore the for part of it. Just understand that you can say I in 4 down to 1. And what that will do is it will reverse. It will iterate over the numbers in reverse. You can also use the stem function as a utility function for a range. This allows you to iterate over numbers with an arbitrary step. So step allows you to skip some numbers. Step can also be negative, in which case the progression goes backward rather than forward. Now, it's not really negative. So when I say the step can also be negative, I don't mean you can assign a -2 to a step. It just means that when you're reversing it using down to, the step is really like a -2. So don't take that literal. So something like this. If you had 4 I in 1 to 4, step 2, println I, print would just be 1 followed by 3, right? Because you're not gonna stepping by 2. It's like an I equals I plus 2. Now, if you were to do the down to utility function, step is still equal to a positive number, but what's happening really is step is minusing by 2. So you'd print 4 followed by 2. That's what I mean by it can also be negative. Another utility function, you can create a range which does not include its end element. You can use the until function, so you don't have an end. So here it would be 4I in 1 until 10. And I is in 1 to 10, 10 is excluded. So this is different than the inclusive part of in where a range automatically has the end as inclusive. This is how you would exclude it. So this would go in 1 to 9. And then once it hit 10, it wouldn't execute the body of the for loop. So another print line. You can also create a range yourself by overriding the range2 function. So all the dot operator is it just points to a function called range2. If you want and the range2 function returns a range. So you could since you can overload operators in Kotlin, you can overload this operator by overloading the range2 function in your own class. And if your class implements the comparable interface, which you need to compare objects, you don't need to do that, but you can implement you can override the range2 a number of ways. You can override the range2, or you can override the comparable, the compare to. Either one will work. If your class implements the comparable interface, then you don't need to override the range2. It's automatically done for you. So when you try to use a dot, it will look for the equals method and the compare to. It will look for the compare to method, which is equals essentially when it calls equals. So you can create a range of any comparable elements by means in the Kotlin standard library. So what that means is the Kotlin standard library provides some classes for you, and all of those classes implement the comparable interface. So anything in the Kotlin standard library, you can use a range on. Or you could subclass to make your own range. This is getting into member methods or classes, but still I wanted to say you can override the range. You can do an operator overloading, and you don't need to do that if you have if you're implementing the comparable interface. It will automatically do it for you. That's the point of this. So here's what I'm talking about is you have a class called int, and here you have the operator keyword, which is how you overload an operator in Kotlin. And if you want to overload the range2, the dot operator, you just overload the range2 function, and you have to return an iterator in this case. Just examples, overloading the range2, how you would overload the dot operator. This will become clear when we talk about overloaded operators, but just wanted to put it out there. So this is the range. We'll use it a lot in for loops. I already gave you some examples for for loops. It'll be clear in the next lecture when we talk about for loops, but it's a pretty neat convention where you can easily look if something is in a range or use it in a loop. Thank you. Hello and welcome. Let's talk about for loops. Now that we've talked about ranges, it should be a little bit more clear on how for loops can work. There's no traditional for loop in Kotlin. And what I mean by traditional is there's no for loop that initializes a variable, updates the value through every step, and then exits the loop based on some condition. The big benefits in the for loop and other languages are that you could initialize, modify, and check the condition of the loop control variable all in one statement. That does not exist in Kotlin. You cannot do that. So if you're thinking of a for loop and you're familiar with it from other languages, the for loop in Kotlin is not like that. Okay, there's no initializing a variable, there's no updating its value on every step through the loop, and then exiting the loop when the value reaches a certain bound. Get that out of your head immediately. To replace the most common use cases of such loops, Kotlin uses the concept of ranges, the in operator, and iterators for collections. That's how you use the for loop in Kotlin. You use a range, you use an in, or you use an iterator when you're going through collections. So the in operator is always used with for loops. So you're always going to see the in operator inside there, even when you're using ranges and iterators. And so another example here of the range, we just saw it, but just to refresh your memory, the dot is the range operator. So you would use the for loop, and here's the nested for loop. You would use the for loop with in and using a range. So 1 to 10 is a range because that's what it's assigned to in the 1.10. You can pass that variable into a for loop by saying for k in 1 to 10. So what you should notice with the for loop is the for keyword, and then the loop condition, how many times it's going to loop, is inside the left and right parentheses, and then you have a bracket to start and end the for loop. Okay, and this is an example of a nested for loop where we have for j in 1 to 5. So what this is happening is in this for loop, it's going from 1 to 10 in the outer loop, and then in the inner loop, it's going to 1 to 5. Right? So you're actually executing this loop 10 times 5, 50 iterations, because you have the outer and the inner loop. This is a big O of n times m. Right? So, and then all you're doing in the inner loop is you're printing k times j. So k is going to be equal to 1, and then it's going to go in your nested loop, and it's going to say 1 times 1, 1 times 2, 1 times 3, 1 times 4, 1 times 5. Jump out. 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5. Print. Right? That's what it's doing. But again, what to notice here is the in operator on a range. That's how you use the for loop in most traditional senses if you're not iterating through collections. You can have nested for loops, but that in operator is really useful, along with the range. Some more examples. I'll just show you all these at once. They should look somewhat familiar. But in the first example, this is a traditional range, for I in 1 to 4, print I. That's going to print 1, 2, 3, 4. For I in 4 to 1, it's not going to print anything. It's not legal. Well, it's legal in Kotlin, but it won't return in the sense that it won't return a compiler error, which you can't do a range from backwards unless you use the down 2, which brings us to our next example. For I in 4 down to 1. That's going to print 4, 3, 2, 1. For I in 1 to 4, step 2. We know the step function because we talked about ranges before. I introduced the step, the down 2, in the until when we talked about ranges. We could have waited to include that in the fors because it's mainly used in fors. But you can use it in a range, really. You don't even have to, and ranges don't have to necessarily be used inside of a for loop. They usually are, but. So anyways, you see some of the same examples you've seen here that you saw in previous lecture. If you say for I in 1 to 4, step 2, you're going to print out 1, 3. If you see for I in 4 down to 1, step 2, you're going to print out 4, 2. And the reason you're printing out 1, 3, and 4, 2 is because we're not printing a new line after we printed out the 1 and the 4. It's not 13, it's not 42. It's printing out 1 followed by 3, 4 followed by 2, just no new line. Last example is using until. For I in 1 until 10, that's where we can specify a range, but we can specify that the end is exclusive, meaning the end is not included in the loop. So it's I in 1 to 10, 10 is excluded. We're going to print ln I. That would print out 1, 2, 3, 4, 5, or actually, that would print out 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Now, when you use the for loop in collections, which is probably the most common scenario because you end up using collections a lot for storing your data, it works just like Java, right? So what that means is you can create a collection. Like here we have a list. List is a list, and we know that because we're using list of. And so what list is going to be equal to is elements 1, 2, 3, and 4. And so if we say for k in list, k is going to represent the current element in the iteration of the loop. So for the first iteration of the loop, k is going to be equal to 1. For the second iteration in the loop, k is going to be equal to 2, and then 3 and 4. And it's going to print it out. So again, you use the in operator, but you use it on a list, a collection. You don't use it on a range. Here's another example where we're creating a set, using a set of 1, 2, 3, 4. Same type of idea. For k in set, print ln k. That's how you use it for collections. You can use objects in a for loop. Any object can be used inside a for loop provided that it implements a function called iterator. And this is what the collection classes do. The collection classes have an iterator, and that's why we can go through them. You could do the same thing if you had an object that you created. So functions must return an instance of an object that provides the following two functions: has next and next. If you want to have your loop if you want to have your object be included in a loop, you have to return an iterator, and that iterator has to be a block of code that contains two functions: has next and next. So here's an example we have an operator fun, and operator is a keyword you're seeing an overloaded function. So we're overloading iterator. Iterator is part of the ini, so every class can override it. We're overriding iterator, and what we're going to make it equal to is a block of code, an iterator. And so some of the syntax may not be familiar, but I wanted to show it to you because it's part of a for loop, and you can come back and review this when we talk about overloaded operators and also when we talk about classes. But this again is just overloading an object to implement an iterator so that we can use it in a for loop. And so what you notice in here is really after the equals statement, this is our iterator that's going to be returned. It kind of looks like an inner class. We're creating an object called iterator. We're creating an object that's going to return an iterator local date. Local date is just a type. We're creating a mutable variable called current. It's going to be equal to the start. And then we see those two important functions, has, next, and next. We have to provide a definition for that. And so we provide definitions for that, and that's going to be returned. So now we would be able to use my function inside of, if this was inside a class, we would be able to use this object. Right? So this one, my function, would be an overloaded function, overloaded operator function inside of a class. And now we could use that object in that class in a loop. Pretty neat. If you want to iterate over an array, we haven't talked about arrays again because arrays are part of classes, but when we do, you're going to want to iterate over it. So we'll talk about this when we talk about arrays, and we'll talk about overloading the operators with those methods when we talk about classes, but I wanted to give you a heads up. An array is a data structure that can hold multiple elements, usually of the same type, unless you're using a collection. Arrays have an extension function called indices, which can be used to iterate over the index of an array. An extension function is another concept we're going to talk about when we talk about functions, but it's a way to add new functionality to a class. So in an array, you can actually extend an indices function, and then you can iterate over it. So you would see something like this: for index in array.indices, and then you could get the index. And you see in here, we haven't talked about this example in a while, but in this example here, we're using a string formatter, right? We're using the nice idea of using $ symbols or our strings so that we can interpolate them. Again, it looks like PHP code. So string template is what I meant to say, string template, which is a formatter. So this is how you can iterate over an array as long as you, because they have this extension function called indices. And so you can just use that extension function, call it on the array, and that's how you do it. So this is the for loop. Again, not like a traditional for loop that you see in other languages, but nonetheless very useful. You see it used with the in operator on ranges or on objects that are part of a collection, as long as they overload the operator here. And you also see it in an array with an extension function. Thank you. Hello and welcome. Hello and welcome. In this lecture, I'd like to talk about return and jump. This is kind of like talking about break and continue, the loop control variables, where you can exit out of a loop on purpose, so you didn't execute the number of times you thought you were going to execute. So loop control statements change execution from the normal sequence in a loop. Normally a loop will run a certain number of times if it's counter controlled. If it's enumeration controlled, it will run based on some condition. If you force it to execute because you put some keyword in there like a break or continue, if you did it like that in Java, the execution stops immediately. And so you can change the loop control variable in Kotlin as well. Kotlin has 3 types of loop control expressions. You can return, that's a keyword, and that will jump out of the loop and go to the outer loop when we're talking about loops. If you're talking about functions, it will go out to the outer function. If it was a local function, it would go out. Break terminates the nearest enclosing loop, so it's not going to jump out of all the loops. If you have nested loops, it's only going to jump out of the most inner loop. Continue will proceed to the next step of the nearest enclosing loop. Continue is used when you want to basically just skip everything else in the body of the loop and just go back up to the next step. All of these expressions can be used as part of larger expressions, not just in loops. And that's why we included the return. You can use the return in the loop, but return is used for many, many other reasons. Break and continue are typically used in loops. So here's an example where we have a variable called s, And this is just an example of a return. We have a variable called s. It is a read-only variable. If person.name, it's using the Elvis operators. And so if person.name is not equal to null, or if it is equal to null, it's going to return. And so that's a way of breaking execution. It's just going to jump out. And again, return doesn't have to be used as part of the loop, and this is one instance. Break and continue labels. Any expression in Kotlin may be marked with a label. We haven't talked about labels yet, but the way that you can have a label is you have an @ symbol before it. So you use the @ sign followed by an identifier. An identifier is just in Kotlin is ASCII characters, alphanumeric characters. It's a variable name. So break and continue you can have with a label. In a label, this would be something similar to like a goto statement in other languages. You can jump to something based on jump to that label. So this is you're not following sequential programming here. You're jumping to some other line of code. It's usually frowned upon when you do this type of stuff because it's harder to follow. It's harder to maintain if you're jumping all over the place in your code. But sometimes it's necessary. So here's an example where we have loop at for I in 100. That's a label. So we could jump to the loop in some other step. So now that we have loop as a label because it has the @ symbol, and in here again you have the identifier and then you have the @ symbol. The identifier is first. So don't forget that. So now that you have that, you can qualify that with a break or continue to jump out. And so what you would do it here is you would use break at loop and you would jump back out to the loop. That's how it works in Kotlin. So here you have a for loop, I in 1 to 100. You have a nested for loop, j into 1 to 100. And if there's some condition that evaluates to true, you're going to jump out of that nested inner loop and go to the outer loop. So it acts as a break. And you use the keyword break at whatever the label is. Break at loop in this case. So a break qualified with a label jumps to the execution point right after the loop marked with that label. Pretty nice. So in theory, if you didn't have the label at the for, you could jump anywhere you wanted. So it's more like a goto. A continue proceeds to the next iteration of that loop. And you would use the continue without the label. So returning at labels, you can also return to a label. So again, remember that you can use these expressions in other constructs besides a loop. We talk about it when we're talking in our section on control flow, but you can use these in other concepts. So you can use a return and a label to jump out of a nested function as well. And here's how you would do that. You would have a function called foo and ints.forEach. So this is referred to as a local function. You have a local function, which is a nested function. And if it equals 0, you're going to return at forEach. So you're jumping out of that nested function. Here you don't even have the label for each. It automatically knows to just jump out of that nested function and go to the outer function. Another use case. The return expression returns from the nearest enclosing function. And that's why it's not necessary to identify the for each function. You don't have to identify that with a label. Because just by saying return, it's automatically going to jump out of the nearest function. So this is a quick rundown of how you can use the break and the continue to jump out of loops and the return if you wanted to. You also use the return though to jump out of functions and things like that. But it's the concept of labels. That's how they pretty much implement it in Kotlin is they use labels. Thank you. Hello class. Let's write a little program that will demonstrate loops and also demonstrate conditional statements. I'm going to write a program called guess the number. And this is going to be a very simple program that will ask the user to input a number. And what the program will do is it will generate a random number. And if the user inputs the number and it's the correct guess, it will tell the user that they guessed correctly. If it's higher or lower, the program will tell them that it's lower or higher and they have to keep on guessing. So the first thing we need to do, our main function, we have to create a read-only variable to represent the number, the secret number. So I'm just going to say val secret number, and I'm going to specify that it's a type of int. And this is going to be initialized with a random number. And I can get a random number from the math class. So I'm just going to say secret number This is never going to change, so it can be read-only when I initialize it. And what I'm going to do is I'm going to call the math.random function. This is a static function in Java that will generate a random number, and you have to give it a seed. So I'm just going to say 999 plus 1. So this can randomly generate a number between 1 and 1,000. And then I'm going to convert that to an int using our nice extension function toInt. I then want to read from the console. So I'm going to create another variable called keyboard. And this is going to use the Java scanner class to read data from the keyboard. So we can just call scanner and we can pass it in system, and then we have to put in quotes in, because in is a keyword in Kotlin, but system.in is a stream in Java. And then we also have to make sure we import the correct class. So if we hit this and say Alt Enter, we can say Java import Java util.scanner. Okay, now that we have our variable set up, well, we also want to create one more variable that represents what the user guessed. And this will also be of type int. Now, what we need to do is we need to write a loop that keeps asking the user to guess until they guess correctly. I'm going to use a do-while loop because a do-while loop will allow me to have the body entered at least once. This is a post-test loop, it's referred to. And so here I'm just going to say do, I like putting it on the next line, or you could keep it on the same line, while guess is not equal to the secret number. That's going to be our exit condition. If they haven't guessed correctly, we're not going to jump out of the loop. And so what I'm going to do here, the first thing I want to do is I want to print out something to the user to tell them to enter a number. So I'm going to say enter a guess, and I'm just going to say 1 to 1,000. And then just put a quote after that. Something like that. And then I'm going to read in from the keyboard. And you can read a number in from the keyboard from the scanner class using the next int method. And that's going to be stored in my guess variable. So I'm going to say guess equal keyboard.nextInt. And that will actually block. It won't return until the user entered something in the keyboard. And now I want to have a series of if statements, because if they answered correctly, I want to jump out of the loop, or at least give them an indication that they answered correctly. If they guess too low, I want to give them some information to say guess again, it's too low. And if they guess too high, give them information to say guess again, it's too high. So I can use the if keyword inside the if parentheses. I can have the Boolean evaluation, which is if guess equals secret number. Then I can just say println your guess is correct. And then, congratulations. And you'll notice I have no brackets after the if statement because it's a single statement. I can then use an else if, asking another question to say if the guess is less than the secret number. And if it's less than, I want to display something else, just saying your guess is smaller than the secret number. And I can have finally another else if, saying if the guess is greater than the secret number, print out something that says your guess is greater than the secret number. And that's it. That's all I want to have in the body of my loop. So to go over this code again, we created our secret number local variable inside our main function. It's of type int. We initialized that with a random number from the math class. We then created a keyboard variable that represented our scanner class, system.in, which means we're going to read from the keyboard. If we did a different stream, you could read from a different stream, like a file or something like that. We created another modifiable variable, a mutable variable using var, because guess is going to change each time in the loop, so it needs to be mutable. And we made that type int. We then started a loop. A loop, remember, repeats code. So during a do-while loop, which is referred to as a post-test loop, it's guaranteed to execute the body once because the check is at the bottom. We then print out enter a guess to the user so they know what to do. We then read in the information from the keyboard stored in a variable called guess, and then we just use a series of if conditions, conditional statements, to see if they guessed correctly by using equals equals for comparison, less than, and greater than for comparison, greater and less than. So let's run this program and see how it works. And let's make sure we use the correct quotes for system.in. Modify that to the forward quotes. Now when we run it, because remember, in is a special keyword in Kotlin. Now when we run it, we should be prompted with enter a guess, and we are. So it says enter a guess 1 to 1,000. It already generated a random number. So I'm just going to put something in here like 500. It's coming back and it says my guess is greater than the secret number. I misspelled secret. Sorry about that. Enter another guess. So now it says it's greater, so I should enter something smaller. So I'll say 250. This is saying it's greater, so I'm going to go down again, say 100. Still greater. Now I'm going to go to 50. Still greater. Go to 25. Now it's smaller, so now I got to go above. Let's try 45. Still smaller, so I'm getting close. Let's try 48. Smaller, so now it's got to be 49. It's got to be the right answer. 49 is correct, and I was guessed correctly. So a simple program to guess the number. The main point here is to demonstrate a while loop, repeating code, and also conditional statements if and else. But many other concepts as well, reading information from the keyboard, creating mutable and immutable variables, and also using Java code, the Java Scanner class and the Math class. Thank you. Hello class, welcome to another lecture. In this lecture we're going to talk about functions. Finally, it's here. I've been waiting for this for so long. I'm so glad we can talk about functions now. Seems like I've been talking about it so much already with all our examples, but now we're going to talk about it, explain the details. So functions. We're using a functional programming language with Kotlin. We know it takes object-oriented aspects and functional aspects. So some of the basics of functions. Functions are defined using the fun keyword with optional parameters and a return value, with one exception. Remember, we know that in Kotlin everything is a type, and so typically everything has a return value. There is one exception we'll talk about in a second. But for the most part, functions, you define with a fun keyword, optional parameters, something like this. Fun, double is the name of the function, and then we have a parameter with x as the name, colon, and then the type, and then the colon followed by the colon is the return value, and then left and right brackets, and then anything inside the body. But that is the structure of a function and how it's defined. Name a function after fun keyword, parameter inside parentheses, a name, an optional type. You don't have to have a type if you can infer it. X colon, and then the colon after the right parentheses specifies the return value, which you don't always have to have in this one exception. And then the brackets. So calling functions uses a traditional approach. How do you invoke a function? You can just call it like normal. You just say double in this case, and we pass in 2. It takes one parameter to int, and it returns an int. So we assign that to a variable called result. That's how you can use a function in Kotlin at the very basic level. Calling member functions uses the dot notation. So when you have a class and you have an object, you have to put a dot when you call a function. And that's really just referred to as a member function. Uses C kind of C++ terminology, member function. In Java, you usually call these things methods. But because Kotlin actually has a concept of local functions, a function that's not part of a class, we refer to these as member functions. We can't just call them methods because there's more than one way to use a function. And so in a class, you just say dot notation. Name of the class, dot, function. Creates an instance of class sample. In this example, it calls foo. Single expression functions. You hear this term, and all this really means it's a one-line function. So a function must declare its return type with one exception. And that's the exception I was talking about in the previous slide, is its concept of a single expression function. So this is often referred to as a one-line or a single-line functions. We've had a lot of examples in our previous lectures where we've used these single expressions. Some functions can use a shortened syntax that omits the braces and uses the equal symbol before the expression rather than the return keyword. the equal symbol after it, that's what's being returned. It saves time. You don't have to type as much. One of Kotlin's big goals. So here's what that means. You have a function called square, and you have a parameter called k of type int, and you're using equal here instead of the bracket. Remember in the previous example, we had a bracket, and then we had the body of the bracket. Well, if your function only has one line, you can just use equals, and you don't have to use return. And that's what this is doing. Equals k times k. That's the entire function, one line. So it's shorter, it's easier to write. You don't have to put in the brackets, you don't have to put in a return type. It makes things go faster. So notice how the function does not need to declare the return type of an int. This is inferred by the compiler. Because k times k is an int, it's going to know that you're returning an int. The reason for this feature is that very short functions are easy to read. You can always include the return value if you like, if you think it makes things clearer. Something like that. Fun square 2, colon, int, that's how you specify return, and then you say equals k times k. Still don't need the bracket. You could put the bracket there too if you wanted, and then have the ending bracket. Single expression functions can always be written in regular style if desired. So we kind of talked about that, but identifying types of strings, having the equals, and having a plus b here. It depends what you want to do, either way. Here's another example where we're going to use the brackets. Function concat2, we're specifying the return value here though. It's still a single expressive function because it only has one line, but we were using the regular notation, the regular style. We're using the return statement and we're using the brackets. If we don't want to use the regular style and just use the equals and no return, we can, but either way is fine. It's still a single expression function. The compiler enforces the rule that only a single expression function can omit the return type. This is the only condition where you don't have to have a return type. Otherwise, you have to have a return type. So remember that. Memorize that. Unit functions. We talked about the unit keyword, unit operator, I guess it is. And a unit operator just means it's void. It means that something doesn't return. But remember, all functions return something except our single expression. And so because everything returns something, you still have to return something even though a function doesn't return. And that's the unit type. Right? So unit functions return a unit type. It doesn't return any meaningful value, but it's defined as a unit. You should understand this from when we talked about unit. Kind of just reiterating this point. Every function but an expression function returns a value, and that includes functions that return a unit, even though they look like they're void. Functions returning unit can omit the return type for procedural style syntax if the developer wishes so. You're still returning something, but you don't have to use that return type. When you do the single expression function, you're actually not returning anything, right? I mean, you're returning something, but you don't even have to specify the return type. Here, because you're using unit, you can or cannot specify unit. So, same type of thing here. Fun print 1, where you have a string parameter of type string, you're returning a unit. In the second example, print 2 string, you're returning a unit. So you're still returning a type, right? It kind of looks like it's also unit functions don't have to return anything, but they are returning a type. In the previous example with the single expression functions, the compiler actually doesn't see it returning a type because it's an expression, even though it is. It kind of infers it, right? It knows what type it is. Here you're just returning unit. There's a difference, and I hope that's clear. Returning unit versus returning a specific type, but it's inferred. Parameters. We're going to talk about default parameters and named parameters, but just some general information on parameters. The parameter list must always be present, even if no parameters are defined. So here's a function that takes no parameters, but you still have the left and right parentheses. So here's a function, hello, it's returning a string. It's a single expression function equal to hello world. Each parameter is in the form name, type, and are separated using commas. Each parameter must be explicitly typed. So you can't do type inference on parameters. You have to have an explicit type associated with a parameter. And we've seen that in all of our examples. No type inference in parameters. And that really would just mean you could pass whatever you wanted if a function had type inference. So here, fun hello, name string, location string, and then returning a string, hello to you, and then we're using a string template, hello to you, $name at location. So the above function accepts two parameters of the type string and also returns a string value. We'll discuss default and named parameters in another lecture, as I mentioned. So this is just an introduction to functions, how you can use basic functions. In Kotlin, functions are a big deal. So there's local functions, there's member functions. You can pass lambdas to functions. You can have this concept of default and named parameters. There's extension functions. We're going to talk about all that stuff, but this is just to give you an idea. Thank you. Hello and welcome. Let's talk about top-level functions. Top-level functions really just a concept of a function that doesn't belong to anything. So like a function that's not part of a class. We've been providing many examples with our main function where we just create a function and it doesn't belong to anything. So top-level functions are functions that exist outside of any class, object, or interface and are defined directly inside of a file. And they usually go at the top of the file. So the name top-level comes from the fact that the functions are not nested inside any structure. They're not part of a class. They're not nested function inside of a function, a local function. So they're at the top of the hierarchy of classes and functions, the very top. Top-level functions are especially useful for defining helper or utility functions. You can use a top-level function when it does not make sense to group them with other functions or inside of a class. Sometimes you don't need a function, a member function. You just don't need it. You just have some helper function that you need somewhere and you can put it outside of a class. You can't do this in Java. Every method is part of an object in Java. So I guess the workaround here is a static function in Java. You can't have a standalone function in Java that is not part of a class. A static function is still part of a class. You just don't have to invoke it with an instance. So in Java, these kinds of functions exist as static functions inside helper classes. But again, the key here is inside helper classes. They're still inside of a class. There's no concept in Java of having a function or a method that's not part of a class. But what they usually do in Java is you have a static method. You don't have to create an instance of the class. You can just call it directly. So in Java, there's some functions that are part of the collection classes that you can access directly because they're static. They're still part of the collections classes, but it's a similar concept. There's no concept of a static in Kotlin. And so you would use this top-level function that way. Some functions are so standalone that it makes little sense to take the trouble of creating a containing object, a class. Just don't need to do it. So a good example would be the require function. A require function is part of the Kotlin standard library. It's a standard library function that is used to ensure that parameters, when invoked, satisfy the invariant conditions. So it returns a pair. Let me show you an example. If there's a parameter that should always be greater than 10, we can do something like this with the require. We can create a function called foo that takes a parameter k of type int. We can call the require function. It's not part of any class. It's just a top-level function. And it says require k is greater than 10. It's a parameter validation technique here. Require k is greater than 10, and then we pass in a block of code which is just a string in this case. But require is not part of any class. The function is placed inside an object. It could be placed inside an object called assertions, and then there's other functions that are similar to require, and we could put all those functions in assertions. We could do it that way, but really it's no big deal. Just had it as a top-level class, and then we can define the functions directly in a file called assertions.kt. So you can have multiple functions in a file called assertions. They could be all these helper functions like require, and you can invoke them without having to create an instance of a class. And that's why they say it's similar to static, but static you still have to have part of a class. So that's a top-level function. It's a pretty simple concept. If you're familiar with just structural languages, it's no different than just a C function. Not part of a class, not part of any containing object. Thank you. Hello and welcome. Let's talk about two other types of functions called member functions and local functions. We talked about top-level functions. These are two additional types. A member function is a function that is defined inside of a class, object, or interface. So this is a method in Java. We have to distinguish and call it a member function because there are different function types in Kotlin. We can't just say function, or we can't just say method. And so this is nothing different than a method in Java. It's a function that's part of a class, an object. When we talk about classes, we'll show you how you can define these in more detail. But since we're talking about functions, I have to give you an idea of the different types of functions. So here's an example. The syntax may be a little confusing, but the way that you can create an object in Kotlin is you say class. You specify the class with the name of the class, and then inside there we have a member function called foo. You still create the function the same way you create other types of functions. You say fun. You still have parameters, pass them the same way. You still have the parentheses for empty parameters, the left and right brackets for the body of the function. You can, if we had parameters, we'd specify the type. We'd have a return type there. This is returning the unit type because it's not there. So it's pretty simple. It's just a function inside of a class. A member function is invoked using the name of the containing class or object instance with a dot, followed by the function name and the arguments in parentheses. So again, this is another Java convention. Up until the previous functions, you can just call them. But if it's part of a class, you have to have an instance of that class and then call the method on it. So when you say sample with a left and right parentheses, that creates an instance. And then you can say dot foo. The dot operator is how you call member functions. There's also, if you're familiar with Java or other languages, there's this concept of this, an object, like the this keyword. They don't have this concept in Kotlin, the specific this keyword, but you can still call member functions inside of a class, other member functions. So I wanted to describe this. Member functions can also refer to themselves, and they don't need the instance name to do this. You don't need to provide the this keyword. Because what will happen is it will act just like other languages with this keyword. It will operate on the current instance. So you can call member functions inside of a class from another member function just by specifying the name. You don't have to use the class name or the instance name. In fact, there's really no instance once you're inside the class. And again, this concept is the same as using the this keyword. So an example here is we have two functions in our class rectangle. We say object rectangle. It's another way to create an object. We have a function called print area, and we have a function called calculate area. Print area is calling another member function called calculate area. You'll notice that it doesn't use the instance name here. It just calls calculate area. So print area takes a width and a height as integers and returns a unit, void essentially, and it creates an area. Area is populated from the calculate area function, member function. You just invoke it, and then it prints out something using a string template. The area is $area. Calculate area just returns a width and a height. Takes a couple integers, returns an int. So you can call member functions without using the this keyword or an instance in a class if you want to call a member function from another member function. Local functions. Local functions are an interesting concept. It's a nested function. So in Java, a large function or a method might be broken down by calling several support functions, helper functions, either declared in the same class or a helper class that contains static methods. This is what you would do in Java. You need a function that needs some help or needs to do something simple. You create a helper function or another class with helper functions. Local functions handle supporting functions by allowing functions to be declared inside other functions. Nested functions. This is this concept. You can have multiple nesting levels. And the reason you do this is it reduces duplication. There's a lot of advantages. There's a couple other advantages for local functions. Reducing duplication and reducing the number of overloaded functions that you need to use as well. And actually reducing the number of overloaded functions has to do more with named parameters, but local functions can help with that. So here's an example, the same example that we had before, except now we have calculate area as a nested function. Calculate area is inside print area. Pretty neat. It's a helper function essentially. We can call it inside the print area function, but the nested function definition is right inside there, right above area. Right, so we have fun and then another fun inside of the brackets of the outer fun. Calculate area is the nested function, print area is the outer function. And we call that function right after we defined it. So a nested function. Nested functions are not accessible to the code outside of the function. So that's why they're called local concerning scope. You cannot call that function anywhere but inside the outer function. It's kind of similar to an inner class where you can't You can't create an instance of an inner class outside of the outer class. So this is useful when you want to hide functions that are just used as implementation details of a larger function. They don't need, it's kind of an abstraction technique. You don't need that function to be used anywhere else. You just create a local function. It's only used inside that outer function. Now, you may be asking yourself, well, why don't we just make the function private? And you can do that. You can make it private. A local function is a bit, either way, it's fine, really. A local function may be a bit cleaner to some degree, especially if that function's only used inside one member function. Now, if that function's used in a lot of other member functions, then you wouldn't want to make it local. You could make it private. And that's probably when you would make it private, if it's used in multiple member functions. If it's used in just one, just make it a local function. Local functions can also access the parameters and variables defined in the outer scope. Sort of like, an inner class. The inner class can access member variables of the outer class, right? If you're thinking about Java. And because Kotlin is based off of Java, we're talking a lot about Java in this class. So I hope you're not getting too frustrated with all my Java examples, but that's why I bring them up, because Kotlin's based off of Java. So we're identifying the difference between Kotlin and Java a lot of the time. So local functions can access those parameters and variables. This allows a nested function to be more readable and saves repeating the parameter definitions. So in the previous example, you should have noticed that we were creating parameter definitions in our calculate area, but they were using the same things in the outer function, right? We shouldn't even needed to do that. We could have just accessed the outer function parameters, right? So we'll do that. Here's print area 2, where we don't define any parameters in our calculate area function. We just use the parameters in the outer function. It's cleaner, much easier to do. So we're using width and height in our outer function. For our calculate area, we don't have any parameters there. It saves repeating the parameter functions, makes it more readable. So I like the concept of local functions. It's pretty neat, and you don't have to use these static things all the time. So we'll be using local functions quite a bit when we have functions that need help and that aren't really used anywhere else. Otherwise, if we're inside of an object, we can just use a private. But also, if you're using the local functions and top-level functions, that would be another use case. Thank you. Hello and welcome. Let's talk about named arguments. Just to be clarified, arguments are what you send to a function. When you have values in a function, those are called parameters. Arguments are what you invoke with. Parameters are what's defined in the function. So that's the difference between parameters and arguments. And we want to talk about naming our arguments. To allow function calls to be more readable, named arguments were introduced into the Kotlin language. What is the Kotlin language all about? Among many things, it's about readability. It's about expressiveness, being concise. With using named arguments, we meet all those goals. We have functions that are much easier to maintain because we know what the arguments represent. So when you call a method written in Kotlin, you can specify the names of some of the arguments that you're passing to the function. This allows us to be explicit about naming arguments when passed to a function. Explicit means you're naming the argument. It's clear to the user, the reader I should say, that what the argument represents. So it has the benefit that for functions with many parameters, explicit naming makes the intent of each argument clear and more readable. And I'll provide with an example where this is demonstrated very clearly. It's very convenient when a function has a high number of parameters or default ones. I have a little problem with this statement, because if a function has a high number of parameters, that's bad. If you've ever read the book Clean Code, you want to stay away from a function that has more than 3 parameters. It's just not good design. More parameters, it's hard to maintain, and it shouldn't take that many parameters. So first off, when you define your functions, try to limit the parameters to 3. Now, if you really can't do that, then definitely use named arguments. One or the other. But I would stay away from functions with a lot of parameters. If you specify the name of an argument in a call, you should also specify the names for all the arguments after that to avoid confusion. In fact, you're required to do this. If you specify one name of an argument, you have to specify all the subsequent ones, but you should also specify the preceding ones as well. Don't try to just pick and choose, because if you're going to make it clear, make it clear. Don't make it confusing by saying, oh, that one's named and the other one's not. Use named arguments. So an example here, if you want to use name arguments, you put the argument name before the argument value. It's quite simple. Here's a function call that does not use name arguments. So we have a string here, a kindness of ravens. We're calling a method on it, function on it, region matches. We're passing in 14, red ravens, 4, 6, and true. And you're probably thinking to yourself, what the heck is 14? What is red ravens? What is 4? What is 6? What does true represent? You have no idea what these arguments mean, right? So with name parameters, you can fully understand this. Here's a function call with named arguments. We call the region matches function. We say this offset equals 14. Well, now we know that 14 represents an offset. Other equals red ravens. Other offset equals 4. Length equals 6. Well, that's pretty good now that we know 6 is equal to length. The biggest one here is true is equal to ignores case, and that's very clear. It means that we want to ignore case sensitivity in this function. So name parameters can make a big difference on readability and thus maintainability. If we would have to grab that region matches with no named arguments from existing code, somebody else wrote it, it would be very hard to understand what the heck's going on there. So it makes it more readable. It's now clear what each of the argument is meant for. And it also, with that last Boolean, you can pretty much infer that ignore case is something to do with case sensitivity. It's very obvious. Again, if you didn't have these named arguments, what would happen is you'd have to go and look in documentation or the source code to see what the parameters are. And that would take more time. And so, again, we're saving times, less amount of code, and it's just easier to maintain. All good things. And one of the reasons why I love Kotlin. The order of the arguments. Named arguments also allow the argument order to be changed to suit the caller. So this is kind of cool. You can do something like this. You can say val string equals a kindness of ravens. You can call ends with, and in one function call, you can say the named parameters on the left-hand side, which is always needed, but you can pass them in a different order. The first parameter is suffix equal ravens. The second parameter is ignore case equals true. And then in the subsequent call, you can call it with the ignore case first and the suffix second. Pretty nice. So you can avoid mistakes by mismatching the parameters if you use named parameters, named arguments. So pretty good deal. You can also, another example here is when you can't, once you name an argument, you have to name all the other ones afterwards. So here in the second delete files, we're specifying the first parameter, we're not using a named argument, .jpeg. The second one we are, the third one we are, and the fourth one we are. We're required to do that. So in the above, the first argument is not named. When calling a function, not all arguments need to be named. And you're going to see this is the same exact characteristics when we talk about default parameters. But not all the arguments need to be named, only the arguments after the first one. So the rule is simple. Once an argument has been named, all the following arguments must be named too. So remember that. Otherwise, you're going to get a compiler error. So this is a nice feature added to Kotlin to make things more readable and much clearer on what's going on when you're talking about arguments. Thank you. Hello and welcome. In this lecture, I want to talk about default parameters. Kind of go hand in hand with the name arguments. So another common problem in Java is the overabundance of overloaded methods in some classes. So for example, the java.lang.thread class has 8 constructors. That's a lot of constructors. All these overloaded constructors. So the overloads can be provided for the sake of backward compatibility, for convenience, or for other reasons. But the end result is the same, duplication. Right? It doesn't matter why they're there, and I'm sure there are valid reasons why they're there, but it's still a ton of duplicate code, and you don't want to have duplicate code. One of the best things about object-oriented programming is inheritance, which can reduce duplicate code, and objects, which can reduce duplication. So you want to avoid duplication. Right? One of the reasons we don't write 10 of the same statements is because we have loops. Duplicated code is just not efficient. It takes you longer to write. So the parameter names and types are repeated over and over. If you call an overload that omits some parameters, it's not always clear which values are used for them. Right? So there are a lot of issues with overloaded methods and providing a lot of them. In Kotlin, function parameters can have default values, which are used when a corresponding argument is omitted. So that means you can use things many different ways. So this allows a single function to be defined for several use cases, which reduces the number of overloads. And that's the main reason we use these parameter defaults, because we can get rid of overloads. And you'll see clearer in a second here with an example. So here's an example. We have fun divide, and function divide takes a divisor of big decimal and a scale of int, and we have int equals 0. That looks a little strange. That looks like a default parameter. And then we have rounding mode colon rounding mode equals rounding mode dot unnecessary. Again, another equals. So another default parameter. And then this function is returning big decimal. So we have two parameters in here that have default parameters. The first one doesn't, divisor, big decimal, but the other two do. So default values are defined using the equals after type along with the value. Just like the named arguments where you have a name and then the argument value, it's the same thing with the defaults for parameters. You have the equals and then the value with the name before it. And again, remember, parameters are used for functions, defined functions inside the parentheses. Arguments are what you pass to functions. So when invoking a function with default parameters, we can omit some or all of the parameters. But once a parameter is omitted, all the following parameters must be omitted as well. So this is kind of like named arguments, where you provide an argument, a named argument, and all the ones after that have to be named. Same thing with parameters, default parameters. If you omit one, all the following parameters must be omitted as well. And so here's an example of how you can correctly call a function that has named parameters. You can call it with big decimal 12.34 with only one parameter. That's fine, because because the first parameter is not named in the definition. You could call it with big decimal 12.34 and 8. Again, that's okay, even though it takes 3 parameters. You can call it with 2 because it has named parameters. It will just, or default parameters. It will just use the defaults. That's the whole point. It's using defaults. Or you can call it with 3, and it doesn't use any of the defaults. It uses what's passed in. So instead of creating 3 overloaded methods, one taking 1 parameter, one taking 2 parameters, and one taking 3, you can create 1, and you can call it 3 different ways. So pretty nice. You're reducing duplication. Hello again. In this lecture, we want to talk about infix calls. And so I was debating whether or not to talk about this concept when we talk about classes or functions, but I'm going to talk about it with functions because they are used in functions. They're also used in classes. One of the difficult things with teaching Kotlin is so many of the concepts are used all over the place. So when you talk about functions, you want to talk about infix calls, but we'll also use infix calls on classes. Infix notation is the notation where an operator or function is placed between the operands or arguments. There's really 3 types of notation. And all this has to do is with the style. It's where things are placed. With infix notation, the notation is between the operator and the function. It's in the middle. With postfix notation, you have the operator or the function at the end. With prefix notation, you have the operator before the operands, or in the case of a function, you have the parameters before the function. You tend to see or utilize these infix, postfix, and prefix notations with operators, but you can also apply them with functions. And all they are, again, is a style thing. If you had an infix function, what that would mean, and this is exactly what this is, calling by infix. It's an infix function. You have the name of the function in the middle, and on the left-hand side you have the invoker, and on the right-hand side you have the parameter. If you had a prefix function, you would have the function and then the parameters on the you would have the parameters before and then the function after. And then for postfix, and this is what you usually see in most languages, is you have the function and then the parameters after it. So when you think of infix notation, postfix, prefix, it's all the same. It's just where you place the symbol. And you all probably heard this term also when you think of incrementing and decrementing. Prefix increment, postfix increment, plus plus I or I plus plus, same type of concept, or I plus J. I plus J is infix, plus plus I is prefix, I plus plus is postfix. So we're talking about infix. We're talking about infix. In Kotlin, an infix call uses the method name in between the invoker and a parameter. It's a styling thing, but it also sometimes makes the code a lot easier to read. But you don't have to use it, but it is a nice feature. So all infix functions must operate on two parameters. They have to, because there has to be something on the left side, something on the right side. There has to be, the first parameter has to be an instance that the function is invoked on, and the second parameter is an explicit parameter to the function. Right. So these are closely related with classes, since you have to identify the instance, specify the instance. So here's an example. You have a variable called pair. It's equal to London to UK. And then you see 1.21.121. The infix function here is 2. It's named 2. And 2 is a function in the any class, so you can use it. It's mainly used for pairs. And so what you see here is the left-hand side is a string. That's the instance that is invoking the 2 function. On UK is the parameter. Same with the other one. So you can pass it, you can call it these 3 different ways. London to UK, or 1.2, and then 1 inside parentheses, like a parameter passing. Or you can just say 1, 2, 1 in quotes, which is kind of the same. The 2 function allows you to pass, I think it's overloaded with an integer or a string. So in the above, the 2 function is in the any class. Any class, remember, is that top level object. It's used to create a pair instance. So the pair class overrides this function, and you can use it to create pairs. And this is how you would use it as an infix. And the reason that it works in the pair class is because it overrides the special method that you need to, which we're going to talk about. So to define an infix function, if you want to have your objects support an infix function, this is what you have to do. Infix calls can be used with regular methods and extension functions. So regular functions and extension functions. Since an infix function is placed between 2 arguments, they have a single parameter and are marked with the infix keyword before the fun keyword. So here, you'd have to have an infix inside as a function. Infix fun concat, and then other : string. It takes a parameter other of type string and it returns a string. And so here, this is an infix function, and it's going to return this plus the other. It's going to do a concatenation. And so you could do this normally without an instance, except in this case it'd be a string. So it really would be an instance, but it's not inside of a member. It's not a member function. It's not inside of a class. So you can still have an instance that's not where the function is not part of a class, right? If the function takes a string or something, a string is an instance, this could still be a top level function. It's not associated with any class, but you would invoke it with string concat string. If you want an infix function in a class, you have to override something. So here's an example where we have a bank account class. This bank account class contains a balance as a member variable. It allows you to add to your account, to your balance. So if we have a class account and we have a function add, we have a member variable called balance. The add takes an amount and a double, and it returns a unit, void. It just increments to the balance. It adds to the balance. This is how it normally would be defined. You could, if you wanted to support an infix operator, you'd have to override a method. So to use this, you would say val account equals account, and then you say account.add. And that's how you traditionally would invoke that member method from an instance. Now what happens if you want to have it support an infix? If you want to implement it with the infix function, you have to override, or you have to create a function inside that class with infix. It's not overridden. Just have to use the infix keyword. So here is an example where we could now use the infix function in between the instance, in the middle. So here we have balance equals 0. Now we have our add function, but it's defined as infix. It still returns the same amount, or it still sets the balance and returns a unit. But now we can call it differently. We can invoke it like an operator in infix style. We can say val account2 equals infix account to create it. And then we can say account2 add 100. Pretty nice. It's easy notation to follow. You don't have to do the account2.add and then pass it in parentheses. It's a little bit quicker. You could still if you wanted to, but you don't have to use the dot notation. And this is what the infix function does. Thank you. Hello and welcome. In this lecture, I want to talk about variable arguments, var args. In Kotlin, you can define a function that accepts a variable number of arguments, referred to as var args. A comma-rated separated list of arguments which the compiler will wrap into an array. Var args are kind of a popular concept. They're in a lot of languages. Java has them as well. It just means a variable number of arguments. Typically, when you create functions, you specify the parameters, and you might specify 1, 2, or 3. In fact, I was telling you before that you should never really have more than 3. Sometimes you don't even have to define, a specific number. You can use the var args keyword in Kotlin. So Java supports var args by using the ... syntax. Something like this. Public void println string ... args. I think there's 3 dots. And that's how you know it's a variable number of argument in Java, because it has the dots. Kotlin's var args are similar to those in Java, but the syntax is slightly different. Instead of the 3 dots after the type, it uses the var arg modifier on the parameter. So it uses a keyword. Something like this. Here's a function that's defined as multiprint, and it has a parameter name of var args, or var arg modifier, I should say. The name is strings, and it's of type string, and it returns a unit, which is void. But you see there, the var arg is the modifier, the keyword, right before the variable name, the parameter name. So in this function, it's going through string, in strings, right? So we're using the for loop here, and strings, because it's a number of arguments, it acts as an array, and it gets wrapped into an array when it gets sent to the function. So strings is an array because it has the var arg modifier before it. So you can use the for loop, and you can use the in operator to search that array. Each iteration of that array, string is going to be equal to the first element in the array on the first iteration, second element in the second iteration, and so on. So that println is going to print out all of the variable arguments that were passed to this function. So this could be invoked in the following way. Multiprint A, B, C, 3. You could send 3 parameters, you could send 4, you could send 5, you could send 1. It doesn't matter because it takes a variable number of arguments. Functions can have regular parameters and at most 1 parameter marked as var arg. So if you have regular parameters, you can't have more than 1 as a var arg parameter. So here's an example of a multiprint. The first parameter is a string, the second one is a var arg. Now I don't know why you just didn't have var arg as all the strings. You don't really need to have that first one. But in this case, maybe it's easier because you can signify the prefix versus the rest of the strings. Sometimes it makes the function a little easier to write as opposed to having to separate the first one. So in this example, it prints out the prefix, and then inside the loop, it goes through all the variable arguments. And that's why it added a parameter, because it was just easier to get out the prefix first as opposed to grabbing the index of the array. The var arg parameter is usually the last parameter, but it doesn't always have to be. If there are other parameters after the var arg, then arguments must be passed in using named parameters. We know what named parameters are. So here we have multiprint. Our first parameter is a string, prefix. Our second parameter is variable number of arguments, var args. Our third is a string, suffix. And what you'll notice there in that third string is it has a name, just like the first one. And just like the second one. They're all using named parameters. We know there's named parameters because they have the colon right before the type. You couldn't just have string after that. You'd have an error. And if the compiler would complain because you need to have a type there. Or I'm sorry, you need to have a named parameter there. So the var arg parameter would be invoked using the following named parameter as a suffix. Multiprint start A, B, C, and then you'd have to use the name parameter to specify the last one to invoke it. And when we talked about name parameters, we talked about how you can change the order of parameters, which is pretty nifty because you just use the name parameter that's in the function. And so you could specify them in any order you want, which is a nice thing in Kotlin. The spread operator. If a function is defined to accept a variable number of arguments using var arg, but you already have an array, then you must use the spread operator, which is the asterisk, when passing in the data. So the spread operator unwraps the elements of the array and passes them in as individual arguments. So this happens when you have two arguments and two parameters in a function. One that takes a variable number of arguments with the modifier and one that takes an array. You have to be able to distinguish from the array. So if you want to pass an array of strings to the multiprint function, we would use the spread operator like this. We would say array of A, B, C, D, E to pass it in, and then when we defined it, when we call it, we created an array of A, B, C, D, E, signed it to strings, and then when we call the function, we pass in strings with the asterisk because it's an array. And it still can be accepted as the var args, but we have to pass it in as an asterisk. So remember the definition for the multiprint, the second parameter was var args. We just have to specify that the string array is of var args. So notice that we apply the spread operator before the variable name, not after it. Kind of looks like you're dereferencing a pointer in C. So that's how you can use var args. Very, very simple, very similar to Java, just a different keyword. And then you also have to remember the spread operator to use the array. And the named parameters can also come in play if you have a parameter, a single parameter before a var args parameter. Thank you. Hello and welcome. Let's talk about function overloading. We'll learn this concept, or we'll revisit it when we talk about operator overloading. But it's important to understand the differences between overloading and overriding. So I wanted to talk about function overloading, especially since we're in a functional programming language. Function overloading is the concept of having two or more functions with the same name, as long as their argument lists are different. So their method signature has to be different. So we do this a lot with constructors. Constructors are often overloaded. Constructor is a special method that gets invoked when you create a new instance of an object. And you tend to overload those a lot because you want to create instances in different ways, different member variables being initialized. So in order for it to be overloaded, you have to have a different number of parameters, a different data type of parameters, or a different order of parameters. I'm going to provide a little demonstration to show you this. Just changing the return type will not make a function overloaded. So Kotlin supports function overloading, and you have to change the argument lists in order for it to compile if you have the same name, two with the same name. Method overloading, this is also known as static polymorphism. We haven't talked about polymorphism yet, but polymorphism, if you took the literal meaning of that, it means the same name, different behavior. All right, that's what it's meaning. So static polymorphism means it happens at compile time. And so what this means is function overloading. Functions have the same name, but they have the different behavior based on the types or the number of parameters or the order of the parameters that's specified. The opposite of static polymorphism would be dynamic polymorphism. And this is used in polymorphism when you have overriding. The difference between overloading and overriding is used inheritance. You have to have an inheritance in order to override a function. And what overriding is, you have a base class when you're in inheritance, and you have a subclass of that base class. The base class has a method, and in the subclass, you have the exact same name as that method with the exact same signature. Same number of parameters, same data type, same order. And what you're doing is you're providing different behavior for that same method in the base class, implementing it in the subclass. And then the way polymorphism works is depending on the type of the instance, the right method will get invoked in the subclass. We'll go through that in more detail when I show you some overriding examples, but it's important to understand overloading versus overriding. If you can think of it, just think of overriding is with inheritance. It happens at runtime. Compile time polymorphism is overloading. It happens at compile time. It has nothing to do with inheritance. Here's an example. We have 3 functions in Kotlin with the name dad. They all have the same name. But what you'll notice is different here is the parameter types. We have the first function that takes 2 parameters of type int, returns an int. The second function takes 2 doubles, returns a double. The third function takes 3 doubles, returns a double. So this is function overloading. Same name, different number of parameters. Okay? And remember that default parameters can reduce overloading. We did that demonstration already where we had default parameters, and you can have one function and you can choose what arguments you want to send. And if you don't send the argument, the default will take in. And that's a way to limit overloading. So let's bring up IntelliJ and look at some of these examples. So here I have my main function in Kotlin. I'm going to create 3 other functions in Kotlin. Those 3 add functions. Let's see if we can make this a little bigger. And just to look at those again, we have an add that takes 2 integers, an add that takes 2 doubles, and an add that takes 3 doubles. And they return different data. Let's try invoking those inside the main function. First, we're going to just call the add method with 2 parameters, 2 arguments I should say. We're going to call it with an integer and an integer. So what should happen is this first add should get called. So when we run this, you'll notice that it did get called because we called it with 2 parameters. If we call it with 2 doubles, it will call the function with 2 doubles. Right, it said in add for double, and it added them up. And if we call it for 3, it will call the third function, the one that takes 3 doubles. It did. So those are the basics of overloading. Now the key here is understanding what constitutes an overloaded method. Right, we said that you have to differ the number of parameters. Well, let's say we changed it to have 2 adds that take 2 integers. All right, and instead we just had it return a double. Do you think this function is going to be considered overloaded? The only thing we changed there was the return type. No, this is not considered overloaded because you have to change the method signature and the return type is not different. So you can't just change the return type in these 2 functions. You have to return the order of the parameters, the type of the parameters, or the number of parameters. We changed the number before. Now we could change this to a double, and then it would compile because we changed the type. Even though we have 2 parameters, we still have 2 parameters, but we have different types. So that's good. Now you can't really, you could also, let's say this was a double. We both have a double, but let's change the order. The order only matters when the only order matters when you have 2 different types. You can't, if you had 2 ints, the order changing would not make it overloaded. But if we change the order, then that again is okay. And actually we should have changed this back to an int. But it didn't matter because we changed the types. So now we build this. We have to return a double because we're adding 2 doubles. We're adding a double, 1 double. So now, if we build this, oh, same thing up here, sorry. Now if we build this, it's okay to have those 2 as overloaded because the order of the parameters is different. And when we run it, it would have different. So it's just a quick rundown of overloading. I didn't want to gloss over it because it is used quite a bit in Kotlin and in Java. Thank you. Hello class. I'd like to demonstrate method overloading or function overloading. Remember that function overloading is when you have the same name of a function, but you have a different number or a different type of parameters. So the first thing I'm going to do is I'm going to create some functions. Let's create some functions and we're going to have the same name. So let's call, say, function, let's say function add, and it's going to take an integer, just I, named parameter. I'm going to have that be of type int, and I'm going to have it return a double. Something like that. And all this function is going to do, it's just going to convert the int to the double. So I'm just going to say return I.toDouble using our conversion function. I'm going to create another function with the same name. So this is going to be an overloaded function. It's going to be add, but it's going to take a different parameter type. It's going to take a Boolean. And so we're going to say Boolean. And this is also going to, this will return a Boolean. And in this case, I'm just going to return the inverse of what I passed it. So if I passed it true, I'm going to return false. So I'm just going to say not B. And again, I'll create another overloaded function called add. This time it's going to take a different number of parameters. It's going to take an int, and it's going to take a double. And it's going to return a double. And all this function is going to do is it's going to return, I'm going to convert the int to a double, calling toDouble, and then I'm just going to add it to y, and I'm also going to add to 1.0 just so that it comes out as a whole number. And then I'll create another overloaded function. Again, same names, but different parameter types. This will also take two arguments, but there'll be a different type. One will be a double, and the other will be a double. And this will also return a double. And this function will just return x plus y plus 3.0 or something. Just something. And so we have four functions here with the same name, but a different number or type of parameters. And you'll notice the return type does not matter. The return type is not going to affect whether or not a function is considered overloaded. So now let's try to call these. First, we'll call it with two parameters. We'll call it with an int and a double. And we'll see which one gets invoked. We'll call it again with another int and a double. And we'll call it, well, let's call the second one just an int. Let's call the third one with, try to execute each function here. This one we'll call just with the Boolean. And then this last one we'll call with two doubles. We'll pass in 10.0 and 30.0. So the first add called, if you want to try to match these up, the first add passed in an int and a double. So this should match this function right here. Second function just passed in an int, so that should match this function. The third one passed in a Boolean, so it should match this one. And the fourth one passed in two doubles, so it should match this one. So if we were to run and execute this, we should see something like that. And we just want to make sure that we put the parentheses after here. Code completion didn't work. And now when we run it, we'll see that the first value is 31. So it should have called the add with the int and the double. Int and the double. So it should have, remember we passed in 10. So it should have said 10.0 plus 20, which is 31. So 31 is right. The next function called 10 with an int, and all that did was convert it to a double, so it printed out 10.0. Third one called add with the Boolean true, and then it just negated it, so it should print out false. It did. And the fourth one called in 10 and 30 doubles, so what it should do is it should say 10.0 plus 30.0, which is 40.0, plus 3.0, which is 43. So a quick demonstration of how method overloading works. It's also referred to as compile time polymorphism. At compile time, all of this stuff gets checked to match the corresponding function with the right parameters and type of parameters. Thank you. Hello and welcome. Let's talk about extension functions. I've been waiting to talk about this concept for quite a long time. I'm really excited to talk about it. It's going to be a lot of fun. And it's a nice feature in Kotlin that other languages don't have. So an extension function is a function that can be called as a member of a class, but is defined outside of it. You might ask yourself, well, why would you ever want to do this? Because there are ways around this. If you're not part of a class, typically what would happen is you would come across a situation where a type that you don't have control over will benefit with an extra function, but you don't have the source code. You know, in some cases, maybe you've always wished that string had a reverse function. Or perhaps the list class had a drop function that would return a copy of a list with the first k elements removed. Something like that. In an object-oriented approach, what you typically would do to solve that is you would subclass either one of those classes and provide your own new functionality, right? Because as opposed to having an extension function, you could just subclass, have your own functions. The issue with that is it's not always possible. Some of the classes that you may want to add new types to may be marked as final, and so you can't subclass, you can't extend it. Also, there are other cases where you just might not have control when the instances are created, and so you can't substitute your subtype for the existing type. It's not always possible in that solution. So then what will happen is, then you'll typically, if you can't do that, you can't subclass, in order to add new functionality to an existing class that you don't have the source code for, then your approach might be to create a function in a separate class that accepts the instance as another argument. Java does this quite a bit. It's quite common in Java to see classes that consist entirely of helper functions for other instances. And a good example of this is the collection classes. The collection classes have dozens of static functions that offer functionality for working with collections. But again, there are issues with this as well. There's really two issues with this. One, code completion won't work in the IDE. So you can't see what function is available. That will slow you down as a programmer. And mainly that's because you write the function name first. Secondly, the other problem is if you have many of these functions and you want to compose them, you end up with code that isn't particularly readable. So the two solutions that you have provided for you that you could utilize to add new functionality to an existing class are not good solutions. So Kotlin came up with this awesome solution of extension functions. And this will allow you to add new functionality to a class even though you have the source code. You can even do it to all the Java APIs. So it's much more convenient and it works much easier and it's much more readable. So this is why you want to use extension functions. Extension functions allow us to add a function to a given class without having to create a new subtype, modify the original type, or wrap the class. Those three solutions are just not good solutions. So an extension function is declared by defining a top-level function as normal. A top-level function, remember, is a function that is not part of a class. That's how you normally do it if you want to do an extension function. You don't have to. You can have an extension function also as a member function. But when you create that function, what you do is, with the intended type prefixed before the function name. So you specify the type. So we'll get to an example, but the type is usually the class name. Kind of looks like a static function, but it's not. So the type of the instance that the function will be used is called the receiver type. These are two common terms that you really need to remember because they use them a lot in the Kotlin documentation. So receiver type, again, that's the instance that the function will be used on. And then you have the extension function. This is the receiver type is said to be extended with. So the type of the instance that the function will be used on is the receiver type. The receiver type is said to be extended with the extension function. And this is how you define an extension function. So you would have something like this. Function string.lastchar. That's the receiver type. String is the receiver type. And then the function that you're adding is lastchar. But you say string dot. So the type is after the fun keyword is the receiver type. Right? Fun is identifying that it's a function. String is the receiver type. And then lastchar is the name of the function, which would be the extension function. And then you have it doesn't take any parameters in this case. You have the colon and it returns a char. And then you're saying it's equal to some, or not some lambda, but some expression. So using the this keyword in this example represents the receiver object, right? And that's really the string who's invoking it, the object that the function was invoked on. So there is a this keyword in Kotlin. You should use it. It's just like Java. I wasn't using it in some previous examples, but you can use it if you like. Sometimes I use it, sometimes I don't. I should get in the habit of using it more. But again, in the example, you see after the equals, you see this.get. And you're probably thinking to yourself, what's this represent? This is the object that the function was invoked on. So that would be the left of the dot when you call dot lastchar. So you can call the lastchar extension function on any string and you're extending this function from the string class because that's the receiver type. You can call the function using the same syntax used for ordinary class members. Under the hood, all that happens is the extension function is a static method that accepts the receiver object as its first argument. So the way this is implemented is static method, first argument is the type, string. Pretty clever. So here is how you would invoke it. You would say println Kotlin, that's the receiver type, dot last char, that's the extension function. So remember those two terms, receiver type, extension function. In the above example, string is the receiver type and Kotlin is the receiver object. Okay, so I said receiver type. In this case, because it's going to be the this keyword and you're invoking it, that could be the receiver object. But the receiver type is in the function definition. Receiver object, you don't use as much because you use the this keyword usually inside there. So you don't really need to refer that, but you do sometimes. So you just added your own method to the string class. The extension function is called last char. Even though string isn't part of your code, you don't have access to the source code for the string class in Java API, you can still extend it with the methods that you need in your project. So wow, this is a big deal. This is super cool. You don't have to go through all this hassle of subclassing the class you want to add the functionality to, or you don't have to do all these other things where you're passing objects around and having utility classes. Very nice feature. So you also have to memorize some rules that are associated with extension functions. In the extension function, you can directly access the methods and properties of the class you're extending, as in the methods defined in the class itself. So you have access to everything in the class that you're extending, the properties and the methods. Unlike methods, the only thing you don't have access to is private and protected members. So unlike methods defined in the class, you don't have access to private or protected members. And the reason for that is because it's defined as static. Remember, under the hood, when you implement, when Kotlin implements this extension function, they're creating a static function with parameters, the receiver type, and then any parameters that are passed. And so a static function is a class variable. You don't have access to instance variables that are private or protected members of the class. You can only access the public variables. When you define an extension function, it doesn't automatically become available across your entire project. You need to import it. Just like any other class or function, right? You can't access string functions. Well, you can access string functions because they're part of java.lang package, and that's implicitly imported in Java. But if you want to access I/O classes, you have to import the Java I/O package. So Kotlin also, in addition, Java doesn't let you do this, but Kotlin also allows you to import individual functions using the same syntax used for classes. If you use Java, usually just import packages. And packages contain many classes. And then if you want to import specific classes in a package, you do that as well. But you're not allowed to import just simple methods of a class. In Kotlin, you can. So here's an example. If we wanted to import just the extension function last char, we would say import strings.lastchar. Remember, lastchar is part of the string class. So you can just say strings.lastchar. And we don't see this syntax in Java because you can't import functions, only classes. And then you would be able to say valc kotlin.lastchar. You can change the name of the class or function you're importing using the as keyword. So this is just another nifty feature. We usually use as for casting, but what can you do if you don't like the name? You can just say import strings.lastchar as last, and then you can use last when you refer to it. And then you would just say valc kotlin.last. Another kind of neat thing. Better naming conventions. Other rules: extension functions cannot override functions declared in a class or interface. So you can't do any overriding. We talked about the difference between overloading and overriding. Overriding is when you have inheritance. And because we're using a class that already has some functions, we can't redefine those functions. So if an extension function is defined with the exact same signature, then the compiler will never invoke the extension function. What happens is the compiler is first going to give preference to all the member functions, all the member methods, and those are going to get executed first. And the reason that it's not going to work where it's going to invoke the extension function that you overrode is because the functions under the hood are defined as static. So you can't actually modify the class as they extend. You don't insert new members into the class. So no overriding. And it makes sense because the way it's implemented is static. It is okay to overload though. Works fine. You can add in a function with the same name but a different method signature, different types of parameters, number, or order. We'd also I want to emphasize that the extension functions are dispatched statically. They are not virtual by receiver type, so no polymorphism, no overriding. This is an important concept because if you don't understand that they're static, you're going to think, yeah, I can override them. You're going to think things work differently. Under the hood, they're static. So here's an example of you're trying to override a function that's already defined in the base class. Right? So you have your class submarine, you have a function called fire, it returns a unit, and it just prints out firing torpedoes. You then provide an extension function. You know it's an extension function because you have the name of the class, which is the receiver type, and then you have dot and then the name of the extended function. Right? And fire is the same as the fire in the base class, in the submarine class. It's got the same number of parameters, the exact same signature, so that's overriding. And what's going to happen here is the compiler is never going to bind to the fire function defined in the submarine class, the extended function. So the extended function is never called. There's no way to disambiguate which function is from what class. Member functions are always going to get precedence. So that's another important rule. Extension functions are usually declared at the top level. We talked about that already. Top level functions have they're not associated with any class. You just say string dot whatever class you're extending, you just provide it there. But you can also put them inside classes as members if you like. And what you usually do this is you'll do it to limit the scope of the extension. So here's an example where you can add a function inside of a class. Right? You have your class definition, my class. You have one function in there called do something, which is an extension function, string dot do something. Right? And then you may want to later invoke that function in another method inside there, and you can just say stir.doSomething on the parameter passed into another add method. Right? But it doesn't really look any different. It's just in the scope of the class, and it can only be used inside of that class when it's private here. Calling extension functions from Java. When calling an extension function in Kotlin from Java, it does not involve creating adapter objects or any other runtime overhead. You call the static method and pass the receiver object instance. That's all you have to do in Java. Because remember, it's a static method and the first parameter is the receiver object. So the name of the Java class containing the method is determined from the name of the file where the function is defined. So what you usually do in Kotlin is you'll create a Kotlin file with the .kt extension and you'll have all of your extension functions in there for, say, the string class. And so in Java, you have to know what the name of the file is in order to invoke it, because that will be the name of the static class. So for example here, if you had that last char method inside of a file called string util kt, you would invoke it in Java this way. Char c equals string uk util kt dot last char. And Java would be able to call your extension function. Which is nice because we want to have this language interoperability, right? We want to be able to call from Java into Kotlin and Kotlin into Java. And this is how you can do it for extension functions. Extension properties. Extension properties provide a way to extend classes with APIs that can be accessed using the property syntax rather than the function syntax. So this is really just a syntactical shortcut type of thing. It's it's really the same thing as an extension function, except it's a property. And so when you access it, you can access it a different way. Properties do not have any state, though, so it's not possible to add extra fields to existing instances of Java objects. It's only used for shorter syntax. That's the only reason you would use this. And so you would do something like this. You would say val string.lastChar, and you'll notice here it's a property because it's string.lastChar, right? And it has a val. It doesn't have a fun. And then you're saying char get equals get. It's an expression. Char get equals get length -1. Right? So you have to add the get method. That's the other thing to be important here. So an extension property looks like a regular property with a receiver type added. The receiver type is string in this case. The getter is required to be defined. Otherwise, it doesn't know how to get the element. So we're defining the property string.lastChar, and then right after that, we're defining a get method. You also can't initialize with extension property, no initializers. And then you would invoke it a little bit easier than invoking extension function, not much, but you would just say kotlin.lastChar, and you wouldn't have to use the empty parameters. So extension functions are really awesome. You're going to see them used all over the place. And in the Kotlin standard library, there's a lot of extension functions in there that you'll invoke to help with, just making your code cleaner and making it better. we'll try to use extension functions in other examples as well. And they're very, very easy. And under the hood, they're just static functions, so they kind of look like static functions when you invoke them because there's no instance. You just identify the type. But man, it's a lot easier than having the subclass. It's a lot easier than having utility functions and all these static methods in the collection class. So again, a pretty nice feature. Thank you. Hello and welcome. In this lecture, I want to talk about Kotlin standard library functions. So just like Java has an API, Kotlin has an API. Kotlin provides a standard library that is meant to augment, not replace the standard Java library. You still have a ton of Java APIs that we're going to use. And remember that Kotlin can call in directly to Java code. So if you want to use Java, you can do that. But there's also a standard Kotlin library that makes things easier when you want to use Java stuff. So it's kind of like wrappers and wrapper classes and things like that. So the Kotlin standard library provides living essentials for everyday work with Kotlin. It's ordered around, there's tons of packages and they're grouped together by what they're doing. So there's packages for high order functions implementing idiomatic patterns. High order functions are the concept of a function that takes another function as a parameter or returns a function. The concept of lambdas, which we're going to get a lot into. But you probably might not have seen that term, but that's what it is. And there are nice standard library calls that use lambdas. There are extension functions in the standard library that provide querying operations for collections and sequences. So a lot of the extension stuff has to do with collections. Collections are a big deal because they store data, and so you want to make them as easily accessible and as easy to use as possible. So the Kotlin standard library has a lot of things with collections. There's a specific package in Kotlin for just collections. There's various utilities for working with strings and char sequences. There's extensions for JDK classes, making it convenient to work with files, input-output, and threading. So it's just improving upon any of Java's inadequacies, making it better. So some examples of some of the packages include Kotlin. Just Kotlin is the biggest package. It has all the core functionality. Kotlin annotation, Kotlin browser, Kotlin collections, Kotlin ranges, Kotlin system. There's a ton of them. There's like 30 or 40. And you have to go through the API and see what they offer. But we utilize a lot of it in the class, and I'm going to give you a description of some of the ones that are more common that do some cool stuff just to show you, give you an idea of what is in there. So the first one I want to talk about is apply. Apply is a Kotlin standard library extension function. It's declared on the any object. The any object is the top level object in Kotlin. It's like the java.lang object. So it can be invoked on any instances of all types. So you can use this apply function on any object in Kotlin. It accepts a lambda. A lambda, again, we haven't talked about, but a lambda is a function literal. It's a block of code that you can pass into other functions. So a lot of what you'll notice with a lot of the standard library extension functions is they take lambdas. And lambdas is a concept that is in Java 8, but it's not in Java 6, and Android uses Java 6. It's one of the reasons why we still use Kotlin. So anyways, it accepts a lambda that is invoked with the receiver being the instance where apply was called on. So the receiver is the instance where apply was called on. We'll give you an example. It returns the original instances. It makes code that needs to initialize an instance more readable. So it really helps with initialization. Here's an example of how you would write some code in Java. You would, and this is Java 8, by the way, this is Kotlin code, but you would, if you didn't use the apply, this is what it would look like in Kotlin. And so I want to show you how it looks a lot better. So val task equals runnable, print lin running. Right, so what that is doing is it's assigning a runnable instance to task, and then what's inside that block is a lambda. So it's passing in print line running to the runnable class. If you know anything about Java, the runnable class is a way to do threading. And so what you have to do in the runnable class is you have to implement the run method, and then you have to start. Actually, the runnable is an interface. You implement the runnable interface by implementing the run method, and inside the run method is what the thread is going to do. So what this is doing that doesn't seem maybe very clear is it's creating an instance of runnable and then implementing the run method with println running. So the first thing we did was we're starting to create a thread. And then our next variable declaration here is a thread, and we're creating a thread from our task. Again, this is Java convention. If you want to create a thread, there's two ways to create a thread in Java. You either extend the thread class or you implement the runnable interface. If you implement the runnable interface, you then have to create a thread instance from the runnable interface. And that's what the first two lines are doing. The first line is creating a runnable instance that implements the run method. It's then passing that into a thread object, which is named task. Then the third one, it's calling the set daemon. It's calling some methods on the thread. Set daemon, and then it's calling start. When it calls start, it starts the run method. But if you look at this code is doing like 4 separate things. It's really initializing an object. It's initializing a thread by implementing the runnable, then calling set daemon, set start. You can use the apply, and it's a lot easier. So you can create your task, which has your runnable instance and your implementation of your run method in that Lambda. And then all you have to do is you say thread, you pass in task, and then you call apply. And when you call apply, you can pass in any methods that you want to invoke to initialize inside that Lambda. And then after those methods are invoked, you can call start on the thread. So you have 2 lines of code here that's doing 4 lines of code in without using the apply. And so the apply can have a Lambda that invokes functions to do initialization. So it's a nice helper function that just makes code more readable, quicker. There's a let function in the standard library. This makes it easier to deal with a nullable argument that should be passed to a function that expects a non-null parameter. So here's a function called send email to, and it takes an email type string. What you'll notice here is it can't be null. We know it can't be null because there's no question mark after the type. If we allowed nullable instances to come to this function, we'd have a question mark. It doesn't matter what the function's actually doing, so the block is just some comments. You can't pass a value of a nullable type to this function. There's no question mark. You have to check explicitly whether this value isn't null if you want to invoke this function. And we talked about nullables. We know that this is one of the rules of nullables, right? Nullable types are not allowed to invoke any functions. And the only way you can invoke nullable types on a function is if you check whether or not it's null before you invoke it. The compiler will remember that you checked, and it will allow you to invoke the function. So that's the exact same thing you'd have to do here if you want to invoke the send email to. You'd have to first check if the parameter you're passing in is null. So you'd have to say if email is not equal to null, send email to email. Right? And that's kind of cumbersome. Using the let function and calling it with a safe call is a better option. The let function will turn the object on, which it's called into a parameter of the Lambda. So the let function will be called only if the email value is non-null. So you use the email as a non-null argument of the Lambda. All right, so you would do something like this. You would use the email with the question mark. This is not the Elvis operator. This is the question mark. It's saying it's null, right? Or it could be null, I should say. And then it's saying .let. And it's only doing the .let inside the Lambda if email is not null. So instead of having to do a check, and remember the Elvis operator only gets operated on the right hand side if something is null. This is kind of the opposite. It's saying if it's not null, then do this. If email's not null, then call email send to email. Email to. Kind of like the opposite of the Elvis operator. The with standard library function allows you to call multiple methods on the same object without repeating the reference to the object. So here's an example of where you're calling a ton of functions on an object. Right? We look at this function called alphabet. It takes no parameters. It returns a string. It in the body of the function, it is has a val result equal to string builder. So it's initializing a variable called result. That's the object. And then it's calling append on that object in a for loop. Then it's calling append again when it gets out of there, and then it also calls toString. So you have an object here that's calling methods on that object in the for, depending on the for loop, many, many times. But at a minimum, 3 times. Well, at a minimum, 2 times really, but if it's not a letter in A through Z. So if you use the with function, you can avoid making all these calls on the instance, right? And repeating the name in each call. So what you can do is, you can do something like this. You can say fun alphabet, and then you can say equals, and you can use with, and then you can pass in the first instance here would be the string builder, right? Because that's what you're initializing in your first example here, right? If we go back, first thing we did was val result equals string builder. So that's the first thing you pass into with is the string builder. And then in the lambda, everything after that, you can just use, this is not a lambda by the way, but everything after inside the function, you can just say append. You don't have to use the instance name. In fact, there's no instance inside here. It's automatically using the instance from the string builder. But you don't have to call with the instance. You can say append letter, append, and then toString. So it's less code, more efficient, right? One of Kotlin's big objectives, less code, clean code, concise, expressive. So the with structure looks like a special construct, but it's a function that takes two arguments, a string builder in this case, and a lambda. The lambda argument here is, I mentioned earlier that it was a lambda, and I didn't think it was, but it is a lambda because of the brackets. I was thinking those brackets corresponded to the function because I didn't see the equals. But with the equals, this is a lambda expression that's assigned to the function, alphabet. I should have probably formatted this a little bit better. But the way we know it's lambda is we have those brackets, right? And we have the brackets after the equals. So you're calling with, and remember lambdas, they have the name, and then you either infer the type or not the infer the type. In this case, we're inferring the type because the string builder takes a string. So we don't have to specify the string builder as a string, and that's the first parameter. And then if you only have one block in a lambda, you don't have to put it inside the parentheses of the with. There's all these rules for lambdas. I'm just trying to give you a heads up on it. But the way we know this is lambda, you have the equals, and then you have with, and so when you have the equals, it's just not part of the function. You're creating a function literal that's assigned to a function. So you have with, and then the rule of lambdas is if the first parameter can be inferred from the argument that you're passing to, you don't have to specify the type. And that's why there's no type here. You're just saying string builder. And if you have in your lambda, if the block inside the lambda is the only block, then you don't have to include it inside the parentheses with the with. And I mean, initially you look at this and it looks like a function because you see the left and the right hand brackets after the alphabet, and that's the mistake I made. But when you see the equals and you see with, and then you can know all the lambda rules, then it makes more sense. So anyways, not to bore you too much with lambdas, we're going to talk about lambdas in great detail, and it'll become much more clear. This function now only returns an expression, and that you know that from the equals. It's returning it's invoking a lambda expression, but it's returning expression. Expression is just something that returns a value. It creates a new instance of string builder and passes it directly as an argument, and then references it without the explicit lambda, which is what I said. So there you go. There are a little introduction to the standard Kotlin library. We're going to talk about a few more functions in there. These are some useful ones. We'll talk about some other important functions like run, lazy, use, repeat, and so forth. Thank you. Hello, let's continue our discussion on standard library functions from Kotlin. Specifically, we'll talk about the run, lazy, and use functions. Run is an extension function that combines the use cases of with and let. We talked about with and let previously. With can help you reduce duplication when you're having an instance that is calling many different methods of the class. You can use a lambda and you don't have to provide the instance all the time. Let is very useful when you're trying to call something that a non-nullable type in a function with something that could be null, a nullable type. And you can use let. Let's kind of like the opposite of Elvis operator. You can put that over there, and if it is not null, it will do something. Right? With the Elvis operator, if it is null, it will do something as well. It's kind of the opposite. So a closure is passed to a run, which has the instance as the receiver. We haven't talked about closures, but closures are the variable data that you can access outside of a lambda. And so a lambda is usually it's a block of code that you can pass to functions. So it's a function inside of a function, and with a lambda you have access to all the variables outside of it, the outer function. So a closure is passed to a run, which has the instance as the receiver. The return value of the closure is used as the return value of the run itself. So here's an example where we have a value, a variable val that is read-only. It has an output path. It's equal to paths.get, and then you're calling on this string paths.get, you're calling .run. And inside run, you're saying val path equals resolve, path.toFile.create new file, and then path. So it's using this non-null types with the let and with the with, and allows you to execute some more code. So the closure is passed to run, which has the instance as the receiver. So the instance here would be paths. And so path ends up being the receiver object, and then the return value of the closure is used as the return value of the run itself. So the key difference between the let and the run is that with the run, the receiver is the instance, whereas in the let, the argument to the closure is the instance. All right, and that's what we did with the let. We checked if it was, we had a nullable type, and then we called let on it, and if it wasn't null, it would invoke something. Right, so it was the argument to the closure. Lazy is another useful function that wraps an expensive function call to be invoked first when required. It's kind of, you can think of lazy evaluation. It's the same concept. If you're calling a function over and over and over again, you only want to call it that first time and then use the same instance or never call it again until you need it. So here's a function called readString from database, and it returns a string. It's equal to some expensive operation. It's something that's doing a ton of stuff. You have val lazy string, and you call lazy, and you pass in that expression, readString from database. And so what will happen is the first time you require the result, you can access the value of the lazy reference. Only then will the wrapped function actually be invoked. So it takes a while for that to be invoked. You only invoke it when you need it, just like a lazy evaluation. So if it's an expensive operation, you don't do it when you don't need to. So val string equals lazy string.value would be when you invoke it. So you're storing it doesn't get invoked in the top when you put it in lazy string. You're not invoking it. You're only invoking it when you want to use it. So this is a common pattern seen in many languages and frameworks. The advantage of using this built-in function over rolling your own is that synchronization is taken care of for you. So you don't have to worry about threading. You don't have to worry about race conditions. If the value is requested twice, Kotlin will safely handle any race conditions by only executing the underlying function once. Use is similar to the try with resources statement that exists in Java 7. It's defined as an extension on an instance of closable and accepts a function literal that operates on this closable, a lambda. So you can safely invoke the function closing down the resource after the function has completed, whether an exception was raised or not. So try with resources, you kind of think of the finally clause, but the finally clause will get invoked when you have an exception, and this will get invoked regardless if you have an exception or not. And so you can say val input files.newInput stream paths.get input.text, and then you can say input.use input read. And so it's going to safely invoke the function whether the exception was raised or not. Right? It's only going to use that resource, cleaning up the resource. So use is a more concise way of handling resources in simple cases without needing a try catch finally block. You don't have to have the finally to clean up sources. You can just use, and use will clean up the sources when the read is done. Again, just a taste of some of the standard library functions in Kotlin. Thank you. Hello, in this lecture I want to talk about some more standard library functions, mainly the repeat, require, assert, and check. So repeat. As the name implies, repeat accepts a function literal and an integer k. This is one of the easiest standard library functions to use. The function literal, you want to think of a function literal as a lambda. It's a term that's used interchangeably. Some of the Kotlin documentation uses both terms, but it's a lambda. So the lambda will be invoked a number of times. It's a very simple function to avoid needing a for block for simple operations. Obviously, if you want to repeat code, you can use a for loop, you can use a while loop, but you don't always have to, and it's easier to do it this way in simple operations. So it's really easy. You just say repeat 10, println hello. Println, printline, however you want to pronounce it. So very simple, one of the easiest ones you'll use. It will print hello 10 times. Require, assert, and check. All these three functions are similar. They're kind of grouped together because they do formal specifications in your program. So Kotlin provides a triad of functions to enable us to add a limited amount of formal specifications to our program. Formal specification is an assertion that should always hold true or false at the location when the assertion is executed. Also referred to as contracts or designed by contract. So require throws an exception, and it is used to ensure that arguments match the input conditions. This is the way you can do input validation. Assert throws an assert exception, and it is used to ensure that our internal state is consistent. And this is kind of like an assert that you would use in C. You put the assert somewhere in your code, and you would say, basically, at this point in my code, this better be true. And if it's not true, take off. So you could assert that an object is not null. You could assert that a value is a given value. But it doesn't have to do with parameters. It just can be placed anywhere in your code. And then the check throws an illegal state exception, and it is also used for internal state consistency. So if your member variables are incorrect or something like that, you can say a check on that. Very similar to the assert. So the key difference between these functions is the type of execution that is raised. Right? Require usually used for input validation for parameters. Assert and check almost the exact same thing, except they throw different exceptions. And the exception is important. A legal state exception versus an assert exception. It can help you debug further. So you still want to make sure you use the right one given the situation. Check is more to do with member variables. Assert has to do more with just other things besides member variables. Assert can be disabled at runtime, but require and check cannot be disabled. So all that means is if you disable it, you basically ignore it, then even in your code, if you say assert, nothing's going to happen, no exception's going to be thrown. But for require and check, you can't disable those. So here's an example of require. You have a function called neverEmpty. It takes a string, and you're requiring that the string.length is greater than 0. Standard input validation. If you pass in a string that's empty string, then you're going to print out some string that should not be empty. So this require function takes a function literal as a second parameter, and it will return that as an expression from this function. And then it won't return it as from this function because it will print it out, and then this will return the unit type implicitly declared here. We always ensure we have not passed an empty string. That's the whole point of this function, input validation. The function literal that is passed as a message to the function is lazily evaluated. Lazy evaluation means it doesn't get evaluated unless it needs to. Okay? And so string should not be empty, will never get assigned if string.length is greater than 0. It only gets assigned if string.length is less than 0. Right, so it's requiring that string.length is greater than 0. It won't be invoked if the condition holds true, if string length is greater than 0. So these ones are a little bit easier, a little more intuitive to use, mainly for validation type stuff. You want to make sure your program's in a correct state, or you want to make sure parameters have the right values when passed in. Nice functions. Thank you. Hello everyone. Let's talk about operator overloading. Overloading is this concept about how you can have the same name for a function, but it differs in either parameters, number of parameters, or the type of parameters. It doesn't matter whether or not you have a different return type. And so an operator, we know what an operator is. There's many operators in Kotlin. There's the plus, the minus. We went through all the unary operators, the arithmetic operators, the logical operators. We can actually provide a different meaning for those operators by overloading them, and that's what operator overloading is. But to provide a formal definition, the ability to define functions or classes that use operators is called operator overloading, providing a different meaning for an operator. You can use the plus or the minus with primitive types and string values, but these operations would be useful for classes and functions as well. And we do provide those. So even though Kotlin, I've said before that Kotlin doesn't have primitive types because they're objects. When you think of primitive types, you don't think objects. A lot of the terminology used in the language refers to them as primitive types, but technically they're objects. So that's why you see this. Sometimes you see this term. So some programming languages allow no operator overloading, like Java, and some allow all the operators to be overloaded. Java allows no operator overloading, if I could speak. Scala allows every operator to be overloaded. So there's one drastic of none and another drastic of all. Kotlin kind of lies in the middle. It tries to do both. So allowing no operator overloading means developers will not be able to abuse operators to create obtuse function names. When a function or a language allows all the operators to be overloaded, it can be abused. Just like any language can be abused, but this one can cause problems. So you kind of want to come into the middle here. Allowing many kinds of operators to be used would mean that powerful domain-specific languages could be created for specific problems, which is a good thing. So you have to kind of think of when you want to use these, whether or not you want to use them all the time or just in the meantime. But like I said, Kotlin provides a kind of a middle ground. So overloaded operators in Kotlin designers opted to sit somewhere in the middle and allow operator overloading in a fixed and controlled manner. Defining and using overload operators in Kotlin is simpler because you can't define your own operators. You can only overload the existing ones. And because Kotlin has a limited set of operators that you can overload, each one corresponds to the name of the function needed to define your class. So if you remember way back in the lecture and we talked about operators, there's always a corresponding method for each operator. And if you want to overload it, all you have to do is overload that corresponding method. Again, I'm using method and function interchangeably here. Arbitrary combinations are forbidden. The ability to swap the left and right sides of an operator, you cannot do. So you can't all of a sudden change that behavior. You can only change the behavior of the meaning, not the arguments. To create such a function, the function must be prefixed with the operator keyword and defined using the equivalent name of the operator. So that you can immediately identify an overloaded operator if you see the operator keyword. Operators can only be defined as member functions or extension functions. So they have to be part of a class or they have to be an extension function. So for example, if your class defines a special method named plus, then by convention you can use the plus operator on instances of this class because you overloaded it. And this is kind of referred to as a convention kind of concept. Kotlin uses the principle of conventions instead of relying on types as Java does, because this allows Kotlin to adapt existing Java classes to the requirements of the Kotlin language feature. So because of interoperability, which is a big goal of Kotlin, it wants to work well with Java. It follows this principle of conventions. It doesn't rely on types. Okay? So if you're working with numbers through the big integer class, it's more elegant to sum them up using plus as opposed to calling the add method. It's also easier to read. I mean, it's just more intuitive. To add an element to a collection, you also may want to use the plus equals operator. So these are some cases where you'd want to overload operators. It makes the language cleaner. When you define an operator, you don't need to use the same types for the two operands. Remember, the operand are really the arguments to the operator. If the operator is infix, it means the operand is on the left and the right-hand side. As mentioned earlier, if you want users to be able to write 1.5 times p in addition to p times 1.5, you need to define a separate operator for that. You can't change the arguments in an operator overload. The return type of an operator function can also be different from either of the operand types, which makes sense. I mean, if you were to do a logical operator or something, you might not return true. You may be just doing something else. Same with or a comparison operator. Comparing an operator requires you to use strings maybe or something or objects, but you can return numbers to say 0 is equal, 1 is greater than 1 is less than, or alphabetical order less than, and so forth. So here's an example of a class. You have class my class, and this class is taking quite a bit of parameters, 4, and then you have an operator function. You immediately know that it's overloaded because you see the operator keyword. And what you're overloading here is you're overloading the corresponding method of the operator. So remember that the plus operator has a plus method, and all you have to do is override that. So operator fun plus, I said the term override, that's why I paused, and you really are overriding it, overloading it by taking 2 of them, but really. So operator fun plus takes a class, and it returns a class, and all it does is create a new class of a plus my class.a, b plus my class.c, and so forth. And so in the above, a function called plus is defined. This will implement addition to the class. That's what it's doing. So notice how this function is marked with the operator keyword before the fun keyword. That tells you that it's overloaded. All functions used to overload operators need to be marked with that keyword. It makes it explicit that you intend to use the function as an implementation of the corresponding convention and that you didn't define a function that accidentally had a matching name. You immediately know what your intention is. You're trying to overload an existing operator. Also, the parameters must be marked with val to be used inside member functions. This is a concept related to classes. If you want to have member variables inside of a member function, they have to be val. Another example, you can invoke the class the following ways, or the same example. You can say val my m1 equals my class to create an instance, and then you can call and create another instance you want to add to. So val m2 equals my class, another class, and then you can just say m1 plus m2. You don't have to. You could say m1 dot plus m2 as well, but you overloaded the plus operator, so you can now add those 2 classes, and it returns another class and stores that in m3. So this example demonstrates how easy it is to use operator overloading. You just use the operator keyword and you specify the corresponding function from the operator. And they're really named very nicely, so it's easy to remember them. The function can also be invoked in a regular dot style if required, but it uses the actual function name rather than the operator symbol. So if you use the dot, you have to call it by plus. Operator functions are not limited to acting on the same type as the class they are defined in. We could have defined a list class to which we could use elements using the plus operator and removing elements using the minus operator. So in the example here, all this is saying is they're not limited to the acting on the same type as the class. So in the example here, if we go back, you'll notice that my class is just using member variables from the same class. You don't have to do that. This was just the example. You can have a class that operates on a list. The list has nothing to do with that class. So that's what that's saying. And as an alternative to declaring the operator as a member, you can define the operator as an extension function as well. And so this is the basics of operator overloading. The big takeaway from this lecture is the operator keyword and then also the corresponding method name. That's what you have to provide in your class. So a lot of fun. It doesn't abuse it. You can't change the order of the operands and all that. A nice handy thing that Java does not include. Java does not allow any operator overloading. Thank you. Hello and welcome. Let's continue our discussion on overloading operators by talking about overloading the compound assignment and unary operators. We know what a compound assignment operator is. It's the plus equals, minus equals, and so on. We know a unary operator is a single operator. So operators such as the plus equals, minus equals, and so on are called compound assignment operators. They'll do a plus and an assignment. That's why they're called compound assignment. So when you define an operator such as plus, Kotlin supports not only the plus operation, but the plus equals as well. So same as writing my class equals my class plus my class. All right, we're overloading operators for classes, so that's the equivalent of doing a plus equals. In some cases, it makes sense to define the plus equals operation that would modify an object referenced by the variable in which it's used, but not reassign the reference. So there are some cases where you wouldn't want to use the existing plus operation, right? Because normally you do plus equals. It also does the same thing with plus. You don't have to do any additional overloading. However, you may want to reassign the reference. In that case, you would want to override the plus equals specifically. So if you define a function named plus assign, which is the mapping of the plus equals, right? In order to overload operators, we know that we have to find the mapping function in Kotlin. And so if we wanted to overload plus equals, we'd have to overload the plus assign. Plus assign with the unit return type, unit is void, Kotlin will call it with the plus equal operator is used. Right, so you would overload the plus assign with the unit return type, and Kotlin will call it with the plus equal operator. When you write plus equals in your code, theoretically both the plus and the plus assign functions can be called. We know that, right? We know that normally if you don't provide the plus assign, it just calls the plus. But in theory, both can get called if you write plus equals. So if you define both and use it this way, then the compiler reports an error. It would get confused because there's two functions that would need to be called, and you can't have both. It'd be ambiguous. So you can resolve this by just calling the function name. If you do have a case where you need to override the plus equals and not use the plus, your best bet is to use the plus assign function call. It's best to design new classes consistently. Try not to add both the plus and the plus assign overloaded operators at the same time. That's really what you need to do. Use the plus overloaded method as much as you can, and then you can use plus equals. That's what you want to focus on. If you really need to overload the plus equals and have a plus equals plus assign function in your class, then you have to call it with plus assign. Because if you try to call it the other way, the compiler is going to give you an error. Unary operators. This is where we have a single operator. The procedure for overloading a unary operator is the same as overloading arithmetic operators. You add a function, member or extension, with a predefined name. You mark it with the modifier operator. So not much different here for unary. Functions used to overload unary operators don't take any arguments, obviously, because they're a unary operator. When you define the inc and dec functions to overload increment and decrement operators, the compiler automatically supports the same semantics for pre and post increment operators as for the regular number types. So that's pretty nice. It automatically supports it if you override inc and dec, increment and decrement. So let's go to IntelliJ and see how we can implement this. First, let's do the compound assignment. And so we're going to create a class called point. It's a data class. It has getters and setters, and it has everything else, has the equals and all that. But you'll notice some similarities here with other overloading operators. You have the operator keyword. Our class point takes two parameters for its constructor, x and y of type int. We have an operator member function in here called plus. We're overloading it, I should say. And plus takes another point, and it returns a point. And all it does is do x plus other, y plus other. So that's pretty simple as far as operator overloading goes. Let's try to use it and see what it gets returned. So let's create a variable called point. This is a point that has 1 and 2 for x values. And now let's try adding to it. So let's try doing a plus equals on that. So remember that it's going to call the plus, right? That's the main point. You don't have to actually implement the plus assign because it's going to call the plus. And that's what this is going to demonstrate. So if we try to print out this point, you're going to see that 1 is plus 3 and 2 plus 4. So x and y is going to be equal to, 4 and 6. I'm going to do my addition. 1 and 3 and 2 and 4. And I don't want to do that point. I want to do a print, sorry. And we should be able to do a print because the toString method is overridden from the any class. Let's run this. And what you see is x equals 4, y equals 6. All right, so we didn't override the plus assign, but it got invoked anyways when we used the plus equal. So that's pretty cool. Now, if we just did the plus assign, it would still work. You'd have to return a unit, though. You can't return a point. But you can play around with this and see how it works. You can't define both. The compiler will give an error. But this is how you can do the compound assignment. Let's try a unary example. Unary is pretty easy as well because it just takes one parameter. We don't even have to have it as a data class. So we can just have a unary minus, and let's put it inside here. So here we can have unary minus. We know it's overloaded because we have the operator keyword. We're doing point.unary minus. We don't really need the point because it should use this keyword. And it returns a point, and it just will negate things. So now if we try to use this, say var point equals 0.12, and then we try to negate it. We don't need to add it, but we just try to do a minus on it. You'll see that it prints out negative values, -1 and -2. So it negates it. So those are some examples of how you can overload both compound operators and unary operators. Thank you. Hello everyone. Let's talk about comparison operator overloading, overloading the comparison operators. So just as with the arithmetic operators, Kotlin lets you use comparison operators. Comparison operators are like equals, equals, not equals, greater than, less than, and so on. You can use this with any object. So you can use the arithmetic operators with any object. The same goes for the comparison operators. Instead of calling equals or compare to, as in Java, you use the comparison operators directly, which is intuitive and concise. So in Java, if you want to compare two objects, you have to implement the comparable interface and then override the compare to method. And then in order to use that overridden method, you call equals on something. You say this object equals this object. What will happen is it will invoke the compare to method, and the compare to method will return either a 0, 1, or a negative value. And that will tell you whether or not the object is greater than, less than, or equal than. What you usually do in the compare to method that you implemented in that class is you will compare some member variables. If one member variable is less than the other, then you say the operator invoking it is less than. So there's some kind of behavior there. But it's kind of confusing. You have to call the equals method whenever you want to do this. You can't use it with operators, the comparison operators. So Kotlin, you can use the comparison operators, which is nice. The equals equal operator in Kotlin is translated into a call of the equals method. So the reason you can't use it in Java, you have to use the equals method because there's no translation. In Kotlin, it maps the equals equals operator, in which essentially invokes the equals method. So you're going to need to implement in Kotlin just like you would in Java. You'd have to implement the comparable interface, and that's what we're going to go through here. So using the not equal operator is also translated into a call of equals, with the obvious difference that the result is inverted. So Kotlin provides this features for these two operators. Unlike all other operators, equals equals and not equals can be used with nullable operands because you can compare null. So those operators can check for equality for null under the hood. For a data class, the implementation of the equals is automatically generated by the compiler. A data class in Kotlin will generate all the sets and gets. It's really, really small. If you remember way back when we talked about the advantages of Kotlin, we showed you how much less code Kotlin can have with a data class. Data class is one of the best examples to show you how concise and expressive Kotlin is. And just like the other methods that get generated, the equals method will automatically generate as well. So for a data class, you can use the comparison operators quite easy. You may want to override them, though, to provide your own meaning. Overload. Sometimes I say overriding and overloading interchangeably. It's important to know that they're two different concepts. Overloading has to do with the same name of a function with different parameters or different number of parameters, and then the return type is the same, but they're in the same class. Overriding, it has to do with inheritance. When you have the same name of a function in the subclass that has the same name as the function in the base class, and you provide different behavior. So I apologize for that. I need to be careful with using those two terms. The identity equals operator, this is the equals, does exactly the same thing as the equals operator in Java. We talked about this when we talked about operators, but it's important to clarify. Remember in Java, if you want to compare the references of two objects, use equals. If you want to compare the contents of an object, use dot equals. And then dot equals will call the compare2 method in the implementing the comparable interface in your class. Right? So those are the differences. And equals in Kotlin is comparing references. So it checks that both of its class arguments reference the same object. That's what the equals does. Or have the same value. That's what the equals does in Kotlin. Using this operator is a common optimization when overloading equals. The equals operator cannot be overloaded. So what that's going to do is equals, it's an optimization for overloading the equals. Right? So when you call equals, it will call the equals that you overloaded. The equals function is marked as an override because unlike any other conventions, the method implementing is defined in the any class. Equality comparison is supported for all objects in Kotlin. This is the same as Java. The Java object class, you can override all the equals method, as well as like the hash code and other methods. Every class has an equals method or supports the equals function. That's why you override it. Again, you typically implementing the comparable interface with a compare2. By calling equals, it will call that method. But if you didn't implement the comparable interface and didn't have the compare2 method in a class, you could still call equals on that object because it's defined in the any class, or in Java, the object class. It just won't really return anything meaningful. You do not need to mark it with the operator keyword. So before, every other operator that we overloaded, we had to mark with the operator keyword. That's how we knew it was overloaded. This is an exception. When you overload the equals, to use the comparison operators, you don't have to mark it with operator. So the base method in any is marked as such, and the operator modifier on a method applies also to all methods that implement or override it. And that's the reason why you don't have to provide it. In the any class, it does have the operator keyword. And so when you override it, you don't have to provide that operator keyword. Just like if you were to override a function that had a default parameter, you wouldn't override that default parameter. Compare2. In Java, classes can implement the comparable interface in order to be used in algorithms that compare values. This is what will be invoked. The compare2 method will be invoked when you call equals. So the compare2 method defined in that interface is used to determine whether one object is larger than the other, or smaller, or whatever. I think it says larger because depending what you return, it will tell you whether it's larger. The limitation in Java is that there's no shorthand syntax for calling this method. You have to call it with equals, dot equals. Object1 dot equals object2. Only values of primitive types can be paired using less than, greater than, and all the other comparison operators. Right? That's the only thing you can do in Java. If you want to use the comparison operators, you have to use them on primitive types. All other types require you to explicitly call the compare2 or the equals. So in Kotlin, it supports the same comparable interface, the same compare2 method you can override. In Kotlin, you use the comparison operators on objects. They are translated into calls of compare2 or equals. So that's how you can use the comparison operators in Kotlin, and you can't use them in Java, because in Kotlin, the comparison operators are mapped to the compare2 method. The return type of compare2 has to be an int. I think it goes with, if it's 0, it's equal. Less than 1, it's smaller. Greater than 1, it's larger, or something like that. Instead of comparing all member variables in this function, you can use the compare values by function from the Kotlin standard. So one of the things in Java when you did in the equals method to figure out if two objects were equal is you would look at the member variables of each object. If one member variable was bigger, you would provide meaning to that, whatever you thought was valuable concerning your member variables. In Kotlin, you don't have to do that. You can use a compare values by function, which makes it much easier. It's much more concise. So compare values by receives a list of callbacks that calculates values to be compared. What it does is it's really comparing the member values. The function calls each callback in order for both objects and compares the return values. So I want to give you, at this point, I'd like to show you how that works in IntelliJ. So first, let's just define a class, and let's just simply overload the equals method. So here's a class called point, and let me just format it correctly so it's easier to read. Should have my auto formatting turned on in Kotlin. But here we have an object called class, which is point. It has two variables, x and y, of type int, and it returns a unit. It looks like, oh, well, actually, the equals method is returning something. The class doesn't return anything. Functions return data. Here we have the override keyword. We have fun. We have equals. So here we're overriding equals. It takes a parameter called object. It can be the any type and it can be nullable, and it returns a Boolean. And this is where we're going to compare some member variables. Right? We haven't used the nice compare values by function yet. I'm just showing you a standard example. And what we're saying is if the object equals this is the instance that's being invoked. It returns true. If the object is not a point, remember is operator is the same as instance of in Java, it returns false. If neither of these are true, it returns object.x equals x and object.y equals y, whatever that may be. So let's try to use this class. So let's add our main function, which gets invoked. And inside our main, we're going to just create a couple points and call the equals operator on them. And you'll notice also in the equals method that's overridden, we use equals. We're comparing object references in that case. First, that's the first thing we're doing. So in our main function, we're going to say print line. We're going to create a new point, 1020, and we're going to say, is it equal to point 1020? And we're going to print out the result of that. So when we say point 1020 equals, it's going to invoke that equals method because it's overridden. So let's run this. And when this runs, it's returning true. So that would mean that it either evaluated to this or it evaluated to this. Right? Well, object equals this. It's only going to be the same if the points are pointing to the same thing. Right? So we could see, and in this case, we're creating two instances. They have the same values, so it did revert to it did resolve to this. Right? Because it's not going to create two separate memory locations for points that have the same data, unless you would explicitly do that in a class. But here it's actually going to evaluate to this. If we change this value, it's going to return false because it's going to end up doing this one at the bottom. If the object isn't a point at all, it would return false as well. But when you run this, it's going to return false because y and x and y are not the same. Now, if we didn't create a point and we just said, well, I don't know how to actually create that, but the other instance would be as if the object is not even a point. Let me also show you how we can use the, let me give you another. We could pass a null. That's what we could do to test that. Let me show you another one using the not equals. Here we're going to create a point 10 and 20, and we're going to say if it's not equal to point 5 and 5. Right? And this will also return true because it does the inversion. It's not equal, and it returns true because we use the not equals there. Still calls the same function, equals, but it inverts the return value. So it would actually say that go to here and say it's false, but then it would turn the false into true because we use this. The last one is we could try passing in the null because it does allow a nullable type. We could say if null is equal to 0.12. And when we run this, we see it's equal to false because it will evaluate to this because the object is not equal to a point. So that's a basic example of how we can override the equals. Let me show you how we can override the equals but use the compare values by. And I don't want to use the point class for the compare values by because it doesn't make much sense. So let's create a person class. And let's have this person class implement the comparable interface. So let's get this format correct. A little more readable. So here we have a person class. It has a constructor that takes a string first name and a string last name, and it implements the comparable interface of a person. So when we implement the comparable interface, we have to override the compare_to method. That's what we're doing here. Now, if we didn't implement the comparable interface, we could just override the equals method. So we implement the compare_to, we override it, and it takes another person object and it returns an integer. That's the difference with the comparable. It returns 0 for equal, and again, I can't always remember it, but I think greater than 1, less than, and so forth. But here we're using this compare values by, and we're passing in this and other. This is the object that's getting invoked, the current class. Other is the one on the right-hand side of the equals. And then we're passing in person last name and person first name. So what this is going to do is it's going to compare last name to person, this last name to other last name, this first name to other first name. But this notation is really cool to use because you don't have to do every single comparison. If you had like 10 member variables, it'd be even better. So now let's try to use this, and let's try to do some more print. So in our main method, let's create a couple instances and print them out. Or create a couple instances and then compare them. So create two variables, objects P1 and P2, person Al Smith and person Bob Johnson, first and last names. Now let's call the print on it using a comparison operator, and we'll see that println P1 is less than P2. And so let's go ahead and run this, and it's going to return false because P1 is not less than P2. So one way to see if these are two equals, I created two objects with the same names. We could call the compare_to method and print out the value here. So person Al Smith, we have two instances of the same in this case. Or we could just say P1.compare_to P2. And remember, the compare_to method returns an integer. So if we invoke it completely, it says 0, which means they're equal. This is just clear on what's happening here. That's why I provided this. If I change this to B and ran it, it is 1. And if I were to change it to P2 to P1, you would see it returns less than 1. So a -1. And that's how the compare_to works. It returns an integer here. We use the compare_to here because compare_to, as I mentioned, returns a value. We wouldn't be able to use the less than or greater than there because compare_to is never going to return true or false. It's always going to return false. So to illustrate this, and the reason that earlier one was coming up false next, the way that the compare values works is it will make a callback for each member variable that you pass in. So if first name, this dot first name is equal to other dot first name, it will go to the next one. If this dot first name is less than other dot first name, it will return, and it won't even evaluate the last name. So let's just play around with this. I want to show you how this works. So let's say if P1 is greater than P2. And again, what this is going to do is it's going to first compare the first names of both. If it's equal, it will compare the last name. If those are both equal, it's just going to return false. So the only way to see if it's actually equal, you'd have to invoke compare_to and check for 0. If we want to use less than or greater than, what we can do is if P1 is going to be greater than P2, then we would have to change this. If we wanted this to evaluate to true, we'd have to change it to AZ. And so it's going to compare P1, AZ is greater than AL. So when we run this, it will return true. Right? If we changed AZ to be B, it's going to return false. It's only going to compare the last names if these two are equal. So if we change this to Alice and leave it as Smith, it's going to return 0. But if we change Smith to be P1 greater, if we change to Z, it's going to return true. And it does. And if we changed it to SA, which is greater than SM, it's going to return false. I just wanted to further clarify how this works because I think I did a bad job earlier. So this is what's happening, and that's why you can't use equals equals, because it doesn't return, it just returns true or false. If you want to see if they're equal, you'd have to call compare to directly. Thanks. So this is just some simple examples of how we can overload the comparison operator. I hope you found this helpful. Thank you. Hello everyone. An important lecture right here, Lambda Expressions. This is one of the most important concepts in Kotlin. So please pay attention and let's follow some examples. But it's a big important concept that's used all over the place. In order to use Kotlin, you really have to understand Lambda Expressions, at least to use it to its benefits. So Lambda Expressions are small chunks of code that can be passed to other functions or assigned to a variable. When they're passed to functions or returned from functions, they're called higher order functions. We have a whole separate lecture on higher order functions. In this lecture, I just want to focus on simple Lambda expressions that are assigned to a variable or that are invoked. So the big advantage of Lambda expressions is they allow for easily extracting common code structures into library functions. Right, you can have blocks of code and you can assign them to variables. They return values, they're an expression, and you then can use them. So Kotlin uses Lambda expressions a ton when working with collections. You see it all over the place. A lot of the functions in the standard library are going to take Lambda expressions. So you need to understand this concept. Again, at the very lowest level, they're just a block of code inside brackets, and you can pass them around. You're probably used to just passing around variables, passing around objects, or you can pass around blocks of code. And that's what a Lambda expression is. And it's a really awesome concept that allows you to do a lot. It's a fundamental concept of functions. And remember that Kotlin has object-oriented features and functional features. And this is one of those functional features that really makes the language very useful, very concise, very expressive. So passing and storing pieces of behavior in your code is a frequent task. For example, when an event happens, you want to run this handler. Right? That would be a block of code. Or apply this operation to all elements in a data structure, like a collection. These are types of tasks that happen all the time that would be really nice if you could just enclose them inside of a block of code and pass them around. Right? And you could do something like a function pointer, which is similar. In Java 8 supports lambdas, but this is a really nice thing to be able to do. So in older versions of Java, you could accomplish the passing of chunks of code by using anonymous inner classes. And this is how you do it in Android, because Android supports Java 6. It doesn't have Java 8, so you can't do lambdas. And that's one of the reasons you want to migrate to Kotlin to write your Android apps is because of this lambda feature. Otherwise, you just have all this boilerplate code that you have to do all the time. And one of them is creating these dumb anonymous inner classes whenever you want to implement an event handler, for example, in Android. So doing this anonymous inner class thing, it works, but it takes forever to write. It's really a pain in the butt. It doesn't make your coding, it doesn't make you happy when you write your code. It's not enjoyable. So we're going to use lambdas as opposed to creating this anonymous inner classes. And so in functional programming, you can solve this problem by treating functions as values, which is what lambda expressions are. And also, you're going to hear the term function literals quite a bit. That's a lambda. They're terms that are used interchangeably. A lambda is a function literal. You also hear the term anonymous functions. That's kind of a lambda, but there's some different rules in Kotlin about that. So instead of declaring a class and passing an instance of that class to a method, as an anonymous class, you can pass a function directly as a method parameter. And this is a higher order function. And it makes the code very, very concise. So the use case, here's a typical use case in Java where you can't use lambdas. You would have to create an inner class in Java to implement an event handler. It's very verbose, it's very irritating, it doesn't make coding fun, and you have to do it all the time. So if you're an Android developer, you know what I'm talking about. Creating that anonymous class to handle an event. I mean, you don't have to do it that way. You can also do the on-click in Android, and there's ways around it. But typically, if you wanted to do it, you would do it this way in the on-create, and you would implement the interface. So you would do something like this. You would you would have a button.setOnClickListener, which is a property, and that property expects you to implement an inner class for the onClick. Well, it's returning an instance of the onClick listener, which implements the onClick. And so an anonymous class creating this, doing it like this, will return it. So button.setOnClickListener, new onClickListener, public void onClick, overriding the methods, and that's how you can create a listener using an anonymous class in Java. And again, quite often used to handle events in Android. In Kotlin and in Java 8, but again, we're not using Java 8 in Android, you can use a Lambda for the above. You can have an expression that returns a value that's a block of code. So you can say button.setOnClickListener, and inside brackets, you can put your event handler. And that's all you need to do. You don't need to create an anonymous class. It's much cleaner, it's much more concise. So the above code does the same thing as the anonymous class in Java, but it's much more concise and readable. A Lambda can be used as an alternative to an anonymous object with only one method. We'll talk about this as well. You can do it this way if you have something called SAM classes, single abstract methods. And that's what you'll usually use it for in a lot of the Java stuff. The syntax for Lambda is the expression is always surrounded by curly braces. So just like when you define string literals, hello, or double literals, you can also define lambdas as a function literal. And so when you use it as this assignment, it's a function literal. And here's an example. This is a lambda. It's inside brackets, and it's a block of code. And it returns a value. It outputs some data. I am a function literal lambda. You can also store a lambda expression in a variable, and you'll see this quite a bit. Something like valPrinter equals your lambda, println I am a function literal. And then you'll usually invoke that printer object, either using run or you can call println on that printer. Once a lambda is defined, you can invoke it later using parentheses like you do in a regular function. Just like that, run printer. Now you should be able to invoke it as well with just the brackets without doing the run function. But I tried that and it wasn't working. So I'm going to try it again when we do some demonstrations. But you should be able to just have the brackets and it should run. But I had to add the run. So anyways, you can invoke it without a variable or with a variable by saying run printer. And then if you're doing something else, like it's not a print line, you can just invoke it by calling another function and passing it into a function. Because remember, that lambda expression is returning data. So if you pass that into a println, it's just going to print out the data, which you'll see a lot. Adding parameters to function literals. In these previous examples, you had function literals that didn't take any parameters. It wouldn't be very useful if you had a block of code and you couldn't pass it data. So function literals can also accept parameters. You write the parameters along with the types before a thin arrow. This denotes the function body. The parameter declarations do not need to go inside the parentheses. Parameter types, so there's no parentheses when you do a lambda. Parameter types can be omitted if they can be inferred from context. So we're going to talk about this more when this comes into play when you're using it as a high order function. When you're passing the function to another function, you don't always have to specify the type when you call it. And that's because the function can infer the type. But right now we're just talking about function literals where you're just using assignment operators or just declaring function literals. We're not talking yet about passing these to functions. But you should know that since we're talking about parameters, that sometimes you don't need to specify the type of the parameter. And also the parameter declarations don't always have to go inside parentheses when you invoke it. The arrow separates the argument list from the body of the lambda. So on the left-hand side is the argument list, the parameters, and on the right-hand side is the body, the code that's going to get executed. The last expression inside the lambda body is treated as the return value if it doesn't return nothing or it doesn't return void. And you'll see this. So a lambda can have more than one expression, more than one statement. And if it has multiple expressions, the last one, just like a regular function, right? Well, unless you had the return keyword. But the last expression is going to be what returns. So here's an example where we're passing a parameter. We have a variable called print message, and we have a lambda. We know it's a lambda because it's inside brackets. and we're passing a parameter. How do we know we're passing a parameter? Because anything to the left of the dash greater than sign is the parameter. And so here we're specifying the type of the parameter. The name of the parameter is message. We have the colon, and the type is string. We know that we're using the same convention we use for function parameters when we specify types. We have colon type. So this is no difference. Everything again to the left of the arrow is the function parameters. And you can have more than one, but this is just showing one. If you had more than one, you would separate them by commas. And you don't have to include the parentheses. Notice that there's no parentheses here. On the right side of the arrow is the body of the Lambda. This is the code that's going to get executed. And right here you only have one expression that's getting executed, but you could have multiple. But here we're just printing a message out. We're just printing the message out that's passed in as the parameter. And I'm going to show you a lot of different examples where you don't have to specify that string. I'll show you that when we talk about higher order functions. So here's one way to do it. You pass in the parameter when invoking, just like a regular expression. So if I were to call that, remember that print message is pointing to a block of code, it's pointing to a lambda, so we can pass a parameter into print message. We say print message and we pass in hello, which is a string. And then what happens? It prints out hello. Here are some more examples. Lambdas can have multiple statements, just like I said, inside the body. Here we have a val sum, and we're saying equals. And again, these are function literals because they're kind of anonymous. We're not passing them to anything. We know it's a lambda because there's a bracket. We know that we're passing types parameters in because everything to the left of the arrow is a parameter. And we have two parameters in this case because we have a comma. We have x is the name of parameter, and then that's the named parameter, and then we say it's an int, that's the type. We have y, that's an int. First thing we're doing to the right of the arrow is the body of the lambda. We're printing out, computing the sum of $x and $y. We're using a string template there. And then we have another statement, x plus y. What this is going to return is the last expression. The last expression here is x plus y. So sum is going to be equal to x plus y. Lambdas can also be written with and without annotations. Annotations are when you specify the type and stuff like that. There's more code. So here, val sum x equals int, y equals int, x plus y. You see a lot going on there. You can only do it without annotations, though, when we talk about higher order functions. In this example, you're using type inference on the arguments because you're passing this in to, say, a function or something like that. So you got to be careful with that, and I'll show you some examples. You want to use the cleanest version as possible, and what you'll usually do is you'll start off defining your function that takes a lambda. You'll define it as having parameters, and then you'll try to call it without parameters. And if the compiler complains, then you'll call it with parameters. But you want to try to use the smallest, shortest syntax as possible, and the shortest syntax sometimes includes not specifying the type of the arguments when you pass the lambda into a function. So you'll see this sometimes with some, but only when using higher order functions. An anonymous function is a little different from a lambda. It's the same type of concept. But the one thing missing from the lambda expression syntax in the last slide is the ability to specify the return type of the function. Or if you notice from the previous slides, we don't specify the return type. We specify the parameters, we specify the body, but we don't specify the return type of the lambda. When we pass it to a function, you can specify the return type of a function. But how do you specify the return type of a lambda? Use an anonymous function. So in most cases, this is not necessary because the return type can be inferred automatically from the expression. Right? And that's what was happening here. Is x plus y was being returned. We never specified that x plus y was an integer. But it was inferred based on the parameters that were defined. And that's what usually happens. They usually get inferred, so you don't have to be explicit about it. But if you do need to be explicit in specifying the parameter, you have to use an anonymous function. An anonymous function looks very much like a regular function declaration, except that its name is omitted. Its body can be either an expression or a block. So it looks something like this. Function, there's no name for that function. It's anonymous. X colon int, y colon int, and then colon, returning an int, and it's x plus y. That's an anonymous function with no name. And you could assign that expression to a variable, and then print it out. Another example here is fun x:\int, y:\int, returning an int, and then also using the return keyword with x plus y. You don't have to do the return keyword, but you can. Two different ways of using that syntax. The return type inference for anonymous functions works just like for normal functions. It's inferred automatically for anonymous functions with an expression body. So just like in the lambdas when you didn't specify the return type because it was inferred from the parameters, it works the same way in anonymous functions. If you don't specify it, you can return it. And it's still an anonymous function because you didn't give it a name. Really, if you didn't need to specify the return type, you might as well just use a lambda. Anonymous function parameters are always passed inside the parentheses. That's another thing you should have noticed beforehand, is you have parentheses around your function. Lambdas don't have that. The shorthand syntax allowing to leave the function outside the parentheses works only for lambda expressions. Lambda expressions, you don't have to have the parentheses. Another difference between lambda expressions and anonymous functions is the behavior of non-local returns. So a return statement without a label always returns from the function declared with the fun keyword. Right? Makes sense? You have a return inside of a function, it doesn't have a label, and you do the return, it's going to return to the outside of that function. A return inside a lambda expression will return from the enclosing function. A return inside an anonymous function will return from the anonymous function itself. Right? So an anonymous function will just jump right out of the anonymous function. A lambda expression, it will return from the enclosing function. So as I mentioned, you have this concept of higher order functions. You pass lambdas to other functions as parameters. And if you did a return inside of a lambda function that was a parameter to a function, it would jump out of the outer function. Where an anonymous function, it only jumps out of the anonymous function. So let's look at some examples in IntelliJ to make this a little bit more clear. Okay, the first lambda expression I'm gonna give you is the most basic one. Just something inside brackets and not being assigned to a variable or anything. Right? So this is a lambda expression. It's inside brackets. And technically from the documentation, if you run this, it should print out. But I was having trouble with this. It wasn't printing anything. So what I did is I just used the run function because that's what you can use run for. And when I used run, then this worked. So here's how you can invoke just a lambda that prints out I am a function literal. And that's the most basic of basics lambdas. You can also assign a lambda to a variable. So what you can do here is you can just say create a variable. It can be a read-only variable, print hello, and then inside there you know it's a lambda because you have your left and right brackets, and then you just have a block of code there. No parameters are being passed to this lambda. If we run that, we see that nothing happened because I didn't print it out. So let me make sure I print it out. I would say print ln, print hello. Because print hello does have a value. It's what's returned from the lambda. So now I run it and you would see output to the console. What you would see here is, and I made a mistake here, I don't need to use the print ln because you're already printing. Duh. So I can just say print hello. And that will print out because it invokes it and will call print ln. What was my mistake there? I didn't use the parentheses to invoke it. Amateur hour here. Now when I call it, let's see. Now we have hello. Yay, thank you. Okay, so that's another form of using a lambda by assigning it to an argument. We can also try using a parameter. So let's create another lambda that takes a parameter. So here is a print message. And this print message will have a lambda. We know it's a lambda because it's in brackets. And we know it's a parameter because now you see this dash, this arrow. Everything to the left of the arrow is the parameter. This is a named parameter. It's named message and it's of type string. There are cases when you don't have to supply the type when you're passing it into a higher order function, but we're not going to worry about that for now. Everything on the right hand side is the body. We only have one statement here, expression here, print ln message. So here we can call this function with a string, or this lambda with a string. Print message, and we can say JSON. And we run this, it will print out JSON. So that's pretty cool. We're able to pass a parameter to a lambda. Now let's create a lambda that has more than one statement in the body, and also more than one parameter. Here we have a lambda that's being assigned to the variable sum and print. It's lambda because it has brackets. And it has two parameters to the left of the arrow. It's a x and y of type int. And it has two statements in the body, two expressions in the body, println and then x plus y. If we print this out, it's going to display x plus y. So if we say print sum and print, if I could spell, and let's add a new line and run this, and you'll see that I don't need to do that again. It does return x and y, x plus y, and it should print out that as well. I didn't use the brackets, and I didn't pass it into integers. So if I say 5 and 7, and now it will print those out, computing the sum of, I believe I have to call print again, computing the sum of 5 and 7, and then I want to print out the result that was returned. And remember, the other one wasn't returning a result. That's why it was printing out that Kotlin message, because there was no return result from the assignment. This one has a return, so we can print it out. So there we go. I also wanted to show you how you can use a lambda with less syntax. So we have our sum and print there. Here's another one where you can only do this if you only have one thing. Well, you can do this whenever you want to. I was going to say one thing in the body, but so here we have some less concise variable, and we have x int, y int, and then we're just saying x plus y. Right? This is what you typically see. That's one way to do it. You could also have it more concise. That's really the best way. One of the best ways to do it. You can supply more annotations here. You can actually specify int, and then an int here, and then say x and y. This is another way to call it, or define it. Define the lambda. You say some more concise, int, and then you're going to have it equal on the right-hand side. And so if we were to call these, they're still going to be invoking lambdas. And so it still does the same thing, but you see the notation is different. They all do the same, but the notation is a little different. It's less concise and more concise. Right? Less concise, you just have the parameters defined with no parentheses, and you'll usually see this structure. If you want to make it more concise, it's a little more verbose. I don't think it's necessary, but you can put the parameters after the colon, have the int there, and then actually define the body. So you want to study lambdas. They're very important. We're going to talk about high order function. Those are also important. We haven't demonstrated how powerful lambdas can be yet. We just shown you a glimpse of it, but you can do a lot more when you pass these lambdas into functions or return lambdas from functions. Thank you. Hello and welcome. Another important concept we have to talk about is higher order functions. One of the biggest parts of Kotlin where we can pass lambdas into functions or return functions from functions. A higher order function is simply a function that either accepts another function as a parameter, returns a function as its return value, or both. Right? So it can do either accept one, return one, or both of them at the same time. In Kotlin, functions can be represented as values using lambdas or function references. There's also this concept of function references. A higher order function is any function to which you can pass a lambda or a function reference as a parameter, or a function which returns one, or both. Again, kind of just reiterated that, but I'm reiterating on purpose. You need to understand this concept. It's when you can pass a lambda or a function reference. Higher order functions allow us to write code faster, and it is easier to read. Two important things. Using them in this way is also a great abstraction technique. It simplifies your code and removes code duplication. And all these are going to become apparent when we start using these. Function types. In order to declare a function that takes a lambda as a parameter, you need to know how to declare a function type. And we've kind of talked about this a little already when we talked about lambdas, so you're kind of halfway there. But you already know how to do this without declaring the type, right? We know how to do this. There's two ways to do it, with type inference or with non-type inference. In this example, we have a val sum, x colon int, y colon int, and then x plus y. We know that this is lambda because it's in brackets. It has two parameters that are integers, x and y, and it has a body x plus y. We have an action variable that's being assigned a lambda, which just does a println of 42. Now, we call this type inference because the compiler infers that both sum and action are function types. You don't have to specify the type here, right? And I'm not talking about the types of the parameters in the lambda. I'm talking about the type of the variable. The variable sum and the variable action, the type is being inferred. They're function types. You can do it explicitly this way. So you can say val sum, and I showed you an example where you had this annotated text here. But this is how you can specify a function type with explicitly. So val sum colon int, and then we have the lambda inside of the brackets, right? So everything to the equals, right of the equals sign is the lambda. Everything before it is the function type, right? So you're specifying the function type here. In parentheses, you're specifying the parameters, int, comma, int, and you're saying that it is going to return an int. And for action, you're saying that it has no parentheses and you're returning a unit. A unit is like a void type. Println is not returning anything per se. Right, so this is explicitly how you define your function types. And this is how you need to define your function types if you have a function that takes a function. This is how you're going to do it. You're going to do it the explicit way. So to declare a function type, you put the function parameter types in parentheses, followed by an arrow and the return type of the function, just like you did in this explicit type information. So for sum, the function type is int, comma, int inside parentheses, followed by an arrow, followed by int, which is the return type. For action, the function type is the empty parentheses, followed by an arrow, followed by unit. And that is how you would declare a function that takes a function as a parameter. You would put that function type in there. So you can specify names for parameters of a function type and a parameter name for the function itself. Right? So we know about named parameters. It's no different if you have a function that takes a function. You can still name that parameter. The name is just going to be a function. It's going to represent a function. It's going to represent a lambda. So here we have foo. We have one parameter, which is a string, and then we have another parameter, which is a lambda, a function type. And we're going to name that. We're going to name it fn. We know that it's a named parameter because the name is to the left of the colon, and then everything to the right of the colon is the type. And everything to the right of the colon here is a function type. We know it's a function type because it takes one parameter called a string, and it returns a string. And then that last parentheses is closing off all the parameters for foo. So again, in this example, you're defining a function called foo. It takes one parameter with a string. You have a comma. The second parameter is a named parameter as well. It's named fn, and it takes a string and it returns a string. And then the entire function itself, foo, is going to return a unit. So that second parameter here is a function type. It's a named function type. And then inside here, we're going to, it looks like we're calling our parameter. Val applied equals fn string. That's how you can call your parameter, and we'll get to that in a second. And then you're printing out the variable that you just assigned from the function. So the above function is named foo, and we'll get back to the calling of the parameter. But right now, the above function is named foo, and it has two parameters. The first is a string, and the second is a function from string to string. String to string means that it accepts a string as input and returns a string as output. The entire foo function returns unit. So this is the syntax that you got to familiarize yourself with. Whenever you see this, function types, it means that you're passing a function to a function. You see the function type in a parameter. The above function has a parameter name for the lambda, fn. It's a named parameter, and no parameter name for the string passed to the lambda. Actually, that's not true. The string passed to the the string passed to the lambda, right? So it has a name for the first parameter, has a name for the second parameter in foo, but it doesn't have a name for the parameter inside of the lambda. And you could have a name there if you wanted to, but it doesn't, right? There's no name after fn colon inside the parentheses for string type. The syntax for calling a function that has a function as a parameter is the same as calling a regular function. So if you see in this example here where it says val applied equals, after the equals we have fn. We're calling our function that's in our parameter. And you're calling it just like any other function. You're just calling it's a parameter passed in. So you put the parentheses after the function name and you put the parameters inside the parentheses, just like a normal function. And so if we passed in a function to this foo as our second argument, and the function was length, string.length, it would find the length of the value of the variable applied and print it out. And that's how we're going to use it. So you pass in a function to this function, you execute the function inside the definition of foo, and then you print it out. So here is calling the function that takes a lambda. This is where we want to call foo. To invoke the function that takes a function as a parameter, foo, you can use a lambda, right, as the second parameter. So here you just call the function like you normally do. You say foo. The first parameter is just like normal. It's a string inside double quotes. You have the comma. The second parameter is a lambda. And we know what a lambda is because it has the brackets, and it has inside the brackets, it has something. Now, we're not familiar with this syntax. The syntax here, it has it. And so there's a special rule for lambdas where if the lambda itself only has one parameter, and in this case it does, it just has a string, the type can be inferred. It's going to know that that's a string, and then if it's only one parameter, you can just say it. It is a special variable. We'll get to this in a second, but just to give you a heads up. So the string we pass in is hello for the first parameter. Hello is then passed in as input to the next function, which returns the reversed value. Hello is passed in as the input to the next function. So let's go back to our function. We pass in stir string, and then our first line in the body after applied, we're passing in stir to our function. That's what that means. So we're passing in our first parameter stir into our function, our second parameter, which is function, fn. So hello is then passed as the input. You might want to read that a couple times. And what happens is, what are we passing in as our second parameter? We're passing in a reversed function. So it's going to take the parameter, it's going to pass it into the function that's passed into the foo, and it's going to reverse it. And then it's going to print it out. So the result of this invocation would be OLLEH, the reverse of hello. So in the above, the lambda only has one argument, so we can use the it as a shortcut to avoid naming the argument explicitly. And I'm going to provide a demonstration of that. It'll become more clear. But again, what we want to look here is it.reversed. That's the function. And it represents the parameter. So here, when we say string stir is the first parameter, it passes into the function, and we know that it is just going to represent the parameter in the function, and then execute it. So that's pretty nifty, and that's how you're going to use it a lot. So this brings us to type inference. There are rules with lambdas that we have to kind of cover that can get confusing, but it's important. So when lambdas are used as a parameter, higher order functions, in that last example we had foo as our function, our second parameter was lambda. So this applies. When lambdas are used as a parameter in higher order functions that take a function, then the parameter can be used to infer the type of the argument. Remember the difference between parameters and arguments? Arguments are when you call the function. Parameters are when you define the function. If the parameter of a lambda is defined as a string, when you call the function, you can infer the type. Not always, but sometimes. So the parameter of the function can be used to infer the type of the argument, and you do not need to explicitly declare the argument type in the lambda. You wouldn't need to say in the lambda like it.reverse. You don't have to say the type of that because it's going to use type inference. And here's another example where if you were passing this lambda right here, message, and then println message, if you were passing that into a function that takes string, it would automatically infer it, and you don't have to say message : string as the parameter. So we know this is a lambda. There's a left bracket and a right bracket. Everything to the left arrow is the parameter. Everything to the right arrow is the body, println message. Normally, in our lambda definitions, we identify the parameter with a type. We say message : string. In this example here, we didn't do that. We didn't do that because the parameter that we're going to pass this function to already has it as type string, and it can be inferred by the compiler. The other part of this with type inference, if there's only a single parameter in the argument type, and in this case for foo, all there was a string for the lambda, just string, and the argument type it can be inferred, then the compiler will allow us to replace the argument with the default argument named it. It is a special variable. So you can use the implicit variable it, and that's what we did in the previous slide. Because it's a single argument to the lambda. And the type was inferred already because it was typed as string and it knew it when we passed it. So the compiler is very smart. If you store a lambda in a variable, there's no context from which to infer the argument types. So you have to specify them explicitly. You will never see this message arrow println message being assigned to a variable. It will not compile because it doesn't know how to infer the type. You would have to say message : string. Here's an example. Val get age equals p : person, and then that's the parameter, and then the body is, or the return type is p.age, right? Because that's a lambda. We define a lambda as the parameter, and not the return type, the body, and then the body to the right of the arrow. So p : person, right to the arrow, p.age. Right, that's the body. The return type is implicit in this lambda. And then we say people.maxBy getAge. MaxBy is a collection method that you can call. And maxBy takes a lambda. It's a helper function. And so what you want to think about when you think about type inference, all of your lambdas is as a parameter in your function. They all have to specify the type. This only applies when you're invoking the function with your arguments. What you should do is you should just always try to make the call to the function without specifying a type. And if the compiler complains, then you specify type. That is the rule you should follow because that will be the shortest syntax and it will make your life easier. Well, you'll just be smaller. Instead of trying to guess, oh, is this type going to be inferred? Are we using this lambda inside of a function? Are we assigning this lambda to a variable? And so forth. I mean, in this getAge function, we're assigning the lambda to a variable, so we have to specify the type. There's no way we can't say p : person. We have to specify person. So let's bring up IntelliJ and try to explain this with some examples. Okay, so we have IntelliJ up with our main routine. I'm going to create a data class. You haven't seen this yet, but well, we saw it in a previous example, but it's a class and object. It has getters and setters. A person constructor takes a name, and it takes a age, and it returns an int. Okay, it takes an age that's an int, and it takes a name that's a string. Two vals, two read-only variables. And this is a data class. So I want to try to demonstrate here how you can call this, invoke this function, and how the type inference will work. So normally, this function is going to we only need the people class because we want to pass it into a function. And the function is going to be a collection function. So we're going to create an instance of people like this. This is actually creating a list of, and we're creating two person objects inside of a list. Now we want to pass that list to a function. And that function is going to take a lambda. And so without any shortcuts, we would have to do something like this. This is what you would have to do where you specify all types and everything. Nothing is inferred. So here we're saying we're taking the list and we're calling a function on that list called maxBy. It's a collection function. And the max by function takes a lambda. And it takes a lambda. We're going to define the lambda. And in this definition of our lambda, to the left of the arrow, we're defining the type. We have all our types. To the right of the arrow is the body, p.age. And this max by is just going to print out like the max thing. We'll see what it does. But this is like the standard way of doing it without any shortcuts. So if we run this, the output is going to be person name Bob equals age. Age equals 31. So it looks like the max by is finding the max age in this case. Now we can simplify this. We can remove the lambda expression out of the parentheses if the last argument. So one of the rules as a lambda is you can remove a lambda expression out of the parentheses if it's the last argument in a function call. And since this max by function takes only one argument, it's definitely the last argument. So when you have only one argument, and if you have only one argument, it's a lambda, you can definitely do this. If you have multiple arguments and the last argument is a lambda, you can take it out of the parentheses. So now I'm going to show you syntax where you don't need the parentheses. So let's go back and we'll show it with the most syntax. So remember, this was what we called, this is what we called with most of the with all the required annotations and syntax. That's what we called. We specified type and everything. Now we're going to call it, and it's a little simpler. We don't have to provide the parentheses. You see here, we had the parentheses for the max by. We don't have to do that. We can have the max by within the parentheses, and we can put the lambda outside. And we can do that because the lambda function, it's only a single argument in max by, and it's the last one. If max by took 3 functions and the last parameter was a lambda, we can do it as well. So this simplifies it a little more. If we run it, it works just like it did before. Print out 2 things, 2 statements. Now we can simplify this even more. We can take the lambda expression out of the parentheses, now what we can do is, if it's the only argument to a function, we can remove the empty parentheses from the call. So we can get rid of those 2 dumb parentheses that right next to max by. Right? So when the lambda is the only argument to a function, you can also remove the empty parentheses. So here we had these. We can get rid of that now because max by takes 1 argument. And again, if we run this, you're going to see that it prints out the same thing. No changes. You can even simplify it even further if you have type inference. And so max by takes a certain type. And let's see if type inference will work. And what we mean by type inference is we're going to remove the type that we're passing in the lambda. So we're no longer going to specify person. We're going to remove it and we're just going to specify p. And if we hopefully when we compile that, it will be inferred, because this doesn't always work, remember? Only if the parameter can infer the type. So now we run it. And there it goes, it worked. So we simplified it even further. Now let's simplify it one more time by using the it variable. Remember what the rule is for the it variable. If you can use it if it's a single argument and the type can be inferred. So now we can come down to our least amount of syntax, and it looks a lot different from our first call. We can say people.maxBy it.age. And again, if we run this, it's going to work just like the other ones. So just to reiterate, look what we did. We started with all of this syntax. Max by, we had it inside the parentheses, we had the type person, everything. And we got down to using that, it.age. And so those are the rules of lambdas. And it makes lambdas much shorter to call and quicker. I mean, I could provide more examples where you don't even have to provide a class. Let's do one more where we have our own function definition. So instead of a data class, let's just define a function that takes a parameter, a string. Right? So here we have our foo function, which we talked about earlier. It takes a string as a first parameter. And our second parameter is a lambda. Function string that returns a string. And then it does something, it calls that function right there to whatever is passed in. And so here we can call it with no shortcuts. We're specifying the type, put it inside parentheses, everything. Here we could say foo, we call it with hello for that string, and then we pass in our lambda, we specify the type of the parameter, and we say message.reversed because we want to reverse it. This is the most syntax you have to provide. We run that and it reverses the string. OLLEH. Let's try simplifying it. Let's see if type inference will work. In this case, we're going to remove the string from our parameter. So we're going to try to see if type inference works. If it doesn't work, the compiler will give us an error. Still calling hello, but this time we're not specifying string. We're hoping that because of the parameter in the lambda, that it will infer that it's a string. So let's run this. And it worked because it printed out twice. Now we can also do this using the it because we only have one parameter into our lambda, a string. So this would also allow us to use the it variable. So let's try it with it. Run it. And it works. So it's just a demonstration of how you can really limit your syntax and make it even smaller from the most complex to the simplest. And these are just rules you got to memorize. It's hard to remember, but you got to remember things like the function or the lambda is the last argument in foo, so you can get rid of the parentheses. The lambda has a string, so you can use type inference. The lambda only takes one parameter, so you can use it. Okay, so let's stop this lecture. We'll pick up the rest of the higher order functions in the next lecture. Thank you. Hello, welcome back. So I was babbling on so much last lecture that we didn't get done with our higher ordering details. Last time we described what higher ordering functions are, and we started talking about how to define function types, how to pass them into functions. But we still have a lot more to talk about. So let's pick up where we left off and talk about function types from Java, using function types from Java. So under the hood, function types are declared as a regular interface. We know what function types are at this point. Function types are how you can pass functions to parameters. In Java, they're declared as regular interfaces. So there are many of them correspond to a different number of function arguments. Kotlin functions that use function types can be called easily from Java 8, as lambdas are automatically converted to values of function types. Right? And Java 8 supports lambdas, so it's very easy for Java to call Kotlin functions that take lambdas. It just passes in its lambda, and it converts it to a function type. In older versions of Java, you can't pass a lambda because Java 6 doesn't support lambdas, and that's what you're using for a lot of your Android apps. So you have to pass an instance of an anonymous class implementing the invoke method from the corresponding function interface. This is the workaround that you have to do for older versions of Java when you want to talk to Kotlin functions that take lambdas as parameters. So here's an example. We're creating a function called process the answer, and it takes one parameter, which is a lambda. The name of that lambda is f. All we do in the process the answer function is we print out whatever was passed into the lambda, which is an int. Right? So it takes an int and returns an int, this lambda, and we're going to print it out, process the answer. Very simple. Now, how can we call this Kotlin function from Java code? What we'd have to do is in Java code, we'd have to do something like this for Java 6 versions. For Java 8, you could just pass it in. Java 6, we'd have to say process the answer, and then we'd have to create a new function, an anonymous function here, that takes integers and integer 1, 2 integers as parameters, and we'd have to override the invoke. So this looks like an anonymous class, right? Because we have a new class that doesn't have an instance. We're just passing it directly into the process the answer. This class invokes a method called invoke, and it will print out the number and return the number plus 1. So that's what you have to do if you are using Java 6 and you want to talk to Kotlin functions that take a lambda. Returning from lambdas, you can write a local return from a lambda expression as well. We talked about how when you wanted to return when you wanted to specify the return type, not returning, but when you wanted to specify the return type of a lambda, you had to use an anonymous function. This is a different concept. This is when you want to return from a lambda. We also talked about how you can return from a lambda, and it's different from an anonymous function. When you return from a lambda with just the return keyword, you're going to jump out of the outer function if you're a function parameter to a function. And you might not want to do that. If you just want to jump out of the lambda function, you can use a label. Now, if you're an anonymous function and you jump out using a return, it's going to jump out of the anonymous function. But if you just want to jump out of the lambda and you're inside of a function that takes a parameter, you can use something similar to a break in a for loop. You can use a label. The label will stop the execution of the lambda, and it continues the execution of the code for which the lambda was invoked. So to distinguish a local return from a non-local one, you can use labels. A local return, again, is just returning from the inner function in the lambda. So we got to remember here, we're talking about higher order functions. We have a function that takes a parameter. The parameter is a function. So it's kind of like a nested function inside there, right? You just want to jump out of the lambda, you can use a label. So you can have a lambda expression from which you want to return. You refer to this label after the return keyword. To label a lambda expression, you put the label name, which can be any identifier. An identifier is usually just alphanumeric characters or numbers after that. And then you have that identifier. You follow it with the @ character before the opening brace of the lambda. And to return from a lambda, you put the @ character followed by the label name after the return keyword. So let's look at this. And this is what you would need to do. So what that's saying is you have your label right before the bracket, right after the specifying the type of the lambda, the body lambda here. This looks like it's an extension function that is taking a lambda. People.forEach. People is the receiver type. ForEach is the extension function name. And then that ForEach is taking a lambda as a parameter. ForEach is a function. It's not a for loop. It looks like a for loop, but ForEach is a function in the standard. I think it's in the Kotlin standard library. I didn't talk about ForEach in our looping discussion because it's technically not a loop. It's a function. But this ForEach function will take a lambda, and that's what's happening here. And so if we want to jump out of that lambda, we have a label right before the bracket, the definition bracket of the lambda. And then when we want to jump out, we use the return keyword inside the lambda pointing to the label, @label. And that will jump out of the lambda there, and then it will print Alice might be somewhere. If you just had the return, you would jump out of the entire function, look for Alice. So if you just want to return from a lambda, this is how you do it. You also don't need to use labels directly here. What you could do is, if you didn't have a label there, you could do a return and you could specify ForEach. The name is ForEach or the name of the or people. I can't remember if it's people or ForEach, but I think it's ForEach. If you specify the name of the function, you can return that way as well. But it's much more clear when you use a label. So if you say look for Alice and you pass in people, Alice might be somewhere is going to be printed out. It's going to jump out of that ForEach, and it's going to print out Alice might be somewhere. Right. So people and look for people. That could be a list of 100 names. Right. And it's going to print out only when it finds Alice, because it's going to be equal to Alice. It's going to jump out and it's going to print. So that's how you can use the label to return from a lambda. You also notice we have our it variable inside there. That's pretty cool. Remember the it. You can use the it inside of a lambda if it's the only parameter and the parameter is inferred. So remember, we're passing this lambda to a ForEach function. So the ForEach function must have a type that can be inferred from it.name. And that's why and it must be a single parameter. ForEach must take a single parameter as well, right? So you can find out a lot about the function by just looking at the lambda. If you know the rules of the lambda, which are you can only use it if it's a single parameter in the function. So ForEach must take a single parameter. And also, it must be doing type inference because you can't use it without type inference. So a lot of nice stuff going on here, but all you got to really remember on this slide is use the label to jump out of that, jump out of the for each function, the lambda. Okay, so I think this does it on our higher order functions for now. We'll talk more about higher order functions when we talk about collections and some other concepts, but these are the basics, how you can pass functions to functions. We're also going to have a separate lecture on how you can return a function from a function. We've only talked about how you can pass the functions in. Thank you. Hello and welcome. Let's continue our discussion on higher order functions and talk about variable scope and member references. So what kind of variables can you access when you're inside of a lambda or you're inside of a higher order function? Scoping has to do with access. Whether or not you have what variables you have access to, what functions you can call, things like that. When using a lambda in a function, you can access the parameters of that function as well as local variables declared before the lambda. So this is referred to as the lambda's closure. You'll sometimes see this term. I don't really use it too much, but some textbooks and so forth will use the term closure to represent this concept. In Kotlin, unlike Java in an inner class, you are allowed to access non-final variables and even modify them in Lambda. So for those of you that know Java, you know that when you create an inner class, you can only access final variables outside of that inner class. Local final variables. Non-final local variables, right? And Kotlin doesn't have that restriction. So I'm sure you've been there where you've tried to, you're inside of an inner class and you're trying to access variables and it says, oh, that has to be declared as final. And it's kind of an annoyance. Well, there's no restriction in Kotlin. You can access certain variables in the outer. So by default, the lifetime of a local variable is constrained by the function in which the variable is declared. Right? So a local variable, normally local variables, when they're inside functions, once you return from the function, the local variable is removed from the stack. It's no longer visible. Not in lambdas. If it's captured by the lambda, the code that uses the variable can be stored and executed later, even if you return from the function. The one caveat is that if a lambda is used as an event handler or is otherwise executed asynchronously, the modifications to local variables will only occur when the lambda is executed. And so we'll provide some examples and I'll show you what this means, but really for the most part, we just think it's kind of the opposite of Java. When you're inside of a lambda, you can access a lot of data, and you can access even data that's being taken off the stack because it's saved inside the lambda. A concept closely tied to that is member references. You can use member references to pass an argument that is already defined as a function. So when you're not using a block, but you want to pass an argument that's defined as a function, you can do this. So I mentioned before, I think in a previous lecture, that the only thing that had function types were function member references and in lambdas. Now we're talking about member references. So you can also pass member references to functions that accept a parameter as a function. So in Kotlin, just like in Java 8, you can do so if you convert the function to a value. So you can use the colon operator. A double colon separates the name of the class from the name of the member you need to reference. So it's all just about referencing something, right? So this is kind of a concept of a function pointer. If you'd see, you don't have a lambda. You actually have a real function that's defined, and you want to pass that function to a function that takes a function. It's not a lambda. It's a member reference. Well, it's a member variable or another function. You can use a member reference to access it and pass it in. So here's an example. You have val get age. You're storing a member reference here, and person : is age. That's referring to the age function of the person class. And then you're assigning it to a variable. You can now use getAge and pass it into a function that takes a lambda. So the above expression is referred to as a member reference. It provides a short syntax for creating a function value that calls exactly one method or accesses a property. So you can do it if it calls a method, or this is not with a method, but this is with a function value that calls exactly one method or accesses a property. It doesn't just have to be a function. It can access a property. This is a more concise expression of a lambda that does the same thing. So val get age, person, person, person age, right? In this example, you're defining a lambda. It's of type person, and the body is person.age, right? In the above, you're saying person.age function, which is returning, or which is getting an expression probably to person.age, it's a getter. So you can have a reference to a function that's declared at the top level as well. Even though we just used the term member reference also means top level functions. Remember, top level functions are not a member of a class. So it would be really crappy if you could only pass in functions of a class to a function that took a lambda. You can also pass in top level functions to a function that takes a lambda. The only difference is you don't need the class name and then the colon. So you can omit the class name if you're referring to a top level function. You would just do something like this. If you had a function called salute, top level function, and it's equal to println salute, right? So we know what this is. This is defining a single expressive function. Remember single expression functions? Those were functions that just were in one line. They were after the equals. That's what this is. Println salute is a function being assigned to the function salute. And so here, this salute function is not part of a class. It's a top level function, so we don't have to specify the class name before the colon. We just say run ::salute, and it prints out salute. Pretty simple. You can store or postpone the action of creating an instance of a class using a constructor reference. So this is formed by specifying the class name after the double colons. This is if you don't want to create an instance, really. So here's an example. We created a data class called person, and then we're creating a person, and we want to make a function pointer out of this. Well, we want to make a member reference out of this. And so we say : person. This is a constructor reference. We didn't actually create the instance right there. We're waiting to create the instance when we use it. So even though we assigned a function here to a create person, it hasn't created it yet. It's just a reference to a constructor. So now in the next statement here, val p equals create person, that's when we're going to create the person object. So val p create person is going to take an Allison 29 and it's going to create the person object. So you can do that when you want to delay the action of creating an instance. And then we could just print it out. And you would see person Alice 29. Extension functions. Now the question is, can you pass an extension function into a high order function? The answer is yes. You can also reference an extension function the same way as a member reference. Right? There's so many. This is a functional programming language. There's so many different types of functions. You have your class functions. You have your top level functions. You have your extension functions. Well, lo and behold, you can also pass an extension functions into high order functions. You can just do something. You can just do something like this. It really doesn't look any different than when you passed a member reference. You say fun person.isAdult equals age is greater than or equal to 21. This is an extension function, and we know it because we have, after the fun keyword, we have our nice resolver type, and then after the dot, we have our extension function. That's how we can identify that it's an extension function. And it's just returning a Boolean, age is greater than or equal to 21. Well, if we want to pass that in, we just say person : is adult. We assign it to a variable. We now can pass in predicate to a high order function. So let's demonstrate some of these concepts in IntelliJ. So first I want to show you how you can access parameters and local parameters of a function inside of a lambda. So to demonstrate this, I want to use the for each standard library function. We talked about this in the previous lecture. It's one of the most basic collection manipulation functions. All it does is call the given lambda on every element in the collection. Right? So here I'm going to define the lambda, or I'm going to define a function that takes a lambda, a higher order function. It's called print messages with prefix. We know it's a function. It takes a parameter, messages : collection string, and prefix string. Right? So this is not taking a lambda as a parameter. We're defining a lambda inside the function. So here we're passing in to for each a lambda, println $prefix. But you'll notice it's a lambda because we have a left and right brackets. So it's not always when you pass in a parameter. You can always, when you're using lambdas inside of a function, just like when you need to return from a lambda inside of a function. So inside the for each, what you'll notice is inside this lambda, what are we accessing? We're accessing a parameter called prefix. That's a parameter to the function. So we can access that. It doesn't have to be final. We can access it. And then we have $it. $it is the parameter to the for each function. So we want a prefix for each message in the for each. We want to prefix it. So that's one way. This is just demonstrating how you can access parameters in a function inside a lambda. And so if we were to try to use this, we would see that it works just fine. So let's just call it, let's first create a list. This will be a list because the for each method has to take a collection, right? A collection is an interface, so we can pass in a list. And then let's call the print messages with prefix with our list. So here we say print messages with prefix. We passed in errors, which is our list, and then we pass in a string, our prefix. And we run this, it's going to just print out everything in the collection. Right? That's what the for each is doing. It's just going through everyone. It's printing out the prefix, which is error, and then whatever's inside there. It's pretty neat. This just took a lambda as an argument, and it specified what to do with each element in the for each, and then the prefix in the lambda accessed the parameter. Let's give another example of how you can access local variables that are not final, like Java. This was an example accessing a parameter. Let's create a function and show how we can access some local variables. So here's another function I want to create. This function is called print problem counts. It's going to take a named parameter response, which is a collection. And then it has some local variables here on line 13 and 14, client errors and server errors. And then again, we're using for each. The for each takes a lambda. Lambda's in between the brackets. And the lambda here is doing a couple things. It's a statement that is just doing an if-else, if. And so in this if-else, we're accessing it because for each just takes one parameter and it's inferred with the type, so we're good to access it. And then we're accessing two local variables, client errors and server errors, inside the lambda. And they're not marked as final, and we can modify them by incrementing them. So that's pretty neat. Let's call this function in our main. And we'll see that there's no errors and that we're able to access all of those. Or I'm sorry, this is not the call. This was actually inside the function. Which is, yeah. So now if we try to call this, we first have to create a list and then invoke the function. So here we're going to create a list of three strings. Three strings we're going to create, and we're going to call print problem counts and pass in responses. All right, we're going to call this. And you'll see there's no errors. We're able to access the local variables fine, and we're able to modify them. So it says one client errors, one server errors. So we just look for starts with. We looked for the first four letters for the client errors. And if any of these start with 4, this one does, so it's 1. It increments the local variable. If any of them start with 5, which this one does, it increments servers. And then it prints out how many, which is 1 and 1. Here's another example of incorrectly use of a variable in scope. So here's a function. Here's a function called try to count button clicks. And it takes a button. And in this function, try to count button clicks, it's not going to compile because it's trying to access clicks. And this function is always going to return 0. So even though the onClick handler will modify the value of the clicks with the clicks plus plus, you won't be able to observe the modification because the onClick handler will be called after the function returns. So we talked about how you can still access variables, local variables, even after the function returns because you can save them. But this onClick function is not going to be accessed until after because it's an event handler. And so the onClick handler is going to be called after the function returns. It's not going to be able to increment the clicks. The correct way to implement this you would need to store the click count not in a local variable, but in a location that remains accessible outside of the function. So for example, like a property of a class. But this should give you a good idea of how you can access variables inside of a Lambda. Thank you. Hello and welcome. In this lecture, I'd like to talk about how you can use Lambdas with the Java APIs. So Kotlin is designed with Java interoperability in mind. We know that. That's one of the biggest goals, right? We don't want to break things if we're trying to use Kotlin. If we couldn't talk to Java, Kotlin would be very limited. So Kotlin can use all the Java APIs. So great news, Kotlin Lambdas are fully interoperable with Java APIs. I'll tell you what, if they weren't operable, that would be really bad news. It just would not be good. And Kotlin would not really work really well, especially with Android. So you can work with Java APIs with Kotlin. We know how to pass a Lambda to a Java method. We've talked about this before with the button.onClick listener. We can have, in the past, you would create an anonymous listener class. We can easily pass this in by using a Lambda. And on the left-hand side of the arrow, we can specify the parameter. And on the right-hand side, we can specify the argument. Or not the argument, but the execution of the block. So that would be the handler method. So that's what you typically do when you override it, when you're implementing set on click listener. And by the way, you would do this a ton in Android, because in Android, usually when you're on create, you're setting up all your listeners and you're creating all these anonymous listener classes. So you're going to be passing in Kotlin Lambdas with Java APIs for sure. So in this example, the Lambda is used to implement the onClick listener and has one parameter of type view, as in the onClick method defined in Java. This works because the onClick listener interface has only one abstract method. Interfaces that have only one abstract method are called functional interfaces or SAM interfaces, where SAM stands for a single abstract method. So if you ever see this acronym SAM, single abstract method. And the reason that we can do this, like with the set onClick listener, where we can just specify the view and then the body of the Lambda, is because they take only one abstract method in the interface. Right? So Java API is full of functional interfaces like runnable and callable. And we actually demonstrated this earlier when we were creating instances of runnable. The runnable interface only implements one method, the run. It has one abstract method that you have to implement. And the onClick listener only has one abstract method, which is the onClick. So this is the procedure you're going to be doing if you want to call into Java and you want to have this short syntax like with the onClick listener. You're going to be doing this, but you can only call in the Java classes that have SAM interfaces. Kotlin allows you to use Lambdas when calling Java methods that take functional interfaces as parameters. Functional interfaces, SAM, same thing. Passing a Lambda as a parameter to a Java method. You can pass a Lambda to any Java method that expects a functional interface. Again, I'm repeating it for emphasis. So here in Java code, we have this function called postpone computation. We know the function is part of a class because everything is in Java. You can't have top-level functions in Java. It doesn't return anything. It has a delay and a runnable computation. In Kotlin, you can invoke it and pass a Lambda as a parameter. So this must be part of an interface that ultimately has only one abstract method. What the compiler will do is it will create an instance of an anonymous class implementing runnable. So there you go. All Kotlin does is act as a wrapper. It's still doing the same thing under the hood. It's creating an anonymous class. So either you can create the anonymous class in Java, or you can have Kotlin do it for you, and you can use Kotlin code that is much quicker and faster. You decide. I'm going to go with Kotlin. So you can do something like this in Kotlin. You can say postpone computation 1000, which is the first parameter, and then the second parameter is lambda, representing the runnable computation. And then what goes on under the hood for the lambda is it creates an anonymous inner class for runnable. So that's pretty neat. And you'll notice here the syntax here too in Kotlin is the lambda expression is outside of the parameters. Why is that? Because the lambda expression in postpone computation in Java is the last argument, the last parameter, I should say. It's the last parameter in the list. And when the last parameter in the list is a lambda function, you don't have to include the lambda function inside the parentheses when you call it. So that's how you can invoke it inside Kotlin. The lambda will be used as the body of the single abstract method, the run method, in the above. So because runnable is the functional interface. I misspoke earlier when I said that postpone computation must be the runnable interface. No, runnable is the interface that has the one abstract method, and that's why you can pass a lambda. Yeah, it's where the lambda is going. You can call any method in Java and pass in all the parameters, but you can only use a lambda if it's a single, if it's a functional interface, a SAM, a single abstract method. And runnable is, so we can do it here. SAM constructor. A SAM constructor is a compiler-generated function that lets you perform an explicit conversion of a lambda into an instance of a functional interface. So you can use this in context when the compiler doesn't apply the conversion automatically. So we mentioned that under the hood, when you are using the lambda, it creates the lambda into an anonymous inner class. That's what's happening. If it doesn't do that correctly and you want to do it, then you can actually go to the compiler-generated function and do that. So if you have a method that returns an instance of a functional interface, you can't return a lambda directly. You need to wrap it in a SAM constructor. So what you do is, here's an example. Here's a function that is returning a functional interface, a runnable. Right? We have our Kotlin function create all done runnable. It's returning a runnable interface. That's a SAM. That's a functional interface. And you cannot return that directly from a lambda. So what you need to do is you need to do something like this. You need to wrap it in a SAM constructor, which is return runnable and then pass in the lambda print all done. So the SAM constructor here is the runnable print all done. And that's performing the explicit conversion of a lambda into an instance of a functional interface. Right? So runnable and then the lambda print all it's converting it to a runnable. And then you can just call create all done runnable.run and you can use it. So again, this applies to when you have a function that returns an instance of a functional interface. And runnable is the functional interface here because runnable has one abstract method. Right? And you wouldn't be able to return that lambda directly, so you have to wrap it in this return runnable and then a lambda. And that's referred to as a SAM constructor. And then you can use it. The name of the SAM constructor is the same as the name of the underlying functional interface. Right? And that's what runnable is. Runnable. It takes a single argument, a lambda, that will be used as the body of the single abstract method in the functional interface. Right? So again, you see runnable is the SAM. And then it takes a single argument, which is the lambda inside the brackets, which is print line all done. Print line all done will be used as the run method because that's the single abstract method is the run method. So that will print all done will be put in there because under the hood, what does it do? It creates an anonymous inner class of runnable and then it implements the runnable method and puts that lambda parameter as the body of the functional interface of the abstract method runnable. Run of the abstract method run. So that's pretty neat. It returns an instance of the class implementing the interface. And again, that's what's happening here. That's why you can say create all done runnable.run because you have an instance of runnable. And that's being returned from create all done runnable. All right. So again, the SAM constructor here is the runnable. The SAM constructor takes a lambda. The lambda is the body of the lambda is what goes inside the abstract method you're implementing, the run method. In addition to the returning values, SAM constructors are used when you need to store a functional interface instance generated from a lambda in a variable. So you don't have to return it. You could put a lambda in a variable. This, this would look like a single expressive function, and you would store that lambda in a variable, and then you could use it later as an instance if you wanted. So suppose you want to reuse one listener for several buttons, and here's an example of what I just mentioned. You could create a variable called listener, and what you're doing here is you're using a SAM constructor, right? The SAM constructor is the on-click listener, and it takes one argument, the lambda. The lambda is a parameter view, and then the body is val text equals win. The val text equals win is going to go inside the on-click event. So on-click listener is our functional interface. It's an interface with one abstract method, the on-click. And so we can use the SAM constructor on what we need to do is we specify the name of the class, and then it takes one parameter, which is a lambda. The lambda has a parameter here called view, and then that val text equals win will go inside of the on-click method. And this is going to return an on-click listener. And that listener class we can use at a later time. We're not using it right now. So we can reuse it too as well. This is a way to reuse one listener for several buttons. And then lastly, the toast happens outside of that win, inside the body still. So we can say button 1.set onClick listener using the same listener. Button 2.set onClick listener. And the listener is still going to work because it's looking at the view ID to do something. So the above code can be part of an activity.onCreate method in Android. That's typically where you put where you set up all of your listeners, event handlers. So that's kind of a cool way to use the SAM constructor when you want to return a functional interface as part of a lambda, or when you're assigning it to a variable so you can later use it. Thank you. Hello and welcome. Let's talk about returning functions from functions. Up to this point, we know how to pass functions to a function using a lambda, but now we want to learn how to return a function from a function. To declare a function that returns another function, you specify a function type as its return type. We learned all about function types in an earlier lecture. We know what a function type is. Returning a function from another function is used less than passing functions to other functions. So you won't see this as often as when you pass a function as a parameter, but you do need it, and it does have a specific use case. Usually when you have a piece of logic in a program that can vary depending on the state of the program or other conditions. For example, calculating the cost of shipping depending on the selected shipping method. Also kind of similar to the strategy design pattern. To return a function, you write a return expression followed by a lambda, a method reference, or another expression of a function type, such as a local variable. So what it would look like is something like this. And this syntax does look familiar. You have your function keyword, and then you have bar, empty parentheses. It's not returning, it's not taking any parameters, and then the colon. Everything to the colon on the right is the return type. And in this case, we're returning a function. So what you see here is inside parentheses, you see the type of the string that's going to be passed to the function, the one that's getting returned. It's a function type, right? This looks like a function type. And then you have the arrow, and then on the right-hand side of that, it's going to be returning a string, and then equals, and then this looks like a function literal. You're going to be the body, which is stir.reversed. So a string that takes a string returns a string for this function, and you notice that there's no type in the body. The type is inferred because you don't need to specify the type here. So stir.reverse, it's just going to reverse the string. Invoking bar will return a function from string to string. The string will be reversed. To return a function, use an equals after the return type and wrap the function in braces. And that's exactly what it's doing, right? That's the body of the function. Before the equals is the parameter for that function and then the return type string. Looks just like previously. It's a one-line function where the single expression after the equals is the function body. We know what single expression function is from previous lectures. You can invoke it as follows. So that example right there is how you would define it. When you're defining the bar function, that's how you define it. You invoke it, you would just say, you could create a variable, and you could assign it to bar, and then when you want to call it, you just say reverse hello, and that will pass in hello to the function that was returned, right? So when you call bar, it's going to return a function, and then you take that function and pass something into it, and that will return something as well. So what you could do is you could print out reverse hello world. So we assign the function bar to a variable called reverse I before invoking it with two different values. Right, and this is a way you can reuse the function, right? We're reusing the function twice here from what was returned from bar. The usefulness of this technique can be seen when we have a function that accepts other values and then returns a function that uses the input to the original function. Another example, let's define a function for creating a modula-based filter. What this will do is it will filter out any of the modules that have 0, right? So here's function modula. It takes an int, and then it returns a function. Returns a function that takes an int as a parameter and returns a boolean, and then the body of the function is after the equal. Right. So this is what the previous example was saying, that it's useful to return functions when you have a function that accepts a value, and then the return function uses that value. Right. And that's what's happening here. You have module, it takes an int, and then we're using that int, the k, inside the body of the function that's being returned. Right. So this module function is just going to it's going to take some data, and if that data has a module of 0, remember module is a remainder. So if you can divide that data by a parameter, and it will return if it's equal to 0. So the input value k is used as a return function. This can now be combined with the higher order filter function available on a list class. So this is how you would use it. You would create a variable of ints, which is a list 1, 2, 3, 4, 5, 6. And then you would say ints.filter, but you would filter on what's returned from modula 1. So what this is saying, all the data inside of the list filtered out for module 1. And module 1 would be 1, it would be 1% 1, which is 0, so it would return 1. It would go through the list, 1, 2, 3, 4, 5, and 6, and filter it out. And then it would go to 2 divided by 1, which is 2. With a remainder of 0. So 2 would be in there, 3 would be in there, 4 would be in there, 5 would be in there, and 6 would be in there. Now, if you did val evens ints.filter on module 2, what would happen is you would go and 1 divided by 2 doesn't have remainder 0, so it's not going to return that. 2 divided by 2 does have remainder 0, so 2 is going to be assigned to evens. 3 divided by 2 does not have 0 as a modulus. 4 does, and 6 does. So I would print out 2, 4, and 6. Val mod 3 for module 3 would be 1 divided by 3, nope. 2 divided by 3, nope. 3 divided by 3, yes, that's modulus 0. 4, no. 5, no. And 6 divided by 3 has a modulus of 0. So again, very useful for having a function that takes a value, and then that value is used inside the function that's returned. And that's exactly what this ints.filter is doing. It's calling module, which the input is 1, and then it's returning that function from there and passing it into filter. Right? And then the Boolean or the modulo function there is using the it operator, it keyword, on the list. So it represents each element inside the list. Pretty neat. Very powerful stuff. We don't use braces here because if we did, that would define another function. So which would invoke the modulo function, giving us a function of a function. So you got to be careful though. Make sure you know what you're passing in and what's being returned. So a pretty neat feature. Again, kind of remember this main use case where you can use the function as input and operate on that function. Thank you. Hello, let's talk about inline functions. This is more of a performance improvement. Little technique that can reduce the bytecode. So using higher order functions, we know higher order functions are functions that take functions as parameters or return a function, can cause certain runtime penalties. There's a performance hit. Functions are instances of objects, and of course, each instance requires an allocation in the heap. That's where objects get allocated. They get allocated on the heap. Local data usually gets allocated on the stack. So there are also method invocations required when invoking the function. Overall, using functions introduces an overhead. So memory allocations, both for the function objects and classes and virtual calls, introduce this overhead. In many cases, this kind of overhead can be eliminated by inlining the Lambda expressions. So the inline keyword can be used to indicate to the compiler that the function is marked as inline, as well as function parameters. This is similar to C. In C, you can inline functions. So the body is inlined, and what that means, it's substituted directly instead of the function invocation. So instead of having the overhead of invoking the function and putting that all in the heap, what it really does is it just substitutes it. So if you were to look at the code, the bytecode, that code would not be creating invoking the function. It would have the function body there. So an inline function is compiled, its bytecode along with the bytecode of the Lambda expression is passed to it, is inserted directly into the code of the calling function, which ensures that the call happens with no overhead compared to similar code written directly. So let's consider a function that handles resources in a safe manner. So a resource will always be closed correctly even if the code throws an exception, sort of like the finally clause in Java. So here we have our function, and it's taking a generic. We haven't talked about generics, but it makes it more useful. It's called with resource, and it takes a named parameter, which is a generic resource, and it also takes a function as a parameter, using that parameter resource, generic resource, and returning a u, which is another generic. We have try, and all it says is call the function and pass in the resource, t. Otherwise, finally, then close it. So it's going to execute it and then close it. Clean it up. So the withResource function is just wrapping the function argument in a try finally block. So if that function causes any kind of exception, it will call the finally and it will get cleaned up. So remove some boilerplate whenever we want to use a closable resource. So here is how we could use it. We have this function called character count, and this function will open a file, read in text, and counts the number of characters. It uses with resource. See the return keyword there? It uses with resource to ensure that the input stream is correctly closed if some exception was thrown. So again, read resource is just wrapping the function in a try catch, try finally. So with resource takes input, which is the file's new input stream. It operates on that input to really read the text. And if that, the length of the text, and if that throws an exception, it will wrap it up, it will catch the resource, allow it to close. So when this code is compiled, we end up with the creation of the function argument as an instance. If code like this was being executed many times in a loop, those allocations would add up. This would be a resource hog. This would be a performance hit because we'd be doing a lot of stuff on input and files, and so we don't want to do this. We don't want to have this data allocated on the heap. We don't want the function argument to be created as an actual object. So what we can do is we can mark the withResource function as inline. This will tell the Kotlin compiler to not generate this code as an invocation and instead just substitute the code. Just put the code wherever it's being invoked, the call site. So first we have to annotate the function with the keyword. And all you have to do here is put the inline keyword before the function fun keyword. That's all you have to do on that side. And then the compiler would translate an invocation of the character count in the following. So what would end up doing with the compiler is it would put the try and finally right inside the code of the function, as opposed to creating an instance on the heap. So in this character count expanded, you see the try and the catch. And the code, the return input .buffered.reader was the lambda, right? The body of the lambda, and now that's in a try catch. You wouldn't see this code in your source code, but what would happen is when the bytecode gets generated, it would look like this. And this is less overhead. It's not allocating on the heap, it's on the stack, so it gets immediately returned when the function returns, and it's just going to be much better performing. So the bytecode generated from the above expansion is much smaller than the original. And other things as far as the inline function is concerned, you have to be really careful using this because the amount of code generated could increase. You know, you may be thinking you're doing a good thing, but you may add it and it may be causing more of a performance hit than helping. So if that means over avoiding many allocations in a tight loop, then the payoff may be worthwhile, but it will be smaller on mobile devices. Again, it's unless you're really sure that you're increasing the performance, you stay away from inline. So using the inline keyword can improve performance only with functions that take lambdas as parameters. Never use the inline keyword on a regular function that takes two objects. Only use it for higher order functions. If the compiler believes that inlining will not result in much improvement, it will emit a warning. You can disable a warning. But again, sparingly use inline. Due to the way inlining is performed, not every function that uses lambdas can be inlined. Generally, the parameter can be inlined if it's called directly or passed as an argument to another inline function. So when you are using it, remember that it may not work. It may decrease the performance. It may decrease the performance, and it also may not work if you don't use it correctly. Sometimes you may wish to only inline some functions. A function marked as inline cannot be assigned to a variable inlined. You want to use the no inline annotation. So I just wanted to give you a heads up. If you see this keyword, you should know what it means. It's a performance improvement, but most likely you're going to stay away from it and not use it too much. Unless you're really seeing some performance problems on your mobile device in an Android app, you're seeing some issues, you can then go around, analyze some of your functions, see if any of the functions are taking a lambda, and if they are, you can maybe add inline to see if it helps. Thank you. Okay, hello everyone. Let's talk about object-oriented programming. Kotlin is an object-oriented programming language, so it's important that you understand what that means. Object-oriented programming is a type of programming paradigm language itself. So it's a methodology based upon objects, having both data and methods that allow for software modularity and software reuse. That's the technical definition. Now, as far as programming and a history of programming, there are different programming methodologies that have been around for quite some time. There's basically three different types of programming methodologies. There's structured programming, or what you can call imperative programming, and then there's functional programming, and there's logic programming. Those are the three types of programming. Under those three types or three categories, there are specific programming paradigms for each one. So for example, for imperative programming, you have languages like C, which is more of a structured language. It's organized around functions and global variables, but there's no concept of objects. Also under the imperative category, you have object-oriented programming, which is kind of the latest and greatest, the most modern programming paradigm, program methodology, whatever you want to call it. It's this idea of organization around objects. For the other categories, things like logic and functional. Functional, we've talked about previously, it's organized around functions. You try to limit the amount of side effects. You don't use a lot of global data. Logic programming languages are used more for artificial intelligence. Things are based on predicates, questions and answers. Programming languages like Prolog or Lisp, where you define rules, and then based on asking questions of those rules, you get true or false answers. Traditionally, imperative programming is much more popular, easier to follow to some degree, and used in the mainstream. Other examples of imperative programming language that fall under object-oriented are things like C++, Java, C#, and Kotlin, because it's based off of Java, is also object-oriented. And there's a lot of advantages to using object-oriented programming that we're going to talk about. But the main thing is you got to think of it's organized around objects. You don't really have functions. You have things called classes, objects, and you have a lot of concepts that are very important, like encapsulation, polymorphism, things like that we're going to discuss. The other great thing about organizing your code around objects is it allows for software modularity. And what that means is you break down your program into manageable chunks. You're modularizing it. You're modularizing it more through classes and methods. And by modularizing it and having these little smaller chunks of software components, it's easier to reuse that software. If you just had one large code base that wasn't organized at all, it'd be very hard to reuse certain parts of it. So the fact that objects are created and encapsulated in classes and are modular makes them much easier to reuse. And those are two very important concepts when you talk about programming. So what exactly does this mean? Well, things are organized around an object, but what is an object? An object is really anything anything kind of like, you can think of it in terms of a noun, a person, place, or a thing. If you were to just look around right now where you're sitting, you can identify objects. If you're sitting at a desk could be represented as an object in your program. A microphone, a monitor could be an object. A chair could be an object. Again, usually a person, place, or thing. And what this means, it's more related to real-world entities. So you're kind of modeling your code around these objects, these real-world entities, and it's much easier to follow and relate to it. And then typically what you do with your objects is you put those objects inside of a class, and a class defines the object. We'll talk more about classes as well. But you organize your program on all these different objects that are created inside these classes, and that's how your program is designed. So another example would be if you were to write a program that maybe simulated a car or an automobile, you would create a class that represents a car, which is an object. And then the car would also have maybe other types of objects associated with it, things like doors or an engine. And then each one of those objects would have certain characteristics and behaviors. So some of the features that object-oriented languages provide are, we mentioned programs are organized around objects, and they're grouped inside this term classes. Classes just are a blueprint for the object. They define the object. The focus is on data with methods to operate upon the object's data. The data is represented as characteristics of an object. The methods represent the behavior of an object. So again, for example, if you have a car that is an object, what are some characteristics of a car? Well, a make, a model, a color, number of doors. Those are all characteristics of a car. And then you also have behavior associated with a car. You can accelerate, you can open a door, you can change an engine, all sorts of things like this. And what happens is, for different programs, you have these different objects, and then the objects interact with one another through this behavior, through these methods. So the interaction between objects happen through the methods inside of the class. The reusability of design through creation of new classes by adding features to existing classes. So the fact that makes them easier to reuse, software reuse, besides just the modularization, which was represented in classes, it's very easy to add new features to a class. If you have a new behavior of a class, you add a new method. If you have a new characteristics of a class, you add a new characteristic. And when we talk about inheritance, it makes it even easier to reuse code. But let's not get too far ahead of ourselves. First, we're trying to understand what objects are and how object-oriented programming works. We mentioned some of the features. Also, I mentioned some of the example languages. C++ is what I use mostly. On a daily basis at my job, I write code in C++, but also Java, one of the most popular languages out there, what Kotlin is based on, Java. Smalltalk, also another popular one. C#, really popular. Object-oriented languages are really the latest and greatest. To understand object-oriented programming and design is going to be very beneficial for your learning, and also if you're interested in a career in this. Object-oriented programming were introduced right around C++ framework and Smalltalk right in the late 80s, and they really took off, and most modern languages use some concept of objects. Some terminology associated with object-oriented programming. We talked about objects. Objects are really the key to understanding object-oriented programming. As I mentioned, you can think of them as a noun, a person, place, or a thing. If you look around right in the room where you're sitting, there's tons of different objects. Examples that I included here are a table, a TV, a car, a microwave. And as I mentioned again, I know I'm repeating myself, but you really have to emphasize this important information. All objects have state and behavior. State are characteristics, behavior is represented in methods. So in this example, dogs have a state. And the state of a dog would be the name of the dog, the color, the breed, whether or not it's hungry. Behavior of a dog would be barking, fetching, wagging tail. Bicycle would be another example of an object that could have state and behavior. Bicycles have a current gear, current pedal cadence, current speed. They also have behavior. You can change the gear, you can change the pedal cadence, and you can apply the brakes. And you should notice a pattern here. The verbs kind of represent the behavior and represent methods. And then the states represent more of characteristics, which are represented in member variables. In Kotlin, we call them properties. Objects store its state in member variables and exposes its behavior through methods. Methods operate on an object's internal state, usually on the member variables. They change the state. So if you want to change the speed or change the current pedal cadence, what you usually do is you'll change a state variable. And that's the primary mechanism for object-to-object communication as well, this method invocation. Polymorphism, that's another important term. We're going to have a whole other lecture on that. This is a nice benefit of object-oriented programming because it allows at runtime to have different behavior based on types. And it's important to be able to do this. It makes the code much more flexible, much more reusable. And so depending on the type of the object, and it's used also in inheritance, certain behavior will happen. We'll get into that more as well. But you'll hear this term polymorphism quite a bit when you talk about object-oriented programming. A package is a namespace that organizes a set of related classes and interfaces. It's a way of grouping together classes that provide some functionality. Java has packages for all sorts of specific functionality like networking, file input and output, core features of the language, java.lang. Encapsulation, another term that you hear quite a bit of. Encapsulation is important because it allows the code to be more maintainable, and it decreases the amount of global data you're using, which makes code harder to maintain, harder to fix bugs. Encapsulation is the mechanism that allows each object to have its own data and methods. It's this concept of having everything inside of a class and then creating instances of that class, which would be the actual object. What you usually do when you implement encapsulation is you have private member variables, and then you have public getters and setters to change that data. Overloading, another common concept. This is where you have methods with the same name, but they have a different number of parameters or types of parameters. I'll provide some examples of these, but constructors are often overloaded. Constructors are a way of creating objects in object-oriented programming. Overriding, this is more related to polymorphism, runtime polymorphism. It's used when inheritance. Inheritance is also another common term in object-oriented programming. It's where you redefine a method with the same name, but it's in the subclass as opposed to the superclass. Some of these other terms you may not be familiar with. Don't worry about it. We're going to have more lectures on them. But I want to just kind of introduce you to some of these basic concepts. A class, I mentioned a class essentially defines an object. When you have something like a dog that's an object, you have to say what the characteristics of the dog are. Well, breed, name, those types of things. And then you also have to define the behavior. When you define that information, it's defined inside of a class. It's just a definition. It will be where your code is when you define the class. You then want to, in order to do something useful in object-oriented programming, you want to use that class. You want to create an instance of that class, which is the actual object. And right, for dogs, you define what a dog is, but you could have many different dogs. I have a dog. My wife has her dog. My neighbors have a dog. Those are all represented as different instances. They share the same state. They all have a breed. They all have a name, and they all have similar behavior. They bark and so forth, but they have different values for that state. Different colors, different breeds. Methods are shared. Composition and aggregation. You'll have these two terms as well. This is when you have an object that uses another object. You can think of this as like a has-a relationship. This describes relationships amongst objects. Terms you hear quite a bit of when you're talking about class diagrams. Constructors, these are special methods that are invoked when you create an object. In Java, you use the new keyword. In Kotlin, you don't have to use the new keyword. Kotlin has concept of primary constructors and secondary constructors. Access modifiers, related to encapsulation, access modifiers are keywords that set the accessibility of classes, methods, and member variables. You don't want anyone to access your data. If you allowed anyone to access your data, that'd be global data. Global data is harder to maintain and harder to fix bugs because anyone can mess with it. And if you limit who can mess with your data, you can control it and you have less prone to errors. An interface, another common term, this is a way to provide abstraction, hide complexity details from somebody that's using your class. We'll talk about interfaces in detail. Abstraction related to interface is a way to implement abstraction is using an interface or an abstract class. Abstraction is hiding complexity, abstracting common features out in procedures that clients can use without causing it to be overly complex. Advantages of object-oriented program. We talked about some of the features. The specific advantages are that they provide modularity. And I wrote that twice just to emphasize it. Encapsulation in objects are maintained independently from other objects, which makes it easier to maintain, easier to fix bugs. An object can be easily passed around inside the system, and you have data that's encapsulated. Information hiding, abstraction more or less. You can interact only with public objects methods, and then the internal implementation can be hidden away from you by using abstract classes or interfaces. And so you don't have to know anything about how the classes actually are implemented to use them. So in Java, there's all these packages, as I mentioned, all these classes that you can use, and you don't have to know anything how they're implemented. You can read and write to a file in Java, but you don't have to know how that's implemented. You just use the class, and you call the methods, and the methods are implemented somewhere else. Software reuse, another big advantage. If you have to write less code and you can reuse code, it's going to increase efficiency. It's important. And usually when software is reused, it's been tried and tested and is proven to be very scalable and very workable. So reusing code is a big deal. You can reuse code in object-oriented languages by using concepts like inheritance and interfaces. Maintenance. Maintenance is much easier. Maintenance is the last phase of the software lifecycle. Maintenance is the idea of you release a product and then you have to maintain it. You have to fix the bugs. You have to add new features. When Microsoft releases Windows 10, it's out in the public people can buy it. It's out there for 10 years. And they release it, but then they have to maintain it. They have to fix all the bugs. And if they want to add new features, they add those new features. And the maintenance phase of the software lifecycle is often the most expensive phase of the software lifecycle. Writing the code, creating the code, testing in it, and all the other phases are cheaper than after you release it and having to maintain it. So it's very important to decrease your maintenance costs, to make your code as easily maintainable as possible. And what this means is if there are any bugs in the code, make it easy to find them. Make it easy to fix them. If you want to add new features to code, make your code very flexible so that when you add a new feature, it's not super hard to do. And object-oriented programming allows the maintenance to be much easier because of how it's designed. And so it's easier to add new features. It's easier to fix bugs if you're writing code in an object-oriented fashion. And so this, as a high level, is object-oriented programming, and this is how Kotlin is designed. So you need to understand this. Kotlin and everything in Kotlin is an object. And everything provides encapsulation. All these different concepts are provided by the Kotlin Programming Language. And we'll talk more about some of these features in detail, but try to understand, try to visualize or relate to this concept of objects, state, behavior, and these different concepts as well: encapsulation, information hiding, abstraction. Thank you. Hello class, let's talk about classes, an object-oriented concept to define objects. So a class is a blueprint for an object. It's where the definition of the object resides. At this point we know what an object is. It's a person, place, or a thing. You can represent an object by pretty much anything that you look at. So if you have an object that is a dog, in object-oriented programming, in code, you have to represent that object somehow. How you represent that and how you define it is you use the concept of a class. And for most languages, there's an actual keyword in your code named class. And if you use that keyword, that starts the definition of your object. And what the definition of an object means is you specify the characteristics of that object through this concept of properties or member variables. And then you also define the behavior of an object inside of a class through methods or member functions, many different terms for that. In Kotlin, member variables are really properties and methods are really member functions. Those are the terms that they use in Kotlin. So in the real world, you often find many individual objects, all of the same kind, the same type, right? There's thousands of cars, all of the same make and model, built from the same set of blueprints, which is a class, and therefore they contain the same set of components, right? All cars have a make, a model. They all have some of the same characteristics. They may have different values for those characteristics, but they share the same characteristics. And they also share the same behavior, which are represented as methods. Now, when we talk about instance of a class, That's really the actual object. So for example, the car that I own, car may be defined in its own class. It may represent an object. But the actual instance, the object that I have, that I own, has certain values for my car. So for example, my car has its own make and model. It has its own color. It has its own number of miles, things like that. And so when I say an actual object defined in code, you create instances of them. You hear that term instance quite a bit. And the instance is the real entity itself. And you can have thousands of instances, right? Because there's thousands of cars. Each instance shares the same attributes, the same member variables or properties, and the same behavior. But there's different values. There's different state data associated with it. So you create individual objects from the class definition. In Java, you have to use a new keyword. In Kotlin, you do not have to use a new keyword. You just specify the name of the class. An instance of an object is the object that was created from the class. That's the real-world entity. And like I said, you can have many, many instances. So let's look at an example. This is kind of pseudocode. It looks like Java. It is Java. But in Java, the way that you create a class, again, the definition of an object, you use the class keyword. And you'll do the same thing in Kotlin. You'll use the class keyword. After the class keyword, you specify the name of the object. So in this example, we have a class named Bicycle. And then anything after the name of the class, you'll have brackets to represent the body of the class, the definition. A left curly bracket and then a right curly bracket at the very end to represent the class block. In between those blocks, you're going to define your member variables or your properties. In Kotlin, they call them properties because there's getters and setters. And you're also going to define your methods. In Kotlin, they're member functions. Because in Kotlin, not everything has to be inside of a class. You can actually have top-level functions that are outside of the class. In Java, there's no concept of a function outside of a class. But anyways, this is what it would look like. You'd have that class keyword, and then you'd have some variables that represent your properties, and that would represent the state. You may initialize them with some values. So here we have cadence, speed, and gear for our state data. All of the instances of an object share these member variables. They may have different values, but they share them. And then you have member functions, methods. Here we have a change cadence method or a change gear. And what these methods usually do is they change the state behavior. They change the state data. And so this would be a simple class with 2 methods, 3 member variables representing a bicycle. And some more methods of this class would be speed up, apply brakes, or print states. Again, simple methods, and then you see at the very bottom, you have your right ending curly bracket that represents the entire definition of the class. So in object-oriented programming, you create all these classes that represent these objects, and then to do anything useful, you have to utilize these classes. You have to create instances of them. You have to create the actual objects. By just defining them, you're not using them. You want to use them and change the state behavior and call methods on them to do something meaningful. So to use a class, you'll do something like this. In Kotlin, you can have a main function by itself. It doesn't have to be inside of a class. But again, since Kotlin is based off of Java, we have some Java examples here, and we haven't talked about Kotlin classes yet, so I'm showing you some pseudocode more or less. But in Java and in Kotlin, your main entry point to a program is your main function, your main routine. And so your main routine is typically where you create instances of objects and use them. Although if you have relationships with other objects inside your class definition, things like aggregation and composition, you'll also have objects that you can utilize and set state data and create new objects inside of a class itself. But in this example, we have a main routine, main function. We're creating instances of new objects. And the way that we do that in Java is we use the new keyword. So these first 2 lines here, we specify the name of the class, bicycle, and then we have an identifier. Just some type of name, usually a meaningful name, so that it's easier to follow the code. And then an equal symbol, and then you say new bicycle. In Kotlin, you can just say the class name. You don't have to say new bicycle. And the way that you create the object is you call the constructor by just having the empty parentheses or an overloaded constructor. But this is the gist of it. You create instances of objects, and then you call methods on those objects. So at the very top, we're creating 2 bicycle objects, and then we're calling methods on those objects. We're changing the cadence, we're speeding up the gear, changing the gear, printing the states. And then for the second bicycle, we also have different states. So what you should notice here is we have two instances, bike 1 and bike 2. They share the same state data, but they have different values for them. You can call the same methods on those instances, but again, they have different values. So bike 1 is going a different speed than bike 2. Bike 1 has a different cadence than bike 2, because bike 1 is one instance and bike 2 is another instance. So if I were to look at the output of this code and I print it out, you would see that bike 1 has a cadence of 50, speed of 10, and gear of 2. Bike 2 has a cadence of 20, speed of 25, and gear of 3. Has different values for its data. So you can think of those bikes, bike 1 and bike 2, as actual real-world entities, actual instances that you perform operations on that have different state data. And you create those instances in Java using the new keyword. In Kotlin, you don't use the new keyword. But this is the whole idea of object-oriented programming. You have objects, you define them in classes, you create instances of those class to do something. Thank you. Hello and welcome. Let's talk about encapsulation. We briefly touched on this in a previous lecture as well, but I want to emphasize it because it's an important concept. Encapsulation is one of the 4 fundamental object-oriented program concepts, along with inheritance, polymorphism, and abstraction. Encapsulation is very, very nice in Kotlin because it's automatically provided for you and you don't have to hardly do anything through the concept of a data class. It's a mechanism of wrapping the data, the variables, and the code acting on the data together as a single unit. So what this means is that encapsulation, the variable of the class will be hidden from other classes. And the way that you can hide data is you can specify the access modifiers, the public, private, data, and so forth. And so the concept of encapsulation is that all of your member variables, or in Kotlin your properties, are private. They cannot be accessed outside of the class. The way that you do access them is you use public getters and setters. And so you can only access private data through methods of their current class. And this is the concept of information hiding. You declare your member variables as private. Again, as I mentioned, luckily Kotlin does this automatically for you with data class definitions. You can create a data class in one line and that will automatically put all of your properties as private and then make them have public getters and setters. Because it is such an important concept, the Kotlin Programming Language said it's so important that we're going to do it for you automatically. In Java, you have to add a lot of this boilerplate code that does all of that, and it's really just tedious and a waste of time and not very efficient. So you make your member variables private, and you make getter and setters. Provide public setter and getter methods to modify and view the variable values. You control who has access to your data. And this is important because if you can control the access to your data, it's easier to find and fix your bugs. And that's what it's all about, right? It's all about having code that is clean, having code that is easy to maintain, having code that is bug-free as much as possible. We know that's not completely possible, but is to make it as easy as possible. And so if you limit who has access to your data, you limit the amount of components that can modify that data or cause bugs. You immediately know if you have a bug, well, hey, this bug can only be in this class or that class because no one else has access to that data except this class. If you were using an imperative language like C where you use a lot of global variables, to find and fix a bug is pretty tough because if everybody's modifying that data, well, anybody can cause the bug. So if you have hundreds of thousands of lines of code, then your potential code that's causing that bug could be any lines of code. Where if you limit the accessibility, you're limiting your problem set and you're limiting who can actually cause that bug. Backing properties. Here is a public class, my class, an example. Let's look at an example of a class that has private member rows and public member methods. And this would be a Java class. In Kotlin, a lot of this would go away because you have your automatic generation of this. But you know this is a class because it has the class keyword. We're specifying the class is public so other people can create this class outside of this file. But you'll notice here that your member variables, your attributes, your characteristics of your class definition are all defined as private. And private is an access modifier. It defines who can access this data. And so what this is saying is that name, ID, and num and age can only be accessed inside this class. You can't access that member data anywhere else outside of the class directly. If you do need to access it outside of the class, you can access it through these public get and set methods. These are referred to as getters and setters. Or they're also referred to as accessors. Sometimes you'll hear that term. But public int get age is getting the member variable age. It's returning that data. This is referred to as a getter. And then if you want to set data, you would have a set method. So get age, get name, those are getters. They're just returning member variables. And then you have set methods. These are setters. Set age, set name, set ID, num, where you can control, you set your member variables, you can control his access. Typically the setters will also have some kind of validation. So if you try to set, a better example here would be if you tried to set a balance member variable of a bank, you can't set it to a negative number. So you would verify that the number you're trying to set is not negative. So you have validators in your setters, but you also control who has access to this private data through these public getters and setters. And this is the concept of encapsulation. The public setters and getter methods are the access points of the instance variables of the class, the member variables. They're referred to as getters and setters. Any class that wants to access the variables should access them through these getters and setters. And you can only access those getters and setters if you have an instance of that class, if you created an object. They're not static, so you can't directly access them. If you created an object, that means you have the right to modify that data. The variables of class can be accessed using the following program. So here's a test program that can access data. You would create an instance of the class. In this example, my class incap, that's just a class name. It's just generic. New my class, in Java use the new keyword, and then you start calling set methods to modify the data. You don't directly access those member variables. And then you can print out the data that was modified by calling the get methods. And this is the concept of encapsulation. Those public, private member variables with public getters and setters. It forces you to create an instance. You can only access that data through the instance. The advantages of encapsulation: the code is more flexible and easy to change with new requirements. You don't have to worry about where the data is or where you have to add things. You have a new requirement, you can just add a new member variable, you have getters and setters, you're good to go. It makes unit testing much easier. For those of you that are familiar with unit testing is the concept of writing code that will check whether or not your methods are correct. And you do this as a unit. You're not testing the entire functionality of your program. You're just testing the functionality of each method inside of a class. And so you're just checking the input. You're providing some input to a method and then checking whether or not the output is correct. And so there are things in Java like the JUnit package, which does this. Kotlin has its own test package as well that makes this stuff easier. Typically, you'll run the unit test when you compile. Every time you compile, you run unit tests to make sure you didn't break anything. And by encapsulation, unit testing is easier because you don't have global data. The data is inside the class. You have inputs and outputs. You don't have tight coupling. You don't have a lot of dependencies. And through this lack of dependencies, it's much easier to unit test. It also allows you to control who can access what. I mentioned the importance of this earlier. Less people accessing data or less code accessing data, easier to know who caused the bug. And it's all about finding, fixing bugs, adding new features. It helps you write unchangeable classes or objects. You know that the class that you created is not being modified directly outside of that class, so you know who's changing the data because you can just look at the instances and you know automatically those instances could be responsible. It reduces coupling of modules and increases cohesion inside a module. Coupling and cohesion are important concepts related to maintenance. Coupling is the concept of really just having dependencies. If one class is very dependent on another class, that means it's tightly coupled. That's not a good thing. That's a bad thing. Because the more dependencies you have, the harder it is to fix bugs. Because again, if you have a bug, your code set becomes much larger. It could be in any of the dependencies. So you want to limit your dependencies. And by writing things that you control who has access to and providing this concept of encapsulation, you reduce the coupling. You have low coupling, you have low dependencies amongst classes, so it's easier to find and fix bugs. The concept of cohesion is how focused your code is. So for example, if you had a class named car, and car was doing 5 million things not related to a car, it's not very cohesive. It's very low cohesion. It's doing too much. It's the same kind of concept if you have a method that has 1,000 lines of code in it. If a method named getInput is getting the input, printing out data, doing some arithmetic, it's not cohesive. A method called getInput should only do the getInput. And so you have high cohesion when you have more modularization, and it's a good thing because once again, it's going to limit your code and it's going to break your code down into modules more. So you want to strive for high cohesion. And encapsulation provides high cohesion because you have these public getters and setters that do specific things. Your data is only modified in one spot. So coupling cohesion, those are traits that you want to, those are goals that you want to have when you write your code. You want to have loose coupling, low coupling, and you want to have high cohesion. You want to design your classes that are very focused and do single things and are highly modularized. It also, encapsulation allows you to change one part of the code without affecting another part of the code. And this is related to coupling, low dependencies. If you have high dependencies, you change one thing and all of a sudden it causes a cascade effect where you have to modify 20 other things because you have so many dependencies. You limit your dependencies, then you modify something and you don't have to modify 100 things. It also makes it possible to separate an object's implementation from its behavior to restrict access to its internal data. So the behavior is separated from its state data. You restrict access. It allows certain details of an object's behavior to be hidden. And it also allows us to create black box and protects an object's internal state from corruption by its clients. Kind of already talked about this. You know exactly who's accessing your data. A black box means that it can only happen in those public getters and setters. So you're controlling the access. You're not modifying that data anywhere else, so it's a black box. That's the only place it can be modified. So this is the concept of encapsulation. It automatically comes for you in a lot of ways in Kotlin, specifically by creating a data class. But what you want to try to strive for, and your goals should be to have your member data be private, your properties be private, and if you will need to change them, have public getters and setters, and have validation in your setters. Thank you. Hello and welcome. Let's talk about constructors. This is a term that you often hear in object-oriented programming related to creating an object. So a class contains constructors that are invoked to create objects from the class blueprint. It's a special method. And you can identify a constructor in a lot of programming languages because it usually is just the class name without any return type and usually has an optional number of parameters. It looks a little different from a method. In Kotlin, there's terms referred to as a primary constructor and a secondary constructor. And we'll talk about those, but basically it's a way to initialize data and so forth. But think of a constructor as a method that gets invoked when you create an object, and it looks a little different from a regular method from the other code. Constructor declarations look like method declarations except they use the name of the class and have no return type, as I mentioned. Here would be an example, and this looks like Java code, very similar syntax. In Kotlin, you have an access modifier before the name of the constructor. The name of the constructor is the exact same name of the class. So if you define your class as class bicycle, you would have a constructor named bicycle. And it can be private or it could be public depending on the access. In Kotlin, same way. It can be, by default, it would be public, I believe. And you can also make it private if you're creating a singleton or something like that. But again, the way to identify it is it's the same name of the class, no return statement, and just an access modifier before it, and no return type, and optional number of parameters. In this case, we have a constructor named bicycle that takes 3 parameters. This is referred to as an overloaded constructor, which we'll talk about in a second. Typically, the code inside of a constructor will initialize member variables. You pass some data in, you want to set the member data. Very simple. To create a new bicycle object called myBike, a constructor is called by the new operator in Java. In Kotlin, you do not need to have the new operator. But again, Kotlin is built off of Java, So we're using some Java examples before we dive right into Kotlin. So you'd see something like the name of the class followed by an identifier, that's referred to as the instance, and then equals operator followed by the new keyword in Java, the name of the class, and then any parameters that you would pass into a constructor or an overloaded constructor. In Kotlin, you would just have bicycle my bike equals bicycle, no new. New bicycle here creates space and memory for the object and initializes its fields, member variables. Overloaded constructors. This concept of overloading methods is where you have the same name of a method, but you have different return types, different parameters, and the return type doesn't matter at all. Either different parameters, types, or a number of parameters. And that's referred to as overloaded, and it allows for flexibility. If, for example, if you wanted to have a method with the same name but different parameters, it would allow that method to have different behavior and you could pass different data to it. Kotlin has some really cool concepts with eliminating overloading by the use of default parameters. And so you don't have to have all this extra code for overloaded methods. Overloaded constructors is the same concept as an overloaded method. You have different constructors based on the parameter, number of parameters or parameter types. And so although bicycle only has one constructor, it could have others, including a no-argument constructor. A no-argument constructor is a constructor that doesn't have any parameters. It's usually referred to as the default constructor, and it would look something like this. You'd be the empty parentheses, and you would just initialize member variables. Now, Java, by default, will automatically have a no-argument constructor if you do not provide an overloaded constructor. Once you provide that overloaded constructor, the default no-argument constructor goes away. And so you have to kind of be careful in Java. Anytime you have an overloaded constructor, you can't create an instance of a class with a no-argument constructor. So the logic of code inside constructors would typically initialize member variables, mentioned that. The overloaded constructors, you will invoke the no-argument constructor to create a new bicycle object called yourBike. Something like this. Bicycle yourBike equals new bicycle invokes the default constructor. Created by default in Java, and in Kotlin the same thing. It is created by default unless you provide an overloaded constructor. Both constructors could have been declared in bicycle because they have different argument lists, the concept of overloading. We'll talk more about overloading when we talk about polymorphism, so I'll give you more examples and it will become clearer. But I just wanted to briefly touch on constructors because they are a term that's used in object-oriented programming. Pretty simple concept. The code that gets invoked when you create an object, usually initializing member variables. Sometimes you'll see exceptions being thrown constructors, usually not a good practice. There's no return data. And the method, it looks like a method, but it's the same name of the class. Thank you. Hello and welcome. Let's talk about abstraction. Very important concept that makes your code more maintainable and allows clients to easily use an API without understanding the complexity. So abstraction is the concept of describing something in simpler terms, abstracting away the details in order to focus on what is important. You should not be bogged down by the details if you want to utilize something, especially if it takes away the focus of you writing good quality code. So for example, like the Java APIs. The Java APIs provide all sorts of functionality for you that you don't have any idea how it's implemented. And it would really be a pain in the butt if you did have an idea, if you had to know those details. If you want to write to a file in Java, you don't have to know how Java implements that. And what's the point of knowing that? You just want to write to the file. So Java implemented its APIs and its packages and all those classes to abstract all that detail away from you because it's not important to you. You just want to write to files. You just want to create a graphical user interface. You don't want to have to understand how it's being drawn on the screen, what's going on in the operating system to do all that stuff. So it's very important to be able to abstract away details that really have no impact on the programmer. The programmer wants to be able to focus on their code and the main core functionality of it. They don't want to have to get bogged down in details of things that they don't need to know about. So this is the concept of abstraction. And so if you want people to reuse your code because you're creating Kotlin classes, these classes are going to be reusable by definition. If you want to reuse this code, you don't want to get bogged down. No one will use your code if they're going to get bogged down by details. You want to make the clients, the people that use your classes, as easy as possible to use that code. So it's a process of hiding the implementation details from the user. The user will have the information on what the object does instead of how it does it. And you can provide for abstraction a number of ways in object-oriented programming, which we'll get to in a second, but mainly through interfaces and abstract classes. So in OOP, object-oriented programming, this translates to using an inheritance hierarchy or an interface. That's how you can implement abstraction. The more abstract concepts are at the top of the interface. The more detailed concepts are lower down in the layers of inheritance, at the bottom. Or if you're using an interface, you just provide the public API methods in that interface, and then you implement those methods in some class that implements that interface. The only thing that the client sees is the interface, and that's what they use. And you do a lot of this in the collection classes in Kotlin. In the collection classes in Kotlin, you utilize a lot of the interfaces, and you don't really know how the concrete classes are working. You may be creating an instance of a concrete class, you may be calling methods on it, but you don't know how those details are happening. This is an important concept, and you can utilize it with inheritance and interfaces. So as an example, at the top might be an interface with a single method. And then the next layer, the class that implements that interface, may have implementation for that method, or it may be an abstract method where it's pushing the implementation down to the next layer. And so you can have this whole inheritance hierarchy with interfaces, or even a concrete base class that has methods that you choose to implement or not implement. And as you go down each layer in the tree or the hierarchy, it gets more and more detailed. So there are concrete classes providing these implementations for any remaining methods that aren't marked as abstract at the lower levels. And it's a way of hiding the details. In Java, abstraction is achieved using abstract classes and interfaces. In Kotlin, it's achieved pretty much the same way. Except in Kotlin, it has a little more flexibility with some of the interfaces where you can provide default implementation of methods in an interface, and you can also have properties in interfaces in Kotlin. So here's an example. If we had a class named person, in Java we would define it as abstract, meaning that you can't create an instance of it and that it has at least one abstract method. And you would use this person class to invoke call methods on it, even though it would be pointing to a concrete class. So this would be your interface, this abstract class. This is what the client would know about, but it wouldn't know about how anything is implemented in any of the classes that implement this abstract class. So this has a name, member variable, it has a get name method, and has a set name. Encapsulation, getters and setters, and a private member variable. And then you would have a class that actually has the details in it that the client never sees. And you would do this by extending the person class, having an inheritance hierarchy. And you would have your member variables, you would have more details in here, and then you would have a main method where you really only know about the person. You just say person equals new employee. You don't know how that employee class is implemented. You just know it exists, and then you can start operating on the person. All the implementation details are hidden in the class that either inherits or extends the interface or abstract class. Advantages of abstraction. I mentioned a lot of them already, but by using abstraction, we can separate the things that can be grouped to another type. All the implementation details are in one class. All the interfaces and what the public clients see are in another class. Frequently changing properties and methods can be grouped to a separate type so that the main type need not undergo changes. So again, it limits your amounts of changes. The interface stays the same. The concrete implementation can be modified. So you could actually have two different teams working on the interfaces, and then the people that implement them working on another team. They don't even really need to know about them. The interface typically always stays the same, and that's what the client sees. And we'll talk about interfaces more, but interfaces are essentially a contract and what you use, the class you use, but you don't actually have to implement. So it adds strength to the object-oriented analysis design principle of code should be open for extension but closed for modification. What that means is you could add new public API methods for clients to use, but they don't have to be modified at all. You just add them, but but you don't have to remove them or modify them, and you just add the implementation details. It also simplifies the representation of the domain models. Domain models are kind of what the user sees, really represented as an interface. You want to use abstraction if you know something needs to be in a class, but the implementation of that varies. Some commonality with inheritance, but also with an interface. You know the things that you want a client to be able to use, but you don't care about how it's implemented, and the implementation may be different, where you can have different subclasses. So abstraction, an important concept. Sometimes you'll be using it and you don't even know it through the concept of an interface. You can also utilize it with inheritance hierarchies. Thank you. Hello and welcome. Let's talk about interfaces. We've been alluding to this subject the last few lectures, especially when we talk about abstraction and encapsulation. An interface is a common concept in object-oriented programming that has to do with hiding functionality and providing a public contract to users, clients of a class. So objects communicate with one another via their methods and expose their methods via an API. An API is an application programming interface. So for example, the buttons on the front of your television set are the interface between you and the electrical wiring on the other side of its plastic casing. You press the power button to turn the television on and off. The interface is the power button. The stuff behind it is the implementation. It abstracts the details from what the client sees. The client will typically deal with the interface, and then there will be a class that implements that interface when we talk about object-oriented programming. An interface in object-oriented programming is a group of related methods with empty bodies, no implementation. A class with no properties and only method definitions, no attributes. Classes that implement an interface must implement all methods defining the interface. This is a rule for Java. Some other languages treat this differently. And with the latest release of Java, Java 8, you can actually have default method implementations. And so Kotlin also provides the same. Kotlin has the concept of an interface. It's this concept of you provide something that is a contract that all clients have to implement, any class that implements it. You use the interface keyword. Typically interfaces don't have any attributes, but again, Kotlin is a bit different. In Kotlin, you can have default properties, and you can also have default implementations. And they are exactly what they describe. They're by default, that's what it is. So not everything in an interface has to be abstract. But in traditional languages and most object-oriented languages, you think of an interface, no attributes, only methods, no implementation. The whole purpose of the interface, again, is to hide complexity, and also it allows for software reuse. So interfaces also form a contract between the class and any clients that want to use the class. So if you have to implement an interface using the implements keyword in Java, you're required to implement all of the methods in that interface. Either that class that implements it or any of the subclasses of that. So that means it's a contract. If you want to force all classes to have specific behavior, then you can create an interface. And then any class that implements that interface has to implement those methods. So it's a way to force commonality as well and common behavior amongst many classes. An interface allows the computer to enforce certain properties on an object, a class. So you can have a car class and a scooter class and a truck class. Each of these three classes should have a start engine action. They all have to in order to function correctly. How the engine is actually started for each vehicle is left to each particular class's implementation. But the fact that they must have a start engine action is the domain of the interface. And so what you would do is you would put that start engine method inside the interface itself, forcing every class that implements an interface to have that method. The implementation can be different, but you have to include it. And then also, clients will use that interface and they can pass the interface around. They allow the program to be more abstract when referencing objects. In Kotlin, you can say var vehicle, vehicle. This can reference any car, truck, etc., anything that is a vehicle. The colon in Kotlin is the same as the extends in implements. So if vehicle is defined as an interface using the interface keyword, you would be implementing that vehicle. There's no separate keywords in Kotlin for extends and implements. It's just the colon. But the key here is if you create a variable called vehicle that is of type vehicle, you can now pass that around as a common object to any methods, and all the methods have to do is take a vehicle. And the method will work for a car, truck, it doesn't matter what the instance type is. So it's a software reuse technique. Interfaces require the programmer to create specific functions that are expected in an implementing class when it implements an interface. You have to implement the functions in the interface. We're going to talk about interfaces in more detail and how they're related to Kotlin. What you really want to understand from this lecture is the high-level concept of an interface. Why would you ever create an interface, and how would you use it? And as I mentioned, an interface is a way to force other classes to have certain implementation, and it's also a way to have a contract for different classes. It's another kind of abstraction technique. You can hide functionality in the classes and implement the interface, and then the client that needs to use those classes can just create an interface object that points to a concrete class. And then lastly, it's a software reuse technique because you can have methods that take interface references, and any class that implements that interface can now use that method. So you don't have to have a method, an overloaded method for different types of classes. So it's an important concept, an abstraction concept. Make sure you study it. Make sure you understand what this means. We'll talk about it more when we talk about Kotlin interfaces. Thank you. Hi class, welcome. Let's talk about inheritance. So in object-oriented programming, some objects will share commonality. They have the same characteristics or the same behavior. So for example, cars, motorcycles, trucks, and boats all share the characteristics of a vehicle. They have a current speed, they have a type of engine, they have a color, a make, and a model. They have commonality. However, each vehicle may have additional features that make them different. A truck has four-wheel drive or a cab, for example. Cars have four doors and different behavior concerning driving. Boats operate on water and have an anchor. So you have some commonality and some uniqueness. In object-oriented programming, it would be nice if when you create these objects inside of a class that for the commonality, you don't have duplicate code. And for the uniqueness, then you could have unique code. Object-oriented programming allows classes to inherit commonly used state and behavior from other classes. And this is the concept of inheritance. It allows you to reuse code without having duplication. So a vehicle could be something called a superclass. And this is a common term you'll hear in the inheritance concept. Superclass, which would be the base class as well. That's another term. And that's the top level class. You can also think of inheritance as kind of a hierarchy, sort of like a tree-like structure. At the very top is the root. Everyone below that would be the next layer and so forth. And you can have multiple layers. As you move down the inheritance hierarchy, it becomes more and more specific. At the very top, it's general, common, and as you move down, more specific. So at the very top, the root would be the superclass, and that would be named vehicle in this example. And then below the vehicle class, you could have subclasses or derived classes, depending on the term, of car, truck, and boat. And car, truck, and boat share common features that are defined in the vehicle class, and then anything unique goes in the car, truck, and boat classes. So each subclass has all the attributes and behaviors defined in the superclass. They inherit it. So you don't have duplicate code. Everything in the base class is in the subclasses. It's a real nice software reuse technique. It also provides for abstraction, as we mentioned earlier. The common classes at the very top can be less abstract, and then details can be in the subclasses. So it allows us to create new classes that reuse, extend, and or modify the behavior of pre-existing ones. As I mentioned, the pre-existing class is called the super or base class or parent class. The brand new class we are creating is called the derived class or the subclass. Typically in Kotlin, they'll use the term derived, and they'll also use the term super or base. Java tends to use the term subclass for classes that are off of the base class. Inheritance is also transitive. If class C is derived from class B, and class B is derived from class A, class C is automatically derived from class A. As I mentioned, you have many layers of the inheritance hierarchy. It doesn't just have to be two. You could have subclasses of subclasses of subclasses. And as you move down the hierarchy, it gets more and more detailed. A derived class will implicitly get all the parent classes, properties, fields, and methods. And if there's a parent class of the parent class, they'll also get all of that. And it's not explicit. You don't have to put that code inside the subclass. It's automatically inherited, so you don't have any duplication there. The importance of inheritance lies in the ability to reuse the code that has already been written. It avoids a scenario where we would have to re-implement the behavior exposed by the parent class. So it's a really, really nice software reuse technique. And as we mentioned before, why is software reuse a good thing? Because first of all, it's efficient. You write less code so you can get things done quicker. Secondly, reused code has often been tried, tested, and works. And it tends to be scalable. It's reliable code. A derived class can also add uniqueness. It can add its own field properties or new methods, thus extending the function available through the parent. So you would say that class B, the derived one, specializes class A, the parent. And so this also makes it very flexible and easy to add new features. If you have an inheritance hierarchy, something like a car, and you have subclasses of that, if you want to add a new type of car, you just add a new subclass. It's very flexible, very easy to add new features. You can't inherit from more than one class in Kotlin. You can implement as many interfaces as you want. So what this is referred to as multiple inheritance. There are a lot of problems if you try to inherit them from more than one base class. There can be something called a cyclic dependency. And so a lot of languages will prohibit multiple inheritance. And Kotlin also prohibits this, and so does Java. One of the ways around that is you can implement many interfaces. You can implement more than one interface, which is kind of getting around the restriction of multiple inheritance. But what Kotlin and Java try to do is the languages are flexible, but they also don't want the features to be abused, so they'll limit some things. And multiple inheritance is one of those things that gets abused and not used correctly, so they pretty much don't let you do it unless you use interfaces. Here's a simple diagram of an inheritance hierarchy. Using the example that we talked about, at the very top you have your vehicle. That's your root class, your base class. It's very generalized. At the next level, you have a car class, which is a subclass of vehicle, and a boat class, which is a subclass of vehicle. All the member variables and all the methods inside vehicle also exist in car and boat. They're not explicitly there, but you can use them and you can operate on them. And then below car, you have even more uniqueness, more specialization. You have a sports car, a truck, or an estate. They have different behavior and different member variables. They extend the functionality of the car, but they also inherit everything from car and everything from vehicle. From the boat subclasses, you have sailing boat, motorboat, and cargo ship. Those again are more specialized boats, so they may have some uniqueness associated with it. But they inherit everything that's in boat and everything in vehicle. So you can see you avoid duplication, you reuse software. As you go from the top of the inheritance hierarchy to each layer, it gets more and more specific. And this is also can provide more abstraction. At the very top level, vehicle has more general, common behavior, and the abstraction, the details, are in car, boat, and any of its subclasses. And then lastly, it's very easy to add new features. If you want to add a new type of car, just add a new subclass, and you automatically inherit everything in car and vehicle. Inheritance is a very, very useful technique. You tend to use it a lot in object-oriented programming because of all of its advantages, and you also use it to provide for overridden methods and polymorphism. Thank you. Hello class, welcome to another lecture. Let's talk about polymorphism. Polymorphism is related to inheritance. You cannot utilize runtime polymorphism without inheritance. We're going to talk about two types of polymorphism. The most common one, which is runtime, but also compile time polymorphism. The one that's related to inheritance is runtime dynamic polymorphism. If you look at that literal definition of polymorphism, it means same name, different behavior. When we talk about generics are kind of the opposite of polymorphism. Polymorphism has the same name for methods, but different behavior, whereas generics have the same different types with the same behavior. I kind of think of them as contrasting concepts. So the opposite generics and templates is this concept of polymorphism. It's when subclasses of a class define their own unique behaviors and yet share some of the same functionality of the parent class. Static polymorphism is at compile time. This is referred to as method overloading. Method overloading is the concept of having the same name of a method, but the different number of parameters or the different type of parameters. The return type doesn't come into play for method overloading. Dynamic polymorphism, which is the more traditional and common concept of polymorphism, is runtime polymorphism. This is where you have an inheritance hierarchy and you have method overriding. Method overriding is when you have the same name of a method in the base class and in the subclass, but you have different behavior, different implementation. First, we'll talk about compile time polymorphism and give an example, which is nothing more than function overloading, method overloading. In this overloading demo class, you'll see that there's 3 methods named add. They're all the same name, but the add method has a different type of parameters or a different number of parameters. The first add method takes a type of int value. The second add method takes a type of string. The third method for add takes a value and a name. And this is the concept of method overloading, compile time polymorphism. It doesn't matter what the return type is. For example, you couldn't have add int value and then another add int value, but one returned an int and one returned void. You'd have a compile time error. That's not method overloading. It's the number of parameters or the type of parameters. So the first 2 add methods both have one parameter, but they have a different type. One has an int, one has a string. So it allows you to have different methods that take different parameters. Luckily in Kotlin, you don't need to have a lot of method overloading because you can have default parameters, default arguments. And default arguments limits overloading because you can just either provide that argument or not provide it. So you have this less duplication. But this is the concept of compile time polymorphism. When you go to invoke the add method, you create a new instance of your overloading demo. You can call the add method with either an int, a string, or an int and a string. And the compiler will know exactly which method to call based on the parameters and the types that you're passing to it. This happens statically at compile time. Runtime polymorphism happens at runtime. Here's an example. And with runtime polymorphism, you have to utilize inheritance. You have to utilize overridden methods. So here we have a top-level class, an abstract class called animal. It's the base class. It has one method called talk. And then we have a subclass cat that extends animal. In Kotlin, you'd use the colon. And then you override the talk method, and you return meow. Also in Kotlin, when you need to override a method, you have to explicitly have the overridden method. You have to have the overridden keyword. Specifically, it's override. And you have to provide that in Kotlin. In this pseudo example of Java, you just have to provide the method name. But you'll see that talk is defined in the base class animal. It's also defined in the subclass cat. It just has different implementation. In the base class animal, it doesn't have any implementation. It's abstract. You have another subclass called dog that extends animal, and you override the method talk again, and it's returning a different string. It's returning a wolf. So you have different behavior for the talks depending on the subclass type. If it's a cat, it's going to return meow. If it's a dog, it's going to return wolf. And then you have the base class animal. So polymorphism is at runtime, based on the type, whether it's a cat or a dog, it's going to call the correct method. Either the talk that returns meow or the talk that returns wolf. So you would utilize the code something like this. And polymorphism can reduce duplication. So one of the common use cases of polymorphism is you'll create an array. And an array takes only one type. You can't have multiple types inside of an array. And so here, this would be an array of animals, an abstract class. This is the base class. And that means if the array stores animals, it can store either a cat or a dog. So you have an array of animals, it's of size 2, and you initialize the first element in the array to be a new cat. So when you create base classes and subclasses, on the left-hand side of the equals assignment, you can have a reference to the base class. Animal sub 0 is an animal. And then when you say equal, new cat is referred to as the instance type. So on the left-hand side of the equals, the reference type, on the right-hand side is the instance type. And so that's how you can store animals in the animals array, because a cat and a dog is an animal. You just say new cat, new dog on the right-hand side. And now you can have a for loop that iterates through the array and calls the correct talk method based on the type of the animal, based on the instance type, not the reference type. So in this case, what will happen at runtime is it will print out, for the first element in the animals array, it will print out meow. For the second element in the animals array, it will print out woof. The correct method gets invoked based on the type that's in the array, whether it's a cat or a dog. And this is the concept of polymorphism. Depending on the instance type at runtime, the correct method gets invoked. And again, what you end up doing is creating arrays, an array of a single type of object, and has multiple different subclass types, and then you can iterate on the array, do certain things, and you only have one line of code. If you didn't have polymorphism, you'd have to create two arrays, one that has a cat, one that has a dog, and then you'd have to have two for loops that would only do things for dogs and only do things for cats. So it can simplify code and also reduce duplication. The advantages of polymorphism: method overloading allows methods that perform similar or closely related functions to be accessed through a common name. A program performs operations on an array of numbers, which can be int, float, or double type. Overloading allows you to define three methods with the same name and different types of parameters to handle the array operations. So it allows for flexibility, and you can call the same name. You wouldn't want to have methods called add float, add int, add double. You have a single add method that takes different types. Method overloading can be implemented on constructors as well. Constructors, remember, are special methods that get invoked when you create a new instance of an object. Typically, constructors will initialize member variables. So you can have overloaded constructors that take a different number of parameters or a different type of parameters and do different initialization. Method overriding, remember, overriding is different from overloading. It has to do with inheritance. It allows a subclass to use all the general definitions that a superclass provides and add specialized definitions through overridden methods. So you can redefine behavior. You can have different behavior, different implementation based on that subclass. And at runtime, based on the instance type, the right behavior will be executed. So method overriding works together with inheritance to enable code reuse of existing classes without the need for recompilation. Other advantages: it also simplifies your code. If you need to write code that deals with a family of types, the code can ignore type-specific details and just interact with the base type of the family. So just like in our example where we had our abstract class animal, all we cared about was our animal. And we called methods on animal. We just had instance types for the actual dog or cat. But you can ignore the type-specific details. So it's an abstraction technique as well. Even though the code thinks it's using an object of the base class, which is the reference type, the object's class could actually be the base class or any of its subclasses. Right? Whatever's on that right-hand side of the equals is the instance type. And that right-hand side could be a base class if it wasn't abstract, or it could be subclasses. It makes your code easier for you to write and easier for others to understand. It also allows for extensibility. The same interface could be used for creating methods with different implementations. Other subclasses could be added later to the family of types, and objects of those new subclasses could also work with the existing code. So it's easy to allow new subclasses or additional functions to an interface. You can utilize polymorphism with abstract classes, with interfaces, or with regular concrete base classes. Remember, an interface doesn't necessarily have any implementation other than maybe default implementation. You don't create instances of interfaces, so the right-hand side of the assignment of an interface would have to point to a class that implements that interface. But if you have an abstract class, you can utilize that as well, like we did in animal, or you could just have a regular base class with implementation, and the base class could create instances of the base class, or it could create instances of any of the subclasses of that base class. Lastly, it's an awesome software reuse technique. We saw that when we saw the for loop. The for loop had a single line of code and iterated through the array. It didn't matter what the types were. It didn't have to call a specific method, whatever the instance was. At runtime, that was resolved. So it reduces the volume of work in terms of distinguishing and handling various objects. Polymorphism is a really useful concept with all these advantages. You should utilize it at some point to reduce duplication and to also be able to store reference base class types. Thank you.